Hello and welcome to this section where we're going to explore a fascinating topic in computer science that is cryptography. The internet as we know it is possible thanks to cryptography. If it wasn't because of this, we wouldn't be able to protect ourselves online, our privacy, our freedom, and so much more. This is a fundamental concept in cybersecurity and we have to understand it. Let's talk about what exactly is cryptography. Now, we're not going to get too technical right now in this introduction video, so I'm going to really simplify and tell you that cryptography all comes down to the idea that we have some information and we're going to use a key to change the information. And the idea is that only people who have the key should now be able to see the original information. So if we don't have the key, we're not going to be able to make sense out of the data. Alright, so the data could be text, video file, it could be anything. But only people who hold the right key are able to see what the data is. And the beauty of it is that it doesn't matter how powerful you are as an entity. Even the most powerful intelligence agencies and, FBI, the most powerful people with infinite amount of money, even they can't make sense out of this information if they don't have the key. Of course, for as long as we implement things correctly, which you'll learn how to do here in this section. Now, if we want to get a little more precise, at the core of cryptography are these three things. These are the primary reasons why we do cryptography: confidentiality, integrity, and authentication. Confidentiality means that we want to make sure that, again, only the right people can access our data. And this right people right here could also refer to only you as a person. For example, if you're using cloud storage and you're uploading your data, you should be the only one who can access it. All right, and cryptography would now allow us to do it. So that not even your ISP or the company that's holding your data or the government can now access your data. It doesn't matter if the company wants to do it or how evil they get, they still can't access it if we use the right techniques to do this. Integrity all comes down to the fact that no one should be able to tamper with our data without us getting notified. So if you're getting some data from me, for example, and if somebody in the middle changes the data, you, wherever you are, once you get the data, you should be able to see that something got changed 100%. Another one is authentication, and this one is about confirming that someone is who they really say they are. So again, if I'm sending you some information from another part of the world, you should be able to verify that it's actually me and not someone else who is impersonating me. So these are the main problems that we can now solve with cryptography. Now also there are some other things that cryptography will now allow us to do, but again, we're not going to get too technical here in this introduction video. For example, non-repudiation is another one. Things that we'll talk about later on, but let's not get too technical in this video. So these three things are at the core of cryptography. And it might not seem much, but it's a huge deal. The internet would look vastly different if we didn't have an ability to do these three things. So let's take a look at how the world would look like if we didn't have cryptography. First and foremost, we wouldn't have any privacy. Every message, email, or call that you're making could easily now be read by anybody, including the government, hackers, and even your neighbors. We wouldn't have secure banking without cryptography. So forget about online banking and credit cards. They wouldn't have existed if it wasn't because of this. Your phone security wouldn't have been there. So your Android or iOS device, you put in a passcode. But without cryptography, that would be meaningless. Everybody who wants it could now access it in seconds, right? And it wouldn't be difficult at all. There wouldn't be any disk encryption, so whatever you were saving somewhere and somebody steals it, they can always access it. Also, HTTPS, SSH, SMTP, so email servers and VPNs, any sort of application layer security would be meaningless. There wouldn't be any way to do it without cryptography. In general, we wouldn't have any sort of online security. When you're signing up, putting a password would just have no meaning. So in short, everything that you now do online or you save digitally will be able to be accessed by practically anybody, which you can imagine would be a massive problem. No more secure communications, and not just for personal use, for governments, for military, they wouldn't be able to do any sort of secure communication without the enemy knowing about it. Again, password protection would be meaningless, and also cryptocurrencies wouldn't have existed without this. Now, I'm not advocating the use of cryptocurrencies to anybody, but I'm just mentioning it here because it's interesting to see how it's done. Bitcoin right now has about $2 trillion market cap, and cryptography is the thing that's keeping it secure. Okay, it's one of the things. And it's just so interesting to see how it can't get hacked. Let's now talk about the Node.js modules that we're going to put our most focus on in this section. First and foremost is the crypto module. Now, well, here we go again, the crypto thing. Now, I just want to mention right now that this section is not at all about cryptocurrencies, okay? A lot of people, when they think of cryptography, they think about cryptocurrencies and also HTTPS, but these two are just such a tiny piece of this massive world that's now possible because of cryptography. So we're not learning this to understand HTTPS, okay? It's part of the reason. You'll be able to do it in no time, but it's not at all our main focus. So with this module in Node, we can do all the different things that we can usually do in cryptography, like encryption, hashing, and whatnot. And then we've got the TLS module, which is based on the crypto. So whatever TLS does individually, so it does many different things, they can all be individually done with the crypto module. And then we've got the HTTPS module, which is built directly on top of the TLS module, all right? So these are the three main Node modules that we're going to be using throughout the section. And well, the main one is the crypto module because it's at the core of everything. So we'll be spending most of our time using the tools that this one gives us. Now, also, all these things in Node are possible thanks to OpenSSL. So OpenSSL, just like libuv and V8, is another dependency in Node. It's an open source project written in C, and it has an implementation for all of these different cryptography algorithms, okay? So these algorithms are not a joke to design and do from scratch. It takes a lot of time to make sure that you implement them correctly. So even Node is not doing them from scratch. It's using OpenSSL. And it's the same thing in different technologies as well. So if you use Python or C, and if you want to do some of these cryptographies, they use usually OpenSSL or something similar to this one or a fork of this for all the cryptographic operations. Now also, having said that, I don't want you to think that cryptography is hard to understand. Absolutely not. Designing it from scratch, coming up with new algorithms, well, that's a huge process. It takes years and years of research by many people to design new algorithms and to make sure that they are secure enough. So that's a whole different league of its own. But learning how the existing ones work is really straightforward. A lot of people don't think that, but it really is, and you'll see that here in this section. That everything makes sense. There's no randomness. You can trace it on a piece of paper, one step at a time. And you can take a look at the implementation of the algorithms and even do them yourself here in Node and get the same output as the crypto module. So these things are easy to do, and they're not confusing. They just have too many different components. But once you take the time to understand each little component, you're going to see how easy the whole thing is. There are no weird things that we can't understand easily. In fact, cryptographic algorithms need to be easy to understand. Otherwise, not a lot of people are going to audit it, are going to look over it to see if there's a vulnerability in it. So a vast majority of the cryptographic algorithms are actually quite easy to understand. All right, so let's talk about these subfields of cryptography. Cryptography consists of three different sections. One is symmetric cryptography, and this all comes down to having a secret key and encrypting our data. And for as long as we have the key, we can encrypt and decrypt. Another part is keyless cryptography. And as the name suggests, here we do not have a secret key, right? So hashing algorithms are part of this one. And here we have an input, and we get an output, but we don't have a key. Again, don't worry about how this works. We'll get into the details later on in the course. And the last field is asymmetric or public key cryptography. Now, this one is all about handling these secret keys. So exchanging them correctly, making sure that you're getting the keys from the right person. And again, not from a malicious user who's pretending to be someone else. So in this section, we're going to be learning about all these three fields. First, we're going to focus on symmetric encryption, and then keyless cryptography. And the last part of the section is going to focus on asymmetric cryptography. We're going to be learning about a lot of different concepts. As I mentioned before, cryptography has tons of different components. All easy to understand, but many different ones. So to help you navigate around this section and not get confused as you're going forward, I have prepared a cheat sheet, and please download this one from the resource section of this video right now, and this one is going to help you a lot in this section. So I want you to download this, and always keep it open as you're going through the lectures. All right, now this is a big one, and we will be learning about all these concepts. So by the time that you're finished, all these terms, all these things will make 100% sense to you. Now also, this is not my final draft. I'm still working on it as of now that I'm recording this video. So whatever you download would look different from this, but the gist of it would be similar. All right. So here in this cheat sheet, I have added these 3 lines here, and I would recommend that you memorize this right away. But if not, it's okay for as long as you can quickly refer to this one. We will be doing these conversions back and forth a lot. You need to know it by heart, that 1 byte is equal to 8 bits, or 1 hex character is exactly 4 bits. So when we say F, we mean exactly 4 ones, all right? And also you need to know that 1 UTF-8 ASCII character is exactly 8 bits. So we're going to be using these concepts a lot. You're going to see me doing some math, using them back and forth. And if it doesn't make sense to you, you have to pause the video and then, well, refer back to this one. All right. Every single number that you're going to see here in this section should make sense. If it doesn't make sense, pause the video and then make sure that you understand how exactly I came up with that number. Okay. We'll also use these buffer functions a lot, converting from characters to binary, from hex to binary, and back and forth. Now, if you scroll down, here in this section, I have defined the terms. So we're going to be using a lot of terms and concepts in this section. And it could be a little overwhelming learning all of them in just 10 hours or so. But you don't have to memorize them. You can always come back to this cheat sheet and then know what I'm talking about. And I'm going to be using exact terms. So when we say clear text or plain text or ciphertext, we mean different things. I'm not going to be using plain text and clear text interchangeably. And if I do, it means that I made a mistake. It wasn't intentional. And please let me know and I'll fix it right away. So let's say that you're going through the section, and then I use this term pre-image resistance, and we have learned about it in one of the previous lectures. Now, if you don't remember what pre-image resistance was, I don't want you to just keep watching the lecture and then guess on your own what this meant. That would be a terrible way to approach this section and cryptography in general. At that point, you should pause the video and come to this cheat sheet and remind yourself exactly what is pre-image resistance. So please don't binge watch this section like a Netflix series. Every single term, a number that I use should 100% make sense to you. But there's a good possibility that you might forget about some of them as you're going forward with the section. And when that happens, that's when the cheat sheet would come into play. And also, please don't hesitate to use Google and other resources in case one of these definitions isn't clear enough to you. Now, if you try to read these right now, it probably won't make a lot of sense to you. But as we keep going forward and define these things, you'll be able to remember them by just a quick look and doing a Control F in this file. This file would also be a good recap resource for you once you're done with the section, so you'll be able to come back here and see all the concepts that we've learned and remind yourself of them. Now, I would also like to mention that this section is an advanced section. You should do this if you are in your 3rd year of development or at the end of your 2nd year and you've been doing it full time. If not, it's going to be really overwhelming. And also, this section is different from the other sections of the course. Doing cryptography isn't really like doing software engineering, as you'll see soon in the section. It's more like doing science work. Cryptography is really pure science. If I were to pick two fields in computer science that would really be just pure science, one of them for sure would be machine learning and all its subcategories like deep learning, reinforcement learning, and whatnot. And another one for sure would be cryptography, alright? So we have to think a lot here. We're using a lot of logic, math, probability, and it's not all just writing code and programming. Alright, that's a big difference between this section and the other ones, and it's really computer science-y, if you will. So if you don't like science, I can tell you that you're not going to like this section. But if you love science, this is really going to be something. Now, if you only care about learning the programming aspect of it, I'll show you how you can do that. Watch this video. That's only 11 minutes. Also link it to the resource section. And then you're done. And that's literally it. That's all that you need to know in terms of programming aspect. So in 10 minutes, you'll learn all the programming aspects related to cryptography. Alright? But now, using them to create secure applications wouldn't be something that you'll now be able to do. This is good if you just want to brag to your users that you're taking privacy into heart, but you really aren't, and you're really compromising your users. Now, don't get me wrong, this is a great video, but this is not meant to be watched by somebody who has no idea what cryptography is. This is great for somebody who understands the theory behind it, and now wants to see the syntax differences here in Node, okay? Not someone to get started in security. This is not how you want to go about it. It would be terrible. So if somebody understands the concepts, in just a few minutes, they will be able to get ready with a new language. So you can do this section not even using Node, maybe using Python or C. You just need to change the syntax that I'm using, but all the concepts are the same. Right? I could have just as easily in the resource section also put the codes using other languages and it would look really similar. An algorithm like SHA-512 is the same in Node, it's the same in C, and the same in all computing. So once you are done with this section, you'll be able to use the concepts anywhere that you want. Now, cryptography is a massive field, to the point that there are many people who dedicate their entire PhDs to cryptography. There are organizations that all that they do is cryptographic work. And we have job titles that have cryptography in their names. Two of the common ones are a cryptographer and a cryptanalyst. The job of a cryptographer is to create and design secure cryptographic algorithms, right? So secure encryption methods. And the job of a cryptanalyst is to attack and break encryption methods. So two job titles in this field. Now this section would certainly not make you a cryptographer or a cryptanalyst, all right? Absolutely not. But you'll learn what they do. You'll learn the idea behind what they do. And our main focus in this section is to learn how to use cryptography to create secure systems and protect others and ourselves. Our focus is not to learn how to design new cryptographic algorithms. That's a whole thing of its own, and that's not something that we're going to be doing. So we'll see how to use cryptography as a tool to do these things. Designing new cryptographic algorithms is absolutely not an easy task. It takes years. Something that's so simple, that's just 100 lines of code, takes years and years of research. Because we really have to make sure that there's no vulnerability in it. If there is something, if there's a little backdoor or something, then what's the point of doing encryption if it could easily get broken? Now, having said that, again, I want to mention, because it's so difficult to design these algorithms, doesn't mean that understanding the algorithms is also as difficult. If you think of other algorithms like merge sort or quicksort, if you want to come up with them from scratch, so imagine maybe merge sort didn't exist and you want to design it on your own now and invent it, now that's really going to take something, all right? But now understanding merge sort, well, that's something that you can do in just hours, right? So this is, again, our main focus in this section. And if you already know the concepts that I mentioned in the cheat sheet, please don't do this section. You'll find it too basic. This section is meant for people who all that they know about cryptography is just setting up basic HTTPS or hashing some passwords or setting up something like JSON W tokens, and they have no idea what is really going on. So this is meant for those people. If you already understand AES and RSA, elliptic curve, setting up message authentication codes and whatnot, you'll find this section just way too basic. These concepts are also usually taught in university computer science courses, so if you also have learned them there, you may not benefit a lot. It could count as a good review and seeing some of them in action in the real world, but don't really expect a whole lot. Now, I would also like to put a disclaimer here that please pay attention to your local laws before using the concepts that we're going to learn in this section for public use. In some countries, you may require licensing from the government if you want to do some strong encryption, and some countries outright ban it. I'm not sure what's going to happen in a few years, so please pay attention to your local laws. Cryptography is a powerful weapon. Think of it. You can set up systems and connect millions of people, and the governments have no idea what's going on. The governments don't like that idea, and there's always a constant attack from the governments on cryptography. Now, for personal use, it really doesn't matter. If you can use a VPN, then of course you can use all these concepts. But for public use, now that would be a different story. I wish I could give you something concrete that this is not allowed or this is allowed, but I really can't. These laws always change. The only thing that I can tell you right now is that in Canada and US, you'll be fine. Now, US actually has regulated the export of cryptographic systems, even the open source ones, so OpenSSL is complying with them. So just something to keep in mind. Now, I wish I could also say that in most European countries you'll be fine, but actually, it's such a coincidence that right now that I'm recording this video for the very first time, in such an unprecedented move by the UK, we see for the very first time a successful attack by a Western democratic government on cryptography. And this just happened yesterday, and it's just absolutely unspeakable that now UK has pushed back on Apple to remove the end-to-end encryption for iCloud. Now, this is just a massive deal, and the domino effect could come into play, and other countries could fall into this. And I'm really hoping that this would be reversed, but if not, it's just only going to get worse. Now, this actually started in 2015, if I'm not mistaken. So this fight has been going on for quite a while. And also, this is not just limited to the UK. It's happening in Canada, in the US. In the US, for example, it's happening by both the Republicans and Democrats. That's that makes it even scarier. It's the people who are helping to protect it. And we shouldn't be taking this cryptography thing for granted. It's really fragile, and it could be taken away from us if we don't fight for it. Just about yesterday, I think, February 22nd, this finally happened. And this is the first time that we're seeing this happening. All right, some countries, again, have outright banned it, but in Western democratic countries, it's just for the very first time. And this just makes you think what's going to happen in the future. So please pay attention to that. I mean, I don't know what's going to happen in 5 years. And so I just wanted to give you this quick disclaimer. All right, so before you go into this section, I also would like to talk about the prerequisites. I'm going to give you something complete in case you were getting this course just for this section. So the first one from the course, you need to have completed the understanding buffers section. This is mandatory. There's no way to do this section without completing this one first. You need to have a deep understanding of buffers and how to deal with binary content, because we're going to be doing that a lot. We're going to be seeing tons of binary content, modify them, deal with them. If you don't feel comfortable dealing with binary data, well, you will be by the time that you're done with this section. Right? So don't sweat it. We're going to do a lot of practice, but I expect you to have completed the section. Now, apart from the course, there are also some other general things. For example, you need to know the file system. If you haven't done it from the course, it's fine, but you need to know how to open files, read and write files, and get a file size and stuff like that. Basic stuff. Also, a bit of Node.js streams, but very basic. All that I expect you to know is how to use the pipeline function and how to give it a read and transform and write stream. So if you see a function like that and you can make sense out of it, that's enough. We're not going to do any crazy stuff in streams. Our main focus in this section is on cryptographic stuff and not really on these other node things. We'll keep the other things really simple. Also, you need to understand some basic networking. You need to know what is a DNS, what is HTTP, what it means when we say HTTP transfers in clear text. You need to know TCP and that HTTP is built on top of TCP. That's it. And also, you need to know some basic discrete math. You need to know combinations, counting, and probability, a little bit of number theory, and the truth tables. If you know these things, that's good enough. But, of course, the more you know, the better. If you know more things like the pigeonhole principle, birthday paradox, or even linear algebra dealing with matrices, that's fantastic, but it's not a requirement. I'll just give you a few questions in just a bit. If you can answer them, it means that you check this prerequisite, okay? So you're good enough. Now, apart from this one, there's also something that I would recommend, and that's just a little bit of Unix. Okay, nothing too much. I'm not going to be using Unix concepts a lot, maybe just a few times, 2 to 3 times, and I'll also explain it, so it's not going to be a massive deal. But I would recommend that if you're on Windows, please go with the WSL thing. Right, so watch my video in the Unix section where I teach you how to set up WSL on Windows. Alright, so about this discrete math, here I have 3 questions, and I want you to do all 3 right now. I'm going to show you the answers in just a bit. If you come up with the correct solutions, it means that your knowledge is good enough to do this section. But if something doesn't make sense, or if you come up with a number that's different from mine and you can't make sense out of it, I would say not do this section right now. Okay, postpone it, maybe do it next year or something. You're not ready for it yet. Right, so pause the video for a sec and do each one, and I'll show you the answers in just a bit. Alright, here are the answers. I'm not going to explain how we came up with them. This is not a math course, but again, I expect you to know exactly how we came up with these. If you have a different answer and you can't make sense out of it, again, I wouldn't recommend you to go through this section right now. In general, as a software engineer, you need to know at least some discrete math. So go ahead, maybe take a course in it. You'll always need this concept sooner or later, and yeah, that's it. Now, just one last point, let me go back right here. So I mentioned that we're going to be dealing with binary content a lot, so it'd be helpful if you can also install a binary viewer application on your machine. On Mac, I'll be using HexFiend, and let me just show you how it works pretty quick. So here, any file that I've got, I can right-click, and then click on Open With, and then this HexFiend. And then here I can see the binary content. I can also modify them. Now this is in hex, but I can also change it to show the actual binary content, but we're not going to be dealing with the actual zeros and ones because it's just too long. Instead, we're going to be dealing with the hex values. All right. And again, going back to the cheat sheet, remember, one hex character is 4 bits. All right. So it's just the same thing. Now on Windows, the application would be this one, HXD, and with this you can do the same thing. And on Linux you can use the Bless Hex Editor. It's installed by default on GNOME desktops, so just go here and search for Bless, and it should be installed by default. Now if you can't get your hands on one of these applications, it's still fine, you can just watch me do that, or just use the Node.js buffers to read the whole content and then log it as hex. Alright, that's pretty much the same thing. Alright, so having said all of that, should we care about learning cryptography? Well, the answer is 100%. Now, security is a process. You always need to build on it. And no system would ever be 100% secure. Alright, there will always be little things that you can get in. So it won't solve all of our problems, but I can tell you this. If you don't know cryptography, the theories behind them, you have close to a 0 chance of coming up with a strong application. There's a very good chance that you're doing something that's compromising your user's privacy. It doesn't matter if some powerful AI thing comes out, you still need to know them to deploy security correctly. Now, the alternative would be to not worry about security at all and always have cybersecurities on your team and let them take care of the stuff. But if it's you, maybe you are the owner, or you're doing the most of the work yourself, or if you want to know how to, I don't know, maybe hire a good cybersecurity person, it would help you massively. And it's not just about creating secure applications and protecting yourself, your business, and also your users, which is just as important. There are many companies, many websites right now that are compromising user privacy, losing their information all the time. Tons of bad things happening that could have been eliminated if these developers have spent some time to learn more about security and cryptography. Right, so I would say that everybody who's online should learn cryptography. Now, I'm a little biased towards it, so take it with a grain of salt. But knowing cryptography would just help you so much more to keep yourself protected. Now, it might not make a lot of sense to talk about it right now, but I can show you one quick example just so that you get some context in terms of what I really mean. Now, here in my browser, I'm on Google Chrome. I'm going to create a new tab, and I'm going to go to google.com. All right, I'm not going to hit enter just yet, but just watch me. So I'll now hit enter, and look at this. Now, if you've heard that if you're using HTTPS, you're now secure, you're now safe to put in your information and whatnot. Well, then look at this. And Google Chrome is telling me that the connection is secure to google.com, their own website, which has the utmost amount of security here. And if I click on this, again, information is valid, certificate is valid, and I see all this info. Now, this could be extremely dangerous. Imagine you go into your bank application and somebody is doing this. They would show you something that looks legit. Now, right now, this is just a hello world message, but it could have been something that would be much more legit, right? Like the actual login page of your bank application. And then you would put in your information. It would be sent to the hacker. So now that person has your credentials and you have no idea about it. Also, I'm not cheating. I didn't click on proceed. I didn't get any warnings whatsoever when I came here. In fact, if I go to a new browser now, maybe Safari, so I've never visited google.com here. I'll actually create a new private tab. And then here, go to google.com. Here, I'll see the exact same thing. And it tells me that my certificate is valid. All right, now I'll get all these check marks. My point being that for somebody who doesn't understand cryptography, these attacks could happen on them and they have no idea. But if you do, you are in a much, much better position to protect yourself against these cyber attacks. And this is just the tip of the iceberg. I just showed you an example to just maybe get some context, but it's much more than that. By the way, this thing that I showed you is what we're going to do later on in the asymmetric section. So we're going to learn about every little detail of HTTPS and set it up from scratch ourselves. So we're not going to be just throwing random stuff in our terminal and then get some files, submit them to a random, application, and then boom, we've got HTTPS. Absolutely not. We're going to set it up all from scratch. And this would now work on any domain name. Even if I go ahead and turn off my Wi-Fi completely, I still would be able to get this HTTPS. Right? So if people told you that you can't get HTTPS locally if you are not connected or if you don't have a domain name, well then look at this. It's totally possible, and you'll see how. So I have a really strong belief in this, that people should learn it. If you are a software engineer, 100%, even if you're not, at least you need to know it. And it's just so fascinating. You have access to the same tools that FBI or CIA, powerful governments, have access to and use to protect themselves against really powerful enemies. And you can understand them and use them yourself to design very strong systems and applications. And it's not just about that. I think people need to learn about it. That UK law that we just saw, I think it wouldn't have happened if enough people knew about cryptography and they would have fought against something like that. It's really fragile. It's incredibly powerful, but incredibly fragile. It could be taken away from us. All it takes is a small little backdoor or an easy way to access the keys, and that's it. It's over. Encryption would no longer be close to a mathematical impossibility to break. It would now become a question of who has the most power, money, and knowledge, who can now see everything that you do online. There are constant attacks on it by the governments and central powers, and I wouldn't rule out that not ever happening. In fact, it has already happened in many countries, but it could get much worse. Now, this wouldn't have been a massive deal, let's say 30 years ago, because nobody was using anything digital much, okay? The internet really wasn't there. But now, everything that we do is online. So this thing happening is just so massive, so insane to even think about, but it could happen. So if you set up cryptography correctly, no one can access it. Okay, this is a really powerful thing. It's the thing that protects our privacy, our freedom of speech most importantly, and so much more. People who understand cryptography, they have a massive digital power over surveillance and censorship. Now, having said that again, it doesn't mean that it would solve all our problems. Again, security is never 100%, but you could get so close. You could make it so much more difficult for somebody to now attack you or to see what you're doing. The more you learn, the better you can now protect your system, your app, yourself. So all the encryptions that we're going to learn in this section are unbreakable, right? Nobody can break them, not even the government. Doesn't matter how much money they have, how many supercomputers they have, it just won't happen as of today. Now, it could get broken one time in the future, but as of now, it just won't happen. Now, I also don't want you to get into the section with some unrealistic expectations. I know I said it's unbreakable, but that doesn't mean that if, say, a powerful government now wants to launch an attack on you, they can't do it if you're using encryption. Again, although encryption is not breakable, security itself is. I will explain later on what I mean by that unbreakable and impossible to break. You'll see that later on in the section. But generally, nobody breaks encryption. What happens is that they break something else in security. For example, one of the most terrifying attacks in cybersecurity is the zero-click spyware attack. This is a type of malware that can be installed on your iPhone or Android device without any user interaction. And it's not just for ancient old phones. This can be done on an iPhone running the latest iOS. So the way that it works is that the spyware gets installed without you even having to click on anything. So your phone sitting right there, it comes in through a WhatsApp or a simple text message, and then it gets installed on your machine, and you wouldn't even know it's there. And it could now spy on you. It could now turn on the camera without even triggering the privacy things. So you wouldn't see any like green dot or something that now your camera is on, or your microphone or whatever you have, because they can bypass hardware restrictions. So if something like this gets on your phone, it doesn't matter if you're now using the strongest cryptographic systems in the world, and you are using HTTPS all the time, your phone is always up to date and all that, it could still happen, and you wouldn't even know that it had happened. That's why it's so terrifying. Now, there are so many conspiracy theories around it that are absolutely not true, but this thing exists. It's going to cost hundreds of thousands of dollars, even millions of dollars, to launch an attack like this. So this thing exists. Its existence is not a conspiracy theory, right? We know that this thing is there. We know that some governments have access to it and have also used it to target some individuals. It doesn't sound legal, but it is what it is. And the way that it works is that, well, if you go here to the Apple security website, as I mentioned, this happens with both iOS devices and also Android ones. So here in the Apple Security Bounty, they show you how much they're going to pay you if you find a vulnerability in it. And if you scroll down here, the most insane one is this one. Network attack without user interaction. Okay, so the zero-click attack. And if you can find this, you're going to earn $1 million. Right? You can also here turn on the examples to see what exactly they mean. So it's a very costly attack. But the way that it works is that governments and spyware companies that have infinite source of funding, they would go on dark web or different places and put on a much higher bounty than this. So they would say, if you can find this and give us the solution, we're going to pay you like $5 million or $10 million. So some people won't give it to Apple or Google. Instead, they would give it to these governments and companies. And this is a constant loop that keeps happening. So something like this gets found, sold to the highest bidder. Then a few months later, or even years, Apple and Google are going to know it and then push a patch. But then after they do that, a new thing is going to be found. And then again, a whole cycle just keeps going on around. Now you might be saying, why don't Apple just put a higher bid? The point is, Apple can't outbid these governments. They have infinite source of funding, so whatever Apple says, they would put something higher. All right, so I don't want to make anybody feel paranoid, but the point that I wanted to make was that even if you set up everything correctly, there's always a way to get in. Now, even against that zero-click attack, you can protect yourself by having another device and not putting a SIM card to it or not connecting it to the internet. So even the most terrifying cyber attack that we have, you can, well, technically prevent it. So not only security can always be bypassed, all the known attacks can also be protected against. It's always a matter of who can outsmart who. But if you don't know the concepts, if you don't know cryptography, you have really zero chance, not just against these ones, but there's a massive world of attacks out there against personal digital devices and also, well, your servers, your web applications. And you need to understand these concepts so that you can now protect yourself. And you can now outsmart the attackers and make it really, really costly for them to launch an attack on you that they're not going to bother. Right? So that's something that you can do. But 100% bulletproof thing is just something that we can't do. All right, so let's get started and start to explore this fascinating world and see the possibilities that now we have because of it. So let's jump right in, and I'll see you in the next one. In this video, we're going to have an introduction to symmetric encryption. We know this is one of the main types of cryptography that we can do. The other two are asymmetric encryption and also keyless cryptography. So let's have an introduction to this one. Let's see how this works. Imagine you've got a piece of data. This could be a piece of string or a video file or anything. It's just a binary data. And then you give it to something called a cipher. For now, just think of a cipher as an algorithm or a method that gets an input of data and then it spits out something that doesn't make any sense. Alright, so we're encrypting the data with the help of this cipher. Now we are doing this encryption with a key. So with this key and this cipher, we are converting this data into something that is totally different. Okay, so this data right here resembles nothing of this data right here. They're totally different. If this is a video file and now you try to open this up as a video file, you just won't understand anything. You won't even be able to play it, and even if you can, you're just going to see some noise. Now that's the idea of symmetric encryption. Pretty straightforward. We've just got a key and an algorithm, and then we change our data. Now this thing right here could be transferred to anybody, and anyone can see this data but won't be able to make sense out of it unless they have this key right here. So this is a one-way function. If we want to go backwards, so we have this gibberish and we want to see our original data, we could at any time that we want go backwards for as long as we have this key right here. Your cipher really doesn't matter because it's usually out in the open. Every time you send a message, for example, through the internet, you almost always specify what your cipher is. But the key is not something that you put out publicly. Okay, you have to keep it as secure as possible. So an important part to understand right now is that if you do not have this key right here, there's no way for you to go backwards. Okay? If your cipher is powerful enough and good enough, there's no way to do this, okay? It's just mathematically impossible, and it's going to take you trillions of years. Now, we'll see that more later on, but for now, just know, if you don't have this key, you can't reverse this process. That's why it's so secure. Now, some of the examples of symmetric encryption, the standard right now and the most common one is AES. We'll dive deeper into it later on, but it has been the standard for the past 20 years. So, it's really difficult to come up with a new encryption system. It has to go through years and years of examination and research to make sure that an encryption algorithm is good enough to use. If you leave even one single backdoor in it, it could now be broken. If we have a skilled hacker, they could easily break into it if you have a backdoor, but if you don't have any backdoors in it whatsoever, it is impossible to break into that. Now, when we say impossible and unbreakable, in cryptography, everything is breakable. Like any other form of security, you can always break it. But by that, we mean that it's so secure that you're not even going to try to break it because it's going to take you trillions of years, okay? Now, another example that we have is ChaCha, and the other one is DES. Now, this DES right now is now outdated. This AES has replaced it about, again, 20 years ago. This DES was also used for roughly around 20 years. This DES became a standard at around late 1970s, and then about 20 years, it was all good. And after 20 years, people realized that it's no longer secure. The computational power has gotten so strong that we can now easily break it. So at that point, everybody tried to come up with a new encryption algorithm, and then after years of trying, they came up with AES. So this is now the standard one. That's why I've bolded the text. Now the ChaCha one is kind of like an alternative to this AES, so that it's the logic of not putting all your eggs in one basket, that if at one point we can break AES, now we don't need to shut down the whole internet. We've got another way of encryption that we can now fall back onto. Okay, now we're going to talk more about some of them later on, but for now, just understand the concept of symmetric encryption. Now, before we move on any further, I want to introduce some terminology that you need to understand. Now, the first one is plaintext. Plaintext just refers to original data. The other one is ciphertext. We refer to our encrypted data as ciphertext. So in our previous example right here, this would be our plaintext right here. And then this one right here would be our ciphertext, okay? The next word that we need to understand is, well, encryption, which just means converting data from plaintext to ciphertext. Then we have decryption, which is the exact opposite, going from ciphertext to plaintext. And then we've got cipher. Cipher refers to our method or algorithm that we use for both encryption and decryption. Now, there's just something that I want to clarify, and that's the word text in both plaintext and ciphertext. Now, the reason that we have this word text is more of a historic reason. I want you to understand that all forms of encryption that we were using right now in computing all deal with raw binary data. They don't care if it's a text file or if it's a video file or an application, they're just going to do it, okay? If you have watched the compression section of this course, you remember that we talked about that we've got some compression algorithms that are more optimized to deal with specific data types. For example, a compression algorithm that could compress video files better, another one that could compress images better. Now, that is not the case here in cryptography. Okay, we don't care what our data type is. We're just doing some mathematical operations on our binary data. Okay, and that's it. Now, the reason that we have this text in these words is, again, historic reason. And if you want to understand it, just look into this Caesar cipher right here, okay? It's, again, another form of encryption and decryption that has been around for thousands of years. Nobody uses it anymore in computing. It's very unsecure. It was broken, but it's something really straightforward. It was usually used in military. Nowadays, it's used by kids, and it's very easy. You can learn how it works in just no time. I'll link a YouTube video to this one that's from Khan Academy that goes over this for just about 2 minutes. The idea of this is that we are just changing our letters. So you can imagine that we're maybe substituting A with maybe D or Z with, I don't know, B, so something like that. We have a map like that, and our key is how we're doing this replacement. And then once we do the replacement, we're going to end up with something that looks like text, but it's gibberish. You can't make sense out of it unless you have the key and you reverse the process. A lot of the textbooks and courses, when they're teaching cryptography, they use this thing as an introduction, but I don't think it's really important because it's not like how we're doing encryption at all right now in computers, okay? In computers nowadays, we're not just dealing with text, we're dealing with raw binary data, but this form of encryption could be a good start if you want to learn how to do some form of something on a piece of paper yourself. Alright, so that's it about the Caesar cipher. I'm not going to be talking about it anymore, and the only reason that I want you to understand it is because the words plaintext and ciphertext. Okay, so because before, believe it or not, again, encryption has been around for thousands of years. And back in the day, they would just deal with text. Okay, so plain text, now to ciphertext. And now, in this day and age, we still stick with these words. These words are standard across all cryptography textbooks and papers, so that's why I'm going to stick with them. Okay, I might refer to this one as plain text or original data. From now on, if I use one of these words, I expect you to know what they mean. Alright, so that's the idea of symmetric encryption, and now let's go ahead and take a look at a simple example here in Node. So I've got my crypto folder, short for cryptography, in my uncc-code, and here I just have one file. We're not going to code anything, but I just want you to take a look at this and run it yourself. So you can download this code from the resource section of this video, and all that I want you to understand at this point are just the comments that I wrote, and that's it. So here we're specifying our cipher, which is AES, and this 128 refers to our key size, which is 128 bits. Now, we can't go with any number that we want. It has to be either 128 or 192 or 256. But if you change it, for example, to 256, now you need to change your key right here to 256 bits as well. Now, we're not going to talk more about it. We'll dive much deeper into AES later on. But for now, just know that we've got the cipher right here. And also this one is our mode, which is something that we will discuss later on again and not now. Next up, we've got the key right here, which, as you can imagine, is just a bit of zeros and ones. And I'm converting this one from hexadecimal to binary, and then we're using it as our key. And that's it. Here we've got the encrypt function that gets a plaintext, and then it gives us ciphertext. Don't worry about what's going on right here. We're going to code more complex things from scratch, but for now, just know what this function does, and that's it. And then same for decrypt. Gets a ciphertext, and then it gives us the original plaintext that we had before. And if you take a look here, both of them are using the key that we had to both do the decryption and also encryption. Alright, moving on. Here we were defining our plaintext, which is again just some amount of binary data. So here my data is, my password is this, and you can imagine that we want to transfer this across the internet to someone else. Now, whenever you transfer something in clear text, for example, using TCP or HTTP to transfer it, anybody could see what is going on. Okay, so they could just connect to your network and see exactly all the traffic, all the packets that are being exchanged. All right, so if I send this buffer right now through HTTP or TCP or anything else, anybody could see what this password is, which is really problematic. Imagine this would be credit card information or a person's personal data. You do not want to send it in clear text. So what we're doing here is that we're encrypting it, we're getting the ciphertext, and then right here we're decrypting it to see the original plaintext that we had. And right here we've got 3 logs for the plaintext, ciphertext, and also, again, the plaintext after we do the decryption. All right, let's go ahead and run this and see what's going to happen. So here I'm going to say node app.js, and here we go. So this is, again, our plaintext, and then if you take a look at the ciphertext, it's just something super gibberish, okay? It doesn't even look like text. It's something that a character encoder doesn't even understand. All these question marks just mean that we've got a piece of data that UTF-8 has no idea what that thing is, or my terminal just can't display it. But the point is, this resembles nothing of the plaintext. In fact, if you can take a look at the ciphertext and learn some things about the plaintext, that means that the cipher that was used for encryption was a horrible one. There should not be any way for you to know anything about the plaintext by looking at the ciphertext. You shouldn't even know the data type. And then after we do the decryption, here we can see that we get the original data and we're not even losing a bit. So this process is lossless. We can encrypt and decrypt without losing anything whatsoever in symmetric encryption. Okay, so that's the idea of symmetric encryption. If you understand what we're getting here in the logs, that means that you are now ready to dive deeper into this concept. Now, before we go deeper into this AES and symmetric encryption in general, I want to take some time and design a symmetric encryption form ourselves from scratch here in Node. The thing that we're going to do is usually described as the perfect encryption. That's the most secure form of encryption that you can do. It's called one-time pad encryption, and we can easily implement it from scratch. The reason that it's not used everywhere is because the key management is going to be a nightmare, and you'll see exactly that in just a minute. But that's going to give us a great start into this world of cryptography. So that's it about this video, and I'll see you in the next one. Now that we have some sort of an idea about symmetric encryption, in this video we're going to implement a symmetric encryption from scratch that is usually described as the perfect encryption. This encryption is called one-time pad encryption, and the pad word right here refers to the key, and one time means we only use our key once. And every time we do an encryption or decryption, we will now destroy the key that we used, okay? Now, theoretically, this is even more secure than AES and any other form of encryption that you might see. It's immune to quantum computing, and there's just no way to break it. This video will give you a strong foundation to explore other cryptography concepts and not have this idea that when we're doing encryption or any other form of cryptography, we have this black box and just things get into it and come out of it. Not really. All that we're doing is that we're doing a bit of mathematical operation on our data with the help of a key, and then end up with a result. So this idea is going to be much more clear to you after this video, and then you'll have a much better idea about what cryptography is. Alright, let's talk about this one. Alright, so here, as the name suggests, we've got some rules that we need to stick with to make sure that we've got the perfect encryption and it's theoretically unbreakable. First of all, the key length must equal the message length. Alright, because we're doing bitwise operation. We take each bit of the message and then each bit of the key, and then the result of that operation is going to be that particular bit of the ciphertext, okay? The second rule is that the key must be truly random. Now, the concept of randomness in computers is quite interesting because they're very precise in programming. You'll see that. You have to define exactly what should happen, and you'll never see random results. So to make sure that we can randomly generate some things in a computer, we have to get really creative. Now, you shouldn't really try this yourself. Even if in your mind what you're doing in a computer is random, in reality it's not. Okay, so if you just take the time and then you do some mathematical operation on it, a cryptanalyst could eventually figure it out and then break your encryption, okay? So we rely on something that OpenSSL does to make sure that we can generate truly random data, and Node is using it. Pretty much tons of other applications are using it, and that's what we're going to do. Okay, so we're not going to take care of the randomness ourselves. It's a very difficult task, but still doable. But we're just going to use OpenSSL to do this operation to make sure that the bits that we're getting from that function are truly random. Now again, this is not specific to one-time pad encryption. Later on, you'll see at different points we need to generate random data. And if the data that we're using is not random, well then that form of security could easily be broken. Alright, the third requirement for this is that our key must only be used once and then destroyed after we use it. Okay, so pretty straightforward. We've got these 3 rules, and of course we've got some other things we need to adhere to that are common with any other form of encryption. For example, keeping the key secure. We need to make sure that the key is only accessible by people who want to communicate and no one else. Alright, so I talked about that bitwise operator that we use to do this thing. Imagine that this is our plaintext, the data that we want to encrypt, and this is the key that we generated truly randomly. Okay, so each bit right here was generated in a very random way. So this is the plaintext again, this is the key, and then we do this bitwise operation right here, which we're going to talk about in the next slide. Once we do this operation, here's what's going to happen. So we take each 2 bits, and then we do this thing, and this is called the XOR operator. And what happens is, if both bits are identical, the result is going to be false or 0. And if one of the bits is different, then the result is going to be 1. For example, in this case, both are 0s, then the result is 0. In this case, one of them is different, then the result is 1. Pretty straightforward. And now if you think about it, there's no way to go from this ciphertext back to this plaintext unless we have this key right here. Now let's talk a little bit more about this operator right here. It's called again XOR operator, and the symbol in computer science is this one. It's done in hardware, so you give it 2 pieces of bits and then you get the result. Now again, it's very easy. If both bits are identical, for example, both of them are 0s, then the result is going to be 0 or false. So again, if both bits are also 1s, it still is going to be 0. But if one of the bits is different, for example, 0 and 1, then the result is going to be 1 or true. Okay, so 0 or 1 or 1 and 0, still the same thing. Alright, let's do one example. Let's say that we want to do this. Let's say that we want to XOR these 2 pieces of data, and here's how it works. Again, notice that it doesn't matter what our data is. Our data could be a string, or it could be part of an image. It just doesn't matter. We can do this operation no matter what type of data we have. As long as it's 0s and 1s, we can do it, okay? Alright, so these 2 are different, so the result is going to be 1. Same for this one, different, and then this one is also, they're both different. Now this 4th bit right here, both of them are 0s, so they're identical, so the result is going to be 0. Now this one, same, identical, so 0. And then these 2 are different, so 1. These 2 also are different, same with the last one. So this is going to be the result of our XOR operation. Alright, here's an example for you. Just pause the video for a sec and calculate this XOR. I've also got the table right here for your reference. So pause the video and I'll see you in just a bit. Alright, so the result is this one. I'm not going to explain it. If you don't have this result, please rewatch this video again so that you'll understand how to do it. Alright, let's now see how we can do this in Node. This XOR thing is quite important to understand because it's used not just in one-time pad encryption, but in tons of other encryption algorithms out there. For example, DES uses it, AES uses it. So if you want to understand how these algorithms work behind the scenes, you should for sure understand this one, which is, as you can see, is very straightforward. All right, so here I'm going to go into my Node REPL. And let's try that last example that we had. So here we've got this, and its hexadecimal value is A4, and then this one, which is F3. Let's do this now in Node. Here I'm going to say const maybe A equals buffer.from A4, and then I'll convert this one to binary like this. And then I'm going to define another one, const B equals buffer.from, and then the second piece of data that we had was F3. And I'll do the same thing and have it in binary from hexadecimal. Right, so we've got these 2 buffers. Now let's say that we want to now do an XOR operation. So we'll take the first byte of this one, which is A and then 0, and also the first byte of the second one. Now, the operator in programming is usually the hat icon, and if I run it, I'll get this value 87, which is in decimal. Okay, so let's confirm this one. So here in my calculator, I'm going to put in those values. So A4 that we had right here, and I'm going to XOR this. So I'll click on the XOR operator, just like the normal mathematical operations, like plus, minus, and so forth. And then I XOR it with F3. Then I hit the equal sign, and here's the result in hexadecimal. If you take a look at the binary value, which is 0101 and then 0111, This is exactly what we had right here. Okay. Now, if I switch this up to decimal, I'll get 87, which is the result that was returned to me here in Node. And that's it. This is the XOR operation. Now, we've got some other operators. Now, we're not going to get into the details of these. This is a topic of computer architecture and way outside of the scope of this course, but it's something that I highly recommend you to learn. If you learn about these logic gates, you'll eventually learn how to design some pieces of hardware, design a simple CPU, a simple microprocessor that can act like a calculator, or maybe transform some text to uppercase. So it's pretty cool, and you'll get to learn a lot, which will give you a good foundation, but we're not going to get into it much deeper than that. So two of the other ones that we have, one of them is the AND operator, and this one is really straightforward. It's like the AND that you do in JavaScript if statement. So if both are false, it's going to be false. If one of them is true, but the other is false, the result is still false. But if both are true, then the result is going to be 1. The symbol in computer science is the hat icon, not to confuse this one with the hat icon in programming that we use to do XOR. And if you want to do it in Node, you have to use the AND. So here, if I do this, this is now going to be that result. Okay, so this one right here is this AND right here. And then same with the OR, but this one, the result is going to be true only if one of them is true, and that's it. These are based on the same concepts that you've learned probably in high school math. So logical math, that P and Q, if both are true, the result is true. If one of them is false, the result is false. And then P or Q, the same thing as this one. All right, so that's it about the bitwise operators. I'm not going to talk about them any more than this. And now let's go ahead and use this to implement the one-time pad encryption from scratch here in Node. All right, here I'm going to create a new folder, and I'm going to call it OTP, short for one-time pad. Now let's create one file. Let's first have a file that we use to generate a key, and that's it. So I'm going to call it generate key.js. And here's how we can generate truly random data in Node. So we first need to grab the crypto module. And then here I'm going to generate the key, so const key equals crypto. And the function that we can use to do this is called random bytes. Okay. We also have another one that's called random fill, but with this one we have to also give it a buffer. But with random bytes, it will automatically return a buffer. So here, all that we have to do is to specify the number in bytes. I'm just going to say maybe 100 bytes. Okay, so now this is going to give me 100 bytes that are all truly random. So there's zero chance for anybody to guess what this thing is going to be. So let's log this. Console.log the key, and let me now run it. I'll exit out of the REPL and then navigate to the OTP folder and node generate key.js. So there we go. Now we're going to use this as a key to now encrypt some messages. Okay, so I'm going to save this key to a file. So let me include the fs module. And then here, instead of logging it, I'm going to say fs.writesync. Let's write it to a file called key, and then our key. I'll also add a comment right here, 100 bytes of truly random data. And of course, if we want to now generate a random number, this is just a number in binary, so you can easily convert it into a decimal number, and there you go, you've got a random number. This one should also be write file sync and not write sync. Okay, so I'm going to run this one more time. And now we have the key right here. We can't open it because it just holds some binary content, and that's it. Now, one-time pad encryption was usually used before and during Cold War and places where security was really important. Nowadays that we have AES, it's secure enough. And sure, this one is going to be still more secure than AES, but the key management is going to be a pain, and it's just so difficult that we're not going to bother with this one. Okay, so AES is still very, very secure. We're going to talk about it. Breaking that is not going to be a joke. It's going to take years and years, and no one has yet managed to break it. Now, the small application that we're going to implement right now would be something like this. So imagine we're in military and we want to exchange some messages across between a command center and also maybe a station. In this case, we're going to go maybe with a submarine. we're going to maybe exchange some nuke commands, so they have to be very, very securely exchanged. The enemy, when they listen to our radio frequencies or the messages that we're exchanging across the internet, they would still see what we're exchanging, but there's no way for them to figure out what they mean, and they can't break it, okay? So here's how we would do it with one-time pad encryption. We will first generate a key, maybe here in the command center, and this is going to be our key. And then someone physically is going to go from the command center to the submarine and have a copy of this key, okay, very securely. So now both entities have this key, and they are both sure that no one else in the world has this key. And the key was not exchanged on the internet. It was exchanged physically with a person going from here to here securely, okay? Now, the message that we want to maybe encrypt is going to be stand by to launch, okay? Now, to encrypt this, just like we saw in the slides, we're going to take a piece of the key, so this much, that's equal to the size of the message, and then we're going to XOR that key with the message. And then, after we do that, we're going to destroy that portion of the key. So now we have our ciphertext, this red rectangle right here. Let's say that this is our ciphertext. And there's no way for us to now go backwards because we destroyed the key. And if someone manages to take a look at this one, they have no idea what this means. The only person that now has an ability to see what this means is the submarine or the station right here. We don't care if the connection is unsecure. We have already encrypted the data. So we're going to send it across. The station is going to, just like before, use a portion of the key that's equal to this size, and then destroy that portion and do the XOR operation, and now they've got the same message, okay? And that's it. That's how we can exchange messages now in a very secure way. And no one could now break this, okay? So if you want to really securely communicate with a person, you can do something like this. You can meet up in person in a park or somewhere, exchange your keys, and then do this. And this is actually what people used to do a few decades ago, before we had AES. Now we have a mechanism to exchange keys securely, so we don't need to meet up in person if we want to do that. And that's the topic of asymmetric encryption, which we're not going to talk about right now, but for now, let's understand this one, which is really important. Okay, so this is the idea of our application. Let's now go ahead and implement this in code. So here we have the key. Let's imagine that these two people are going to now have the key. So I'm going to have two files here. One of them I'm going to call it commander.js, which we're going to use as the command center. And then one more that we're going to call maybe station.js. So imagine this one is one entity, maybe in New York, and this one is another entity, maybe somewhere deep within the ocean, okay? So here in the commander, we're going to do this. We're going to first read the key, so we need to have the fs module, require fs, and then here's the key. So const key equals fs.read file sync, and I'll go with that key. And we're going to do the exact same thing here in the station, so I'll paste the code here. And this thing that we're doing here, reading the file, I can imagine that this is the part where one person takes the key and goes to the submarine to give the key to them, okay? So that's what we're doing here. All right, so now that we have the key, let's have a function here called encrypt, which is going to get some amount of data, or we can call it plain text. Let's actually call it plain text to be more consistent. And now let's create a buffer for our ciphertext. So I'm going to say buffer.alloc, and we want to have this buffer that's the same size as the plain text. So plaintext.length. So right now this is just a buffer, but now we need to do the XOR operation and write the results to this ciphertext buffer. So let's have a for loop. Let I from 0, and then I plaintext.length, and then I++. For each byte, we're now going to do this operation and then save the result to this ciphertext. So I'm going to say ciphertext, the element I, is equal to the plaintext of I, and then XOR this one with the key, but the ith element, like this. And then after we do the XOR operation, we're going to destroy the portion of the key that we used. So I'll say key I is now equal to 0. And then once we're done, we're going to return the ciphertext. And that's it. All right, so let's now encrypt something. So here I'm going to say maybe const message1 is equal to buffer.from. And let's say maybe Commander Henrik has said stand by to launch. And then right here, I'll say const message1 encrypted is equal to encrypt the message1. And there we go. We're now ready to send this message across to the station. And the station should now be able to decrypt. Let's log the message. So console.log message1 encrypted. Let's run this and make sure that we don't have an error. So node commander.js, and here's our buffer. Now we're going to manually copy it and put it here in the station because we don't want to set up a TCP thing and then transfer this across. We've already talked about how to do it in great detail in the networking section and HTTP, so we're not going to do it again here. But let's just copy paste it to emulate the process of sending it across the radio or across the internet. So here in the station, we want to do the exact opposite of what we did in the commander. Let's imagine that we don't want to do any form of encryption here from station. We just want to decrypt the messages that are coming from the commander. So I'll have a function called decrypt. We're going to get the ciphertext. And then here I'm going to have the plaintext. So const plaintext, just like before, let's allocate a buffer. So buffer.alloc. And it's going to be the same size as the ciphertext.length. Now with the plaintext in place, we're going to do a bit of for loop to do the XOR operations again to reverse the process. So let I equals 0, I less than the plaintext dot length, and then I++. And then here we're going to say plaintext I is equal to the ciphertext I, just like before, and then XOR this one. So this byte is going to be XORed with the key. And then we're going to destroy the portion of the key that we used. So key I should be equal to 0. And then we're going to return the plaintext. All right, let's now have our message. So message1 is equal to buffer.from. I'm going to go ahead and copy the buffer here from my terminal. I'll just copy the hex values, and I'll paste it right here. And I'm going to remove all these spaces in between like this. It's going to take just a few seconds. And now I'm going to hit the backspace and then say convert this now to binary from hexadecimal. All right, with the encrypted message in place, now we're going to do a decryption. So I'll say const plaintext, or here we could have also called it ciphertext. Again, I'm going to use these terms interchangeably, and I expect you to know what they mean, okay? So const plaintext is equal to decrypt the ciphertext. Now let's now log the result. So console.log plaintext.toString and UTF-8. All right, so let's now run station.js. And I got a quick typo right here. Just need to have a space here. And now it should work. And there we go. We've got the message from the station that says Commander Henrik, stand by to launch. So this is the idea of one-pad encryption. As you can see, it's very straightforward to do, yet so difficult to break. All right, so I just want you to now think about something else. The problem that we have with this approach that we're using. And the problem is the key management is going to be so incredibly difficult. Our key should be the same size as our data. So what if we now want to encrypt our whole disk drive? And our disk is 1 terabyte. We need to generate a key that is 1 terabyte in size and then keep that securely, which is going to be a challenge. If you want to encrypt all the traffic throughout the internet using one-time pad, we need to always generate just the same amount of key as the same amount of data that we have. So all of a sudden we have to double the amount of storage on all the data storages in the world, which is going to be insane. Okay, so we have a big problem with this one, and that is, again, the key management. Having said that, before AES and also DES, again during the Cold War and sometimes when military needed to do some very secure communications, they did use this approach to do them, alright? Because it could work if your communication size is not that large. So you can just add in a few zeros here and then all of a sudden you can now communicate way more, okay? So it's not that difficult to do so, but not to encrypt the whole internet. Plus, AES is still secure enough that you don't even need to bother with something like this, okay? You can just stick with AES and you will still get, well, not as secure as this one, but still ridiculously secure that no one is able to break it. So you can imagine that now you can use this one to encrypt and decrypt multiple messages. Here we're only going with one, but if you have another one, for example, const message 2, because you want to do this back and forth all the time, right? So this one, so it's a very easy change. You just need to also take care of an offset and also make sure that your key is long enough to cover the whole communication. So here, let's say that we have another message from the same commander, so Commander Henrik, and this time he says terminate operation immediately. And you'll do the exact same thing, so you'll take the message, you'll encrypt it, but now here we also need to take care of an offset, so an easy change. So let's key offset equal to 0, and here you have to add it into the key, so key offset plus this I, and then the same thing here, so key offset plus I. And then here, once you're done, you have to update the key offset, so key offset equals key offset, and then plus the plaintext dot length. So the next time that we want to now encrypt, we're going to now use the next portion of the key and not the portion that we used and destroyed. Here at the beginning, you can also have a check that says if the key length is not enough to encrypt the message, just return an error. I'm going to fast forward this. All right, here we go. So this message just says if the key length is not enough to encrypt, we're just going to return an error. Now, if I run this, we should get the same results. So node, commander, and then here's our buffer. And we can do it multiple times, so we can also encrypt message 2. And then I'll log the other one as well. And now we're encrypting both of them like this. Now we also need to do the same thing here in Station. We'll do it right now pretty quick. I'll fast forward, and then you can grab the code from the resource section if you're interested. Alright, here we go, and you can see that now we can exchange multiple messages with the help of that key offset. I missed this last portion because in my log, the last byte was not displayed, which is not problematic. But you can imagine that this is how it works. Now also again, you want to destroy the key after you read it because, well, we have the key right here and we are not adhering to one of the rules that says destroy the key. Well, we're doing it here in our memory, but still it exists on the file system, which is not something that we want. So here after this part, after both read the key, you can imagine that we're going to destroy the key from the file system. We're not going to do it for the sake of testing and playing around with it. Alright, so that's it about this video and one-time pad encryption. Hopefully now you have a better idea about what happens when you're doing encryption. Again, it's not magic, it's just some math like this. And with this knowledge in place, we are now in a much better position to understand AES. Alright, so that's it about this video, and I'll see you in the next one. Now that we understand how symmetric encryption works, in this video we're going to dive deep into the most common form of symmetric encryption, which is AES. AES is used in tons of different places in the computing world. For example, it's used in database encryption, in end-to-end encryption. When you send a message on WhatsApp, iMessage, or any other messenger application that uses end-to-end encryption, they use AES primarily to encrypt your messages, and then that message is going to get decrypted on the receiver's device. So the server, for example, WhatsApp or Apple, they have no idea what the message is that you're sending across. And there's no way for them to do that because we haven't yet managed to break AES. Another example is SSH. Your commands are being encrypted and sent across the server, and then from server encrypted, sent to your machine, and then decrypted on your machine. It is used in banks and ATMs for securing the transactions and so much more. It's used in HTTPS to encrypt traffic from your machine to the server and vice versa. So let's see this HTTPS pretty quick right now. So here I'm on Firefox and you can do the same thing. And I went to the Bank of America website and I want to log in now. So let's see what encryption algorithm is used. When I put in my user ID here and password, and then click on login, let's see how my data is now being encrypted and then sent to Bank of America servers. So here if you click on this little lock icon, and then click on this thing that says connection secure. Here, if I click on more information, in this pop-up menu, if we zoom in the technical details, we can see exactly the type of cryptography mechanisms that are used right now to encrypt my traffic from my machine to the servers. So here we can see that it says AES-128 GCM mode. Alright, so AES is used now to do this encryption. Now we've got some other things. For example, it says ECDHE, which is Diffie-Hellman, and RSA, so these with the AES. We're going to talk about all these items right here, so by the end of the section, you'll understand exactly what TLS is, what Diffie-Hellman is, what RSA is, and also this SHA-256. But for now, in this video, we are just focused on this section, AES-128. And then in the next video, we're going to focus on this GCM section, okay? Now, in short, this portion, so this ECDHE and RSA, is used to make sure that the key that we have for AES is securely exchanged, okay? Because AES doesn't provide any mechanism in terms of how we can now exchange the key. That part, we have to figure it out ourselves. And these other algorithms, which are part of asymmetric encryption, will come into play to help us with this. So, it's used in HTTPS. Another place is in military and government. And US government actually helped a lot with this AES thing. They needed to make sure that they have a very secure way so that they can now encrypt their top secret classified documents. It's used in password managers, so if you've used applications like LastPass, Keeper, and so forth, they use AES to encrypt your whole data. Another place is in disk encryption, so iOS, Android, Mac, Windows, and any other thing that we have, they have a mechanism to encrypt all the data on disk. For example, here on Mac, if you go into Settings, and then here in the Privacy and Security section, here you go to the Security section, you're going to see an option called File Vault. And what this does is that if you turn it on, it's going to encrypt your whole disk using AES. Now, it doesn't mention AES right here, but if you go to the Apple official website, it does mention there that it uses AES to do this operation. On Windows, the equivalent would be BitLocker. It uses the same thing, AES, to encrypt your whole disk. Now, on desktop machines, this option is usually turned off, and on mobile devices like Android and iOS, it is turned on by default. I always turn it on because if my device gets stolen and they chop off the SSD and try to forcefully get access to it, now if I have encryption on, they have no idea what's going on there, unless they could break AES, which is not possible. Alright, so they need to have access to my key, and if they don't, there's no way for them to see what I've got on the disk. It's always a good idea to turn on encryption whenever you can. It's just a simple switch, and it's going to give you tons of added security. And also about cloud storages like Google Drive and iCloud, sometimes they do not use end-to-end encryption. For example, in my case, I was not using it, and if you don't do that, all the photos and files that you upload to their servers is going to be able to be seen easily by Google and Apple and other companies. But if you do turn on end-to-end encryption, that will just be impossible. Another example is cryptocurrency wallets. Pretty much the same thing as the other ones, and you usually see that when you turn on disk encryption or you want to create a crypto wallet, it's going to give you a key first. That's just some random letters or random words, and then that thing is used to derive a key for AES. Alright, so a key that's 256 bits exactly, or 128 or 192. So that key is derived from those pieces of letters that you're given to when you turn on disk encryption or you try to create a wallet. And same thing with password managers. Usually your password is used to derive the key, but if you lose the password, that's an alternative. Okay? In another video, we're going to talk about how we can use a piece of string or, for example, a 6-digit number to derive an AES key that's exactly 256 bits or 128 or 192. But in this video, we're not going to talk about that. Another example in VPNs and another one in Wi-Fi security in WPA2 and 3. This is used to encrypt traffic from your device to the router. Okay. Alright, so these are just a few places that AES is used. You can see that we're not just learning it to understand how HTTPS works, it is used all over the place. And you can do a vast majority of them here in Node. So if you want to set up an end-to-end encryption with Node, you'll know how to do it. If you want to maybe, I don't know, do some disk encryption or design a password manager and tons of other things, you'll know how you can do them, not just with Node, with anything else, the concepts will remain the same. So AES is the most common form of symmetric encryption. The other one is SHA-2, but we're not going to talk about it here in this section, okay? It's rarely used and not as much as AES, but it's usually, again, used as a fallback method, that if at one point we break AES, we have something else that we can use. That, and also the fact that it's faster on devices that don't have hardware-accelerated components to do AES. So, AES is so common and used everywhere that your device has a piece of hardware component in it that will do the AES algorithm more efficiently. But some devices don't have that, and on those devices, if you try to do AES, it will be a little slow. But SHA-2 is going to be a little faster. Okay, so now let's talk about how AES works. Let's dive deep into it and see all the operations. It's not as difficult as you might think. It's quite straightforward. It uses a bit of math. If you understand some discrete math and linear algebra, that's more than you need. We're not going to dive deep into all the math. We're going to do that for just one of the encryption algorithms, and that is RSA. If you want to do that with every single encryption algorithm that we're going to talk about, this section length is going to be probably more than 50 hours. So we're not going to do that, but we will try to conceptually understand what happens when you do AES encryption. So let's say that you have 56 megabytes of data and you want to encrypt it. It's important to know that AES always works with 128-bit blocks. So if you give it this much data, it's going to first break it up into 128-bit blocks like this. So if you do the math, 56 megabytes, which is this many bits, so this divided by 128, which is going to be this much, okay? So if you want to encrypt 56 megabytes of data, it is going to individually encrypt more than 3 million blocks, and then at the end, it's going to somehow combine them together. So we're going to first divide it up into these blocks, then encrypt each individual one like this, and the ciphertext would be the equivalent size of this, and then at the end, this combination. Now, if you have a data that's not divisible by 128, it is going to add some paddings to the last block of data that we have, okay? Now, let's talk about exactly what happens for each one of these blocks. It's the same set of operations that are going to happen for each block, and let's now talk about that. So let's focus on just one block. Let's say that we have this piece of data, which is exactly 128 bits, and we have a key that is also 128 bits. So the way that AES works is that it's going to first organize the data into a 4x4 matrix. Like this. If you don't know what a matrix is, don't worry about it. Just think of this like a 2x2 array that we're going to put in all the bytes into them. So the first column right here has our first 4 bytes. And then all the operations are going to now happen on this 4x4 matrix. Now, first of all, what we're going to do for each block is that we're going to XOR this data with our key. Notice that they are both 128 bits in size. Now, this key is actually not exactly our key. It's a key that was derived from our key. So if you go with AES 256, it is going to derive a 128-bit key from that key. And this is called a round key. But let's not worry about that right now. For now, just know that we've got this key. That's exactly 128 bits in size. And we'll also put that into a 4x4 matrix like this. So once we do that, we're going to XOR our key with the plaintext. And then imagine that we're going to end up with data like this. Every single byte is now going to be different. Now, after we do this initial XOR operation, we're going to now do some byte substitution. And byte substitution is pretty straightforward. All that we do is that we take each byte And then we use a mechanism that for now you can just think of it like a lookup table, that we look into it, and if we see, for example, BB, we're going to replace it with FA. If we see, I don't know, maybe 6A, we're going to replace it with something else. And we have a table for all of these items. All right, so we're doing this substitution. And then after we do this, imagine that we're going to end up with this. Okay? Now we can, of course, reverse this process, but we're going to keep going. So pretty straightforward, nothing special about it, just some replacements, and that's it. All right, after this step, we're going to now shift the rows. So shifting the rows would be something like this. So we're going to take, for example, this fourth row and shift it to the right by 3 bytes. Right, so we're going to do this shifting, and we don't shift the first row at all in the AES specification. And we have exact numbers for it. For example, as I mentioned before, the fourth row will always be shifted to the right by 3 bytes in a circular way. Now, after we shift the rows, we're going to mix the columns. We're going to now do this, okay? And this is done by some matrix multiplications and calculating some inverses of matrices. But let's not worry about the math again. The concept is this. So first doing that XOR operation, then some substitution, then shifting the rows, and then mixing the columns. Now, after we do all these, at the end, we're going to XOR again with the key. Now, this key again is a key that we're going to derive from our original key, okay? Not the actual original key. We don't want to reuse that for every single XOR operation. We derive a new one, and that's it. So we're going to do this, and then we're going to change our data completely again. Now, at this point, we're going to go back to the step 2, which is shifting the rows, and do that all the way until this point many more times. The amount of times that we do it depends on our key size. So if we want to summarize this whole operation, this would be it. It doesn't matter what our key size is, what our mode is, it's the same thing among all of them. So first, we break our data into 128-bit blocks. Then we're going to XOR with a round key. And again, a round key is just a key derived from the original key. Next up, we're going to substitute the bytes. Then we're going to shift the rows, and then we're going to mix the columns. Now we would skip it for the last round, and we're going to XOR with a round key again. Now, each round is this much. So from this step up until this step would be 1 round. And we would do this 10 times if we have a 128-bit key. Here in this table, you can see how many times we're going to do this, and if our key size is 192 bits, we're going to do this operation 12 times. If it is 256 bits, we're going to do this operation 14 times. Okay, so pretty straightforward. And again, for all of them, we're going to skip this mixed column step in the last round. And then once we're done with this whole operation, we're going to combine all the blocks together. Now, in terms of how exactly we're doing this combination, that's going to be what we're going to talk about in the next video. That's where the modes come into play. But for now, let's understand exactly what happens for each individual block. So let's calculate how many times we're XORing with a key if we have a 128-bit key. So we have 10 rounds, so 10 XORs with a key, and then the initial one. So in total, we're going to do 11 XORs for one of these blocks. All right, and if we have millions of blocks, we're going to do millions times 11 XORs for the whole data, okay? Now this round key, let's talk about it again for just a sec. So it's done through a mechanism called key scheduling or key expansion, and all that you need to understand is that we have our original key, which is 256 bits, or one of the other two, 128 or 192, and what we're doing is that through some mathematical operations, we're going to derive a key that is exactly 128 bits. Okay, and it's called a round key because we're going to do this for each round. Now, all these operations, although we didn't get into the math of exactly how they're done, all of them are publicly available. And we're going to take a look at a document that mentions all the math behind it. Okay, and it's not that difficult to understand the whole thing. Now, let's see some code first, and then we're going to talk more about this. Right here in my code editor, let's create one folder, and I'm going to call it, let's call it ECB-encryption. Now, ECB is one of the modes of AES, Again, let's not worry about the mode. You'll understand exactly what this ECB means, but for now, again, let's worry about the general mechanism that's done for each individual block. Here, let's create a file called encrypt.js, and let's now do some AES encryption. So for that, we have to first include the crypto module. And then the first thing that we're going to need is to have a key. So I want to say const key. For now, let's go with something by putting in some random letters. So I'll say buffer.from. And we need exactly 128 bits of data. All right. So let's specify this in UTF-8. If we want to do that, we have to do some sort of a math. So 128 divided by 8, which is 16. So if I put in 16 characters right here, that's going to be a valid key. So I'll go with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then maybe A, B, C, D, and E. All right, this should be about, okay, it's 15, one more. So 1F, and there we go. This is now a valid key. Now this is a terrible key because it's predictable. It's like choosing 1, 2, 3, 4 for your password. So you should never ever do this. But for now, this is not our main concern. We just want to see how this works. And then we're going to fix the key. So this should be really random. So something like this. And you shouldn't choose it yourself. You should just use the crypto module, crypto.randomBytes, to do this thing. Okay? But for now, we just want to keep it as simple as possible to make sure that we understand it fully. So I'll say UTF-8 right here. And now that we have the key in place, let's define a plaintext. So const plaintext equals buffer.from, and let's go with just maybe character 2 or anything else that you want. And here I'll also say UTF-8. Alright, with these two in place, we are now ready to create our cipher, so const cipher, and here's how you do it in Node. So if you want to create a symmetric encryption and tell it to encrypt data, you have to first call the crypto.createCipherIV function. Now, at this point, we know what a cipher is, but we haven't talked about what an IV is. Again, let's not worry about it at this point. So here, I'm going to specify my algorithm. Here you can see the list. So I'm going to go with AES-128-ECB. And then after the algorithm, we have to specify the key. And here, let's put a null. We don't know why exactly, but we'll get into it in the next video when we're talking about the AES modes. Okay? Now, after you have the cipher ready, you can feed it data, and then it's going to give you the encrypted data. Okay, so the way that we do it is like this. We have to call the cipher.update method and give it some amount of data. So I'll give it the plaintext, and if you want, you can call it multiple times with different data. And then once you're done with all of them, you're going to call cipher.final. Alright, and each call is going to give you a buffer. So I'm going to call it cipher chunk 1. And then here in cipher.final, I'll say const cipher chunk 2 is equal to this one. So these are buffers. Now let's go ahead and log these two and see what we're dealing with. So console.log cipher chunk 1. And I'll do the same thing with the second one. I'll head over to my terminal and then navigate to ECB-encryption and node encrypt.js. So at this point, we don't get anything here in the first buffer, but we could. And we can also use node streams to do this operation, but we'll see that later on in the section. So what I'm going to do at this point is to concatenate these two together. So I'll say const ciphertext equals buffer.concat, and then cipher chunk 1 and cipher chunk 2. And this has to be in an array like this. There we go. And now let's log the ciphertext. So console.log, I'll say ciphertext is the ciphertext. I'll duplicate the line and say ciphertext.toString and then hex. All right, and I'll remove these two logs right here at the bottom. Let's run this code. And now we get this whole thing, but now in one straight buffer. So if we want, we can go on ahead and add in as many updates as we want if our data is large, and it's going to give us the whole ciphertext at the end. Now, if you try to run it through a character encoder, you're just going to get gibberish. And it doesn't matter if it's a character encoder. If you try to do the same thing with an image encoder or a video encoder, you will just see gibberish and noise. Okay? So here, if we try to log it, so toString UTF-8, and I'll say ciphertext UTF-8, here we can see that we're getting something that doesn't make any sense at all. Now, if I change my plaintext to something very similar, so 3, like this, if I log it now, notice that my ciphertext is now completely different. Okay, so it's not just a little bit different, it's now totally different. I have no idea that these two ciphertexts correspond to two plaintexts that are similar to each other. And again, no matter how many times I run it, I get the exact same ciphertext. So for as long as our data is the same and our key is the same, we're going to get the exact same ciphertext. Now let's talk about that padding part and the size of the ciphertext. So here, let's log both. I'm going to log first my ciphertext size. So ciphertext.length. And let's also log the plaintext size. So here I'll say plaintext size is this. All right, let's run this. And our plaintext size is 1 byte. And notice that the ciphertext size is 16 bytes. All right, the ciphertext size is always going to be divisible by 128 bits. Okay, so 16 bytes is 128 bits. And the paddings that are added to the data are just zeros and Fs. Okay, so let's confirm that. Now, for your cipher, you have this option that says set auto padding. So cipher.set auto padding. It's by default true. But if I say false and I run the code again, it's going to give me an error that says the final block length is wrong. Okay? Because I only gave it 1 byte of data. I need to give it something that's divisible by 128 bits. Now I'll change this to true. Run this again. Let's keep track of our ciphertext. And I'll now change it to false and try to add the paddings manually. The paddings are added like this. So let's first change this to hex because we want to be able to specify binary. And character 3 in UTF-8 is 33 in hex. Let's actually confirm this pretty quick. So here if I put in 33, yeah, there we go. So the ASCII character is 3, all right? So I'll change this to 33 because now we're specifying it in hex. And the paddings that we have to add in are just zeros and Fs. Okay, so we have to add in enough of these so that the data size is going to be exactly 128 bits. Okay, so how many do we need? This 33 right here is 1 byte, so we need 15 other bytes. And each character is exactly 4 bits, so we're going to need to have 30 of these characters. So 15 0 and Fs in total. Let's see how many do we have right now. So I have 11 selected, so I'll add in a few more until I reach that number. And now we've got exactly 32 characters, which is going to be 32 times 4, which is 128. So now my data is exactly 128 bits. Let's run this again. And you can see that my ciphertext is not changed at all. So it might seem like that we changed our plaintext and ended up with the same ciphertext, but we did not change our plaintext. We're just manually adding the padding because AES only works with 128-bit blocks and nothing else. So now with this works. If we drop even a single one of these characters and try to run it again, we're going to get an error, which is going to say that the block size is not divisible by 128. Okay? Now, if we try to change this now to maybe this, and just add in 2 more, so now this is more than 128 bits, and I'll change this to true, so that I'll let it do its own thing, and I'll add in just 1 more. So now we have 35 times 4 bits, which is 140 bits. Now this is not divisible by 128, so AES is going to add in some paddings to my last block of data. And now if I run it, you can see that the size of the ciphertext is 32 bytes, and 32 bytes is exactly 256 bits, okay? And my plaintext size is 17 bytes or 136 bits. So at this point, you should understand exactly what the paddings are here in AES. They are just these zeros and Fs that are added to the last block that we have, so that now everything is a perfect 128-bit block. I'll also add in here that this is a terrible key, so that you're not going to use this in production. And actually, ECB is also a terrible mode to use. And the reason that it's unsecure is because what it does is that it's going to just attach all the cipher blocks at the end together. Alright, so if you have 2 blocks of data, so 2 different 128-bit blocks, and they have the same plaintext, the ciphertexts are also going to be identical. And that's problematic. But if your data is quite small and you know that you don't have any repetition, ECB is good enough. But still, it would be more secure to add in some random data to make sure that you don't end up with the same ciphertext if you encrypt multiple times. So again, the fact that all of our ciphertexts are identical, this is not a good thing. You don't want it to happen. So if you have 2 emails that are repeated in your plaintext, they're going to end up having the same ciphertext. And an attacker could use this to your disadvantage and learn some things about the plaintext, which is problematic. Now, I also want you to understand that the math here is really solid. Okay, so if you have the same data and the key, again, the ciphertext is going to be something exact. You can calculate on paper what your ciphertext is going to be given your key and plaintext. But that's a long operation. It will probably take you days to do all the math, but it's doable. Okay, so it's not random. The ciphertext that we're getting is not a random thing. There's logic behind it. And you can trace it one step at a time to see how you ended up with this data. Now, in this video, we did not get into all the math, which you could if you want, but you need to understand some basic college-level math. Now, if you want to see exactly how this is done, you can download the specification, and let me show you that pretty quick. So the specification is published here in NIST website, which is part of the US government. So the algorithm was approved by National Institute of Standards and Technology, which is part of the Department of Commerce. Okay, so the government is involved in this algorithm. We're going to talk more about the history later on, but the specification is published right here on this website. So if you go to this link, I'll link it to the resource section of this video, which is about 52 pages, and the article is called Advanced Encryption Standard, okay, or AES. And this thing was published in 2001, okay? That's when the algorithm was approved, and everybody started to use it. And for about 25 plus years, it hasn't changed a bit, okay? So it's really solid. And this is actually how it works in cryptography. If you come up with a good tool, it's not going to change tomorrow. It's not like JavaScript frameworks that every few years you've got a new thing. If the foundation is strong, they don't have to change much. And changing them is going to take a ton amount of time. Everything about the algorithm is public, and it's so important for a cryptography mechanism to be public, because people need to see exactly how it's done. So if there's a vulnerability in it, somebody would find it. Okay? So if you scroll down, all these steps that we mentioned right here in the table of content, you can go into much more detail about every single last one of them. For example, shift rows, or mixing the columns, or adding the round key. We talked about all of them, but if you want to see exactly how the math is done, just go into that page and you can learn more about it. Now, the decryption is the exact opposite. For example, we're inversing the shifting rows, and we can do all these operations if we have the key, because now we can do all the XORs. If we don't have the key, we can't do the XORs, and we can't do the decryption. Here it's talking about mixing the columns, and here's the matrix multiplication that's done to do so. We're not going to get into the math of these, and here it's talking about the key expansion. So how are we getting these round keys from our original key If your math is good, I encourage you to go over it, and you can see the algorithm that's used to do the operation. And anything else that you want is documented step by step, very clearly, and it's not actually complex. If it's complex, it'll be a huge downside, because now not a lot of people are going to be able to understand it and then test it to see if it's secure. It has to be straightforward and simple so that now everybody has a chance to scrutinize over it and make sure that it's really secure. Okay, so that's it about this document. Again, we didn't go over every single math operation here, but you should have the big picture in terms of how these are working. So the substitution, shifting the rows, mixing the columns, and driving the keys. And it's all just some college level math and nothing too crazy. In just about 50 pages, you'll know exactly how this is implemented. Alright, so now at this point you should understand what's happening here with our cipher. So how this plaintext is converted into the ciphertext with the help of our key. Now in the next video we're going to talk much more about the modes of AES that we have. We said that this ECB is not secure to be used in places like HTTPS and real-world examples, but if your data is very small, it's good enough. We'll see exactly why and the other options that we have that are much more secure than this one. So that's it about this video, and I'll see you in the next one. In this lecture, we're going to talk about modes of AES. So far, we understand exactly what this AES means, but we haven't talked about this third part, which is the mode of AES. So in this video, we're going to understand what these modes exactly are. We're going to primarily talk about the ECB mode, CBC, CTR, GCM, and XTS. And in this lecture, we're going to focus on the first three, and then we're going to discuss the other two later on in the section. Once we really understand them, we're going to have a very strong foundation in the modes. And if we want to understand another one, we're going to have a really easy time. For example, this GCM is built directly on top of CTR. It's basically CTR, but with a new feature added into it, which we'll see later on. Now, in ECB mode, we understand that, well, in all modes of AES, we're going to first break it up in 128-bit blocks. And then here's what's going to happen here exactly with ECB. It is going to encrypt each individual block, and then we're going to end up with the ciphertexts. Now, as a convention, I want to point out a few things because we're going to see slides like this a lot throughout this section and this lecture. Every time you see a gray box like this, we mean that this is our plaintext. And if it's a red box like this, then it means that this is our ciphertext. Now, the yellow K here means that this is our key. And also here, when I say AES and then this little E letter, it means that we're using AES to encrypt, okay? So we can run the AES algorithm in two different ways, either to encrypt or to decrypt. And decryption is just the exact opposite of encryption. So in encryption, we're shifting the rows and then we're mixing the columns. And decryption, we're going to do it, but in the exact opposite way. Now, here we said that after ECB does all of this, it's going to literally attach all these blocks together. So if you modify one of these blocks of your plaintext, only that block of your ciphertext is going to get modified. So the rest are going to be exactly identical. So if an error happens in one of these blocks, only that particular block is going to get affected. So we have 56 megabytes of plaintext, and the result is going to be 56 megabytes of ciphertext. Again, in decryption, it's the exact opposite. Let's say that we want to decrypt. We're going to take one of these ciphertexts, and then we're going to run it through this. But this time around, we're going to run AES in decryption mode, just the exact opposite, and then we're going to get the plaintext. And we're going to do this for every single last one of these blocks. And just like that, we're going to end up with our plaintext. But again, remember, we're going to need to have the key. If we don't have the key, we cannot reverse this process. Now, I want you to think about this architecture for a bit. See if you can find a problem. And, well, the problem is, if we have two blocks of data that have the exact same plaintext, we're going to end up with two blocks of ciphertext that are exactly identical. Now, this could reveal some patterns about your plaintext to an attacker, and it's something that we absolutely don't want. So if one of these blocks is consistently maybe your email address, an attacker can see that these ciphertexts are always identical. So it means that it's something. Maybe an email address that you usually send emails to, or a web page that you frequent, or a password that you constantly use, which is very problematic. We don't want this to happen. Now, to demonstrate this problem, here I have a picture, and this picture is pretty straightforward. Just a few shapes, and I want you to pay attention to one thing about this, that we have tons of repetition in this data. So if I really zoom in into one of these shapes, you're going to see that these pixels right here all have the same value, all right? So tons of repetition here. All these blue pixels have the same value, same with this, same with the star, and also same with this one. With this square here, we've got a gradient, so each pixel has a different value, and also the background is a gradient, so each pixel has a different value, all right, from row to row. All right, let's now go ahead and encrypt this with ECB and take a look at our ciphertext. So here, let's clean up a little bit. We're going to use this file a lot now to experiment with different modes. So I'm going to change the name of this folder. Let's change it to AES. And let's change this encrypt.js to app.js. And here at the top, I'm going to add a piece of comment. And say that this is the ECB mode. And it's a very simple encryption. Okay. We're saying that it's simple because all we're doing is that it's a very straightforward plain text. Our key is also very simple. Now we're going to stick with this key as much as we can, but I want you to understand that this is not how you should do it. This is good for experimenting and educational purposes, but in production, here's how you should generate your key. So you should say const key equals crypto.random bytes. Okay, so your key should be truly random. All right, and then the size should be 16 bytes, which is going to be 128 bits. So this is how keys should be generated. All right, but we're going to stick with this because if we want to do it this way, and then after we run it, we want to now decrypt, we're going to have to save this key somewhere because if we have a different key, it's not going to work, obviously. So we're going to just stick with this, but I'll always add this disclaimer that this is how we should do it, because if you go with this in production, this is terrible. All right, your encryption is going to get broken and your user's data is now compromised. So never ever do this, and I'll come back to this a few times throughout the section because of its importance. But for now, just know, always generate with crypto.random bytes. All right, so let's comment this section. Now let's add a new one. And here I'll just say ECB mode and then encryption, and that's it. All right, so we're going to now go ahead and encrypt this plaintext.bmp file, which is an image, with ECB. And we're going to use node streams to do it, because that's usually how you would do it, okay? So we'll first have to have our key. Actually, I'm just going to copy paste these two keys. So this as our disclaimer, and then we're going to go with this simple one, just so that we don't need to regenerate and save the key every single time we want to run it. And then let's have our cipher, crypto.create cipher IV. We'll go with AES 128-ECB, and then the key, and then this null. We'll talk about this null in just a bit. And then once we have the cipher, let's have our plaintext. So we're going to have a read stream that's going to be this. So fs.create read stream, and then plaintext.bmp. Now we need to include the fs module. So const fs equals require node fs. Now with this in place, let's also have our ciphertext, which is going to be a write stream. So fs.create write stream. And for this one, we're going to create a file and call it ciphertext.maybe-enc, encrypted. And then we're going to pipe this plaintext to the ciphertext, and in the middle have a transform stream that will be this cipher. So let's include the pipeline function, so const pipeline from the node stream. Okay. And then right here, we're going to call the pipeline function. The read stream is going to be the plaintext. the transform stream is going to be the cipher, and then the write stream is going to be the ciphertext like this. And then a function with the error. We'll say if we have an error, just return an error. So console.error, pipeline failed. And if we don't have an error, we're going to log that the encryption was successful. Pretty straightforward. So here's how we can now use these ciphers in the stream mode. So you can use a cipher, a crypto.create cipher, in two ways. Either using the node streams, which we saw their power in the streams section, or you can use this .update and then .final that we used right here. This is good if you just have a small piece of data, but if you want to encrypt gigabytes and gigabytes, large amounts of data in general, this is a much better way of doing it. Okay, alright, let's now run this. We just have a quick typo here, stream like this, and then stream like this. Great. Let's now go ahead and run it. I am here in the AES directory, and I'll say node app.js. Alright, it says encryption completed, and now we've got the original image and its encrypted data. Okay, now here I'm going to do something to demonstrate the problem that we have with the ECB mode. It's a common way of showing it, and you don't need to do this, just watch me do it. What I'm going to do is that I can't go ahead and open this ciphertext.encrypt using an image viewer application right now, because, well, everything is messed up, we don't have any headers, and that application is going to check that this is not a valid image, so it's going to return an error. But we can somehow force an image viewer application to do so. It's a BMP image, which is like a PNG or JPEG, and what we can do is to grab the headers from this one, so that's about the first 50 bytes, and add it to this one, and then change its extension to .bmp. So we're kind of forcing and duping an image viewer application to think that this is an actual valid BMP image. Alright, so it's just going to display some things. It's like putting random data into a character encoder. It's going to spit out gibberish, but still, it will work. Alright, so here's how we can do it. Again, you don't need to do this. So what I'm going to do is to use some of the concepts that we talked about in the Unix section. If you haven't watched it, don't worry, I'll explain it pretty quick. So I'll grab the first 54 bytes from the plaintext. This -c means in byte mode, and 54 means the first 54 bytes of this. And I'll save it into a file called header. Alright. So now we've got this header file, and then I'm going to use the tail command to grab from the 55th byte forward from the ciphertext.encrypted file, okay? And I'll put it into something called body. And then let's cat these two. So we're now combining these two together into something called a ciphertext. Let's call it ciphertext-new and .bmp. So here's what I've done. I've got the plaintext, the ciphertext. I grabbed the first 54 bytes from the plaintext, put it into this new file, and then this much, everything after the 55th byte from the ciphertext, and now it's here in this file, okay? So now if we feed this file to an image viewer application, we're going to be able to, well, open it up because the header is now valid. We're not going to get an error that says this file is not a valid image file, okay? For some reason, I can't open it here on my Mac, but I could do so using the default image viewer application here on Linux. So here I have the ciphertext.bmp, and I'm going to open it up with the image viewer, and take a look at the ciphertext. Alright, so this is our ciphertext, and this is supposed to be very secure. And again, remember, a very important concept is that if an attacker takes a look at your ciphertext, they shouldn't have any idea whatsoever about what's going on in the plaintext. Clearly, that is not the case here. I hope it's clear enough on video, but you should be able to see here that we can still see the shapes. We can still say that there's a polygon right here, a star right here, and a rectangle right here. Okay, this was our original image. Let's open this up again. And this is the ciphertext. All right. Again, notice that here, this square, because we don't have much repetition, we can't see that, and we're just seeing random noise. But with the other shapes, we can see them, as you can see right now. Right? Now, in case if you want to take a look at it, I'll take a screenshot of this and link it to the resource section of this video. But you should also be able to do it yourself. It's pretty straightforward. Here I'll paste the commands that I ran. And if you want, you can try it. But you need to have an image viewer application that will open this up and not give you an error. On Ubuntu it works, but on Mac I couldn't get it to work. Alright, so that's a very big problem with ECB, and other modes don't have this problem. So if we try it with, for example, CBC, this won't happen. If we take a look at the ciphertext new.bmp, it's going to be random gibberish, all noise. We won't see any patterns whatsoever. But with ECB, because it's going to literally attach all the ciphertext without doing any chaining, without doing anything random, it is going to be a big problem. That's why people say never use ECB in production unless your data is just a few bytes and you know that you don't have any repetition in it. So each block is going to end up with a different ciphertext. Well, that's rarely the case, and you should try to not use this ECB mode as much as you can. An upside of this is that we can now run it in parallel. Because if you take a look here, we can encrypt and decrypt each block of data independently of the other ones. So if we have 4 cores in our CPU, one core can take care of the first 25% of the data, another core can take care of the last 25% of the data, and so on and so forth. So if we want to encrypt this one, we don't need to wait for the previous one to get encrypted first. Okay, let's talk about another thing that we discussed. And that is, if we change one of the plaintexts, for example, an error happens or an attacker is modifying our data, only that block of data is going to get modified. Alright, let's see this in action. So here, let's create a new file. Let's call it plaintext.txt. And here I'll put this is some text and more and more. I'll copy this and paste it a few times. Let's now copy it again and paste it a few more times. So now we have about 25 lines of this text, which is pretty good. Now I'm going to go ahead now and encrypt this plaintext.txt. Here all we have to do is to change it to .txt. We're going to call the final one ciphertext.encrypt. That's good enough. Let me change this back to ECB. Let's go ahead and run it now. Alright, encryption completed. And here's our ciphertext.encrypted. And if you take a look at it, it's just random gibberish. Alright, so let's now have a piece of code that's going to decrypt. So I'll copy paste this comment. And I'll say ECB mode decryption. Let's also copy this one, paste it right here. It's going to be pretty straightforward. All we have to say is create decipher now instead of cipher. So create decipher IV. Everything is the same right here. In the plaintext, I'm going to call it plaintext-decrypted just so that we don't overwrite the first one. And then in the pipeline, we're going to now pipe from the ciphertext to the plaintext and not the other way around. Okay. And then here I'll say decryption completed. I'll now comment this one. Everything else is commented out now except the include lines and here in the decryption. Now this time around we're reading from the ciphertext, so this one should be create read stream and this one should be create write stream. Now, let me also change the order. So we're reading from the ciphertext, decrypting, and writing to this plaintext-decrypted.txt. Let's now go ahead and run it, and it says decryption completed. And if we now would take a look at plaintext-decrypted, well, it's exactly what we had in the first place. Alright, so plaintext.txt and plaintext-decrypted, as we expect, are exactly identical. But now let's simulate an attacker fiddling with our data. So I'm going to encrypt again. So I'll uncomment this first section, ECB encryption. Let's run it. Now we've got the ciphertext.encrypted right here. Let me also delete this body because we don't need it. And also this header. I'm going to open this up and take a look at the binary content of the file. And I can do so with an application that I've installed called Hexfiend. Alright. So here's the binary content of the ciphertext. And let's say that we want to just change maybe about 4 bits of the data. Okay, so only this much. This B3. Let's say that this B3 gets changed to B4. Alright, fair enough. Not that bad. Maybe in transmission this happened, or an attacker did this. So let's see what's going to happen. If you want to do this, feel free to install an application like this, or you can read the whole thing using node buffers and then modify one of the elements like this and then write the buffer back to the file. Okay, so I'll save this and then close. So now our ciphertext.encrypted is now modified. It's now a corrupted ciphertext. I'll now go ahead and decrypt this one so we don't need to encrypt it again. So I'll comment this last part of my code and then I'll run it. It says decryption completed. Notice that no error was detected. And this is actually another problem that we're going to discuss later on. So if our ciphertext gets changed, we don't care here in this ECB mode. Now, if we take a look at plaintext-decrypted, you can see that for the most part, all of them are correct, but this line right here got modified. All right. And if you want to calculate this exactly, so from this up until this, okay, this E is correct. So only this much of the plaintext is now completely corrupted. Now, the size of this exactly is 128 bits. Okay, so from this up until this point, again, notice that the E was not changed, all right, but this portion was changed. This is exactly 16, all right, so 16 characters, 16 times 8, which is exactly 128 bits, all right. So only the block that we modified is now corrupted. The rest is all correct, okay? This is an important characteristic that we need to understand about the ECB mode, and it's pretty straightforward. If you understand the concept that we are independently encrypting and decrypting each block, this should make total sense to you. All right, so far we've seen a big problem with this ECB mode, and that is, again, the same plaintext will end up with the same ciphertext, which is something that we absolutely don't want. There's another mode called CBC that will fix this problem. Let's see how this one works. With CBC, we also need to put in another 120 bits of data right here, which is called an initialization vector. Okay, let's see how this works. So now we're talking about the CBC mode in encryption. So we have our data again. Just like before, we're going to divide it into these blocks of data, and we're going to have exactly 3,500,000 blocks of data. Now, to eliminate 2 blocks of data with the exact same data, ending up with the exact same ciphertext data, we're going to introduce a bit of randomness to our encryption and also chain the final ciphertext together. All right, so the first part, introducing this randomness, we're going to have a random 128 bits of data, which is called IV. That stands for initialization vector. All that it is again 128 bits of random data. Okay. Now we're going to first XOR this one with our first block of the plaintext. Then after we XOR this, we're going to encrypt the result of the XOR, and we're going to come up with the first ciphertext block. Okay. Now for the next block of data, we're going to take this and XOR it again with the plaintext, okay? And then, just like before, we're going to encrypt the result of the XOR operation and end up with the next block of the ciphertext. And we're going to keep on doing this until the very end. So we'll take this ciphertext, XOR it with the next plaintext, and then encrypt the result, and there we go. And for the last one, we're going to take the ciphertext before it, do this XOR, and then encrypt, and here's our ciphertext. And then at the end, we're going to attach all these together, and we're going to end up with 56 megabytes of ciphertext. All right. Now, notice something about this, that if we now have 2 blocks of data, let's say that these 2 blocks that have the exact same 128 bits, we're going to end up with 2 ciphertexts that are totally different. And this happens because we are chaining them together. All right. And this started with this initial vector. So if you now encrypt 2 pieces of data, so 2 megabytes of data that are exactly identical, so if you encrypt the same image now 2 times with the CBC mode, you're going to end up with 2 ciphertexts that are completely different. Because for each one, you should use a different IV, all right? This is a very important part about this IV vector, that you should never ever reuse it. So it should be truly random, just like a key, and also you should never ever reuse it. If you do so, well, it's going to be the same problem again. Let's say that you've got 2 images that are identical and you use the same IV vector twice. Well, your ciphertexts are going to be identical. Now, also this IV vector is out in the open, you usually send it in clear text with the ciphertext, and then in decryption, you're going to take it and reverse this whole process and end up with the plaintext. So I want you to understand something about this, that if we want to encrypt one block, one plaintext block, we need to know what was the result of the previous encryption block, okay? So we can't just independently encrypt each plaintext block. We need to wait for the previous ones to get encrypted first so that we can now encrypt a particular plaintext block. So we can't do it in parallel. So multi-threading doesn't help us here. We're doing it in sequence, one block at a time. And that's a bit of a problem because it's now not as fast, but it's much more secure than ECB. All right, let's see this pretty quick in code. So I'm going to comment this and copy the key and also the comment, paste it here. I'll say CBC mode encryption. We're going to have the same key, and here let's encrypt the plaintext again. I'm going to create the cipher, crypto.create cipher IV. We're going to go with AES 128-bit, and this time around the mode is going to be CBC. The key is going to be like before, and now here as the third argument we have to specify our IV. Okay, so let's do that. Here I'm going to say const IV equals, and we're going to use the same method that we used. We're going to say buffer.from, which is again a terrible way of doing it, but we don't want to always save it, and for simplicity we're going to do that, but add this disclaimer to it. Okay, so I'll say buffer.from. Again, remember we need exactly 128 bits of data. We can use this exact same thing here, and then UTF-8. Now notice if you go with 256 version, you still need to have exactly 128 bits of data for the initialization vector, okay? Because AES always works with 128 blocks of data, regardless of the mode and the key size, all right? Please remember that. Here I'll say 128 bits, then a horrible way to generate an IV, all right? So never ever please do this in production. Here's how you should do it. You should say const IV equals crypto dot random bytes and then that much. Okay, 16 bytes always. This is how it should be done in production. All right, let's now go ahead and have our plaintext fs.create read stream. Let's go with the plaintext again, so plaintext.txt, and then the ciphertext, which is going to be write stream, so create write stream, and we'll call it ciphertext.encrypt, just like before. And now we're going to have the pipeline from the plaintext. The transform stream is going to be the cipher, and then the ciphertext is going to be the write stream. And then the exact same thing that we had before. All right, and now we need to make use of this IV, which again is going to be the third argument of the create cipher IV function, or if you're doing the decryption, the third argument of the create decipher IV. All right, great. Now let's go ahead and run this. Well, I get this error invalid key length because I said 256. So let's change it back to 128. We can also change our key, but let's do it this way. So I'm going to run it again, and it says encryption completed. Let's now have the same version of the code, but now for decryption. Actually, I'm saying decryption, which I should say CBC mode encryption. So now for decryption, it's going to be really straightforward. I'll just copy this, paste it here. Now this one is decryption. The key, just like before, IV like before, cipher is going to now be create decipher IV. And then the ciphertext this time around is going to be a read stream. The plaintext is going to be a write stream. And then I'll call it plaintext-decrypted.txt. The pipeline is going to be from a ciphertext to the cipher, and then to the plaintext. And here I'll say decryption completed. I want to now comment the encryption portion and then now decrypt this one. This plaintext is not being used, and well, I forgot to put it right here, so plaintext. And now let's go ahead and run it. And now if we take a look at plaintext-decrypted, we'll see the exact same data that we had here in the original file. Now in decryption, here's how it works. So we've got 56 megabytes of ciphertext. We're going to first, again, divide it up into these blocks. And then we also have this IV data. Okay? Again, it will be out in the open. We're not going to encrypt it or anything like that. We'll usually just put it in our ciphertext and send it over. So we're going to take the first block. Now notice, in this time around, we're using AES in decryption mode. So just the reverse of the encryption mode. And then, once done, we're going to XOR it with the initial vector. And we're going to end up with the first block of the plaintext. Now, XOR, if you do it twice, it's going to reverse itself. That's why we can now do it in backward. And again, if this XOR doesn't make a lot of sense to you, please refer back to the one-time pad encryption that we talked about. That it's very secure. Alright, you need to have both pieces of data if you want to be able to reverse it. And you can't figure one of them without the other. Alright, so after this, we're going to now decrypt the second block of the data and XOR the result with the ciphertext before that. And now this time we're going to end up with the next block of the plaintext, and so on and so forth. Here in the last one, we're going to do the exact same thing. XOR this last block with the decrypted version of the ciphertext. And there we go. Alright, notice something about this, that we can now decrypt at any point that we want. It's not like the encryption version, because we don't need to wait for the previous blocks to get decrypted first to decrypt a particular block, right? Because we only need the ciphertext. We don't need the plaintext to do the XOR operation. So I want you to now think about it. What's going to happen if we modify one of these ciphertexts and then do the decryption, right? Do you think that only that block of data is going to get changed, or maybe all the blocks afterwards? So just pause the video and maybe think about this for a sec. Alright, so the answer is, if you only modify this second block, for example, only the plaintext of the second block and the third block are going to get corrupted. The rest will be just like before. And you can try it yourself if you want. It's a pretty straightforward test. All you have to do is to encrypt again. So let's do it pretty quick. Plaintext to ciphertext. Let's run it. And now I'm going to again modify it. So ciphertext.encrypted. Here I'll open it up using my HexFiend application. Now let's modify maybe this 1F to maybe 2F. Alright. I'll save this. And now do the decryption. Now if we take a look at plaintext-decrypted, you can see that only those two blocks got changed. Alright, if you calculate them, the size is exactly now 256 bits because two blocks now got corrupted. The blocks before the corrupted block and the ones after it remain unchanged. Now, I encourage you to play around with this more. So modify this time around your plaintext, maybe this much, and then take a look at your ciphertext, just like that we did with HexFiend application. And you're going to see that in CBC mode, if I change this I to maybe capital I, now all the ciphertext is now going to be different because we are chaining them on, alright? And the ones before it, well, they will be the same thing. Of course, I mean if we use the same key and IV vector. If we change one of them, the ciphertext is now going to be completely different. So that's the idea of an IV. The only reason is to introduce some randomness so that if we now encrypt multiple times and the data is the same thing, we're going to end up with totally different ciphertexts. Alright, so let's now talk about another mode that we have, and that is the CTR mode. This one offers the benefit of ECB and also CBC. Alright, let's see how this works. In CTR encryption, we have first a random number. So we're going to generate 128 bits of data, and it's nothing but a random number, kind of like the IV. And for each block of the plaintext, we're going to take this number, and let's call it counter from now on, just for the sake of saving some space. And for each block, we're going to add 1 to this counter. All right, so for this one, it's the first one, so we're going to add 0 to it. And instead of encrypting the plaintext, we're going to encrypt this counter, all right? And then we're going to take the result of the encryption and XOR it with the plaintext. And then we're going to come up with the ciphertext of this block. Now for the next one, we're going to do the same thing. We're going to take the number. Now this time, add 1 to it. So this time it's going to be +1. Encrypt the counter, and then XOR the result with the plaintext, and that's it. Same with this. We'll take the counter +2, encrypt, and then XOR, and that's it. And for the last block, we're going to add this number to it, because we started from 0, and then encrypt, and then XOR. All right. Now, I want you to notice that we are not encrypting our plaintext with AES. We're encrypting this number with AES and nothing else. The result of the XOR operation then is going to be the encryption for the plaintext. So an attacker knows exactly what we're encrypting in this case with AES. That it's the counter, and this random number is also out in the open. You send it with the ciphertext, so an attacker knows what this random number is. And, well, also the AES algorithm, but the thing that they don't have is this key. And because of it, they have no idea to know what the plaintext is. So the fact that the attacker knows what we're encrypting with AES is not a problem at all. Okay, not even a little bit. It's very secure. If you go back to the one-time pad encryption concept, we talked about that we have a key that's random, and we XOR it with the plaintext, and that is a perfect encryption. We don't have an encryption that is more secure than that. So we're kind of doing the same thing here. We're generating this random key, and we're XORing it with the plaintext. But the difference is that this thing is being generated from the key that we have specified. All right. So mathematically, we are generating these with this key that we specified, and that's pretty much it. Okay. Okay, let's now see this in Node, and then we're going to come back here and talk about how the decryption in CTR mode is done. Here, I'm going to comment out this section, and then I'll grab the first portion of the CBC mode encryption, and then paste it right here. I'll uncomment this. I'll go with the same key, change this to CTR, and now let's create the cipher. So crypto.create cipher IV. We'll go with AES 128-CTR. Key the same thing. And now here as the third argument, Node is calling it IV, but this is that random number that we talked about. So I'm going to specify this IV, which is a random 128 bits of data. Now, if we want to be precise, this is called a nonce plus a counter. Okay. The first portion, probably the first 8 bytes or 64 bits, is a nonce value, which is just a number that is fixed. And then the next portion is called a counter. And we're increasing this counter block by block. All right. Now, you don't need to worry about it. You can just think of it like a 128-bit of random data that we're adding 1 to as we keep going along with the blocks, okay? But here in Node, it's calling it IV, which is not technically very accurate, but it kind of makes sense because it's the same exact setup that we have here with the CBC mode, all right? So it's exactly 128 bits. We specify it here, and it does the exact same thing. So the goal of having this is to have that randomness in our data, so 2 plaintexts that are identical will not end up with the same ciphertexts. And the rest would be all the same as before. So we can just copy-paste this portion, and I'll put it right here. So the plaintext, the ciphertext, and then this pipeline. Okay. Now let's go ahead and run it. Encryption completed, and here's our ciphertext. And decryption would be the exact same thing. In fact, let's again just copy the CBC mode decryption and then paste it here. We'll just have to change a few things. So the CTR mode, the cipher is going to be now the CTR mode, and then all the rest just like before. And let's also run it. And here's the plaintext -decrypted. Now, if you want to see a difference between CTR mode and CBC mode, you can try to change your ciphertext. Okay, so encrypt the data and then change the ciphertext so you're making it corrupted, and then decrypt it. With CBC, as we saw before, you were going to see that 2 blocks are going to get corrupted, but with CTR, it's like the ECB mode. So if you change 1 block of plaintext or ciphertext, only that corresponding block is going to get changed. And with this, we can also run it in parallel. So we can easily divide it up. We don't depend on the blocks before and after. So one CPU core could take care of this much, another core, another portion. You get the point. Now, the neat thing about this is that the decryption is also exactly identical to this, all right? The only thing that we're going to do differently is that instead of having the plaintext here, we're going to have these ciphertexts. So let's take a look at that. We're going to take each block and the same counter that we had before, and we're going to encrypt the counter again. Notice that we are encrypting and not decrypting, all right? So we're running AES in encryption mode. And then we're going to do this XOR, and there we go. We've got the plaintext. And then the same thing with the next block, and the next one, and the next one, okay? Now, if I go to the next slide, here we can see the encryption mode, and here's the decryption mode. So if I go back and forth, you can see that the only thing that's different is the placement of the ciphertext and the plaintext, all right? So if you were going to implement this from scratch in code, so the same thing that OpenSSL does, you don't need to implement AES in decryption mode, so you don't need to do the operations in reverse. You just handle the encryption, and that's pretty much it for the CTR mode. All right, so that's it about these 3 modes that we discussed. We have the ECB mode, and also here are what they stand for. So ECB stands for Electronic Code Book, and CBC is Cipher Block Chaining. And you should know what is this block chaining. It's the fact that we take each ciphertext and then XOR it with the next one. And then CTR simply is counter, all right, because we have a counter and we add 1 to it for each block. All right, so at this point, you should have a pretty good understanding about the AES modes. There's something that we haven't discussed yet. Although the CTR and the CBC modes, they are secure, they are rarely used. The one mode that is more secure than these ones, and is way more commonly used, is GCM, which is something that we're going to discuss later on. Now, GCM is this CTR mode, but with something called a message authentication code added on top. Now, we'll discuss this in great detail in another lecture, but basically all that it means is that you saw that I modified my ciphertext, and then when I decrypted it, it just went okay. All right, I saw some gibberish, but it didn't matter. I didn't get an error or something. And a very skillful attacker could do it in a way to actually change stuff. For example, change my ciphertext in a way that the password that I'm specifying is going to get modified and then sent to a server. So it's a big problem that an attacker could listen to us and change the ciphertext, and the other endpoint has no idea that it was changed. Okay, so GCM mode is going to add something to this CTR so that if we change the ciphertext and then do the decryption, we'll know that something is going on and our data is corrupted. Okay, so that's why CTR mode, although it is secure, it's not used that much, because with that message authentication code in place, we can also verify the integrity of the message, that if we get something from someone, it is exactly what they intended to send and not something that was modified along the way. So that's it about this video, and I'll see you in the next one. In this video, we're going to talk about breaking AES. Now, in short, it's not possible unless we have the key, but this video is going to give you some idea in terms of how secure AES really is and what it's going to take to really break it. At the end of the video, we're going to talk a little bit about how quantum computing can help break AES. Alright, so let's take a look at a piece of code. You can grab this from the starter.zip file from the resource section of this video. Now, here we're going to kind of emulate breaking AES. We're brute forcing it. So here we have a ciphertext. Imagine that an attacker took this ciphertext. He or she maybe was sniffing a network and then got this ciphertext. So maybe it's part of an HTTP request or something like that. We don't know, but we have the ciphertext. And also we've got the IV, which is usually out in the open, and also the algorithm and the key size, which is also, again, out in the open. You saw that using Mozilla, we can actually see these values pretty easily. So these are usually out there, but the thing that we don't have access to is this key, all right? So usually we don't know what the key is, and we're going to have to brute force it, okay? Now, in this hypothetical case, let's say that we have somehow figured out this first portion of the key, and we just don't know the last 4 bits. So maybe the developers by mistake pushed a portion of the key to GitHub, or maybe our attacker kind of attacked the server. We don't know, but hypothetically, let's say that we know this portion, and we just want to find out the last 4 bits, all right? Which is usually the case if you want to brute force maybe AES, okay? In reality, you don't know much of the key, or maybe in some best case scenarios, you can just somehow figure out a bit or 2, but not this much. Unless, again, you get access to the key itself. But in this case, we want to say that we know all these bits of our key, and we only don't know the last 4 bits. Now, think about how many operations we need to do to find the key. If you know some basic discrete math, you should know this right away, that we've got 4 boxes. Each box can hold 2 different values, either a 0 or a 1. So 2 times 2 times 2 times 2, which is 2 to the power of 4. So in total, we have to do 16 encryptions until we find the key. Okay, if we do that much, we are guaranteed that at one point we're going to find the key. Okay, so here in this for loop, what we're doing is that we're trying every single combination of those last 4 bits. All right, so here the last byte is 30. So we know that these 4 bits are 00 and then 11. And we don't know the last 4 bits. Okay, so we have to try every single combination that we have, maybe starting with all zeros, which is 30 in hexadecimal, going all the way up to all set to 1, which is going to be 3F. All right, so that's what we're doing here. We're starting from 30 and go all the way up to 3F. So we're trying every single combination, and once we do that, we are guaranteed that at one point we have found the key. We could find it sooner, so it could take us a little less than 16 operations, but in worst case scenario, we're going to have to do this much. So in the logs, we're saying that the tried key is this, so we're setting the last byte of the key, the 16th byte, to this value. So we're going to go with 30 first, and then 31, 32, all the way up to 3F, all right? And then after we set the byte correctly, we're going to create our cipher with that key, and then decrypt the data, this ciphertext, and then log the plaintext. And then we're going to move on to the next key. All right, so let's run this pretty quick and see what we're going to get. Here I'll say node bruteforce.js, and let's scroll all the way up and see what we have. So here's our first try. It tried this key, 30 at the end, and the plaintext looks gibberish. All right, so we know that this is not the answer. Now this is the next tried key, 31, still gibberish. Now let's keep scrolling until we find something that's a little meaningful. Still all gibberish. And if I keep scrolling, now here when we tried 39, you can see that, well, this is a valid HTTP request, right? So we can see all the headers that were sent, the version of the HTTP, and also the body of the request. Okay, so at this point, we can say that this is the key that was used to encrypt the traffic. And we have now found the key by first some other ways of figuring out the first 124 bits, and then we brute forced the final 4 bits. And we found it at this point. All right, so notice that any other case that we've got here, the plaintext is just gibberish. So at one point where we set all the bits correctly, we're going to see the actual plaintext that it now makes sense. In all the other cases, we're just going to see gibberish. And also we logged the time that doing these 16 AES encryptions took about 23 milliseconds on my machine, which is not bad. All right, so this is the idea of breaking AES. We have access to the IV, the the ciphertext, and also the algorithm and the key size. These are again usually out in the open. But the one thing that we don't have access to is the key. All right, now in reality, also we don't have access to any bits of the key. We don't have any way as of now to find out a portion of this key by just taking a look at the ciphertext. It's just not possible. Unless a one-point mathematician or a cryptanalyst finds a weakness, but so far we haven't found anything yet. So if we want to break AES, and we don't have access to any portion of the key, well, we have to try every single combination. So we're going to have to start from this key, all the bits set to 0, and keep going up. Try every single combination. So flipping this first bit to 1, now here we have a valid key, we have to try this. Now here's another one, and then here's another one, and then we have to go all the way up until this point. You get the point, all right? So we've got 128 boxes, and if we want to try all these combinations, we have to do 2 to the power of 128 encryptions to make sure that at one point we're going to find the key. Now the number looks kind of small on the screen, but this is a very gigantic number, okay? And if you try to do this many operations, it's going to take you a very long time, all right? Now let's do a bit of math. Let's see how long it's going to take the most powerful supercomputer on Earth as of now to try this many operations. Now here I have gone to top500.org website, which lists the top 500 most powerful supercomputers on the planet. And I want to go into lists, top 500, and grab the list from November 2024. All right. If I scroll down, here you can see that as of now that I'm recording, the most powerful supercomputer is El Capitan, and it has 11 million cores, which is a crazy number to think about. And here you can also see how many petaflops per second this computer can do. Now, a flop is a floating point operation. So multiplying maybe 1.1 by 6.7 is counted as one flop. We're adding two floating point numbers. And this computer can do this many petaflops, right? So peta is a very big number per second, all right? Now using this number, we're going to calculate how long it's going to take El Capitan to brute force AES 128 and find the key, all right? So we've got the ciphertext, the IV, and the algorithm, but we just don't know the key. Now let's see how long it's going to take on this computer. Now keep in mind, this is a very powerful computer. It took $600 million to build this computer, all right? Very expensive. This petaflops per second is equivalent to 30,000 NVIDIA 4090 GPUs, which is one of the most powerful consumer-grade GPUs that we have available. So we're talking about some crazy power right now. All right, so if we want to do the math, we know that we have to do 2 to the power of 128 AES operations. Now let's say that we get very, very lucky and we find the answer quarter way through. All right, so after trying maybe 25% of the keys, we're going to find the answer. We're being very optimistic. It's way more accurate to go with halfway through and not this much. But again, let's try to be really generous. So we're going to divide this number by 2 to the power of 2. And now we've got 2 to the power of 126. So if you do these operations and we get really, really lucky and find the answer after trying only 25% of them, we're going to find the answer. Now, let's also estimate how many operations we do for each AES encryption. We've got 10 rounds in each one. We're going to do a few hundred integer operations, all right? And by integer operation, I mean shifting the rows or XOR or anything like that. So let's say 10 times 100, which is 1,000. Again, in reality, it's a few thousand, but let's go with this. Now, this is also how many floating point operations El Capitan can do per second, which you can see is a very crazy number. Now, in AES, we're primarily doing integer operations and not floating point operations. So let's also have another estimate and say that one integer operation takes 20 times less to do compared to a floating point operation, which again, we're being really generous. In reality, the number is close to 2 to 5 times faster, but let's go with this. So whatever number now we're going to come up with, we know that in reality, it's going to be much longer than that, okay? All right, with these numbers in place, now we can do a bit of math. So we're going to take this number and then multiply this by 1,000. So this is how many integer operations we have to do. And then divide this by this gigantic number right here, all right? And we also said that an integer operation on average would be maybe 20 times faster compared to a floating point operation. So we're going to multiply this number by 20. And if you plug this into your calculator, you're going to come up with this number. So this is how many seconds it's going to take to brute force AES. Now let's get rid of this number and say that it's only going to take 10 to the power of 21, just so that we've got a round number to work with. Now if we divide this number by this, which is how many seconds we've got in each year, now we're going to have the time in years, which is this much. All right, so this is how many years it's going to take to brute force AES 128. And if we divide this by 10 to the power of 9 to get a number in billion, it's going to be this much. Okay, so 30,000 billion years, or 30 trillion years, is what it takes to break the simplest form of AES. So don't ever think about trying to find the key by just having the ciphertext. So if you have encrypted your disk using AES, and you forgot the key, you lost the key, you've got no chance, absolutely no chance, at reversing the encryption process. Even if you've got the most powerful supercomputers on Earth, unless you're willing to wait more than the age of the universe. So, not possible. Now, we don't have any vulnerability in AES encryption that we know of, alright? So, this is how much we have to do. And the only threat that we have found out so far is quantum computing. Now, this is not a course about quantum computing, but I just want to talk about this really briefly. They're using an algorithm called Grover's algorithm, which is only for quantum computers. And keep in mind that we don't have a practical quantum computer right now that could do this, and we are years, if not decades, away from having this at our disposal. So we have to go a long way until this becomes a reality. But in theory, we've got this, and what's really special about this is that now using this algorithm with a quantum computer, our searching time is now going to be exponentially faster, all right? So on average, on a classical computer, if you have 1 million items and you want to find one, and it's unsorted, you're going to have to do 1 million operations to find the one that you're looking for. But on a quantum computer with this algorithm, it's only going to take you square root of that number, so square root of 1 million, and then you've got the answer. So now breaking AES 128 is going to only take us square root of 2 to the power of 128, which is 2 to the power of 64. Now, theoretically, on El Capitan, this only is going to take a few minutes, all right? So at this point, we can say that we have broken AES. Now again, keep in mind, we're saying theoretically, because we don't yet have a practical quantum computer that could do this. Okay, this is all in theory and math, but we know that if it becomes practical, this would be close, all right? Now, with AES 256, it's still the old problem, right? It's still going to be the square root of this, which is 2 to 128, and this still takes trillions of years, all right? So even if we get a very powerful quantum computer, which we're at least 10 years away from, we won't still be able to break AES 256, right? So we say AES 256 is quantum resistant. So if you want to encrypt some files and then make sure that they stay encrypted for many decades, it's much better to go with AES 256, okay? Because we don't know, maybe at one point quantum computers are going to become a reality. But if that's not what you worry about and you're only encrypting for a few years, AES 128 is secure enough, all right? Nobody is going to wait billions of years to break your encryptions. If you want to break it, you've got a much, much better chance at finding the person and forcefully getting the key. Now, this is not a mathematical guarantee. Still, we've got that possibility that someone, maybe a cryptanalyst or a mathematician, is going to find a vulnerability in AES, all right? So we don't know that yet, but we know that during the past 25 years, nobody has yet managed to do that. Now, OTP, one-time pad encryption, has been proven mathematically to be unbreakable, but AES has not, right? So we can't say that AES is going to be unbreakable during our lifetime or during the age of the universe. We don't know, maybe in 100 years or in a few decades, we're going to manage to break AES, right? But OTP is one algorithm, that's why it's called perfect encryption, that has been proven mathematically to be unbreakable. So it doesn't matter if we get some unprecedented, powerful computers that are even more powerful than theoretical quantum computers. It doesn't matter, we still won't be able to break OTP. But AES, we are not sure. We have to wait and see what's going to happen in a few years. Right, so now at this point you should know that breaking AES is not going to be an easy job for as long as the key is being kept secure, right? So if you are encrypting with AES, you can have a peace of mind that no one in the world is now going to be able to break it. Not even CIA, FBI, no government, absolutely no one. Unless your key gets compromised. So if you're encrypting with AES, but then you're keeping your key on a server that has 1234 as its password, well then, it's gonna be breakable. An attacker is going to now attack your server, grab the key, and then break your encryption. There's a saying in computer security that your system is only as secure as your weakest part, okay? So if you've got that weakness and people can get access to your AES key, well then it doesn't matter how secure AES is, all right? So you gotta be careful that you keep your key as secure as possible and do not ever compromise it. Never push it to GitHub or somewhere online that you know is not gonna be kept secure. So for as long as you make sure that your key is not being compromised and you're using an implementation of AES that is secure, which OpenSSL is, and also you take those things into account that we talked about. For example, you have to use truly random data for your key and IV and never ever reuse your IV vector, and also don't go with modes like ECB. So for as long as you don't make these mistakes, you can almost have a peace of mind that your encryptions won't be broken. And I say almost because, well, your keys could get compromised. You never know, maybe there's going to be a zero-click attack on your servers or your devices, or there's going to be a keylogger application installed on your machine without you knowing about it, and it's going to record all the keystrokes. Or maybe in a few years, a new vulnerability is going to get discovered in AES, and then it'll be time to move on to another algorithm. Alright, so that's it about this video, and I'll see you in the next one. In this video, we're going to talk about what happens if we try to brute force one-time pad encryption. This video is for those of you who are now wondering, now that you know what it means when we say brute forcing AES, now you're wondering, is it still the case that OTP is still more secure than AES when our data is small? So if we have 50 bits of data, will it be more secure to go with one-time pad encryption or with AES 128? Now, your logic might seem like this, that you might be thinking that AES 128, here our key space is 2 to the power of 128, so this is how many operations we have to do to finally find the key. And if we go with OTP, which we described as the perfect encryption that is unbreakable, now our key size here is only 2 to the 50, which is an amount of operation that we can easily do on a fast enough computer. So you might think that in this case, if you go with this, now you've got more security. Now, if you were thinking like this, you are badly mistaken, alright? This is not how it works. And the reason is, if we try to brute force OTP, we're gonna find tons of different keys that will give us different results after doing the decryption that are equally likely to be our answer. Now, if you understand the XOR operator and also how UTF-8 characters are represented in binary, you should understand what this means. That if you've got the ciphertext and the key, you can change the key however you want to come up with any plaintext that you want. Now, if that doesn't make a lot of sense to you, I've developed a piece of script here that you can play around with to really see this in action. So here, this file is called xor.js here in the OTP folder. You can grab it from the resource section of this video. And we've got a function that will get two buffers and then XOR them together, just like in the OTP file here in commander.js, and then return the result. Alright, so here we're grabbing the arguments, we're doing some error checking on them, and then here we are converting those strings to a buffer, XORing them together, and then we're running the result through UTF-8, and then logging it to the console. Now let's run this pretty quick and see what's going to happen. So here I'm going to navigate to the OTP folder, and if I say node xor.js, and I give it two different hex values, well, in this case, I'm not going to get anything because these two XOR together, it's going to be 0, alright? But let's first run the commander.js. If we go back here, we're encrypting two messages. One message is Commander Henrik standby to launch, and let's not worry about the other one. Let's just focus on this message 1. Here we've got it, here we are encrypting it, and then we are logging the hex output, alright? And we're also logging the key here at the beginning. So here's my key and the ciphertext of message 1. So let's try to do the XOR now manually using that script. So node XOR.js. Now I'm going to grab a bit of my key that will be equal to the size of this ciphertext. So if I start from 4, it should be the same length as my ciphertext. So let me copy this, and I'll paste it here as the first argument. And as the second argument, I'm going to provide this ciphertext. And if I run it, now we see these two values XORed together, and then the result ran through UTF-8, all right? Which is this one. Now, let's say that we were trying to brute force this thing, all right? And at one point, we're going to come up with this key. So I'm going to copy paste the exact ciphertext as before. And for the key, let's go with this key. So node XOR.js, the exact same ciphertext as before, but now we're going to go with another key, okay? So I did a bit of math here, and here's the key. Now, if you take a look here, they look really similar, but they should be different at one point. For example, if you look here, this one has 35, and this one has 0f. But for the beginning, they are identical, all right? And also at the end, here it ends with C18, this one ends with 204. So we get the point. If we are now brute forcing it, at one point we're going to try this key, and then at another point we're going to try this key. Again, these ciphertexts are exactly identical. So now if I run this, look at the result. Now we get Commander Henrik nuke launch command 7F2. So if we are brute forcing it, how do we know if this is the answer and not this one? And we can actually change our key however we want to get any result that we want, for as long as we have the same length, of course. So this Henrik could be another name that has the same length, or this command could be anything else. So we've got thousands and thousands of different possibilities here, and we don't know which one is going to be the answer. Of course, some of the keys are going to result in a gibberish plaintext, but also many of the keys will give us something meaningful like this. All right. Now, if we try to focus on a smaller portion, so here, let's say that this is our ciphertext, and this is the key that we are XORing it. And if we do the XOR operation, we're going to come up with this. Okay, so all the values here are correct. If you want, you can pause the video and go through this. And this plaintext here, if you run it through UTF-8, you're going to get 7F2. Now, if we change our key like this, all right, so notice here, I'm going to back up. Notice that I'm only changing these 4 bits. All right, now the result of the XOR operation is now going to be this, which if you run it through UTF-8, you're going to get 7C2. And if I now change it like this bit set to 0 and this one set to 1, now the result is going to be WA2, all right? So we have no idea to know which one of these is the actual result, because our key is the same size as our ciphertext, and it's truly random. We can change any of the bits, and it's not like AES that if you mess up one bit, you're going to get complete gibberish. And if you set all of them right, all of a sudden now everything makes sense. Here, that is not the case. We don't know which one of these results is the actual answer. And I just did a small bit of math to come up with these numbers. There are tons of other possibilities that could happen, all right? So this WA2 could be any other piece of string that is 3 in length, okay? So that's why we say OTP is immune, not only to quantum computing or to any other mathematical attack, but even to brute force, all right? So that's why this is the perfect encryption, that if we don't have the key, there's just no way for us to find the answer. And we can try many different keys, and many of them are going to give us some good outputs. Many of them are going to give us gibberish. All right, so that's it about this quick video, and let's keep going. In this video, we're going to briefly talk about the history of AES. Now, before we had AES, the mainstream standard encryption that we had was simply called Data Encryption Standard, or DES. DES uses a 56-bit key, which you can imagine can easily be broken right now on our computers, and also it operates on 64-bit blocks. All right, you can use it if you want, but again, it's deemed unsecure and you should never use it in production. So before AES, we had this one for about 20 plus years. Its development started in early 1970s by IBM and NSA. And NSA stands for National Security Agency, which is part of US Department of Defense. So the government was directly involved in its development with IBM, and it took a few years to develop it, and then it was adopted as federal standard in 1977. Now, all was good at this time. Many were using this DES, and then in the late 90s, it became vulnerable to brute force attacks on special expensive machines. So if you had a special machine, you could break this DES at that time in just a few days. Still, it wasn't cheap, it was really expensive, but for an encryption algorithm, we don't want even a single person in the world to be able to break it. If that's the case, then it means it is not secure. So because of this, people now realized that it's now time for a new encryption, alright? And this one was going to be called Advanced Encryption Standard, because now it's supposed to replace a data encryption standard, alright? So it's now more advanced, more secure. Now, the development of this one was a little different from DES. NIST, which is the National Institute of Standards and Technology, part of U.S. Department of Commerce, announced a contest in January 1997 that the federal government no longer has access to a secure cryptography mechanism, so we need a new encryption. Now, everybody throughout the world was invited to participate in this contest and submit their algorithm, so people were working on it from all around the world, and about 15 algorithms were submitted to this one. The contest had very strict requirements, and it wasn't easy to really make it. But about 15 were good candidates, and out of those that were submitted, the one that was called RheinDial became the Advanced Encryption Standard, okay? So sometimes online you see that people refer to AES as RheinDial, and that's the reason that originally the algorithm that was submitted and accepted to be the new encryption standard was the RheinDial algorithm. Now, if you want to see the whole list of the 15 algorithms that were submitted, you can come here to the NIST website, right, to this paper. If you download it, on the second page, you can see the whole list of these algorithms, right, so profiles of candidates. And you can see here that RheinDial was submitted right here, and it became a standard. It was developed by only 2 people, and some of these algorithms were developed by companies, and they were submitted from all around the world. For example, CAS256 was submitted from Canada, E2 from Japan, and the others from the rest of the world, Germany, Israel, Norway, South Korea, and so forth. So this one was the one that made it through, after being tested by NIST and world's best cryptographers for a long amount of time to really make sure that it's secure. Now, security wasn't the only criteria for this. If security is all that we care about, then we're going to go with OTP. There are other things that we need to take into account as well, like how efficient it is, how easy it is to design hardware-accelerated components for it so that now we can do decryption and encryption faster, and also how easy it is to understand so that now many people have a chance to look over it and make sure that there are no vulnerabilities in the algorithm. So efficiency and simplicity were also another 2 big requirements for the algorithm, apart from security, of course, and RheinDial checked all the requirements. Alright, back to the slides. So, NIST announced the contest, and then the development of the algorithms began at that time, and these 2 gentlemen, Damon and Vincent, were working on AES, alright? So, the development again took a few years, it was submitted, and then after years of scrutinizing over it by NIST and other people, it was then selected and then became a standard in 2001. So that's a brief history of how AES came to be this. And I want you to pay attention to something here, that the moment that we found out that DES is no longer secure, which was around late 1990s, it took us about 5 years until we came up with a whole new algorithm that can now replace it, okay, which was now the year 2001. So if right now AES becomes, well, unsecure, it's not going to be like that tomorrow we're going to have a new one. It's going to take a bit of time until we can make sure that we have an algorithm that we can now all trust, okay? Now, also, part of the reason that the NIST organization wasn't directly involved in the algorithm development, like with DES, that NSA was directly involved in it, was that during the time that DES was developed, there were a lot of talks in the government that we need to ban encryption because it's getting too strong. Well, you can kind of understand this perspective of the government and why they want to ban it. that if somebody, a criminal, does something online and they have a warrant to arrest the person, they want to be able to go to the company that has the messages, for example, WhatsApp, Apple, or even the ISP companies, and ask for a copy of the messages or the files that that user has uploaded. But right now, they can't do it because AES is unbreakable. So not even the companies can see your messages and what you're doing, provided, of course, that you're doing end-to-end encryption and not encryption that's just from you and the server. So this is a bit of a problem for the police enforcements and the government, and of course it's something that the public is not going to trust. So at that time, when all these talks were happening, they're still happening in 2025 right now, usually governments don't like the idea of a strong encryption, and there's always this talk to introduce some sort of a backdoor into them. But we know that if we do that, then the algorithm is no longer secure. It essentially means that we can now break it. And if somebody can break it, if a single person can break it, now other people can do that too, alright? Even if it's going to cost a lot, it's still nothing that should happen. And during that time, during the time of DES, the talks were more prominent. And people didn't really have this public trust towards the government to trust the government to now develop a whole new algorithm. So what NIST did was that it didn't directly get involved with the development of the algorithm, and rather it announced a contest. And this is how we have this AES. So we shouldn't take this encryption that we have right now for granted. It could one day be banned, which I'm really hoping won't ever happen, but it could. Okay, there are efforts from different people in the government, and not just the US government, from many different governments around the world to do this. They're not as strong, but the threat, well, kind of exists. Alright, so that's it about a quick history of AES, and I'll see you in the next one. In this lecture, we're going to take a break from encryption and move on to another topic of cryptography, which is hashing. Hashing is a fascinating topic. It allows us to do things like verifying exactly who is sending the data, doing authentication. This is what is at the core of Bitcoin and other cryptocurrencies. So it is a very important topic, and it would now allow us to do so much more. Now, before we get into this exciting topic, let's first take a look at our cryptography roadmap and see where we are. So far we know how to encrypt data, and we know how to do it in a very secure way so that now no one in the world could break it. No governments, not even the most powerful person on earth. And we know that we can do that for as long as we keep the key secret. So we got that part covered. But we yet haven't talked about how do we derive these AES keys in a user-friendly way. So your Android or iOS device is encrypted with AES. And it would be really impractical so that every time you log in, it's going to ask you to put in 128 zeros and ones. Okay, that's ridiculous. So we need to find a way to derive these keys from something that's much smaller. Let's say maybe a 12-word password, or a password that's 10 in length. So this is something that we need to first talk about to make sure that we have a cryptography system that is actually usable in the real world. Another problem that we need to tackle is how do we ensure that we have integrity and we can now do authentication. Now, integrity, all it means is that we have a peace of mind and we are 100% sure that the data that we are getting hasn't been tampered with in transmission. Okay, so if an attacker is listening to our conversation, which is pretty common, and they are modifying our bits, we want to make sure that once we get the data, we can know with 100% certainty that something bad happened in the data. If we have no idea that the data was tampered with, now we have a problem. So we need to make sure that we have this integrity. Now, authentication means that if we're communicating with someone and we're getting data from him, that someone is who they say they actually are. So if someone else is impersonating that entity, we want to make sure that we know it. All right, so if you're talking to Google, if you're doing a Google search or you're putting your password to log into your Gmail, you are getting this data from a server, right? So what if now someone else tries to tell you that they are Google? So all they have to do is to specify Google's IP address and domain name and send you the data. Well, if we don't have authentication in place, there's no way for us to know. And now we're duped into putting our password and giving it to that attacker, which is a very big problem. Now, another problem that we need to tackle is how do we exchange our keys, our symmetric keys, AES keys, in a very secure way in clear text. If we can't do this, then encryption really wouldn't make sense, right? We can't always meet up in person to exchange our keys. So we need to make sure that we have a way that we can send the keys in clear text through HTTP or TCP, for example, and make sure that no one has an ability to see that key, all right? You can't just send your AES key through HTTP and hope for the best that no one in that period of time is going to pick it up. Okay, that's never going to work. You need to make sure that you have a system in place that this key exchange could happen in a way so if hundreds of people, attackers, are listening to your conversation, they have no idea how this key was exchanged. It's pretty interesting, actually, to see how we can do that. Now, to solve the first two problems, we're going to have to first talk about hashing. Okay, so hashing is at the core of solving these two problems. Without hashing, we can't ensure integrity and do authentication. All right, and also we can't really easily derive an AES key from something else. And for the last problem, we need to talk about asymmetric encryption. So asymmetric encryption is what will now allow us to do this key exchange in a very secure way. So once we solve these three problems, then we can say that we have a very strong cryptographic system in place that is incredibly secure and also very user-friendly. So we have that peace of mind that with a very high probability no one can break into our system unless the users compromise their keys or mess up their security in one way or another, but we need to do our best from our part. All right, so let's first go ahead and talk about hashing so that we know how to solve these two problems. And then in the next part of the section, we're going to talk about asymmetric encryption and see how we can do this key exchange. All right, now on to hashing. Now in hashing, we've got a hash function, which is just an algorithm that gets an input that's called message. And this input could be any in size. It could be only one character or it could be terabytes in size. It gets the data and then it does a bit of processing on it. It compresses it down a little bit, does some math, and then it would give us an output that is fixed size. So in this case, we're going to get 256 bits of data, which is called the hash or digest. Right, so please pay attention to a few things right now. We don't use the terms plaintext and ciphertext here in hashing. Instead, we've got message for the input and hash or digest for the output. These are standard terms and we're going to stick with them as much as we can. Another point is that our hash is always a fixed size, and ideally it shouldn't change. So again, the message size could be pretty much anything. So it could be only maybe 10 bits in size, and then we can feed this data in, and these 10 bits are going to become this 256 bits of data, all right? Or the size could be, I don't know, maybe 10 terabytes. We can feed this data into our hash function, and then we are going to get another 256 bits of data. All right, so that's the idea of hashing. Pretty straightforward. Now, hashing is all about comparing two pieces of data to see if they match on every single bit. So that's why we need to do hashing. So this is what will now allow us to verify the integrity. So if we're getting the data, we can now compare this one with what the user intended to send in the first place and see if they match on. Now we have integrity. If even a single bit is modified in any shape or form, we're going to now get a completely new hash so that we know that something went wrong. Or in terms of a login authentication with email and password, we shouldn't save the passwords of our users in our database as they are. Okay, we need to hash and salt them first. Salting is something that we're going to talk about later on. But the idea is, again, based on hashing. So when the user signs up, we get the password, we hash the password and salt it, and then save that hash to our database. So that in subsequent logins, we're going to get the password again and hash it again and see that if the passwords match, we know that the user is who they say they are, so that now we can log them in. So it has many use cases, not just in cryptography, in many other places as well. Now let's first, pretty quick, go to our Visual Studio Code and develop a hashing function from scratch, just so that you see how easy it is and get the idea of hashing. Here, let's create a folder and call it maybe hashing, and then inside have another file called simple-hash.js. Now here, let's have a function and call it simple hash. That's going to get a message, which is a buffer, and then it's going to return the hash. So here's how we're going to call this function. We're going to say const digest or const hash equals simple hash, and then we're going to give it some amount of data, so buffer dot from, maybe string hello. And then we're going to log the output. Digest dot toString, and we're going to get the binary value because the output of a hash function is a binary value. So we're going to now log it. Now we're calling it again message here, but in hashing we don't care what our data is. It could be an image or a video file or a simple string. We are only dealing with the raw binary data. So let's do this process. What we can do now is to go through this message one byte at a time, and then maybe modify them in some way or another, multiply them by some prime numbers, for example, and then add them together, take the modulo of that number maybe, and then return it. So pretty straightforward. So let's just do something random here. I'm going to maybe have some primes. Let's come up with a few prime numbers. Let's say that we want to have maybe 10 prime numbers and each one 8-digit in size. So let's see if we can grab some from the internet. So I'll search for a prime number generator. Here I'll go into this big number generator and I'll put in 10 numbers, number of digits, 8 each. And let's see. All right, so these are good enough. I'm going to copy all of them. And let's paste them right here. And then I'm going to put them all into the array right there at the top. So I'll do this. I'll hit the backspace and then put in a comma. And that should be pretty much it. Now I'm going to wrap it up in these brackets. And this is now going to be our list of prime numbers. So what we're going to do is to maybe take each one in a circular way and multiply it by each byte that we've got. All right, that seems like a pretty good hash function. Okay, so again, remember, the goal should be that this message should be anything in size, and then the output is going to be maybe 32 bytes of data. All right, a piece of data that always corresponds to that message. So for as long as I don't change my message, I should always get the same hash. And if I change my message even by a little bit, I should now get a new hash. All right, so that's how we can make sure that the message was not changed. So let's now loop through our data. So I'll say for let I from 0, and then I less than the message dot length I plus. And here we're going to maybe say message I, so grab this byte, and then multiply it by the primes that we've got at the top, right? So one of the elements, so primes, and then I'll grab the ith element, and then get its remainder by 10, okay? So because the message length could be very large, but we only have 10 prime numbers right here, okay? So we're going to multiply this, and then let's save it to this variable called temp, and then here we're going to set, let's maybe XOR the byte again with this temp. Okay, why not? That sounds like a reasonable thing to do. So I'll say message I equals message I. And then remember how we do the XOR? It's this operator and then with temp. Now in hashing functions, we do a ton of XORs. Okay, so that's why I'm doing it here. Now, after this, we can just go ahead now and return, but let's do something else. Let's also shift each byte to the right. So I'll say for let I equals 0, and then I less than the message length, just like before. And then here we're going to say message I is equal to message I, and then we're going to shift it to the right by 2 bytes. And excuse me, I said shift it to the right by 2 bytes. It's actually shifting to the right by 2 bits. All right, so shift the data to the right by 2 bits. So for example, if our data is this, if we have 8 bits of data and we shift it to the right by 2 bits, so shifting it to the right by 1 bit is going to be this, and then by another bit is going to be this. All right, so that's essentially all that we're doing, okay? We are modifying our data, and we want to make sure that we have something that's pretty much one way, all right? So we shouldn't be able to go from the hash back to the message, right? So sure, we're losing data, but that's what we want. We want to get some sort of a fingerprint from the data. So we should have something that would represent the original data, but we shouldn't be able to know what the message is just by taking a look at the actual hash. So it is expected that we lose data right here, all right? We're turning something that's terabytes in size into only maybe 32 bytes, all right? So of course we're losing tons of information. Now after this, let's maybe multiply the numbers by the prime again. and then add them all together and get the remainder by maybe a big number to get something fixed size. So let's do that. So we're going to have something called result, which is going to be 0 initially. And then we're going to do pretty much the same thing here, but with a bit of a modification. So let me quickly type it. So I from 0, I less than the message length, and then I++. Here we're going to say result plus equals to the message, the ith element, and then multiply this by the primes, the ith element, just like before, and the remainder by 10, so that we can now circulate. And then here, because this result could get pretty large, we're going to always do this modulo and get its remainder by this number. So result equal to result, and then its remainder by maybe 1. Let's put in a few zeros here. Maybe 8 zeros, so 3, another 3, and then 2 more. So now I've got 8 zeros right here. And then after this, we can go ahead and return this result to be our hash. So we can have something called the result buffer. We're going to allocate 4 bytes to save this. So buffer.alloc4. Because this number cannot be bigger than 4 bytes. Again, use your programmer calculator if it doesn't make a lot of sense, but using only 4 bytes, we should be able to represent this number. After this one, we're going to write the result to this buffer. So result buffer dot, I'm going to write it as an unsigned integer that is 32. And then I'll say the result, start to write it from the very first byte, which is something that we want, and then return the result buffer. That looks pretty good, so let's go ahead and run it. So here I'll navigate to hashing and then node simple hash.js, and now we get this number. Now notice if I run it another time, I'm going to keep getting the exact same number. All right. So if we have 2 hash values that are the same, then it means that it corresponds to the same data. Now if I put in a very large amount of data here, so I'm going to keep on typing, but this data could be anything because we're doing this again in a circular way, and our hash value is not going to get ridiculously large because we're always doing this thing right here. And if I run it again, we can see that I get another number, all right? And I can keep on doing it, and even if I run it 100 million times, I'm going to keep getting the same value. Now if I change only a single thing here, so from F I go into capital F, and I run it again, notice that now I get a totally different result. Now, it's not totally different maybe, because it seemed maybe a little similar to what we had before, so maybe that's not a very good hash function. There are some requirements that need to be in place to make sure that a hash function is cryptographically secure. This is not a secure function in terms of cryptography, but it is a valid hash function. So let's try maybe a few more values and see what's going to happen. I'll try this. We get this value. And then let's maybe change this to capital I. Run it again. Well, it's a little different. But I'm trying to maybe find something that's called a collision. Let's see if we could do that. Well, here we can see that they look a little similar, which is not something that we want in a cryptographically secure function, but we're getting there. Actually, I'm going to pause and try a little bit. Alright, so I came up with this number, and notice that when I run it, I get this hash. Now I'm going to make this last I into capital I, run it again, and notice that now I get the exact same hash. Alright, so this is what we call a hash collision. And if we want to use it to verify integrity, now we've got a big problem. Because, well, I just came up with this thing in no time. Using some mathematical operations, we can now find tons of messages that would result in the same hash. And if we can do that, we can learn a lot more about this algorithm and then know how to break it. So now we've got a problem. Now an attacker could modify the data in one way or another, and then make sure that they modify it in a way that the hash is not going to get changed. Okay, so this is a big problem, and we should not be using this for cryptographic purposes. So I'm going to write a comment here. Although it's a valid hash function, this is not cryptographically secure. So I'll say a simple hash function for non-cryptographic purposes. This is very important. Now we're going to talk about what characteristics should be in place to make sure that the function is cryptographically secure. But for now, just try to please get the idea of hashing, that this is what we're doing. All right, so now that we have some sort of an idea of what we're doing in hashing, Let's now use the crypto module and try to use some cryptographically secure hash functions. So here I'll create a new file and let's call it app.js. So first we have to grab the crypto module. And then here we can create our hash function, const hash function equals crypto. Now the function that we use to create hash functions is called simply create hash. And then here we have to specify our algorithm. All right, so we can, for example, go with something that's called SHA-256. We're going to talk about what options we have available. And then now we've got the algorithm. So this is now like this simple hash function that we've got. So all we have to do now is to give it a message, and then it's going to give us an output. Now, SHA-256 is 256 means that the output is always going to be 256 bits in size. So let's try it. So I'll say hash function dot update. So we have to call this function every time we want to pass it some amount of data. And I'll say hello. Now we can keep on passing it more data like this. So maybe some more text right here. And then once we're done, we have to call the digest function. So hash function dot digest. And here we can specify the output that we wanted, the encoding. I'll say just hex. All right, let's also log this. So here, this is going to be our final digest or the final hash, and then console.log the digest. Okay, pretty straightforward. Now we can also use this in the form of a stream. So this hash function could also be a transform stream. So you can give it terabytes of data, and then at the end, it's going to give you only 256 bits of data. So let's run this, node app.js, and you can see now we get this hash. Now I'm going to run it again, and this time around, because it's a secure function, it's going to be absolutely close to impossibility to find two messages that would give us the same hash value. In fact, we haven't yet found two messages with this SHA-256 that would give us the same digest. Although we have trillions and trillions of possibilities, we still haven't found even two of them. So it's a very fascinating thing to think about how this thing really works. So with some simple math, we're creating a fingerprint for each piece of data. Now we're going to come back to this in a bit, but let's first take a look at the list of all the hash functions that we have available. So to see that list, what we have to do is to log. We can also do this with a simple OpenSSL command to get the complete list, or you can do it here in Node, but let's do it here. So console.log crypto.get hashes. Now this is going to give us the complete list of all the algorithms that we can specify in that function. Now it might look a little overwhelming, but it's actually really easy. We can categorize all of them in a very neat way. Some of them are very unsecure. For example, everywhere you see MD5, please do not use it. Okay, stay away from MD5 at all costs. It has been broken, and we'll see that in just a bit. So we've got all these different functions. You can, for example, try this one, SHA-3256, and this is going to give you another result that's now obviously different, but still 256 bits in size. So these numbers that you see at the end, they usually mean the final size in bits. All right, I say usually. For example, here you see SHA-1. It's not that the size is always going to be 1 bit. Of course, it's going to be more, but this one here means that it's family 1. Or MD5, it doesn't mean it's only 5 bits. But usually these bigger numbers that you see, like 224 or 512, these are the size of the final digest. Now, another point that I want to mention before we go ahead and categorize all of them, these RSA things and these other names that you see, like ID RSA and then this whole thing, it really doesn't matter. We're going to worry about these in the asymmetric part and not right now. All right, so for now, know that they are the same thing. Okay, so if I run this here in the create hash function, so this crazy value, but notice that the final thing is SHA-3-384. I'm going to also comment this one out. So if I now run this, I'll get this value. And if I now remove this part of it, and just go with this, I'm going to get the exact same value as you can see right now, all right? So when we're using this create hash function, all these things are going to be the same thing. For example, this one is the same thing as this one, or this one is the same thing as this one. SHA-384. All right, so now it's much simpler to now think about this. And let's now try to categorize all of them. So, first of all, we've got MD5, which is a valid hash function, but something that you should stay away from. It was broken, so I'm going to put it in red. Next up, we've got the family of SHA functions. SHA stands for Secure Hash Algorithm. And we've got 3 families of them. The first family is simply called SHA-1, and we've got only one algorithm here. This one has also been broken, and you should stay away from it at all costs. Now, next up, we've got the second family of the SHA functions, and this one is called SHA-2. And here we've got 4 different variations, right? 224, 256, and these other 2. And the numbers at the end only say the final size of the digest, all right? And that's it. They are all the same algorithm, SHA family 2, which is a different algorithm from SHA-1, but still in the same family. And these sizes are different. Now, these are all secure. They haven't been broken yet. That's why I'm putting them in green. Now, I've also boldened SHA-256 because it's the most commonly used algorithm in the world. Not just in hashing, it's one of the most common ones. If we were to name top 5 algorithms that are mostly used around the world, SHA-256 would be one of them. All right, this is at the heart of Bitcoin and tons of other things that we're going to get into later on. So I have boldened this one because we're going to really focus on this and understand it because it is considered secure. And if we really focus on just one algorithm and really get it right, the rest would be pretty easy to understand. Okay, so this is where we're going to put in our most focus into. Now, SHA-224 is also considered secure, but it's not as commonly used as SHA-256. And this one is also a little more secure. It's better for future-proofing yourself. So if you want to use family 2, go with 256 and not 224. The very few bits that you're saving is really not worth it, right? Now, the next family is SHA family 3, and we've got these different variations, okay? Again, the final value is the size of the digest. The family 3 is considered more secure than family 2, but again, family 2 still hasn't been broken, okay? So mathematically, it's a little more secure, but nothing that would make SHA-2 obsolete like SHA-1 or MD5. Now, there's also another thing that we've got, and that is the Blake algorithms. And we've got 2 of them. We're not really going to talk about them much. They're used in some places, especially in password hashing. But again, we'll talk a little bit about them later on, but not so much. All right, so these are all the algorithms that you need to worry about. Again, you also need to worry about MD5 and SHA-1 because they're available to us and we should never ever use them. For example, here, if I go ahead and specify MD5 and run this again, it gives me a hash, but I don't see any warning whatsoever that this is considered unsecure. All right, so many people have been using it even after it was broken, and it was catastrophic for many people. Okay, many people lost their passwords, and HTTPS certificates got fabricated with something bad. So we had tons of problems with this, and developers weren't moving away from it, which they should have, but they didn't. And, well, that's what we have right now. All right, so let's take a look at the timeline of these algorithms and see when they came from and when they got broken. So here I'm going to put in the release date for each one and the broken date. MD5 was released in 1991, and it got completely broken in year 2004. Now, you might be thinking, what happened in the year 2004 when MD5 got broken? Well, did it mean that we had a catastrophic event and tons of things got stolen? Well, absolutely not, because many, many years before 2004, mathematicians and cryptanalysts have discovered some vulnerabilities in MD5, mathematical vulnerabilities. But we were still years away from getting into a computational power that we could now utilize them and then make that practical and actually break MD5. But many developers did not pay attention to those theories and they stick with MD5. And well, it was a catastrophic event for the users of those applications and those businesses. It's a common mistake that developers who don't understand the theory behind the concepts usually make. If it's broken in theory, if it's mathematically broken, then it's only a matter of time before it becomes practical, and it's now time to move on from it. But again, a mistake that many developers made, and well, a lot of people also realized this and they moved away from it, so it wasn't a problem for these people that MD5 got broken, but for those who didn't pay attention, it was a costly mistake. Again, it's a common mistake in cryptography, And if you don't want to fall victim to the same thing, you need to pay attention to the theory behind it and not just do applied cryptography. In SHA-1, the same thing happened. It was introduced in 1995, and then it got broken in 2017. But again, a few years before that, we knew in theory, using math, that it is now broken, considered broken, although we can't practically do it. But then in this year, 2017, the computers got so strong that everybody can now actually break it. Now, SHA Family 2, this was introduced in 2001, and we still don't have a broken date. So there's no theory behind it that it's now broken. It's considered very secure, and we're going to talk about what it's really going to take to break it, like we did in AES. So this one is considered secure. SHA Family was actually developed by NSA, and the NIST organization then published it. And we're going to take a look at the specification in just a bit. So although this was designed by a government agency, and tons of controversies were going on around them, that they're trying to kind of break the algorithms, introduce a backdoor into them, so that they can now listen to what people are doing and whatnot. But this is actually considered to be secure. Now, SHA-3 was released in 2015. Same thing, no broken date. And the Blake algorithm also in 2013, and still no broken date. So we're using SHA-2 for about 25 years now, and we still haven't found a way to break it, all right? So you'll be just fine by sticking with SHA-2. You can also go with SHA-3, which is a little more secure, but it's usually not a cause of concern, unless you want to stick with it for many decades. Alright, so we've been talking about breaking these algorithms, but we still haven't talked about the kinds of attacks that we have available, which is important to understand. But before we do that, let's again do another recap on hashing. So SHA-256 is what we're going to stick with as much as we can. And every time we give it a bit of message, we will get exactly 256 bits of data. And if we change our data even by a little bit, we're going to now get a completely new hash. Now, if you've watched the streams section, we were moving some big files around using node streams, and we were trying to figure out whether or not we had messed up some of our bits, all right? And we used a very horrible way to check that. We checked the file sizes, and we said that if the file sizes are the same in bits, it means that the data hasn't been changed, which was a terrible thing for me to say. It's good to get a rough idea that it's practically the same file, but what we should have done was to check the hash values of those files. So we've got an app.js and simple hash. Let's say that we want to make sure that these two match up. So we've got this command in the terminal called SHA-256. You have access to this most probably on Linux and also on Mac. On Windows, I'm not sure, but you can just watch me do it. So SHA-256, and then you can specify your file. For example, app.js and then simplehash.js. And if I run it, you can see that now the hash values are now totally different. So we can conclude that these two files are now not the same. If I copy app.js into app2.js and then get the hash of these two files, so app.js and then app2.js, now you can see that the digests match, meaning that we can now be 100% certain that these two files have the same content. Now if I go into app2.js and maybe change it just a little bit. Maybe, I don't know, comment out this line. And do that again. You can see that now we get a totally different hash for these two. Which means that the app.js and app2.js, they don't have the same content. Again, even if a single bit changes in terabytes of data, we're going to end up with a totally different hash. So this is what we should have done in the streams section and not actually just checking the file sizes. Anyway, so that's again the idea of hashing. It's not only using cryptography. For example, if you're dealing with objects in Node or other languages that you have key value pairs like this, for example, name is Joe, and then you might be having millions and millions of other properties here. And then when you want to look up something, so you do something like this, object and then name. Now, if you have a million key value pairs and your property is all the way at the end or somewhere in the middle, it doesn't mean that now you're going to do a million checks against each one until you find that property. What's happening behind the scenes is that the keys are getting hashed and the hashed values are saved. Hash values are numbers that would in this case correspond to memory addresses. So when you're looking up something like this, you're just moving around in your memory, which is instant time. So if your object only has one property, or a million, in both cases, looking up items is going to take the same amount of time, right? Which is pretty great. So hashing is also used in places like these. Now, I have to say that the hashing algorithm that's used for this is not, again, cryptographically secure. It's designed to be really fast, but not really secure, okay? Now, we've been talking about this security in hash functions quite a bit now, that some of them also got broken, but we haven't talked about what that security should look like exactly. So let's take a look at the complete list. For a hash algorithm to say is cryptographically secure, 4 properties need to be there. The first property is called the pre-image resistance. What this means is that if we have a hash value, there shouldn't be any way for us whatsoever to get to the message. Okay, we should not be able to do this in any shape or form. If we can do this, then it means that the hash algorithm is not secure to be used in cryptography. Now, this is part of what happened in MD5, that if you have a hash MD5 right now, you can easily find what the message was. But in SHA-256, there's no way to do that. And if you can find a way to break SHA-256 like this, you can get access to all the bitcoins in the world. And you can wreak havoc on the internet if you can somehow do this process. So trust me when I say there's no way now that when you do this hash, SHA-256, there's no way to go from this back to the data that we had. Now, if our data is very small, we can brute force it, but if it's large enough, it's close to impossibility, okay? Or if you want to do it, it's going to take you trillions of years, which is something we're going to talk about later on. So this is the first property that a hash function should have to consider it to be secure. The next property is called the second pre-image resistance. What this means is that if we have a given message, let's call it given message 1, well, we know it's hash value, right? It's pretty straightforward. You just give it to SHA-256 or any other algorithm and you get the hash value. Now, it should be impossible to find another message, message 2, that will give us the same hash value. All right, so we shouldn't be able to do this. If we can, again, we would consider that algorithm to be broken. Now, the third property that we have is called collision resistance. It's pretty similar to the second one, but it's a little different, and we've got a different attack on this one, which we're going to talk about in the next video. But what this means is that now we shouldn't be able to find 2 messages that would give us the same hash value. All right, so in the previous one, we had a given message, let's say message hello, and our job was to find another message that would give us the same hash as string hello. But here in collision resistance, we are free to choose any 2 messages that we want. And the reason that this is a problem is that if we can do this, then we can find some vulnerabilities in the hash algorithm. So this again hasn't been done yet in any of those green algorithms that I've showed you. None of these have happened in those green ones, but in the red ones like MD5 and SHA-1, these have happened. Now, I want you to just take a break a little bit and think about them for a while. That, for example, in second pre-image resistance, let's say that a user logs in with a specific password, and then an attacker steals the database, which is something that could happen from time to time. It's not impossible to do that. And then they can take a look at all the passwords in the database, but they've got the hash values. But if the company is using a hash algorithm that is not secure, the attacker can now come up with another message that would give the same hash value. So now they could log in as that person, which is a big problem. Now, another property that we have is called the avalanche effect. What this means is that even if we change a single bit in our data, we should now get a whole new hash. So if we change only a single bit, or if we change all the bits, it shouldn't matter. We should, in both cases, get totally different hash values. So there shouldn't be an easy way for us to modify the message in one way or another to get a specific type of a hash. For example, a hash that has some numbers or looks a little similar to something. That shouldn't happen in a very secure hash function. So these 4 properties are very important to have in a hash algorithm to be used in cryptography. If we don't have them, we can't use it there. Again, notice that in our simple hash, we don't have any of those 4 properties. Okay, it's just a simple hash function, but not for cryptographic purposes. So we've got a collision right here. When I change this, let me actually write a comment right here. So we've got a collision. If we use this one and also this one, they would both give us the same hash value. A big problem. And also, it's not that difficult to go from a hash value back to the actual message. because we're only using, how many? 32 bytes of data. So if we have a hash value, let me run it again. So node simple hash, we've got only this much. Okay, so 32 bits of data. So if an attacker wants to find the actual message, all they have to do is to do 2 to the power of 32 operations. And if they do this much, they are guaranteed that they will find a message that will give the same hash. All right, so a big problem. This is a very tiny bit of operations. You can easily do it on your computer in a matter of seconds. So we don't have pre-image resistance, we don't have second pre-image resistance, collision resistance, and also the avalanche effect is not there. So if I've got this data and I change it up a little bit, for example, remove this E. Now in this case, well, we've got only a bit of data, so it might not really be that noticeable, but I've been playing around with it, and in some cases, when I've got a bit of data and I change it up a little bit, my hash would then look a little similar to the previous one. So we also don't have the avalanche effect here. But still, although it's not cryptographically secure, it is a valid hash function. Now, to show you the avalanche effect and how difficult it is to do that here in SHA-256, we can talk a little bit about Bitcoin. I'm not a Bitcoin miner or a crypto trader or anything like that, but it's just fascinating to think about. So Bitcoin at its heart is SHA-256. And when you're mining Bitcoin, if you have heard that term, all it means is that you are calculating trillions and trillions of SHA-256 hashes. The goal is to find a particular hash that looks similar to something, and because of the avalanche effect, we can't lead ourselves to that. We have to brute force and try many different combinations. Now we'll talk more about this in one of the future lectures, but that's essentially what Bitcoin miners do, that they are calculating trillions of these SHA-256 hashes to find a particular one. And if they can find it, they're going to get a few Bitcoins in reward. And we have specific devices. Yeah, I got this link. I'm going to paste it here. It says 8 best Bitcoin mining machines. And these machines, okay, these hardware machines, all that they do is that they are specifically designed to do SHA-256 and nothing else. And here, if you take a look, it says hash rate. For example, this one can do 255 trillion SHA-256 hashes per second. And all these other machines right here, and you can see that they cost a bit, all right? Now, you might be saying, for example, if we buy maybe 1,000 of these machines, and they're much more efficient than the most powerful GPUs at calculating SHA-256, would we then be able to find even one collision in SHA-256? So you might be thinking that we're calculating trillions and trillions of hashes per second. So surely at one point, we're going to come up with 2 values that would give us the same hash. Well, it hasn't happened before. And if you think about it, so we only have 2 to the power of 256 possibilities. But we have tons of data combinations that are much more than this. So all the data in the world is something much bigger than that. All right. So we have trillions and trillions of messages that would give us the same hash based on the pigeonhole principle in math. Now we're going to talk a little bit more about that in the next video, but based on that principle, if we've got this much data, we are guaranteed that some of them, or many of them in this case, would end up in the same box, for example. All right, so they're going to end up with the same digest, but we haven't managed to find even a single one. Now, this SHA-256 is also absolutely not magic. All right, if you want, you can implement it from scratch. You can find tons of code online. And also the specification, let's also very briefly take a look at the specification. So here, if you go to the NIST website again, and if you open up the publication here and take a look at the paper, well, I've got it right here. So it's FIPS 180-4. And here in only 36 pages, you can see how this SHA algorithm works. And actually the whole family. So it's talking about SHA-1 and then SHA family 2. Also, just a few more points. If you see SHA dash a number, it means it's SHA family 2. And if you see SHA-3 dash a number, it means it's SHA family 3. So I believe here in this file, it's only talking about SHA-1 and SHA-2, right? There's no SHA-3 here. Now, also, when you see something like this, for example, SHA-512, we had it here as well. So if we get the hashes, here we also have something like SHA-512 and then 256. All this means is that it's still SHA-512, but then it's going to truncate the output to be 256 bits in size. And the reason that we might want to do this is because of efficiency reasons. SHA-512 is faster than SHA-256, And another reason could also be compatibility reasons, that if you want to now change to SHA-512 from SHA-256 to make things faster, now you don't need to change your whole system to work with 512-bit of hashes. You can still stick with 256-bit of hashes. All right, so let's keep going with this specification just a little bit. So here, if you scroll down, you're going to see how some of them are done. And here in this table, it's showing these algorithms and the message size. So if you want to use SHA-256, if your data is larger than 2 to the power of 64, it's not going to work. Now, this is a very big number. 264 in bits is, I think, hundreds and hundreds of terabytes in size. So it's a very gigantic number. And the block size, we'll talk a little bit about what the block size is, and also the message digest, which is always 256 bits. For SHA-512, it's always 512 bits. Alright, so that's it about SHA-256 and hashing in general. I'm going to cut this video right now. In the next optional video, we're going to take a look at an implementation of SHA-256 in Node from scratch, which could give you a better sense of really what's happening behind the scenes and get this idea that it's not really magic. So that's it about this video, and I'll see you in the next one. In this optional video, we're going to take a look at an implementation of SHA-256 in Node from scratch. You can skip this video if you don't want to go through this. We're not going to write it ourselves. We're not going to understand every single line. But still, if you go through it, it's a good practice. It will give you a better idea of how a cryptographically secure function works. There are just a few things in code that I want you to pay attention to. Alright, so I want to create a file here, SHA-256.js. And I encourage you to go over this code if you want. Again, it's not that difficult, and I don't want you to think that, well, hashing is magic. Nothing in cryptography is magic. Everything is simple math that you can trace on a piece of paper, one step at a time. It's not random. Well, it appears random. For example, we don't know how to change our message to get that final value. But if we have the message, we can easily trace it on a piece of paper to see what the final hash is going to be. So nothing in cryptography is magic or seems like magic. Well, actually, I take that back. There's one little thing in cryptography that feels like a little magic. Magic is a strong word, but it kind of feels like it. And that is the crypto.random bytes. All right, so generating truly random bytes could seem like a bit of a magical process. So some things are happening behind the scenes to do this, like reading some of your hardware components. And again, it's not magic actually, but if we were to only name one thing in cryptography that would, be worthy of this word magic, it would be this generating random bytes that's done by OpenSSL behind the scenes. If you want, you can look over it. There are some good videos on YouTube that are talking about it, but we're not going to do that. But everything else should make 100% sense, and they're pretty straightforward to understand, right? Like this SHA-256. So here we have the algorithm implemented from scratch. Again, it's one of the most widely used algorithms in the world. So just like quicksort and merge sort, we can implement them if we want. And if you're comfortable with using another language, feel free to Google it, and you can find tons of these implementations online. Now, we're also including the crypto module right here, but only to check at the end to see if our hash values match up. So here's SHA-256. This is our own function, and our data is this. Okay. So we're calculating the hash with this code, and then we're doing it with node crypto.createHash. SHA-256. So let's go ahead and run this pretty quick. Here I'll say node SHA-256.js. And here if you take a look, our own function gives us this hash output, and the crypto module gives us this one, and they match on every single bit. And if we change our data even a little bit, like this, now we're going to get completely new hashes. But again, still our function works well. Now, there are just a few things that I want you to notice about this code. Again, it's very straightforward, just about 100 lines of code. Again, I've added tons of comments right here, but if you remove all the comments, it's only a few lines of code. So what we're doing in SHA-256 here, we've got two functions, rotate right, which is going to rotate a bit of data to the right in a circular way. All that means is, if you read the comments right here, for example, if we call rotate right 79, and then rotate it to the right by 8 bits, here's what we're going to get. So 79 in binary is this. We've got all these zeros and then a little bit of this at the end. It also deals with them in 32-bit words. Okay, so that's why here we've got 32 bits, and this is here in specification. Word size is 32. Now the block size is something else that we're going to get into in just a bit. So it's going to rotate it to the right by 8 bits. So this value, if you just do it right now, it's going to come right here. Now if we just shift it to the right like this, we're going to lose the values after they just get across here. But in rotation, if it's at the end, it's going to come back right here at the beginning. Here's another example with hex value 40. In binary, it's this, and then we're shifting it to the right by 2. So this one will move right here. All right, pretty straightforward. So we're doing tons of rotations in our data. And let's keep scrolling down. Here we've got another function called pad message. Now, in SHA-256, we're dealing with 512-bit blocks. All right, so just like in AES, that we're only dealing with 128-bit blocks, here we are only dealing with 512 blocks. So if our data is not divisible by 512, we're going to add a bit of data at the end to make sure it is divisible by 512. And that's what padding is. So if you take a look here, what we're doing is that we're checking how many zeros we need to add at the end. Now again, read the comments and it should show you how this works. So we pad a message to make sure it's divisible by 512, and we follow 3 very simple steps to do it. So we first add this binary after our message, which is 80 in hexadecimal, and then we keep adding zeros until we reach this size. And the reason that we want to reach 448 is because we also want to put the size of the original message at the end of the block, all right, at the end of the padding, so that we know where the data starts and ends. So we add the length of the message in the last 64 bits of the data. So that's why we have 448. So 448 plus 64, which is 512, the size of the block. Now here we've got 2 examples. So if you call pad message on hello, so it's going to first be converted into binary. So binary value of hello is this, which is now displayed in hexadecimal. Otherwise, it's going to be very long. So here we've got 40 bits of data. Now we're going to first add this binary at the end of this message. So we're going to end up with this. So 80 is going to get added to the end. And then we're going to keep on adding zeros until we reach 448. All right, so we've added tons of zeros right here. Now our size is 448 bits exactly. And then we add the length of the original data, which is 40 bits, to the end of the result. So we're going to take this and add the 40, which is this number in hexadecimal, at the end. So we're going to come up with this. If you scroll all the way to the end, you can see this 28, which is the size of the original data, which is from here up until this point, which is 40 bits. And here's also another example. Now this time around, our data is exactly 512, but the output is going to be this. So we still would add one last block at the end to make sure that we've got the original size in place. All right, but still, the output is going to be divisible by 512. Okay, so it's the size is 512 times 2. And that's it. So that's what this pad message does. You can also copy this, go into your REPL, and play around a little bit. So all you have to do is to paste it, and then say pad message, give it a buffer, and then you can see the final padded message. Right, so this is the hexadecimal value of some text. This 80 got added to the end. Now the rest is not displayed here, but if you want, you can do .toString hex to get the complete data. All right. So if you now scroll down to the SHA-256 implementation, again, it always works with 512-bit blocks, or 64 bytes. And the output is always this much. So here's how it works. So we've got, you can see some crazy numbers here, but they're pretty straightforward to come up with. These are derived from fractional parts of square roots of prime numbers. And here we can see an example. We're not going to go over it, but the first number here it says is this one. So the cube root of 2 is this. And then we take the fractional part, we multiply it by 2 to the power of 32, which is the size of our word. We come up with this number and this number, we floor it, and its hex value is this. So we come up with this number. Right, so we're doing that here to come up with these values. Here we've got exactly 8, and each one is 32 bits in size. So what we're doing is that we're going to go over our message and modify these 8 values, 32 bits each, many, many times, okay? Exactly 64 times. So if you scroll down here we're going to do it for about, where is it? Let me just see if I can find it. So here in the main compression function, we run this 64 times for each block. And all that we're doing here is that we are modifying those 8 values, right? Those 8 H values right here, okay? And then at the end, we're going to combine those modified 8 values together. So we're going to map over the H. Again, H is this. All right? So we're going to go over it, literally put them all together. So joining them all together and return it, and this is our final hash. So if you want, go over this code a little bit. This is what is now running Bitcoin and tons of other things. All these Bitcoin miners, all that they do is that they are extremely optimized to run this simple algorithm right here. All right, and nothing else. Now, I don't expect you to go over it and understand every single line of code. If you want, you could. It's going to take you a few hours. Don't expect to do it in just a few minutes. But you could easily do it, and then once you learn how it's done, again, it just requires you to understand some basic college math, and maybe not even that, but we're doing tons of XOR operations, and I don't know, the AND operator. Now, this is not the same as the AND and if statements. This is the AND operator that is used to deal with binary data, and also shifting to the right when we have this one. It's just a little neat trick to make sure that our data is 32 bits in size and we're getting rid of all the fractions. And also tons of rotations. So if you take a look here, we're doing a ton of rotating to the right. So this is pretty much all that we're doing here in SHA-256. Tons of rotations, tons of XOR operators, then some numbers here that we're adding into those things, and then at the end, we're going to come up with the final hash. All right, so pretty interesting stuff. And that's it about this video, and I'll see you in the next one where we're going to talk about what it's really going to take to break this SHA-256. In this video, we're going to talk about what it's really going to take to break SHA-256, and also the common attacks that we have on hashing in general. Now, if we want to launch an attack on a hashing algorithm, we usually have to target one of those properties that make a hashing algorithm cryptographically secure. So we should either target the preimage or second preimage, or find a collision, or even the avalanche effect. Let's start by talking about the avalanche effect, just so that you see how powerful this avalanche effect is. I've prepared a piece of code that's brute forcing SHA-256, and you can find it attached to this video. Let's go ahead and run it to see what it does. So node SHA-256-brute force, and then here we can specify a pattern, for example, 2 A's. And what's going to happen is that it's going to keep on trying different values, different messages, until the digest of one of those messages start with this thing that you specify right here. Now, this is what happens in Bitcoin mining, that the goal is to find a hash number that is smaller than a particular number. I'm using Bitcoin as an example just so that you get the idea of how difficult this really is. So the goal in Bitcoin mining is that you've got a piece of data. Here we're going with this simple string of data, and you also have a counter. So you need to constantly change this counter until you find a message, right? So this would be your whole message, that its hash is going to be smaller than a particular number. So essentially, it means that it should start with a few leading zeros and then the rest, all right? Now, if we say that we want to find a hash value that starts with only 1 0 in binary, the probability of doing that is 1 over 2. If we say that we want to have a hash value that starts with 2 bits that are 0, the probability is now 1 over 2 times 1 over 2, and so on and so forth. So if we want to find 8 leading zeros, we're going to have to try 2 to the power of 8, so 2 to 8, which is 256, all right? So let me run that and put in 2 zeros here. So on average, we have to do about 200 trials until we find a hash value that starts with 8 zeros in binary or 2 zeros in hex. If I run it, here we can see that after about 100 trials, we found this hash. So if we go with a message, that's data 13, the SHA-256 hash of this is this one. Now let's go back to the code pretty quick. It's a really easy code. Here you can see it says starts with pattern. It just calls this starts with function in JavaScript with the pattern on the hash in hex, and then we've got the value. So here's our message. That's data and then a counter. And we're constantly adding 1 to this counter and then getting its hash. And if we find that pattern at any point of time, we're going to log that a match was found. The message is this, the hash is this, and in total we tried this much. And we also log our progress after about 1 million trials, just so that we know something is happening. If you scroll down here, we've got some error checking to see if the thing that we specify is a valid hex value, and that's pretty much it. All right. Now, let's say that we want to find a hash value that starts with maybe 6 zeros in hex, which is 6 times 24 bits. So the probability of finding a hash that starts with this is 1/2 to the power of 24, which is around 16 million. So if I now run this, after trying about 16 million, we will find that. Now, it's not like at least 16 million or something like that. It's, again, probability. So what we're doing right now is that we're saying we want to toss a coin 24 times. And we want to get ahead on all of them. All right, so if we want to do that, our probability is 1/16 million, this number. So after tossing a coin 24 times for 16 million times, we can expect to find that perfect combination. So we're doing the same thing here. And you can see that now we found it after about, well, in this case, 36 million. All right, so a number close to this one, but again, it could vary. So if you go with maybe this one, so this hex value, still the probability of finding this is the same as for zeros. And here in this case, you can see that we got really lucky and we found it after only 1 million trials. Now, going back to the Bitcoin example, so the goal is for people to find a hash that starts with a few leading zeros. And let's say that you kept on trying for a long amount of time and you found this specific hash right here. All right, so you know that with this thing, with this number and your data, you'll get this hash value that starts with 6 zeros. And if you can now flip another one to 0, well, you win the contest and you're going to get hundreds of thousands of dollars. All right, now you might be thinking, once we found this, are we now closer to just changing this message a little bit, not too much, to change the hash a little bit? Well, the answer is not at all. You're not even close to finding the answer once you hit this point. Now, this is the avalanche effect. At this point, we have no idea how to modify this so that our hash, for example, will be like this. For example, this E gets changed to, I don't know, maybe 2. We don't know how to do it. And if you can find a way right now to do this, well, you'll get rich overnight. You'll earn millions of dollars overnight. So this is not a joke. The avalanche effect is incredibly strong and we don't know how to lead it, right? We don't know how to lead our messages to modify the hash values in a way that we want. And this is what makes Bitcoin so secure, okay? Bitcoin doesn't do this to bother the people. It's doing it because now no single entity in the world can find these hashes, right? We don't have that computational power. So now everybody needs to work together to find these hashes. All right, so I hope all these numbers make sense to you. It's just basic probability, so just basic discrete math. And now that we know this concept, now that we know what brute forcing a hash algorithm is like, and also how strong the avalanche effect is, let's now see the attacks that we can launch on SHA-256 or other hash algorithms and see how long they will take. So again, as we mentioned before, if we want to break one of these hash algorithms, we have to target one of those secure properties that we mentioned. So if we want to target the pre-image resistance thing, we have to brute force. And for this, we've got a hash value and we want to find the message. Now, if you do the math, on average, we're going to have to try 2 to the power of 256 trials until we find the message. Trying this on the most powerful supercomputer is insanity, as we discussed in the AES video. We know that doing 2 to the power of 128 is going to take an eternity to do, so let alone doing this. So we know that mathematically, this is impossible. And if it's mathematically impossible, well then practically it's hundreds of times impossible. Now, another type of an attack is to target the second pre-image resistance thing, and for this one, we also need to brute force. So here what we need to do is that we already have a message, and we know its hash value, obviously, and our goal is to find another message that will give us the same hash value. And this one also takes about 2 to the power of 256 on average to find it, which as we know is impossible. Now you might be saying, what's the difference between this one and the other one? And well, in SHA-256, there isn't really any difference because it's really secure. So it doesn't really matter if you already have a message. It's not going to help you to find another message that will give you the same hash. Now this is not the case with broken ones. For example, in MD5, if you want to brute force MD5 and you've got a hash value and you want to find the message, it's going to take you a long amount of time. So 2 to the power of its digest size. But in MD5, if you now want to target the second pre-image, so you already have the message, and you want to find another message that will give you the same hash, it's now far, far lower than the attack on the pre-image, because mathematical vulnerabilities have been discovered in it, so this attack in MD5 or SHA-1 is far lower than 2 to the power of their digest sizes, okay? But in SHA-256, it's really solid. It really doesn't matter if we have a message or not. It's the same thing as this one, alright? Now another attack is to try to find a collision. Now, this attack is called a birthday attack, and what we need to do here is to, well, as we know, find 2 messages that would give us the same hash value. Now, this is based on a mathematical principle called the birthday paradox. I encourage you to go over it, it's really interesting. I'll put a great YouTube video to the resource section of this video that talks about the birthday paradox, and essentially what it says is that in a room full of 23 people, we have more than a 50% chance to find at least 2 people that have the same birthday. Now, I know it might not really sound intuitive. I mean, it sounds simple, but not really intuitive. But that's mathematically proven why that's the case. And we've got 365 possibilities for an actual birthday, but it's 50% chance to find at least 2 people that share the same birthday. All right, it's quite interesting to see why that's the case. Now, attackers have utilized this mathematical principle to launch an attack on hash algorithms to find a collision. So now, it's not going to take 2 to the power of 256 to find 2 messages that would give us the same hash value. It would now take the square root of that to find 2 messages that would give the same hash. But still, in SHA-256, it's impossible to do it. But in other hash algorithms that their digest is much lower than this, for example, if you have a hash algorithm that digest is only 100 bits, even though it's very secure and has all those properties, it would now only take 2 to the power of 50 operations to find 2 messages that would give the same hash, which is a big, big problem. Now, you might be wondering, why do we keep saying that we have collisions in SHA-256 and other hash algorithms, even though we haven't even found a single one? Wouldn't we be more accurate to say that we aren't certain that we have these collisions and say instead that there might be collisions and one day we might find one? Well, absolutely not. We are 100% certain, not 99.99, 100% certain that we've got an infinite number of collisions here in SHA-256, and yet we haven't even found a single one. And we've got mathematical proof for it, which is based on the pigeonhole principle. Now, if you haven't ever heard about this concept, I've linked a video to the resource section that talks about the pigeonhole principle, so I highly encourage you to watch it if you have no idea what this is. But in basic terms, all this means is that we are guaranteed that if we try to feed n+1 items or pigeons into n containers or holes, we know for certain that at least one of the containers will end up having 2 items. Now, it's something that sounds so simple, yet brings in so many interesting implications, especially here in cryptography and, well, more specifically, here in hashing. Now, applying the same principle, let's start with something very simple. Let's say that we have all these 4-bit combinations. Here I have a list of all of them. So all 4-bit combinations are 2 to the 4, which is 16. So we have 16 items. Now let's say that we want to have a hash function that would output a 4-bit hash. So it only accepts 4-bit data, and it only outputs 4-bit hashes. So we've got in total 2 to the 4 containers, or 16 unique hashes. Now, we can easily design a hash algorithm for this case that won't give us any collisions. We can maybe easily create a mapping. Say that if we have 0100, we want to output 1100 as the output of our hash. So we can have this mapping for all of them, and then we know for certain that we won't be having any collisions whatsoever. But let's change things up a little bit. Let's say that now we want to design a hash function that accepts any 5-bit data, and it only outputs a 4-bit hash. So still we have 2 to the 4 or 16 containers, which means that we have 16 unique possible hashes. And here we have 2 to the 5, which is 32 data items. So we have 32 possible 5-bit combinations. If we design a hash algorithm for this one, we are guaranteed, based on the pigeonhole principle, that we will have at least 16 collisions, all right? Doesn't matter how perfect the hash is, we will have these collisions because we can't fit in more items into fewer containers without each container ending up with more than one item, okay? Now, going to SHA-256, it's the same concept. So here our hash size is 256. And let's say that we only want to focus on 257-bit combinations, all right? So just a few bytes of data, nothing too crazy. Let's see how many collisions we have in this case. Now again, doing the math, this is going to be the number of collisions that we have, which is a gigantic number. You can't even write it down on a piece of paper without running out of space. All right, so we know that we are guaranteed in SHA-256 that only with 2 5-bit combinations, we have this many collisions. We could have more, but we know that at least we have this many. And it's just 2 5-bit combinations, let alone data sizes that are kilobytes or megabytes in size. So we know that we've got infinite number of collisions here in SHA-256. But isn't it just so compelling that after over 20 years, with all these computational powers that we haven't even found a single collision in it. So we haven't found 2 messages that would give us the same hash value. And this is really the power of math, the language of the universe, that we're using it to create something that resembles a bit of nature itself. In this case, creating fingerprints for data, like we have fingerprints in human beings. It's truly captivating to think about. So every piece of data that we have right now on our databases, hard disks, on the cloud, we know that they all have a unique SHA-256 hash. So now we know what it's really going to take to break one of these SHA-256 properties. Now there's something else that I want to mention, and that is the rainbow table attacks. Now what this is that attackers have usually prepared tables that have the common phrases and their SHA-256 values. Right, so now we can look up in the table and find the hash of a particular message. It's commonly used in password cracking. That in this table, we see all the common passwords and their hash values. For example, password 12345 or something like that. So now we don't need to brute force to find the hash. All we have to do is to look up in the table and find that particular hash and then see the message. All right. This is far faster than trying to brute force every single combination. So we've got these tables with thousands and even millions of records in them, and we can just look up a value and then find the hash. That's why it's so important to choose a password that's not common and it's unique. Now, this brings us to another topic. You might be wondering, what if we have a hash value and we know that our message is only 4 bits in size? So now we can go from hash to message given that we know how big the message is. Well, you're right. If your message is so small, we can easily brute force it. All right, but if the message is large, it's now going to be impossible. So here I have this table that shows you the message size in bits, how many trials we need to do to find that particular message that corresponds to that hash, and also the time that it's going to take if we can calculate 500 trillion hashes per second, which is very large, but let's go with this. Okay, let's say we're years in the future and we can easily do this. We can even right now do it if we get 2 of those Bitcoin miners. That's going to cost more than 10 grand, but we can get to the speed. It's not that difficult. So if you look here if our message is only 32 bits in size, and we know that, we can easily try all the combinations, and at one point we're going to find the hash. So we just have to try 2 to the power 32, which is going to take less than 1 millisecond at this speed, and you can even do it on your own computer. But look what's going to happen if we increase the number of bits. Once we get to 100, which is about 12 characters in UTF-8, it's now going to take us millions of years to find the message from the hash. Alright, so that's why, again, it's very important to choose passwords that are long. If your password is really small, but yet random, it's only going to take a little bit amount of time to brute force it. So if you choose a 50-bit password that is even truly random, it's only going to take a few seconds to crack it. Now, I also want to point out that you should not use plain hashing to hash passwords, right? We're talking about it right now, but doing that is a terrible mistake. Some developers make that mistake, some companies have made that mistake and still even do, I don't know. It's a very costly mistake. You should hash and salt, and not just hash. So I want to make that 100% clear to you right now, in case you want to quit the section right now. Don't go and use this SHA-256 now to hash your users' passwords. In one of the future videos, we're going to talk about how to do it. What we're going to do is based on SHA-256, but we're going to introduce some new things into it, some randomness, to make sure that it's impossible to brute force or use the rainbow tables. Okay? Alright, so we know that SHA-256 is going to be really, really secure for now and who knows, maybe years in the future. And also, again, these common attacks that we talked about and how long they take, you can also do the same math for different algorithms. For example, for Blake algorithms or for SHA-3 or for anything else that you've got. You just have to make sure to see that no mathematical vulnerability has been discovered in that algorithm. And if there hasn't been anything like that, you can just take the final size of the digest and do these operations if you want. And I'm talking about these ones. Now, there's another attack that we have available in SHA-2, but in SHA-3 it's resolved and that attack no longer applies there, and that is called the length extension attack. Now, we're going to talk more about that in the next video. There it's going to make more sense, so just keep that in mind, and we'll get into that later on. It's nothing that would now make SHA-2 obsolete. There's an easy fix for it. But just keep in mind that there's just one more that I'm missing right now, but we'll get into that in the next video. Now, the only real threat as of now that we have against SHA-2 and even SHA-3 is quantum computing. There's a quantum algorithm designed by these people, and this is the paper that they have published. So I'll link this if you want. I'm not sure if you can access it for free. You have to access it through your university or organization. But it doesn't really matter, you don't need to read this paper unless you're learning about quantum computing. But the only thing that I want to point out right now is that with this algorithm, it's now going to take us this much to brute force and find a collision in a specific hash algorithm, right? So now with this, if we want to find a collision in SHA-256, it will no longer take us 2 to the power of 128 with the birthday attack. It will now take us the cube root of 2 to the power of 256, which is this much, which is 2 to the power of 80 something. And it's something that we can do on a powerful computer. It's going to take a bit of time, but still, it's doable. So this is the only threat that we have in SHA-2, and also the other hashing algorithms that are not quantum proof, but, well, it's something that we probably don't have to worry about for many years, because we don't have a practical quantum computer as of now that could do this. But just know that in theory this exists, and if one day you read in the news that this has happened, well, then you'll know what to do. Alright, so that's it about what it's really going to take to break SHA-256. And we know that as of now, we don't have any known attack that would help us to break this. So we're fine for now unless a new thing gets discovered in it. Alright, so that's it about this video. Starting from the next video, we're going to see some of the applications of SHA-256. The only real thing that we used it for was to check if two files are identical. But the actual use cases of this is to do authentication and to verify integrity, and also to derive keys and stuff like that. So in the next few videos, we're going to see some of the applications of these hashing algorithms, and we'll also see more in the asymmetric part of the section. Alright, so I'll see you in the next video. In this video, we're going to talk about message authentication codes, or MACs in short. This is based on hashing. And now with this, we can verify integrity and also authenticate the entities that we are communicating with. Now, to see how MACs are going to help us do these two things, let's first go back to the CTR encryption and recall that here all that we're doing is that we're encrypting something and then we are XORing the result with our plaintext. So now when we're sending our ciphertext, an attacker can now change the ciphertext and it's going to directly reflect when we decrypt the ciphertext. So let's say that two people right now are communicating, maybe one of them is in California and the other one is in New York, and both entities have access to the same key, alright? Now let's say that this person has this ciphertext and now wants to send it to this other person right here. So this ciphertext is now going to be transmitted across this network, and then this person is going to get it, use the key, and then, as we know, decrypt and get the plaintext. This is how it's going to work in an ideal case, alright? But we know that in the real world, things could get really ugly. So what if when this data is being transmitted, an attacker comes into play and then starts to modify this ciphertext, maybe change it to something completely different or just change it up a little bit. So this person could be connected to the same network as this person, or could be connected right here and then do the modification right here, or even somewhere in the middle, maybe from the ISP, who knows, or one of the routers that are now transmitting your data. You can never be sure that this is not going to happen. Whatever you're sending on top of TCP is out in the open, and people can see it and even modify it without the other entity knowing what's happening. With message authentication codes, we can now mitigate this problem. Now, to see that more clearly, let's try that in action. Here I have created a folder called MACs. You can grab this from the starter.zip file. And I've got two pieces of code. One is encrypt and one is decrypt. And I copy-pasted these two portions from this app.js from the AES video. Alright. So we know that this CTR mode is one of the most common modes of encryption, and it's XORing something with our plaintext. So now, if somebody changes our data, well, they can really do whatever that they want. Let's try this pretty quick. Here I have a plaintext. It says this is a text that should be kept secret, and my password is this. Alright, so we're encrypting it with this encrypt.js. I'll navigate to the MACs and then node encrypt. Now we've got the ciphertext.encrypt file. Let's now say that I am an attacker. I am in the middle of the communication, I can see the communication, and I can also modify it. Let's try to do that. Here I'm going to open up the ciphertext in my HexFiend application and maybe modify this a little bit. Maybe let's change a single bit. So I'll change this 78 to 79. I'll save and close it. Now let's decrypt. And as we know, we're not going to get any errors, but if we now take a look at plaintext-decrypted, we can see that something was changed here. Alright, so this is some text that should be kept secret, and this that got changed to this text right here. Alright, so we're not seeing gibberish, we're seeing something that looks legit, and we can do this however that we want. We can maybe change this password, or change this word password to maybe email, because we are XORing it, and we can change every single bit that we want, so we've got full control over this. Now, of course, it's not going to be easy to change it in a way that would be actually useful for an attacker, but they could play around with it, and after tons of effort, they could now change it in ways to benefit them immensely. For example, if they study the structure of the web server, how their JSON body is structured and whatnot, they can now start to get creative and change it in ways that could wreak havoc on the server or the users of the server. So this is a very big problem, and again, as you noticed, we didn't get any errors whatsoever here or any warning that the ciphertext was modified. Alright, so we got a problem right now and we gotta fix it. And with message authentication tags, we can now ensure that this is now mitigated, and no one can now modify our data without us knowing it. So let's see how we can solve this problem. Again, we've got two people communicating together. Both have access to the same key. Let's imagine that this key was exchanged securely with asymmetric encryption, which is something that we haven't talked about yet, but that's what we're assuming at this point. Now, what we're going to do at this point, Well, we still have the ciphertext, obviously, but let's combine these two together and then feed the result into a hash function, and then the result of our output is now going to be called a message authentication code. And the idea is that now, along with the ciphertext, we're going to also send the digest, or in this case, we're going to call it a message authentication code because we also have the key. And now we'll be sending this combination as opposed to only sending the ciphertext. So this person is now going to get it. And what they can do at this point is that they can grab the tag and then recompute this hash, right? Because this hash function is something public, everybody knows what that is. We will also tell the other person that, hey, we used SHA-3 or something like that. So this person is going to take the same hash function with the same key and ciphertext, just like here, and then recompute this and come up with this tag. And if the tag that they get is the same as the one that they got from this person, they now know that the message wasn't changed in any shape or form, and also this person sending it is who they actually say they are. Because nobody else in the world has access to this key, so they can't come up with the same hash. So if the attacker is now again in the middle, and they get this data, so an attacker sees the ciphertext and the message authentication code, but if that person goes on ahead and modifies the ciphertext to maybe ciphertext 2, they cannot come up with a new tag, alright? Because that person doesn't have access to the key, alright? So now, if this person gets it, it's going to recompute this hash and it's going to see that it doesn't match up. So he or she now knows that the data was modified. Alright, so this is the idea of message authentication codes. Again, it's based on hashing. And we also introduce this new key into what we are now hashing. Now you can get really flexible with this. You can add in more data here to the input of your hash. Instead of ciphertext, you can go with plain text. The idea is that only the entities who have access to this key can now come up with this new tag, all right? And that's how we can now authenticate and also verify integrity. Alright, so let's now try to use a message authentication code in our example to make sure that we verify integrity and also authenticate the user. Now we can use a variety of different message authentication code algorithms to do this. One of the most common ones is called HMAC, and we have access to it here on the crypto module. So we can do this. We can say crypto.create HMAC, and then as the input, we can give it the ciphertext and also the key, and then come up with that tag, all right? This HMAC is also used in JSON web tokens and many different places. And well, after you're done with this cryptography section, understanding how to authenticate with email and password and all these different things that are usually talked about in the world of Node.js will be like a piece of cake for you, all right? Before understanding cryptography, there will be like this black box that you can never really understand well, but after you understand these concepts, well, you'll really see how easy they really are. Perhaps we're going to talk about them in the security section of the course, just to show you how easy they really are after you understand these concepts. Anyways, let's go back to here, and let's compute a MAC for our message for this file, ciphertext.enc, and then somehow give this MAC to the decrypt file, and then verify integrity and authenticate. So a good way to do it would be maybe here. After we're done with the pipeline and we have the ciphertext, we can go ahead and read the content and then do this. Or we can do it on the plain text. But the idea is, again, it has to have the key inside. So here in the HMAC, once you're creating it, you have to first specify a hashing algorithm, all right? So let's go with the classic SHA-256. And then you're going to have to give it the key. So I'm going to give it the key that we had from here. And then now your HMAC is created. So let's say const HMAC. It's now a function that you can feed data into it. So let's say hmac.update. Now let's read the content of ciphertext.encrypted. So I'll say const ciphertext for maybe HMAC and fs.read file sync. Let's read it all in one single buffer. So ciphertext.encrypted. And then now all that we have to do is to specify that ciphertext for HMAC right here to this algorithm. All right. Now it's going to use this data along with our key, and well, the underlying hash algorithm is SHA-256. So now we're going to get a digest. So let's log the digest or hash that we'll get. And actually, let's chain them together to keep it simple. So I'll put it here and then say .digest hex. All right. And now let's log it. Console.log HMAC of ciphertext and then HMAC. All right, now I'm going to go ahead and run this. Node encrypt again. And the encryption is now done, and we also have this result, which is 256 bits because we're using SHA-256. And now we can go ahead and maybe modify the ciphertext again. All right, so let's do it. Here I'll open it up using my HexFiend application. And the 78 that we had, let's change it to 77. I'll save and close. Now before we decrypt, let's also compute the hash again and verify that it's correct. A good way to do it is right before we do the decryption because we already have the ciphertext. So I'm going to grab the ciphertext again. So ciphertext for HMAC. And then fs.read file sync from the ciphertext.encrypted. The reason that I am reading it again is because we're using the ciphertext here in the pipeline, and in Node.js streams, if you're reading like this, it's not a good practice to read it again. Alright, so I'm doing it this way. I am grabbing it all in a single buffer, but you can also use Node streams to do it if your data is large. Now with this in place, we can compute the HMAC again. So crypto.create HMAC. We have to go with SHA-256 because we used it for computing it. And then the key. And now let's give it the ciphertext buffer. Now let's grab the digest in hexadecimal. And then I'll just log it. So HMAC of ciphertext. And then the HMAC tag. So now I'm going to go ahead and decrypt again. Remember that I modified my ciphertext. So if I run it, it still says that decryption was completed, but if we take a look at our HMAC, it doesn't match with the one that we had before, alright? This will now tell us that something is going on, that the data is now not the exact one that the user sent, okay? So maybe it got corrupted, maybe an error happened, or well, maybe an attacker modified our data. Now let's do the encryption again. Let me delete the ciphertext just to keep things clean. And also the plaintext here, if you take a look again, this data was changed, but we got a warning in this case. All right, we now see that the tags don't match up. So now we know that something is going on. Let me delete this one as well. And now let's encrypt again. We get this tag, and now I'm going to decrypt. And now you can see that the tags match, meaning that the data that we got is exactly the same thing that the original sender intended to send, all right? And also, no one else can now pretend to be that same person, because that new attacker, that new person, does not have access to that key. And if I take a look at plaintext-decrypted, this is exactly what we had here in the plaintext. So this is the idea of message authentication codes. Again, pretty straightforward. It's really easy to understand because now we understand the hashing, and this hashing is really at the heart of it. So this HMAC isn't really doing much apart from making sure that the key and the actual data gets combined before running them on the hash function. All right, that's pretty much really all that happens. Now, you might be saying, why do we have to use HMAC when we can easily combine the key and the ciphertext or any other message ourselves, and then we give it to the SHA-256 function? Well, you could, but with SHA-Family2, there's a vulnerability in it, and you can utilize it by something called the length extension attack. So let's see how that works and how this HMAC is solving this problem. So we know that we can compute this hash value or our HMAC value or message authentication code, whatever you want to call it, by using this structure. So having our key and then message, giving it to the hash function, and then getting the tag. And for as long as no one else has access to this key, they can't change this message and come up with a new tag. Unless we are using SHA-2 and we are just attaching them together like this. So here's what an attacker can do in one of these hashing algorithms that are susceptible to this. And these include SHA-Family 2, MD5, and SHA-1. SHA-Family 3 and the Blake algorithms are not susceptible to this. But let's see how this works. So this attacker can take this message. We know that this message is out in the open. Anybody can see it. And they can now append a new message to it. So they can put some data at the end of the message. Not in the middle, not at the beginning, at the very end. And now, because they have access to the previous hash, they can now recompute a new message authentication code for this data. All right. And then, well, attach this one to the ciphertext, send it across, and the user still gets the data, they verify the tag, and the tag matches. So this is a big problem. Now, if you want to understand why this can happen, it's really easy. You can even do it yourself. If you didn't skip the SHA-256 from scratch video, you should have some sort of an idea of how this would work. Right? I'm going to just briefly mention it. So here, when we are computing the padding for the message, we mentioned that we're going to attach the length of the message at the end of the padding. So in the very last block, we're going to have this size of the original message. And here, the attacker can do that same padding because, well, they have access to the size of the message, and they can also know what the size of the key is. Right? It's usually, again, out in the open. You saw previously here in Firefox that when we take a look to see how our connection is encrypted, the size of the key is also specified. All right? So it's not that difficult for an attacker to know the size of the key. And also, well, again, the message is in clear text, so they can easily see what the size is. So they can now compute that final padded message with this new more data added to it. And also, back here, they have access to the final state of the hash. Because we said again that we have this state, and at the end of the hashing, we're going to literally attach all of them together. All right. So here they can put in the final hash. They can divide it into 8 different sections and put it here, and then recompute it with that new more data added to it. So they can do this whole process without having access to this key, right? But it's only about appending data, so they can't change the message. They can only append to it. But still, this is something that we don't want to happen. So if you use plain SHA-256, this is going to happen. But if you use the HMAC algorithm, well, this is not going to happen. HMAC is going to do some things to ensure that this is not going to ever happen. Also, if you go with SHA-3, this, again, is not going to happen. All right, SHA-3 is immune to this attack. So that's why we used HMAC here and not just straight hashing. We can also do that if we go with SHA-3, but I also wanted to show you this HMAC because it's pretty popular. It's also used in JSON Web Tokens and tons of other places. So it's good to see how this works, all right? Now, it's also really easy to understand how this works. We're not going to really dive deep into it because we want to save some time for the RSA section. So when we're learning about the RSA algorithm, which is an asymmetric encryption algorithm, we want to really understand it deeply. So we're going to do it from scratch on a piece of paper and do every single step of it, all right? We have to do it because if we don't do it, this concept of asymmetric encryption is always going to be a black box. So that's why I'm going to skip over this. We don't have time to go over all these algorithms. But if you want to go over it, you can come to this specification, this RFC file 2104. And here's the specification of HMAC. And it's only 10 pages in length. All right, so it's really easy to see how this works. This document describes HMAC that can be used with various hashing algorithms. And also it mentions something very important here, that the strength of HMAC depends on the properties of the underlying hash algorithm, all right? So if you use it with a hash algorithm that is not secure, like MD5, well then your message authentication code is also not going to be secure, alright? Because again, HMAC is not magic, and if you want to see how this works, just grab the PDF. In only about 11 pages, that's pretty much all that you need to know. And here you can also see an implementation of it from scratch, here using C, and it's also using MD5, but it doesn't matter. You can also see a few examples that if your key is this, and then your data is this, your final tag is going to be this, alright? And you can trace it if you want. Now, essentially, all that happens here in HMAC is that we have an inner padding and also an outer padding. Basically, what happens is that the key is getting tangled up with the message, both at the beginning and at the end of the hash function, to ensure that we can now prevent the length extension attacks. I apologize for using such an informal language, but that's really basically all that happens, and that's as far as we're going to talk about it. Alright, so now that we understand message authentication codes, we are now ready to understand AES GCM mode. We mentioned this a few lectures ago and we said that we're not ready to understand it, but now we are. So let's see how this one now works. The AES GCM mode is basically the CTR mode, but with a message authentication code added on top. So let's see that pretty quick here in code. I'm going to duplicate this encrypt, and I'll call it encrypt-GCM. I'll do the same with decrypt and call it decrypt-GCM. Now let's go into encrypt-GCM, remove the HMAC portion, and then let's change the CTR mode to GCM. Now GCM, AES GCM is the most common mode of encryption on the internet, right? And the reason is it's the counter mode, but now with the message authentication code. So we don't need to manually now calculate the MAC every single time you want to send a packet or something. This mode will itself take care of that for us. Now I'm going to go to the decrypt-GCM. Again, remove the HMAC portion and change it to GCM. Let's also delete ciphertext.encrypted and also the plaintext-decrypted. And now I'm going to go ahead and run the encrypt-GCM. So now it's going to encrypt, give us this ciphertext just like before, and now I'm going to decrypt it with GCM. Alright, notice that it now gives me an error that says unsupported state. It's unable to authenticate data. Alright, but if you go back here and you take a look at the plaintext-decrypted, you can see that it's the exact same thing that we had before. So the decryption was successful, but we get this error that it cannot verify the authentication, meaning that we are not sure of the integrity of the message, and we also don't know who the actual person who sent it really is. It could have come from someone who's impersonating the actual person that we intended to communicate with. So AES cannot now verify this message. And we get this error because we're using now the GCM mode. To make sure that we're not going to get this error, all that we have to do is to, well, verify the MAC, to double check to see if it matches. And it's really easy to do. Here in encrypt-GCM, all that we have to do is to grab the tag, which is on the cipher object. So I'll say cipher.getAuth tag. All right, so this is now our MAC, and I'm going to log it. Now this is going to be a buffer, so let me also grab the raw binary, just so that we can easily copy-paste it. And now I'm going to go ahead and encrypt again. So encryption completed, and now we get our tag, which in this case, it's 128 bits. Now, this GCM mode is not using HMAC, all right? It's using another MAC algorithm called ghash. So HMAC isn't the only message authentication algorithm out there. We've got many others, but they all work in the same way. They are all based on a hashing algorithm, and they take the message along with the key or a secret data, and even some additional data that we want, and then give us the output of the hash. And that's it. That's really all that happens with all these MACs. So this is now using Ghash as opposed to HMAC, and the only reason that it's using Ghash is because it's faster compared to HMAC, right? Because here we want to be as fast as possible. It's really optimized for AES and hardware components, so it all comes down to performance and not really because HMAC is not secure enough, okay? Using HMAC with SHA-256 is going to be an overkill here in this case, so this is a little simpler but still secure enough. Alright, so now that we have this tag, we can do this check in the decryption. Here, all we have to do after we call a create decipher, we have to call a function called setAuthTag. Alright, just like before, here we called getAuthTag, and now we're going to call setAuthTag. And as you might have imagined, we now have to give it this tag that we had here. So I'm going to copy this, and then give it a buffer. So buffer.from this. Now let's convert this into binary. Now let's say that this is a hexadecimal. So now this is going to be converted into binary. And that's it. I'll save it. Let's run the encrypt again. And now the decrypt. And now we do not get any errors whatsoever that something is wrong. Because now we are verifying the tag. And we are now 100% guaranteed that the integrity of the message is verified. And also we authenticate it. So we know that this message came from the user that we wanted it to come from. Now also if you want to verify more data here in your encryption, you can feed it more stuff. And the function that you can call for it is setAAD. And this stands for additional authentication data. All right, so you can put in whatever you want here, maybe say email, that my email is this. And now when you're verifying, you have to call setAAD again before you say setAuthTag. Again, pretty straightforward, but still it's something that's going to help us to now have something that's incredibly important, that without it having encryption really doesn't make a lot of sense. Alright, so we're now done with this concept, but let's do a quick recap. We know that in message authentication codes, we usually have a bit of message and also our key, and the important part here is the key. Alright, so this ciphertext could be plain text, or I don't know, we can have in some additional data as well, but this key is the important part. And then we give it to a hash function. So this could be HMAC that's using SHA-256, or it could be Ghash, we don't care. So we're going to get this tag. We'll now attach this tag to the message that we want to send, and then we send this combination to the entity that we're communicating with. And now this person can verify that this message came from this actual person because this is the only person who has access to the key. And also, if an attacker changes our data, we can now 100% know that something happened, all right? Because now we're going to get a tag that's different from the tag that was sent across from the other person. And here in code, we talked about the HMAC. So here, all that we're doing is that we are calculating. So calculate the HMAC of the ciphertext with SHA-256. Or you can use any other hashing algorithm. You can use, I don't know, SHA-3 or Blake. But do not go with MD5. You're not going to get an error, but it's not going to be secure. Or also SHA-1. Do not please go with these red ones that we mentioned before. And also this HMAC stands for hash-based message authentication code. We have many other message authentication code algorithms apart from HMAC. Ghash is one of them that we saw that's used in AES GCM mode, but this is the only one that we get right out of the box with Node Crypto Module. So here, if you go to the documentation and search for HMAC, here class HMAC, this is the only function that we get that we can use to easily compute message authentication codes, all right? And then we saw how we can verify this once we have the tag, so we actually copy-pasted it, but you can imagine that this could be coming from part of the message that you're getting, so you can append it to your ciphertext before sending it on top of TCP, or anything like that. It doesn't really matter. But here, essentially, all that we're doing is that we are checking integrity and also we are authenticating. Checking integrity and authentication. Alright, so going back to our cryptography roadmap, we now know how to ensure integrity and to authenticate. So one more thing crossed off our list. So now that we know this, in the next video, we're going to talk about how to derive AES keys. Again, using the same hashing concept and also using HMAC. So that's it about this video, and I'll see you in the next one. Now that we understand hashing and we tackled the problem of how to verify integrity and do authentication, in this video we're going to tackle another problem in our cryptography roadmap, which is how do we derive AES keys from something that's low entropy, meaning derive 128 binary numbers from maybe 6 digits, or something like that. So to see how to do that, we need to understand key derivation functions. With this, we can both do that, and also we can use it to hash user passwords before saving them to our database. You should not be saving your users' passwords using maybe encryption or using HMAC or plain SHA-256 or something like that. This method that we're going to now describe in this lecture, this is how you should hash your users' passwords. So we're killing two birds with one stone. We're learning the same function, but we can solve different problems with it, alright? Now these functions are really based on hashing. They could be a little complicated to understand if we don't understand what hashing is, but now that we understand hashing, we know how SHA-256 and HMAC work, understanding these key derivation functions is going to be really easy, alright? So in no time you'll be able to use them in your applications. Now, we've got a few of these functions. The first one is PBKFD2. It stands for Password-Based Key Derivation Function. And also we've got scrypt, HKDF, and Argon2. We also have something called bcrypt, but we're not going to talk about that in this lecture. You can always stick with these and don't really ever worry about bcrypt, okay? Now we're going to really focus on PBKFD2 and understand exactly how this works. And once we get that foundation, understanding all the other ones is going to be really easy. This PBKFD2 is the function that's used on iOS and macOS devices to derive an AES key when you put in your password. So your iPhone password or your Android password, it's usually something that's 6 digits or a passphrase. So what needs to happen is that the phone needs to derive an AES key to then encrypt or decrypt your disk, right? So this is a very secure function. It's used in the government, it's used in some password managers in places that security is of utmost importance. So we're going to learn how this works and then briefly talk about the rest. Let's jump right into code and see what we can do with this. Let's create a folder and call it KDF. Let's have an app.js and then include the crypto module. And then we can call the PBKDF2 function to now derive keys or to hash passwords. Let's say that our password, I'll say const password, is equal to maybe my password. A terrible password, but let's go with this one. And now we want to derive an AES key from this one to maybe unlock our disk or to set up an end-to-end encryption with another user. For that, we need to, well, first derive an AES key from this one. We should never ever save the AES keys on our machines, right? In some cases you could, but in cases where you have a password, it's ridiculous to also save the AES key. For example, if you have an external SSD drive and you want to encrypt it, you should use an application that would derive an AES key from your password. If that application also stores that AES key somewhere on that disk, that's a terrible security practice. Now, an attacker can forcefully get access to the disk, grab the key, and then unlock it. Alright, it's not going to be easy, but it's still doable if someone is really proficient, and maybe after a few days, they can do it. But if you go with a strong password and a function like this to derive the AES key, now it's going to take them millions of years or even trillions of years to break into your disk. Alright, so this is extremely powerful. Now let's see that right now in action. As the first arguments, we have to, of course, specify the password. Next up, we need to put in a salt. Now, what salt is, it's, well, just some random data. And the whole reason that we're using salt is because we don't want attackers to use the rainbow tables, okay? So we added a bit of salt, And the salt is going to get mixed up with the password, and then we're going to get the hash value, the final hash value, all right? And the salt needs to be random, all right? So this is kind of like an AES, that we were using ECB mode, but we saw many terrible problems. And then we switched to another mode like CBC and then added some randomness to it, and well, the problem was solved. So here it's the same idea. So we have to use the crypto.random bytes to do this, all right? And I'm gonna go with maybe 32 bytes. And your salt should be large enough. The NIST organization recommends to go with a salt that's at least 16 bytes, all right? Here we're going with 32, so we're good. Now, after the salt, we need to specify something called the iterations, all right? So let me put it right here, const iterations equals, let's go with maybe 100,000. Now, this number is how many times we want to run the underlying hash algorithm on top of our data. Now, let's keep going with this, and it's going to make much more sense in just a bit. And then after the iteration, we're going to specify our key length. Now, the key length is how many bytes we want this pbkdf2 function to give us. So let's put it here, const key length. And we can specify anything that we want, but if you're deriving an AES key or SHA-256 key or any other key for any symmetric encryption from this, you need to specify something that matches the key size of that. So let's say that we want to go with AES 256. So we need 256 bits divided by 8. So we're going to have to specify 32, and this is now going to be the final size. So 256 bits of data that we will then use to encrypt with AES. So I'm going to now specify the key length. And then as the final thing, we need to specify our hash algorithm. So let's put it again right here. So I'll say const digest. Now let's go with SHA-256, or actually SHA-512, all right? And then I'll put the digest here, and then the callback with the error object, and also the derived key. Let's say that if we have an error, then console.log the error. And if we do not have an error, let's go ahead and log the derived key. So derived key is this. Now this is going to be a buffer, but let's get the raw binary data like this. All right, great. Now I'm going to go ahead and run this. I'll navigate to the KDFs and then node app.js. All right, so here we can see this key that we've got. And this was derived from this password, all right? So that's pretty much it. We only have this password right now, and we used it to derive 256 bits of data. We can now use this derived key to do AES encryptions. So here I'll say, now use the key to do AES maybe 256 encryption. Or we can also use it to store our users' passwords in our database, okay? For that, we have to save the derived key plus the salt to our database, right? And we do this for password hashing. Now, you might be saying, why not just use SHA-256 to hash the user passwords? Well, that is a terrible thing to do, because brute forcing it could be easy if a user password is not really strong, and also the rainbow tables could come into play. So common passwords with their hash values could be listed, and it's now just a lookup to see what's the corresponding password for a given hash. But now with this, because of the salt, this is now impossible, all right? Rainbow tables with this approach is now something ridiculous, okay? It's not going to work. You cannot have a rainbow table for every possible salt, all right? If you want to do that, you need to have 2 to the power of this number, so 2 to the 256 rainbow tables if you want that to be effective, and that's a ridiculously large number. All right, so this is the idea of key derivation functions, and most of them are based on, well, HMAC. Here in PBKDF2, you are literally calling the HMAC function when you are doing this, all right? It depends on your iteration. So here we're calling HMAC a million times to do this operation, all right? So we're hashing the input, then we're hashing the result again, then the result again, and so on and so forth. So we're hashing and hashing a million times, and then we're going to get the final output. You might be wondering about something right now, that we can specify anything that we want here. So maybe this many bytes. But then we know that we're using SHA-512. So our output is always 512 bits. So how does this now work? So if I now run this, you can see that we derived this key, but, well, we're using SHA-512. What happens right now is that the function is going to now run in different blocks. So depending upon your key length, there's going to be multiple blocks of data that are going to be hashed many times. Now to see that in action, we can maybe time our code. So here I'll say console.time, and then pbkdf2. And then I'll do the time end right here. So console.timeend. Let's also specify the key length that's the same as this one. So I'll change this 32 to 64. 64 in bytes, which is going to be exactly 512 bits. All right, so this is now going to be one block of data. Let's change this also to 1 million. Let's run this and see how long it's going to take. 300. Let me add in one more zero here. So now we've got 10 million. Now, this one took 3 seconds to complete. Let's change the key length now to 65. I'll run it again. And now we can see that it took twice as much, because now we have 2 blocks. Now, if I change it to, let's say, 120. So 120 is 960 bits, all right? Still, with only 2 blocks, we should be able to do this. So the time that it's going to take is still going to be 6 seconds, as you can see right now. But if I go even a single byte, more than 512 times 2, so 512 times 2 is 1024. This divided by 8, this is 128. So if we go with 128 bytes, still it's going to be 6 seconds. But if we now change it to this, now we're going to have a new block. So this should now take 9 seconds. And as you can see right now, that's exactly what happened. All right. Now, let's try to visualize this PBKFD2. Again, we said that what we're doing here is that we're calling HMAC many times. The input of the HMAC function is going to be the password and also the salt. All right, so one of them is going to be the data, and the other one is going to be the key. So let's try to visualize this, and let's take a look at one example. Let's say that we go with iteration count of 500, and the key length is 800 bits. We're using SHA-512, and we also have 128 bits for our salt. So our input to the function is going to be maybe password 1234 plus the salt that we generated right here and all these other configurations. So we're going to give these to the PBKDF2, and here's what's going to happen. Because we need 800 bits and we're using SHA-512, we need to generate 2 blocks. All right. And for each block, we're going to get 512 bits because we're using SHA-512. Now, for the last block, we're only going to take 288 bits off of it. All right, so we're going to truncate it because we only need 800 bits. If we need a little more, we're going to, well, take more from this. But if we now need more than 512 times 2, we're going to add a new block. So now we've got this block 1 and block 2. All right, and the indexes start from 1 here in this function. Now, for each block, we're going to run HMAC this many times. All right, so in this case, our iterations is 500. So we're going to run HMAC 500 with this, and again, another 500 times with this. Now, the input of the HMAC function is this. All right, so the same hashing algorithm that we specified, the pass123, actually in this case, I should have gone with password 1234, but that's the same idea. And then the salt plus the block index right here. So one of them is going to be the secret of the HMAC, and the other one is going to be the regular data. And also, this is pseudocode here. This is not valid Node.js syntax, because if it were to be valid one, we should have gone with the .update method and then pass in the password or salt like that. But that's really all that happens here in this pbkdf2 function. All right, so we're just essentially running HMAC many times. And in each subsequent HMAC run, we're just grabbing the output from the previous run and then hashing it again. All right. So here in code, we can actually get the same output as the HMAC. And let's try to do that pretty quick. So if we go with iteration 1, and I'll change the key length back to 512. 512 divided by 8, which is 64. So I'll go with 64 right here. And then let's do an HMAC operation. So const HMAC equals crypto dot create HMAC. And then I'll put in the digest, which is SHA-512. And then the password. So this is now going to be our secret. And then I'll call the .update function and now give it the salt. But it's not just the salt, it's salt plus the block index. So let's also have the block index right here. I'll say const block index equals buffer.alloc. It uses 4 bytes for the block index, and then I'm going to write a number to it. So write an unsigned integer that's 32 bits, and it's going to be simply number 1. And then here, we need to pass in this block index concatenated with the salt, and that's it. So here I'll say buffer.concat, and then give it the salt, and then the block index. And then at the end, I'll say console.log. HMAC output is this. Now let's also call the digest to grab the hex value. So now this is going to be a hex string. All right, so I think we're now good to run this. So I'll run node app.js. Now here I've got a quick error, and that's because, well, we need to call this right uint after we have allocated it. So I'm going to cut this and say block index.that. All right. And now it should work. So let me run it. There we go. So the derived key is this one, and the HMAC output is this one. And you can see that they match on every single bit. All right, we have an extra space here, which if I remove, we should get them now in a nice line like this, all right? So they all match, which means that this function, all it does is running HMAC many times. Now, if you want to go with iterations 2, now you need to grab the output and then give it to another HMAC, all right? So you need to do this in a for loop, okay? And if you want to go with a key length that's larger than 512, you need to do that for loop that many times, all right? So create multiple blocks, and of course for each one, go with the correct block index. All right, so I'm going to comment out this part because I just want to show you that that's essentially all that happens. So here I'll say this is what happens behind the scenes in the pbkdf2 function. And that's pretty much it. I'll switch this back to maybe 1 million right here. So again, you can use these KDF functions like pbkdf2 to both derive an AES key and also to hash passwords. So if you want to hash passwords, you need to save the final derived key along with the salt. And then when the user logs in and puts in the password, you know the salt because you need to save the salt into your database. You grab the salt and the derived key and then run the operation again. So you're going to put in that user password here to this function along with the salt and the same iteration and key length. And if you get the same value, it means that the user specified the correct password and you can now log them in. Now we're going to talk more about this password hashing in the security section in a lecture that should be called How to Securely Store User Passwords. So be sure to check it out if you want to learn more about this password hashing. But we're using the same function with the exact same arguments, okay? Now, the crypto module gives us 2 more KDF functions. One of them is scrypt, and the other one is hkdf. I'm going to give you a piece of code where you can see all of them side by side. I'll create a file here called demo.js, and I'll paste some code right here. You can grab it from the resource section of this video, final.zip file. So here, we're demoing pbkdf2 first. We saw all these things before. We've got the iterations, the digest, and also the password, salt, and key length. If you scroll down, you're going to now see the script, which is a more modern KDF, but this is still extremely secure. All right. It's just that this one, script, it's better for bad passwords. So if your users tend to specify very weak passwords, it's now going to be a little more difficult to brute force. All right. Because with this one, we're doing SHA. And we've got the Bitcoin miners, as you saw before, that they can do trillions of hashes per second. So if you attach many of them together, you may be able to brute force some of these simple passwords, all right? But if your password is really strong, let's say 12 characters in length and random, and you're hashing it with this, pbkdf2, with maybe 1 million iterations, it's now going to take an attacker billions of years to crack your password, all right? Nobody's going to do that. But if the password is really weak, especially if you're using some words that could be socially engineered, like maybe the name of your dog or something like that, in that case, now it's going to be much easier to brute force if the attacker knows it and they could deduce that it's part of your password. But provided, of course, that your password is random and it cannot be guessed, brute forcing it is close to impossible. We're talking about billions and even trillions of years to do it. All right, so here again in script, we have the same inputs, so password, the salt, the key length, and also here in this case, we have the options. We do not have the iterations. Instead, we have something called the cost factor, which should be something that's a power of 2. Now, the script is based on pbkdf2, so it's doing the same thing, HMAC and stuff like that. It's, of course, a little different, but we're not going to get into the details. And then if I scroll down, here we've got one more, HKDF. This one, still the same thing. We're using a digest. It's based on HMAC. That's what this H stands for. So it's HMAC key derivation function, or to be more specific, this one. And then here we also have this info. If you want to pass in a little more data apart from the salt, you can do so like this. And that's it. You're also calling all of them at the end. So let's go ahead and run this. Node demo.js. And here you can see all the derived keys. Of course, they're going to be different, but these arguments are identical in all of them. The salt, the password, and the key length. And each one has its own unique things, like maybe the digest one for HKDF and pbkdf2, and this cost factor for script. Now, there's just one more KDF function that I want to mention, and that is Argon2. This one won a password hashing contest in 2015. We'll talk a bit more about it in the security section when we're talking about storing user passwords and password hashing. But for now, just know that this one also exists. Alright, so now at this point, we know how to do 2 of these problems from our cryptography roadmap. We know how to ensure integrity and do authentication, and also how to derive AES keys in a very user-friendly way. And talking about this concept, we now also know how to hash user passwords before saving them to our database. So now we've got only one more problem to tackle to complete our cryptography roadmap, and that is to see how we can now exchange our keys securely in clear text. We can't always derive them from a password. For example, when you're establishing an HTTPS connection, you do not want to every single time put in a password. That AES key should be derived automatically behind the scenes for you. All right, so that's what we're going to tackle in the next section of the course. But before we move on to that section, let's use all the general concepts that we've learned throughout the section so far in one application. So we're going to build a file encryption application in the next video that we can use maybe for end-to-end encryption. And with that, we're going to see hashing and symmetric encryption all in one place. So that's it about this video, and I'll see you in the next one. In this video, we're going to do a wrap-up of what we've learned throughout the section so far and put most of the concepts that we've learned into use to build something useful. We're going to build a file encryption application, and let me first show you a quick demo of how it works. So here we've got one file that we can use to encrypt and one that we can use to decrypt. And here's also our plaintext. So all we have to do is to run the encrypt, and then it's going to encrypt the file. And now we have this data.encrypted. And the idea is that we should only do it with a single password. I have set an environment variable called file encryption _ password. And this is the password that this Node application used to derive an AES key and then encrypt this data. Alright, so now the decrypt file is going to read this password and then decrypt the file. So now we have this other file, data _ decrypted.txt. Now we want this application to be really secure, so secure that it could be used in military, the government, bank applications, you name it. So we're not going to compromise security for simplicity. We want it to be so secure that we can go ahead and put this data.encrypted online, maybe upload it to a hacker community or something like that, and then have a peace of mind that no one is going to be able to decrypt it without having this password. And if they want to do it and they have access to a supercomputer, they should be able to do it only after trillions of years of trying. So we want to make it incredibly secure, all right? And we will also do it from scratch. All right, so let's now go to our Visual Studio Code, create one folder called file-encryption. Here, let's create two files, encrypt.js and decrypt.js. Let's also have our plaintext, so I'll call it data.txt, but our application should work with any data format, so it could also be a video file or an image or whatever you have. It should work with no problem. In this file, let's put in, I don't know, maybe we owe about $1 million to Adam Smith with social security number, maybe this. So this is now our data that we want to encrypt and then send the encrypted data, the ciphertext, out in the open, right? So maybe transfer it through TCP or something like that. And no one should be able to decrypt it if they do not have access to our very strong password, okay? All right, so let's try to see how we can tackle this problem. Remember that if we want to have a very secure mechanism in place, we need to have the salt, because we are deriving our key from a password, so we need to use a bit of salt, and also we need to use an initial vector for the AES encryption. We also need to take care of the message authentication code, because we want to verify integrity and do authentication. And also, of course, we have our AES key, which we're going to use a key derivation function to come up with. Now, we don't want the users to handle these four things. That'd be ridiculous. We only want them to take care of one master password, and that's it. Right, so let's first include a few modules. We need the fs module because we're going to write and read files. Require the node fs. And then we're going to need the crypto. And also, just like before, let's include the pipeline. And then have this master password right here. So I'll say const password. And for now, let's go with a very non-secure password. So I'll just say non-secure password. But then we're going to come back to it and make sure that we're using something that is incredibly secure. Now, this is right now not secure at all. We should not hard code the password here, but just for debugging purposes and getting started, it's good enough. So ideally, the way that we want to do it is to read it from our env. So we have to say process.env.fe, file encryption, _ password. So this is how we're going to do it later on, but for now we're just going to put this thing in place. We want to make sure that our application works, and then after that we can specify whatever strong password that we want, okay? So this is now our master password. Hey, this is Future Me, and I want to make sure that something is 100% clear. At the beginning of the video I mentioned that we're not going to sacrifice security for convenience. Well, that's exactly what we're doing right here. Now, by that, I meant our information security and in terms of cryptography, and not the security of our whole system, okay? As we mentioned in the introduction video, security is never 100%. It's a process, and you can always improve it. For example, here we're going with environment variables. But this is not a really secure way of handling your secrets. It'd be far more secure to go with a key management system like AWS Secrets Manager. So this one, and I'll link this to the resource section of this video. So this is a way more secure way of handling your secrets as opposed to using environment variables. Environment variables could get leaked. Anybody who can log into your system can also now access them. So it's not really a secure way of going about it, especially if you're working in a team. Now, we'll also have a lecture in the security section to talk more about the key management system and how to handle our secrets. But it could be a little while until I publish that lecture, so I just wanted to give you this heads up right now in this video, especially that in the Node.js community, we see a lot of people thinking that the environment variables are the way to go to handle the secrets. Sure, it's much better than hard coding your secrets right here in your code and then accidentally pushing it to GitHub. But still, it's not a really secure way of going about it. A KMS usually is a far better choice. Alright, back to the main video. Alright, let's now specify the algorithm that we want to go with. And let's go with AES-256-GCM. So we're going with GCM mode with 256 bits of key. Let's now generate our salt. So crypto.random bytes. And for our salt, we need to have about 16 bytes. This is what we're going to use for the key derivation function to derive a key that is 256 bits in size from this password. Okay. So now we have also our salt. And then, of course, because we're using this one, we need to have an IV vector. So const IV equals crypto.random bytes. Remember that this one has to be truly random, so we have to use crypto.random bytes, okay? And then the size should also be 16 bytes or 128 bits. Remember, AES only works with 128-bit blocks. All right, so this one has to be 128 bits exactly. Hey, it's Future Me again, and I made a mistake in the main video. I said that the IV vector has to be 16 bytes exactly for the GCM mode, which is incorrect, all right? It is recommended to go with 12 bytes or 96 bits and not 16 bytes, all right? And the reason for this is if you go to the GCM specification, which was published by the NIST organization, I'll link this document to the resource section of this video. And here, if you read the document or search for 96, I'm going to find this one. So here in the beginning, it mentions that for IVs, it is recommended to stick with 96 bits, okay? Now, this will now make it more efficient. And to see why we should stick with this, if you keep searching for 96 to find the implementation right here, so here it says that if the length of our IV vector is 96, it is then going to attach 32 bits of data at the end. So these pipe symbols here just mean append, all right? Attach this one with this and then with this. So this IV is our nonce, number used once. It's the random number that we generate. And then this portion, these 32 bits, are now going to be our counter, okay? So the combination of the whole thing is going to be 128 bits. And for each block, as we mentioned before, we're going to add 1 to it and then encrypt this one and then XOR it with the plaintext. All right. So at the end, whatever we generate here, this is now going to be our IV or nonce, whatever we want to call it. And then we'll have 31 zeros. So here we're going to have 31 of these and then a 1 at the end. All right. So 32 bits and then 96 in total, 128 bits. All right. This is not 0 to the power of 31. This means 31 zeros, all right? Now, if you don't go with 12 and you go with another value like 16, it's not going to give you a warning or an error, but what's going to happen is that the ghash function, the hashing mechanism that's used to compute the MAC, so this ghash function is going to come into play and then change your IV to make sure that the output is going to be suitable for the GCM mode. So not going with 12 means that we're doing an extra ghash, and it's not really efficient. It might not seem like much, but if you have millions of connections to your server, it could really add up. All right, so I'll change this to 12 and change the comment to say recommended to be 96 bits exactly. Now, throughout the rest of the video, you are going to see me sticking with 16 with a comment that says has to be 16 bytes exactly. I wish I haven't written that, but please keep this in mind. You can also go with 16, but if you do at the end of the video, make sure to change it to 12. And then also change all the other places that I'm using a bit of math with this to make sure that it's going to work correctly. If you download the final .zip file, you're going to see that I went with 12 and not 16. Alright, back to the main video. And I'll say that this is the salt for key derivation function. Now let's actually put it right here. Alright, so now we have the IV as well, and let's now take care of the AES key. We can use many different key derivation functions, but I'm going to use the pbkdf2 function. Here we need to put in our password, the thing that we want to derive a key from, and then the salt, and then the number of iterations. We're going to go with 1,000,000, which is a pretty secure one right now for this function. And then also the key length. We need to have exactly 256 bits in size. 256 divided by 8 is 32. Okay. And then our hash algorithm, which let's go with SHA-512. All right, now we're going to get the callback with the error and then the derived key. So now this is going to be our AES key, so we have also now taken care of this one. Let's first do a quick error check that if we have an error, let's return console.error the error. And then here we're going to create our cipher. So crypto.create cipher IV. First, the algorithm that we specified before, and then here we have to specify our key, which at this point we have just derived, and then we'll need our IV vector, which we also generated at this point. And that's it. Now we have our cipher in place, ready to accept data and encrypt. So let's go on ahead now and create our streams. We need one for the input from the plaintext, and then one to write our encrypted data into. So let's name these variables standard cryptography names. So I'll say plaintext. This one is going to be the read stream of whatever file that we have, right? So in this case, we're going to hard code it in, so data.txt, but you can easily read it from the command line, right? And then the ciphertext, which is now going to be a write stream. And this one, let's call it maybe data.encrypted. Okay, you can name it whatever you want. All right, so let's now have the pipeline from the plaintext to the cipher and then to the ciphertext. A quick error check that if we have the error, just return console.error. And then at this point, we need to take care of our message authentication code. Let's grab the auth code. So const auth code equals cipher dot, remember the method that we call to grab the code. It's called getAuthTag. So here we are getting, so get the message authentication code. All right, so at this point, we're now done with the encryption. We've got the message authentication code and also the IV and salt. Okay, let's now try to imagine what's going to happen if we go ahead and decrypt it. Remember that the idea is that we should only have the password. And with the password in place, we should be able to decrypt the file. But right now, we can't do it. Let's actually first run the code to make sure that we don't have any errors. I'll go into the file encryption and then node encrypt. All right, so it runs fine. And also now we have this data.encrypted, okay? Now the problem is that if we now write the decrypt file and then read the data.encrypted and try to now decrypt it, we need to also have the salt, the IV vector, and also this code so that now we can verify the integrity and authenticate. At this point, all that we're saving to our file is the ciphertext. But let's also take care of the other things. Now, a very simple and secure solution to this one would be to also write the IV, salt, and the code to this final file. All right, we can do that. And then in the decryption, we're going to read those metadata and then use them to decrypt the ciphertext. Okay. All right, so here's how we're going to structure our final file. Imagine that this is going to be the file, data.encrypted. We're going to use the first 16 bytes to store our salt. And then we're going to write the initial vector to the next 16 bytes. And then afterwards, we're going to have our ciphertext. And in the last 16 bytes, we're going to put in our message authentication code. All right. So now in the decryption, if we have the password, we also have everything that we need to now decrypt the ciphertext. Remember that none of these items need to be kept secure. All right. The only thing that needs to be kept secret is the AES key. And in our case, we're deriving the AES key from the password. So now our password is the thing that needs to be kept secure. All right, so let's now implement this here in our application. It'll be pretty straightforward to do. Here, after we have the plaintext stream, we're going to write some things to it. So I'll say plaintext.write. First, the salt. And then we're going to write the IV vector like this. Now let's scroll down, and here, after we're done writing the ciphertext to the file, we can also, just like before, write this to the file. What we could do is to append it, so I'm going to say fs.append file sync, and then specify the path, data.encrypted, and then this auth code. And then at this point, we are now ready. So console.log, encryption completed, and authentication tag written. Let's also here at the top put in the structure of our file so that we know what this protocol that we have developed looks like. So the first 16 bytes is for the salt. The second 16 bytes is for the IV. And then the last 16 bytes will be our message authentication code. And everything that we have here in between, so everything here is going to be the ciphertext. Let's also log the things that we have. So after this point, we're going to log the salt. We're going to do it for debugging purposes because later on here in decrypt, we're going to read these 3 pieces of data, salt, MAC, and IV, and then use them to decrypt the ciphertext. So just to ensure that we have the right things, let's log all of them. So salt, and then salt.toString, the hex value, and the same thing now with the IV. I'll add in one more log here at the end after we grab the MAC. So console.log, the MAC, which is going to be this auth code. All right, great. Let's now run this and see what's going to happen. Node encrypt.js. We've got a bit of an error here. It says plaintext.write is not a function. Let's see if we have a typo or something. Well, my bad. I'm writing it to the plaintext. I should write it to the ciphertext. Hopefully you catched this mistake. So we need to have these items to the ciphertext. We're not sending the plaintext over. We're only sending the ciphertext. Awesome. So now we are encrypting this. And we're also saving all these values to the final file. And now because of this, let's change this ciphertext name to something else. All right, because now we're adding these things to it. So technically it's not only the ciphertext, it includes the ciphertext, but it has other things in it. So I'll rename this to output, all right? Now let's also get this in hex to be more consistent. And then here I'll say, this is the, let's add in all these things. So salt plus IV plus ciphertext plus MAC, okay? Okay, now let's implement the decryption, which is going to look pretty similar to what we have right here. We now need to do it in reverse, okay? First, let's include the modules. the FS module, and then the crypto, and finally the pipeline. Now, let's grab the password just like before. We need to read it from the environment. And if we don't have it, we're going to fall back on something that's not secure, right? So process.environment variables, and then here we need to grab the file encryption password. If we don't have it for now, we're going to go with non-secure password. I'm only adding this portion in case one of you don't know how to set this one, because I'm not assuming that you have gone through the Unix section. In the real world, you don't want to have something like this. And then the algorithm, which is going to be the AES-256-GCM mode. All right, so now that we have these things, let's read the salt, and then we need the IV and also the auth code. So let's allocate a buffer for each one of them, and our size needs to be 16. Right, so all of these items are 16 bytes in size. So the salt, 16, IV, 16. The tag is also 16. We don't have it here, but we can just add a comment. So here at the end, I'll say 16 bytes. Let's also copy-paste this thing so that we know what to do and how to read them. Now, we can use the fs.read_sync function to now fill up these buffers with the data that we want. Now, this one first accepts the file descriptor, which is the ID of the file. We don't have it right now, but we can easily get it by opening the file. So I'll say the file descriptor is equal to, let's open it up, so open sync, and then the file name is data.encrypted. And then I'll specify the flag, which should be R. All right, we're now in read mode. And then here, for the first one, the salt, which is the first 16 bytes, I'll pass in the file descriptor, and then the buffer that we want to fill, which is salt, and then the starting position to fill up the buffer from, which is 0, and then here we're going to have the length, which is 16 bytes, and then the offset to start reading from the file, which in this case, it's going to be 0. And then we need to have one more of this, so read sync. Actually, two more. So this one is going to be for the IV vector. So IV, and then the offset to fill up the buffer 0. We need to read 16 bytes. I will need to start reading from position 16. All right. Now the last one is going to be for the auth code. So from the FD, here we need to specify the auth code buffer. From 0, fill it up, and then read 16 bytes from the file. And now the position here, we need to go all the way to the end. All right, so what we could do is to grab the file size and then specify that here. So here we can say file size minus 16. And this is going to be the starting position to start reading from here in our file to grab the auth code. Now grabbing the file size is pretty straightforward. Here we can do it from this file descriptor because we have already opened the file. Here I'll say file size is equal to this fs dot, I'm going to use the fstat, and then sync function, which accepts a file descriptor, and then at this point, we just need to specify whatever we want, so I'll say dot size. Now, before we go ahead and try to do the decryption, let's make sure that we're grabbing everything correctly, so here I'll add in a few logs. First, for the salt, and then two more, one for the IV, and another one for the MAC. Now let's run the decrypt file. Actually, let's first run the encrypt, and then decrypt. And I believe I fixed this one. I'm not sure why it's still happening here. Oh, actually, here we've got a bit of a problem. I shouldn't be calling this on this one where we're appending it to. We need to call it here on the log. All right, so let's run it one more time. So node encrypt, and then node decrypt. All right, great. So now if you take a look, we're grabbing the exact values. So here we have the salt that was written to the file, and here's what we read from the file. All right, same thing with IV and also the MAC, and they all match up. All right, so with these three in place, we're now ready to go on ahead and do the decryption. First, let's do the key derivation thing. So crypto.pbkdf2 with the password, the salt that we grabbed, and also 1 million iterations, which is exactly what we specified here in the encrypt. And then 32 bytes for the key length. The digest that we used was SHA-512. And then we're going to have the error and the key. A quick error check. And then at this point, we can create our cipher to start to decrypt. So crypto.create decipher IV with the algorithm, and then the key, and then the IV. And remember that now what we need to do is to set the auth tag so that it can now verify it to ensure that the integrity is now there. So here I'm going to say cipher.set auth tag, and then the auth code that we read at this point. We'll just add a comment and say set the MAC for verification. So now if the data is modified in any shape or form, at this point we're going to get an error. Alright, so with these in place, we can now create our input. So I'll say const input, which is going to be the data.encrypted, and I'll say fs.create read stream from the data.encrypted. Now we need to specify some options here. We can't start to read from the very beginning because whatever we get, we want to then pipe it out to this cipher, which is a transform stream, and then get the plain text. So we need to exclude reading these three things that we read before. Okay, we only want to grab the ciphertext. Now if you go to the Node.js documentation, or if I hover over it, here you can see that as the second argument, we can specify some options. Some of these options are starting position and also the ending position. So let's put them here. So I'll put an object and say start. So the starting position should be from the 32nd byte. So here we're excluding the salt and IV. And we need to now keep going forward until we reach the MAC. So remember that the MAC is the last 16 bytes. So here we can grab the file size and then say -16, right? And we also need to add 1 to it like this. And then here what we're doing is that we're excluding the MAC. So we need to subtract 17 from the file size to get the index of the end of the ciphertext. So the index of the last byte in the ciphertext. And now that we have the input, we can create our output, which in this case is going to be the plain text. And then here I'll say fs.create, now write stream. Let's call it data_encrypted.txt, and then our pipeline. From the input to the cipher to the plain text. And then we're going to have the error. We'll do a quick error check. And then log that this was successful. So decryption completed and authentication tag verified. All right, great. So I think we should now be done. Well, of course, we need to take care of the password, which we will in just a sec. But let's now run this first. So node encrypt, and then node decrypt. Let's now go to the data_decrypted, and you can see exactly that we have the same thing. And I have a typo here. I wanted to say we owe this much to Adam Smith. So let's start again from scratch. I'll delete this data_decrypted, and then data.encrypt. Now we only have our plain text here at this point. And I realized that we had a problem in the name of the file. Now this one shouldn't be data encrypted, we should call it data decrypted, alright? Now let's do one final check. I'll head over and then run the encrypt first, and then the decrypt. And now, if we go back here, we can see that these two files match, alright? So now at this point, we are encrypting and then decrypting, and all based on our master password, alright? But the password right now is absolutely not secure. So let's go ahead and pretty quick choose a password for this one that we'll know will never be broken by anybody, alright? So something that is going to be really secure as a random AES key, or even more actually. So here I'm going to go to this website. I'll link it to the resource section of this video. And all it does, so let's quickly see it. I'm going to change this to maybe 12 and then click on generate. And then it's going to give me 12 random words. Now these words are generated based on this BIP 39 specification. So basically, all we're doing is that we have a pool of 2,048 words. And then we randomly pick 12 words out of that pool. Alright, so I'm going to copy this. And then here in the terminal, I'm going to set that to my environment variable. Now we talked about this in the Unix section. If you don't know how to do it, it's fine. You can just watch me do it. So here I'll say export, and then the name of the environment variable, which we called FE underscore and then password. And then paste those 12 words that I copied. So now if I log the password and then run it, so we are now generating our key based off of this one, all right? So we came up with this 12-word thing, but how secure it really is. We know that we only have 2048 words in total, and we're just picking 12. So you might be thinking that surely somebody could easily come up with the same combination and then now decrypt our files. Well, that's not going to happen. Now this specification is the same that's used in cryptocurrency wallets. So if it was that easy, well then, if you could do it, if you could come up with a combination that somebody else is using, you can become rich overnight. So although it might not seem to be very secure at first glance, it is incredibly secure. And you can see that by doing a little bit of math. We've got 2048 words in total. We're picking 12. So in total, we have 2048 to the 12 combinations. If you change the base like this, and then do this, in total, we have 2 to the power of 132 combinations. So if somebody wants to brute force this, they have to try all these different 12-word things. And we know from the AES video that doing 2 to the power of 128 is gonna take trillions of years. Now this is even worse. Not only our number is now bigger, but also for each operation we have to do 1,000,000 SHA-512s. So we're talking about a ridiculous amount of security right now. If now everybody on the planet tries to brute force your key, we have a pretty good probability of somebody coming up with your combination after billions of years of everybody trying, okay? So it's not going to happen, and this application that we have right now is incredibly secure. So you can now go ahead and upload this data.encrypted online and have a peace of mind that no one will ever get to the plaintext. And only people that you give your password to, only those people can now see what the plaintext is. Now with this system that we have developed, you can also implement end-to-end encryption for your users. You now understand the basis of end-to-end encryption, so let's talk about that for a sec. Imagine that this is your server, okay, your app.com, and two people are connected to your server and they want to communicate together. So let's say that this person here has this file, or it could be any data, maybe a piece of message, that they want to now securely exchange to this person right here, okay? Now, if you're just using HTTPS, the traffic is encrypted between you and the server. So this data is going to get encrypted first, and then sent to the server. The server is now going to decrypt it, because, well, you and the server have access to the same secret, and then it's going to send the encrypted data back to this client, and this client is now going to, well, decrypt it. But the problem right now is that the server knows what you two are talking about, okay? They have a copy of your plaintext. So let's say that an entity comes to the server, maybe the government, and pressures the company to give up your data. Well, they can easily do that, all right? But let's say that now you want to do end-to-end encryption. So using this exact same logic here, let's say that we want to now do that end-to-end thing. So if you and the other person both have access to the same password, let's say a 12-word passphrase, you can both derive an AES key and then communicate together. So imagine these two both have access to that same thing. This person is going to encrypt the file and then send the ciphertext to the server, all right, to your server. Now, you're not going to decrypt it. You can't even do it if you want because you don't have access to that password that this user has. Right? The AES key that was derived from the password is securely saved on the user laptop and only on this device and nowhere else. The key will never leave this device. Now, all that you're doing at this point is that you're going to now send this ciphertext to this client. So you can keep a copy of the ciphertext because, well, you're saving it to your database, and that's usually what happens. For example, in chatting applications like WhatsApp, they do store your ciphertexts because when you log out and then log in again, or if you lose your phone, you're not going to lose all your data, all right? Because it's stored on the server, but the encrypted version, all right? So now this person here has access to the ciphertext, and they also have the same 12-word passphrase. So what they could do is that they can now easily decrypt and get the plaintext. So notice what just happened. At this point, only these two entities have access to the plaintext. You as the server, you have no idea whatsoever what's going on. So if the government comes to you and says that one of your users is doing something bad and I want you to give up their data, well, you can't do it. Even if they give you millions of dollars or shut down your whole company, there's no way for you to give up the plaintext. You have a much better chance at finding this person and then forcefully get access to their laptop and then, well, do the decryption right there, right? You cannot do it here on the server. We talked about the math, so we're not going to go over it again. Now, this is really one difference between security with cryptography and security in the physical world. In the physical world, it doesn't matter how secure your stuff is. If you put in a very secure lock on your door, well, there's still a way to get into it. Worst case scenario, the military could come and then bomb down your door and then get in. The point is, it could happen. Very unlikely maybe, but here in cryptography, there's just no way to do it. And it doesn't matter how powerful you are. If you want to do this decryption without having access to that key, it's going to take you trillions and trillions of years, provided, of course, that the system is implemented securely. It's one of the beauties of cryptography that would allow us now to do all these different things and have a peace of mind that no one is going to break it. Now, notice that we have a bit of a problem here. That these two people, if they want to do this end-to-end encryption, they always need to meet up in person and then exchange the password. There's an easy way to now automate this thing, all right? Or even between you and the server. You want to automate this process of two entities coming up with the same password. So what we could do is to use algorithms like Diffie-Hellman to come up with some random data for two entities. So with the help of Diffie-Hellman, we can make sure that two people will have access to the same data. And then with that data, we're going to derive an AES key and then do this process. Well, that whole idea is the topic of the next part of this section. So now we're done with the first part of the section. You now understand symmetric encryption and keyless cryptography like these hashings and so much more. And in the next section, we're going to tackle how we can now securely exchange our private keys. All right, congratulations on completing this first part, and let's get ready to jump into the next part of the section. Hey, and welcome back. In this lecture, we're going to start the second part of our cryptography section, and now we're going to talk about public key cryptography or asymmetric cryptography. Going back to our cryptography roadmap, we're now going to tackle this final problem that is about how do we now exchange our keys securely in clear text. So if we have, for example, a TCP connection, how do we now set up encryption between us, knowing that even if hundreds and thousands of people are listening to this communication, they would have no idea whatsoever what we're talking about? There are two important things that we also need to tackle in this problem. One is the actual key transport or key exchange. These two are slightly different in how they work, but at the end of the day, all that matters is that we both end up with the same key. Key transport means that one entity generates a key, for example, an AES key, and then transports it, so transfers it across the connection to the other entity. Key exchange means that both entities now contribute to the final AES key that they're going to end up with, okay? So they work slightly differently, but the goal of both is essentially the same thing. Another thing that we need to tackle here in this final problem is how do we now ensure that the key that we're getting is coming from the right person and not from someone who's pretending to be that person. So this is again the authentication problem, and we'll see how we can solve this using public key cryptography. Alright, now let's see how this form of encryption works. Let's imagine that you and I want to communicate together. Alright, so this is you and this is me, and let's also say that this red area right here is the private area. Right, so this could be your computer, your memory, your disk, whatever you have here, no one else should be able to have access to it. If they have, it means that you are hacked. Okay, so you have this area, I have this area too, and then we also have this communication channel between us. This could be a TCP connection or any other protocol. The point is that it is in clear text. So our ISPs or our organizations, if you're communicating with me from your company or university, for example, all these people have access to this clear text and they can see exactly what we're talking about. Every single bit that we exchange across can be seen by these people who have access to this network. But that's a big problem for us. We don't want that to happen. If we want to, for example, exchange our bank information or some very secret data, we don't want everybody who has control over this network to also be able to see what we're talking about. Now, if we encrypt our traffic, for example, using AES, before sending it, well, the problem is solved. But the main problem now is, how do we now make sure that both of us have access to the same AES key? Okay? If I go ahead and send this key, so I create a copy and literally just send it in clear text to you, this is a massive problem. Although you're going to get it and we're going to now encrypt it, all these people in the middle now also know our AES key, so they can decrypt all of our communication. So obviously, this is a terrible idea. Now, if we meet up in person, and then I give you my key, and then we go back to this connection, again, in this case, problem is also solved, but this is not practical in the real world. On the internet, if you want to, for example, do a quick Google search, it's ridiculous to go to the Google company and exchange a key, all right? That's not what we want. We want something that's way more efficient through this communication channel itself without needing us to worry about other things like that. All right, so this is where public key cryptography comes into play. And with that, we can solve this problem. So here's how it works. In public key encryption, just like symmetric encryption, we encrypt and decrypt. So we have ciphertext and plaintext. All those things that we discussed before are also applicable here. But the difference is that now, instead of only one key, we have two keys. So we would have a structure like this, key 1 and key 2. Okay? Now, the main idea in public key encryption is that we can use any of these two keys, so key 1 or key 2, to encrypt our plaintext. But we can only use the other key to reverse the process, meaning to decrypt. So if you go ahead, you generate two of these keys, If you go ahead and encrypt using key 1, you can now only decrypt using key 2. You cannot decrypt using key 1, okay? So that's the important part. This is how we can now solve this final problem, okay? And that's why it's called asymmetric cryptography, because we have two keys. They are mathematically related. We'll dive into the math in the next lecture. So these two keys are related, but they are not identical. That's why it's called asymmetric. Now, it's called also public key cryptography because you keep one of these keys secret, for example, key 1, and then you put the other one in public. Okay, so you would say, for example, that I want to keep key 1 in my secure area right here. I will not ever let it leave my computer, my memory, my disk, but I will put key 2 out in the open. All right, so now this is going to be your private key, and this is going to be your public key. All right, now here's how I can send you this AES key. I can take your public key, because again, you have put it out there, and then I'm going to encrypt this AES key. So now I'm going to have the ciphertext. Right, so this red color means our ciphertext, and this is our plain text. So now my AES key is encrypted. I will now go ahead and send it to you through this communication channel, which could be TCP, for example. And maybe millions of people are here in the middle listening to our conversation. They will also take this AES key that has been encrypted, but they cannot do anything about it because you are the only person who has this other key that can use to decrypt this ciphertext, okay? So everybody else is just seeing gibberish here in the middle. So you're going to take this key, you'll use your private key to decrypt this ciphertext, and now you're going to have the plain text, okay? So just like this, we both now have the same AES key which we can use to encrypt our whole communication. So this public key cryptography is going to help us solve this problem. But if we can do this, why do we now have to bother with AES? Why can't we just use public key cryptography to encrypt the whole thing? And the answer is, public key cryptography is so much slower compared to symmetric cryptography. Sometimes hundreds and even thousands of times slower than symmetric cryptography. If encrypting something with AES is going to only take 1 minute, encrypting the same thing using public key cryptography would usually take many hours and even days to do the same amount of encryption. So we're going to only use public key cryptography for cases like exchanging a bit of data, which is usually our keys, okay, our symmetric keys. Remember, these keys are only a few hundred bits in size, 128 or 256, so it's not really that big of a deal to encrypt it using public key cryptography. All right, so this is the main idea of asymmetric encryption. Now, I want to make an important point that although this is going to solve the problem of eavesdroppers listening to our communication, this will not solve the problem of a man in the middle. So if a malicious user now comes into play, so let's say that this third person is going to come between us and pretend to be you. So now I'm going to use this person's public key instead of yours. Let's say his public key. I'm going to use this one instead of this one to encrypt this AES key. And I have no idea that now I'm talking to this person and not you. So if you're Dylan and this person comes and says, hey, I'm Dylan, this is my email address, which is your email address, now I have no idea to know who is who. All right, so now I gave up the AES key to this third person, and now this person has access to everything that I am sending to you, which I think I'm sending to you, but I'm actually sending to this person. So please make that distinction that a man in the middle is different from people who are listening to our conversation. A man in the middle is someone who can not only listen to our conversation, but also has control over the bits that we are sending and receiving, right? So this person can just put your IP address and his source IP address, and that's it. Now, this is the second problem that we had. This assurance that we're getting the keys from the right entity, okay? So if we have someone in the middle, we should be able to now also know that there is that malicious person and do not continue with the communication. So both of these problems can be solved with this public key cryptography, which we'll see later on in the section. And just to give you a bit of idea about this second one, let's go back to this example. Let's say that you now want to authenticate me, all right? So I'm going to put some message out there, and you want to know that this message was really produced by me, okay? So just like you, I'm also going to generate 2 keys and put this public key here on the internet. But here's what I'm going to do. I'm going to use this private key, so my private key, to encrypt this message, maybe along with a hash as well. I'm going to encrypt it and then put this message out there. And you want to know that this message really came from me, okay? So you're now trying to authenticate me. What you could do is that you can take my public key and decrypt this message, okay, using my public key. Excuse me, I'm saying your, I should say my here. Okay, so this is my private key and my public key. So you're going to take my public key and then decrypt this message and come up with the plaintext. And you'll see if you come up with the right plaintext. For example, if the hashes match, it means that this message has for sure come from me, because I am the only person who has access to this private key, meaning that I am the only person who could have encrypted this message. This is also the idea of how do we do this authentication with public key cryptography, which we'll dive deep into later on in the section. But again, this is the basic idea. Now again, in both of these 2 problems, we have this assumption that the public keys really belong to this identity right here. So I now have this assurance that this public key belongs to you, and again, not to a man in the middle. And you also have this assurance that my public key really belongs to me and was generated by me. To really come up with this confidence, we will have a third-party person that is going to assure us that a particular public key belongs to the actual identity that we're trying to communicate with, okay? But let's not worry about that third party right now. That third party is also using public key cryptography to do this process, which we'll again talk about later on in the section. But, well, this is the main idea of public key cryptography that I want you to understand. That we have 2 keys, we put one of them out in the open, in the public, for example on the internet, and we keep one of them secret. And if we encrypt using one of them, so either using our private key or public key, we can only decrypt using the other key, all right? So if you use this public key to encrypt something, you cannot use this public key again to decrypt it. That's the most important point right now to understand about this topic. Now, in terms of the algorithms that we have in asymmetric cryptography, we mainly have these RSA Diffie-Hellman and Diffie-Hellman with elliptic curve, all right? HTTPS usually uses Diffie-Hellman with elliptic curve, plus with RSA as well, to do authentication. Again, a topic that we'll discuss later on. But it's important to know what these are. You can do all of them using Node.js. Now, in this section, we're going to dive deep into the mathematics of RSA, okay? So we're going to understand exactly how we can use it on a piece of paper to encrypt and decrypt. It's actually quite straightforward. If public key cryptography feels like magic to you, you'll see that it's not magic at all. It's really just some basic math based on number theories. Now, the math behind Diffie-Hellman is even simpler than RSA, but we will not really talk about it. We'll mention a few things, but we will only focus on RSA because with RSA, you can solve both of these 2 problems, okay? So with RSA, we can do a key transport, and we can also do this authentication. With Diffie-Hellman, we can only do key exchange. We cannot do authentication. That's why it's usually used with RSA itself. Now, Diffie-Hellman with elliptic curve is faster compared to RSA, but all these algorithms that we discussed are considered secure. And the reason that we're not just sticking with RSA and we're using, for example, elliptic curve Diffie-Hellman is mainly because of speed. Before I end this video, I want to talk about one last point. So we're now talking about public key cryptography, which itself has 3 core subcategories. One is public key encryption. A common example is RSA. The other one is digital signatures. Common examples are RSA and elliptic curve DSA. And another one is the key exchange protocols. And 2 of the common examples are Diffie-Hellman and elliptic curve Diffie-Hellman. In the previous slide, we were specifically talking about public key encryption when we were talking about transporting my AES key across to you, and we also briefly touched on signatures when we were talking about what you would do if you want to authenticate me. So if I put a message out there, what would you do to ensure that it actually came from me? Okay? Now, we will understand this whole picture by the end of this section. I know it seems like a little too much at this point, but don't worry about it. At this point, it's crucial that we take our time and deeply understand one of these public key cryptography algorithms. And we're going to do that with RSA. So with this, we can both do encryption and handle signatures. And once we understand the math behind it, we will be much closer to understanding this whole picture. Understanding key exchanges will also be fairly straightforward after that point. In all of these, we have a private and public key. Here in the public key encryption, obviously we can use them to encrypt and decrypt. So we have the plain texts and ciphertexts. And here in key exchange, we still have a private and public key, but we don't use them to encrypt. Rather, we use them to generate a symmetric key, okay? So both entities will use their public and private keys to make sure that they will both end up with the same shared secret. That's it about this video, and I will see you in the next one where we're going to dive deep into the RSA algorithm. Before we move on with the rest of the section, I want to take a moment and mention something about OpenSSL because you need to have it set up if you want to follow along with the section. And also I want to mention something about setup and also put another emphasis here on the prerequisites. Now, so far in the section, you should have had no problems following along with the section if you did not understand HTTP and TCP really well. But starting from this point on out, you need to have this basic understanding if you want to understand and follow along easily with the rest of the lectures. If you are not comfortable with the idea of TCP, if you have never heard about what is a TCP handshake, or if you don't know what it means when we say that we are transmitting data in clear text, well, in that case, you have a really bad chance at understanding TLS and HTTPS. So I want to make a huge emphasis on this one here. Make sure that you have used the NET and HTTP modules in Node as well, at least for a couple hours. If you haven't ever done that, go ahead, give it a shot, use the NET module, move some bits around between computers, maybe upload a file, and really get comfortable with this idea that HTTP is built on top of TCP. You can either check out the networking and HTTP modules of the course, or learn them on your own and play around with these 2 modules for a bit. Now, also if you're on Windows, and if you haven't done so already, make sure that you get WSL installed. We're going to be running some OpenSSL commands, and I cannot guarantee you that you're going to get consistent results as me if you are using, for example, PowerShell instead of WSL, all right? If you install WSL, you will have easy access to OpenSSL. Alright, so that's it about this one, and also next up, I want to mention Firefox. Still, if you haven't done it yet, please make sure that you go into firefox.com and then download the Firefox browser, right? We're going to be using this heavily throughout the rest of the section, specifically to investigate some certificates. Also, make sure that you have access to Python. We're not going to do anything crazy with it. We're not going to write a program or learn its syntax or anything like that. We're going to use it just like a calculator, and that's it. Python is great for scientific work, which can help us quite a bit for understanding some cryptographic algorithms like RSA. It's not that we can't do those things in Node, but it's just simpler to do them with Python. So make sure that you can run Python on your machine. You can either download it here from python.org, or if you don't want to install anything, you can go here to online-python.com, and here you have access to a Python IDE. If you do end up installing it here from this website or a package manager, you should have access to a command like Python or Python 3. So you probably have access to one of them. Here's how you can go into the Python REPL. And if you want to exit out of it, Control-C is not going to work. You have to say exit with parentheses to do this. And just like with Node, you can also run Python code by saying Python and then the name of your .py Python code file. Now I want to show you one example here in the IDE just to see how simple this is. Again, you do not need to know anything about Python. Now let's run one example to make sure that we have access to it. I'm going to include the math module by saying import math, and then I'll use a function called GCD, which will calculate the greatest common divisor. So we're going to give it two numbers. I'm not going to explain how this function works. This is some basic high school math, but basically if you don't remember, this will give us the greatest number that we can use to divide both of these numbers by. So by putting 12 and 8, we're going to get 4, okay? And here's how you'd save variables in Python. You can just say this. You don't need to use anything like var or const. And then I'll go ahead and print it. So this is like console.log in Node. So let me run this. And here you can see that the output is 4, right? If you put in two prime numbers right here, you will always get 1, okay? All right, so that's it, quite straightforward. And you can also easily convert numbers between decimal and hexadecimal here with just one simple function like this. And you can also deal with gigantic numbers without needing to worry about any additional data types, which makes Python an ideal tool to use when doing cryptographic research. All right, next up, I want to talk about OpenSSL. Open up your terminal and run OpenSSL version -A. If you get an output similar to me that says library is OpenSSL and version maybe 3 point something, you should be good to go, okay? Many operating systems are shipped with OpenSSL installed on them, so you don't have to normally install anything about it unless you are on maybe Mac OS, or if you are on a very light Linux version. I want to show you how to do that in just a bit. So this is what you should see. Here I am now on Windows. I have installed WSL, and you can see that when I run it, I get this output, all right? Now, if you don't have this installed on Linux for whatever reason, maybe you are on a very light version, just run sudo apt update and then sudo apt install OpenSSL. And then once you run this, you should be able to run OpenSSL version -A and get this same output, okay? If you are on another Linux distribution that you don't have access to the sudo apt, please just Google how you can do it on your own operating system. It should be fairly simple. So if you see something like this, feel free now to skip the rest of the video and you're now good to go. There's one final point that I want to mention if you are on Mac OS, because Mac OS does not come pre-installed with OpenSSL. All right, so here I am on a Mac. And if you run OpenSSL version -A right here, it is libreSSL and not OpenSSL. You still have access to the OpenSSL command, but a lot of the commands that we're going to run in the section are not going to be supported by libreSSL. All right, so you're going to see a lot of discrepancies if you do not install OpenSSL. Now, libreSSL is a lighter version of OpenSSL. OpenSSL is an open source project, and this is a fork of OpenSSL. A couple of years ago, OpenSSL had a massive vulnerability, so this was developed as a result of that, and macOS defaulted then to this, and so far it is still using libreSSL. Because it's a lighter version, it is easier to maintain it and make sure that there are no bugs and vulnerabilities, okay? But this is not good enough for us. Fortunately, it's an easy operation to get the real OpenSSL setup on your machine if you have Homebrew installed. Now, if you do not have Homebrew installed, please refer to the setup videos of this course in the first section and download a file that is macOS setup commands. And all you have to do is copy-paste these first two commands in your terminal, and then you should get Homebrew installed. So after you are done with those two, you should be able to have access to brew-v, and with this in place, installing OpenSSL is as simple as running brew install OpenSSL. Alright, it's now done. I'm going to create a new tab and then run OpenSSL version-a again. And now this time around, you should see OpenSSL installed. Alright, so library here should say OpenSSL and not something else. Alright, so now with Firefox and OpenSSL in place, you are now ready to follow along with the rest of the section and do the exact same things that I'm going to do. Alright, let's keep going. Before we dive into the RSA algorithm itself, in this lecture we're going to first see it in action, do some encryption and decryption, and once we get comfortable with it, then we're going to deeply understand how it really works. You're in my crypto folder. Let's create a folder called RSA, and then inside, let's have an app.js to play around with this a little bit. First, we need the crypto. And then we have a function on the crypto module called generate key pair. So with this, and I'm also going to call the sync version because this could also be async. So I'll try to just stick with the sync versions as much as I can to keep things simple. Now this function, as the name suggests, is going to give us two keys. All right, it's going to give us a key pair. And here in the first argument, we need to specify the public key cryptography algorithm that we want to use to generate the keys and then do encryption and decryption with. So here I'll put RSA, and then here we need to specify a few parameters. One is called modulus length. We'll talk more about this later on, but for now I'll just put a random number. Think of this right now as our key size, but we'll come back to it and understand exactly what this is. All right, so it's our key size in bits. Then we need to specify some encoding for the public key and private key that we're going to get. So this is going to return, so I'll say const, let's save the keys that are going to be returned from it. We're going to get an object, so I'll destructure. The first one is going to be the public key, and then the next one will be the private key. Now here we also need to specify the format that we're going to get these two. So I'll say public key encoding. The type here, I'm going to put in SPKI. Let's not worry about this right now. Here we have two options for RSA. One is this, and the other one is, I'll say other option, is PKCS1. All right, this is an older format for this, so SPKI is a newer one, but I'll maybe talk about this later on, but it's not really important. And then the second argument is going to be the format, and here I'll say PEM. Now, the PEM format is a very common extension in cryptography. So if you've ever done SSH, for example, connecting to a server or setting up SSH with your GitHub account, you have for sure downloaded some keys, and the format was most probably .pem. So you have maybe downloaded something like maybe idrsa.pem or your key.pem. Okay, so this .pem, this is a common format that's used to save public keys and private keys and also certificates in the world of cryptography. Okay, so if you were going to set up HTTPS for your server, there is a great chance that you're going to get your certificate in a .pem file and then set it up on your server. We've got some other options as well, but this PEM one is one of the most common ones. Now we need the same thing here for the private key encoding, so I'll say private key encoding. Now the type, here we have two options again. This is the encoding of the private key. One option is PKCS8. And the other option for RSA private key encoding is PKCS1, just like before. But it's more of a legacy format, so let's stick with this for now. And then for the format, I'll put the same thing. We need a PEM file. Okay, without doing anything else, let's just go ahead and log our keys. So I'll log the public key, and I'll also log the private key that was generated. Let's go ahead and run this. I'll navigate to the RSA folder and then node app.js. If you scroll up, here it says begin. So everywhere you see a few dashes and then begin, and then a few dashes and then end, these are PEM files. For example, begin public key or begin private key, and then at the end public key or end private key. Now here in the middle of the key, it seems like it's just some random data, like maybe an AES key, but this is actually not random. There are some numbers hidden inside of it, but we need to decipher it, right? We'll talk more about this later on, but just know that this is not some gibberish, this is not just some random data, and we can actually learn some things from this if we give it to OpenSSL, which we'll do later on. But so far, we have our public and private key. We can go ahead and save them to a file. That's what we would usually do. So let's go ahead and grab the FS module and then save these two keys that we generated. So I'll say fs.write file sync. I'll call this one private.pem, and then the private key is going to be the content, and then fs.write file sync again for the public key. So I'll say public.pem and then the public key. Now to keep our keys the same thing for the following encryptions and decryptions, because we want to do it multiple times, we can go ahead and read them after we have saved them instead of having to generate every single time. So here I'll say const private key pem and then fs.read file sync private.pem, and then I'll do the same thing for the public key. So public key pem fs.read file sync public.pem. So let's first go ahead and generate another key pair and then save them. So now here, if you take a look, we've got the private key and also the public key. Now I'll go ahead and comment this section, and in the subsequent runs, we're just going to read these two files instead of having to generate them every single time. Alright, great. Now with these two keys in place, let's go ahead and do some encryption and decryption. Now, before we go ahead and use it to encrypt and decrypt, we need to first convert these two binary data into an actual key object, right? So a crypto key object. So for that, there's a function on the crypto object called create private key, right? And we also have the same for create public key. Here, all we have to do is give it this binary data, and then it's going to give us a key object format, something that we can then use to encrypt and decrypt. So I'll specify the key, which is here the private key PEM, and the format, which is a PEM file. And I'll do the same here with the public key. So the key is public key PEM, and then the format is same as before. So let's go ahead and save these two. So const private key, and then const public key. So at this point, these two are exactly identical to this that we had previously. So these two are also key object types. And yeah, so we can now go ahead and do some encryption. Let's first have some plain text. And I'll say buffer.from. And then maybe this is my password, which is this. And this is going to be from UTF-8 into binary. And then we have two functions for encryption. Crypto.public encrypt, which, as the name suggests, here we're going to use our public key to encrypt. We also have crypto.private encrypt, and here we're going to use our private key to encrypt. Now, the inverse of these two would be the public decrypt, and then, as you might have guessed it, private decrypt. So depending on which one we use to encrypt, we have to use the other one to reverse the process. So let's go ahead now and do public encrypt. Here we first have to specify our key, which should be a key object. And we already have a key object because we have converted our PEM file into this key object. All right, or this one, this public key right here. So the key is the public key. And after this one, we need to have our plaintext. So I'll specify the plaintext right here. And this is now going to give us the ciphertext. And then I'm going to log this. So console.log the ciphertext. Let's go ahead and run this. Node app.js. And here you can see the ciphertext that we got. Okay. So far so good. Shouldn't be anything too confusing at this point. We just have two keys. We used one of them to encrypt, and now let's use the other one to decrypt. So we have three more functions. I want you to now guess which one we should use to reverse this process and get our plaintext. Hopefully you've guessed it right. We now have to use private decrypt to do the process. So let's go ahead and do it. So I'll say const decrypted data, and then I'll call that function. So crypto.private decrypt. And the format is just like before. We have to specify our key, which is the private key, and then the ciphertext. Let's also log this one. So console.log decrypted data .toString, and I want the UTF-8 format. Okay, now if I go ahead and run this, here you can see that I got my decrypted data. All right, so that's it about RSA in action. Now, if you go ahead and try to, for example, use the public key again to decrypt, for example, say public decrypt, you're going to get an error. So let's try this. And then here I'm going to specify the public key. And now if I run this, it's going to give me an error that it cannot do the decryption process. Okay. It doesn't really know why not, because it has no idea that this ciphertext is as well just some gibberish. It doesn't know that it was encrypted using this. And you have to do private decrypt if you have used public encrypt. I'm going to back up here. Now, I want you to pause the video for a second, play around with this a bit. So maybe do private encrypt or public encrypt, and then try different functions and really make sure that you understand the fact that I mentioned before, that if you encrypt using one of your keys, you can only decrypt using the other one, okay? All right, so let's end this video with one challenge. And the challenge is going to be, let's emulate what we have talked about in the previous video. In the slide that we were talking about, what you and I would do if I have an AES key and I want to send it across to you. All right, so let's do this as a challenge. Let's create two folders here, and we can call them user1, user2, you and I. I'm going to actually go ahead and call one of them client and the other one server. Okay, so the client here would be me, the server would be you, and we are trying to establish a shared AES key so that we can now do our communication encrypted. And both, let's have an app.js. Same here in the server. Now here the client doesn't need to generate any keys, okay? All the client has to do is to reach out to the server, grab the public key, and then encrypt the AES key using the public key and send it to the server. So let's have a few assumptions. Here I'll say this client wants to share an AES key with the server. And also let's imagine that everything that we have here in this folder, so in this client folder, is in the private space of the client, right? For example, the user's laptop or something like that. So if anybody from the outside can access the inside of this client folder, it means that the client was hacked, right? So we're going to imagine this to make it easier for us to understand the problem. Now I'm just going to copy paste the same thing here for the server. And here I'll say this server wants to share an AES key with the client. And then imagine everything in this server folder is in the private space of the server. For example, the server's disk, okay? Or the server's actual computer or something like that. All right, so let's have a basic setup here, and then I'm going to give you this as a challenge to solve this problem of key transport. So let's include the crypto, and then also the FS module, because we're going to write and read our key files. I'm going to go ahead and generate two keys. Let's first destructure and call them private key and public key. And then the generate key function. So generate key pair sync. We'll use the RSA. And then the modulus length. Let's go with 1024 right now. Again, we'll talk way more about this later on and know exactly what we should specify here. And then the public encoding. I'll actually try to fast forward. And then the format, the common PEM file format. And then the same thing now for the private key encoding. And also public key encoding. I'll put the type PK and then CS8. Format the PEM file. And now with these two in place, we can go ahead and do the exact same thing that we did before. Write file sync. Let's write the private. I'm going to call this server-private.pem. The private key. And then server-public.pem for the public key. So we're going to run this once. Server and then app.js. Got a bit of an error here. Private key is not defined. And that's because I forgot to put the K in capital. And now it should work. Okay, so now we have two keys here. And actually they ended up here in the RSA folder because my current working directory is here. And what we could do is to, if you want to run it from there, we can say maybe server and then slash. Okay, or we can resolve the path, but let's just do this. I don't want it to be too complicated. And then let's remove all these four. So I'll select all the PEM files, delete all of them. And now I'll run it from this folder again. I've discussed this in the Unix section, so I'm not going to talk about why that happened. So now we have the keys here inside of the server folder. Okay. Now, as we know, the public key is, well, public, so everybody has access to it. And to emulate that, I'm going to move it to the RSA folder, okay? Because remember, whatever we have inside of this server folder is private to the server and the server only, okay? So the client should not be able to access whatever is inside here. So I'm going to put the key here outside, so now the client can go ahead and read the public key. Okay, so now I'm going to comment out this section now that we have our keys. Now let's go ahead and read the keys. So const private key pem fs.read file sync. Here we need to read it from this folder. So I'll go into the server and then slash server dash private dot pem. And then let's also read the public key. So public key pem equals fs.read file sync. And here, this is going to be in the root RSA folder from which we're going to run the file. So I'll say now server dash public dot pem. All right, now that we have these keys in place, we can go ahead and create key objects. But for now, I'll leave it up to you to do as a challenge. Let's now go to the client and let's generate some amount of data. So let me include this crypto first. And also the FS module. So let's generate maybe 48 bytes of data. I say this is going to be our shared, maybe secret data. The thing that we wish to send over to the server so that we can both run a KDF function on top of it to end up with maybe 256 bits of data, which we can use as our AES key. I'm also going to log this shared secret data. And now let's run that. So node now client app.js. So this is our shared secret. Every time I run it, it's going to be different, of course. But your challenge right now is to go ahead and send this shared secret data over to the server. And you have to assume that you're doing it in clear text. So you need to first encrypt it using whatever server is going to give you, and then send the encrypted data over to the server. So here you're going to read it. So you can say const maybe received shared secret data. And here you can either go ahead and write this to a file, put it here in the RSA folder because it's going to be in the public, and then read that from the server. Or you can just, after you encrypt it, log this one. Actually, let me call this received encrypted shared secret data. Okay, so you can log it after you encrypt it from the client, and then from the console, grab the hex value and put it right here. That's going to be our emulation of sending it over TCP, for example. Or you can write it to a file and then here use the FS module to read it. Okay, and then decrypt it using the keys that you have. So feel free right now to pause the video and give this a shot. If you still have difficulties understanding the problem, I'm going to again move back to the slides to explain it. So here we have the server, and then right here we've got the client. Okay. This is the exact same thing that we discussed in the previous lecture. The server has a private key and also a public key. You do not have these, but instead you have an AES key or some data. So I'll just call it secret data. And you need to now securely send this secret data through this channel over to the server, so that whoever is listening to this conversation would not have any idea whatsoever what is going on. Okay? So go ahead and take this as a challenge, and I'll see you in a bit, and I'm going to show you my solution. Alright, hopefully you've managed it, and here's how I'm going to do it. So at this point, what I need to do is to grab the server public key. So I'll say fs.read file sync. And then I'll say server-public.pem. Remember that we cannot read the private.pem. Technically, we can right now, but we're assuming that whatever we have in these folders are private. Okay, so in the real world, you cannot read the private key of the server, but you can easily read the public key of the server. Okay, so I'm going to save this into server public pem, and then create a key object off of it. So const server public key equals crypto dot create a public key. I'll put in the key. The key is going to be this server public pem. and the format is PEM. Okay, with this in place, we can now go ahead and encrypt this shared secret data. So I'll say const ciphertext equals crypto.public encrypt, and I'll specify my key first. Key is the server public key, and then the plain text, which is the shared secret data. With the ciphertext in place, I'll go ahead and log it as hex. So ciphertext.toString hex. So now I'll go ahead and grab the binary code and put it right here in the server code. Let's first run this. Node client app.js. Here's the encrypted data. I'm going to copy this. And now, well, the client doesn't need to do anything else at this point. So in the server, I'm going to read it. So it's just like as if we're now receiving that encrypted data through TCP or HTTP, for example. So I'll say buffer.from. I'll put in the hex. And I'll also specify the format to convert this one from hexadecimal into binary. With this in place, we can now go on ahead and decrypt it. Remember that the original data that we had was this one, so let's keep track of this. It starts with 05 and then ends with C8. So here I'm going to go ahead and first create a key object from the private key. We do not now need to use this public key to do anything here in the server. So let's go ahead first and create a key object, because that's what crypto.private encrypt. Well, in this case, we need to use private decrypt to do this operation, but that function requires a key object and not just some random binary data like this. So I'll say const private key equals crypto.create private key. Create this from this key, which is the one that we have above. So private key PEM. The format, which is a PEM file. And now we can go ahead and do the decryption. So crypto.private decrypt. I'll specify the key object. So the private key, and then the actual ciphertext. Our ciphertext right now is this received encrypted shared secret data. It's a very long name, but let's type it out. So received encrypted shared secret data. And this is now going to give us the actual shared secret data. Now this one should be now exactly identical to this one. This is what the client generated. So let's go ahead and log this. Console.log shared secret data. And now we should be good to run this server file. So I'll say node server and then app.js. And if I run it, you can see that now we've got exactly the same amount of data that the client generated. But what we did was that we first encrypted it and then sent it from the client over to the server, and the server used its private key to decrypt the ciphertext. Now that we both have this shared secret data, we can go ahead and run the same KDF function on top of it, maybe using SHA-256 to end up with exactly how many bits that we need to use for our AES encryption. Alright, so that's it about this challenge and RSA in action. This is actually what happens if HTTPS is using RSA to do this key transport. But so far, we really don't know how this RSA works. I mean, sure, we can use it, but we don't understand the mathematics behind it. Okay, we don't really quite understand this modulus length right here. We don't quite understand this key object thing, and so many other things that we need to understand about the algorithm to really help us understand the public key cryptography. So in the next video, we're going to dive deep into the actual algorithm behind this to understand what really just happened here in this example. So that's it about this video, and I will see you in the next one. In the previous video, we saw RSA in action with Node.js, and we did some encryption and decryption. In this video, we're going to understand the algorithm behind RSA. We're going to do some encryption and decryption on paper ourselves, and after this video, you're going to have a much better understanding of public key cryptography. So let's first discuss what exactly these two PEM files contain. When we look at them here on the screen, it seems like that it's just gibberish, some random data, but it's actually something that we can decipher with OpenSSL. So let's first take a look at the public PEM file that we've got, and then we'll take a look at the private one. So let's go to our terminal and make sure that we have the OpenSSL command available, okay? Now, to decipher these PEM files, I'm going to type OpenSSL and then say RSA, because it's an RSA key. Then I'll say -pub_n. So this pub stands for public, and this means that I'm about to give it a public RSA key. And then I'll give it the input, so -n, meaning the input, and then the PEM file, which should be here in the RSA folder, and then server-public.pem. And then I'll say -text to see the output in text. Now, if I run this, so here's the actual PEM file, and then here's the deciphered content. So this is exactly what this is containing. All right. Now, to clean this up a little bit, to not see the PEM file, we can also give it the no out option here. And with this, we're only going to see the deciphered content and not the actual PEM file. So let's take a look here and see what we have. Here on the first line, we can see the length of our key, that is 1024. This is exactly what we specified here when we were generating the keys. So we said 1024 bits. And that's the one right here. And then we have something called modulus, and this is actually a number, all right? The number is displayed in hexadecimal, but if we go ahead and remove the colons and put everything in a single line and then convert it into decimal, we're going to see that it's just a number, but this number is quite large, all right? It's hundreds of digits in length. Now, moving on, we have one more thing that's called our exponent. This is usually 65537, and we'll discuss this later on. All right, so far we know that our public key only contains these two numbers, one called modulus and the other one called exponent. All right, let's now go ahead and take a look at our private key. We will in just a bit understand exactly how these numbers are generated and why are we going with them. Now, to decipher an RSA private key, we can use this command. So OpenSSL, again, RSA, and then -input, and here I'm just going to specify the private key. So I'll go into my server folder and then server-private.pem, and then I'll say -text and then -no output to not see the PEM content and only see the actual numbers. I'm going to clear my terminal and then run it. And let's scroll up. So here, again, we see that we have the size of our key, which is, again, 1024. Then the modulus, this is exactly what we saw in the public key. And then here we have something called public exponent. This is also exactly what we saw in the public key. Then we have something called a private exponent, then two prime numbers, so prime 1 and prime 2, these two were randomly generated, and then we have three more things at the bottom. Now, these don't have to do with the RSA logic, they are just here for optimization purposes, so these three will speed up our RSA encryption and decryption. If we really want to understand how RSA works, we only need to focus on these numbers above. So the prime numbers, these two exponents, and then the modulus. All right, so that's it. That's what our RSA keys contain, just some numbers. And with these numbers, we're going to now do our encryption and decryption. Again, all these numbers here except this public exponent, so this one, they are all displayed in hexadecimal. This is of course in decimal, and here's the hexadecimal format of this number. And if you again want to convert them into decimal, just copy them, remove all the colons, and there you go. All right, let's now go to our whiteboard. All right, so now I am here in my whiteboard, and let's have one example first. Let's say that you and I want to communicate together. So I'll give you a private space right here, kind of like what we had in our slides before. So this is you, and no one from the outside internet can access your private space right here. If someone can do it, it means that you are hacked. Now I will also give myself some space, and I'll give myself just a bit more space because I want to do some math here. So this is me, and this is you, and your goal is to send me this message. So let's put some bits, 0, 1, 1, 1 maybe, and then 1, 1, 1, 0. And then let's imagine that we have a TCP connection here between us. This is in clear text. All right, so our goal is that you are going to send me this bit of data right here in clear text. So we have to make sure that this is encrypted first, and then I'm going to get it and decrypt it. And because we're going to both end up with the same data, we can both run the same KDF function on top of it to end up with the same AES key, so that now we can encrypt all of our communication through here. All right, let's see how we can solve this problem. Now we're talking about RSA. So the first step in RSA is that we need to generate two prime numbers. So I'll say prime 1. And for this one, let's pick 307. And then for prime 2, for this one, let's pick 311. Both of these are prime numbers. In reality, we're going to pick very large ones, but because now we're trying to do it on paper, let's pick simple ones so that we can do the calculations, but the logic is going to be exactly identical. Now, I also recommend that you grab a paper and pencil and do the exact same operations that I'm doing. I'm going to give you a challenge afterwards, so you're supposed to do the math yourself too, and you'll see how easy it is, right? RSA is very easy to understand, and using just some basic math, we can do this encryption process. All right, so once we have picked our two prime numbers, well, we're not going to actually pick them from a poll or something, we're going to generate them. So kind of like when we randomly generate bits, we're going to do the same thing, but after we do that, we're going to check if it's a prime or not. If it is not, we're going to continue generating until at one point we end up with a prime number, okay? So once we have these two, we're going to calculate something called modulus. Now, all that modulus is the result of the two prime numbers multiplied together. So let's go ahead and calculate this. So I'll say 307 times 311. I'm going to plug this into my calculator. 307 times 311. And the result is 95,477. So 95,000. I will also put these dividers in my numbers to make them more readable. All right, once we have this modulus in place, we need to calculate yet another number. This one is called phi, all right, PHI. We're going to call it PHI to keep it simple. And to calculate this one, we have to subtract 1 from both of our prime numbers and then multiply them together. So let's do that. Here I'll say 307 minus 1, and then this one times 311 minus 1, and the result, let's go ahead and plug it into our calculator. So this is going to be 306 times 310, which is 94,000 and then 860. All right, great. So with these two numbers in place, I need to calculate one other number here in my private space. And this one is called the private exponent. To calculate this one, what we need to do is I'm going to zoom in a little bit here in my space. So I'm going to write here private exponent. And it's also referred to as simply d, so I'll put this d in parentheses. Now this modulus here is also mainly referred to as number n. Okay, so I'll also put that here. Now this phi number, this is actually a function, so if you open up a textbook and try to read about RSA, you'll see this referred to as this. So this symbol right here, this is a function, so phi of n, this n is our modulus, and all it means is that if you say phi of 95,000 and then 477, what that means is to take that number, divide it up, find out the two prime numbers that were multiplied together to end up with this. Once you factor it, subtract one from each, and then multiply them together, and that's going to be our result. So this is why this is called phi, and it's just a function like that. And that's as far as I'm going to talk about it. I'm deliberately trying to stay away from using mathematical syntax here, but not simplifying the logic, okay? We're going to stick with JavaScript and simple math syntaxes just to make sure that it's very easy to understand. But all these also have fancy mathematical syntaxes, which is something that we're not going to talk about. Okay, so now let's talk about the private exponent here. Well, we first need to calculate one other number, and this other number, we're going to put it in public, all right? So this private exponent here, this one is still going to be in the private space, but here, let me scroll up a little bit. Here in the public space, we're going to put in two numbers. First, we're going to put in our modulus, which is n. So let me put the number here. This is going to be now my public key. So I'll first put in the modulus, which is 95,000, and then 477. Then we need to have another number, and this one is called number e, or public exponent. So let me write that right here. So our public exponent. Now, for this number, we need to pick something so that it's smaller than our phi right here. And also, the greatest common divisor of phi and e should be 1. A very common choice for this e, we have multiple things that we can pick for as long as we stick with those two things, is 65,000 and then 537. Now, I'm going to talk about in a bit why this is a very common option to choose for our public exponent. But for now, let's go with this. And then once we have the public exponent, we're going to use it to generate our private exponent. Right? These two are kind of the inverse of each other, and we're going to talk about that in a bit. So if we use this public exponent here to encrypt, we have to use the private exponent here to decrypt. Right? And we're going to keep one of them private and one of them public. Now, to calculate the private exponent, we need to find a number such that if we multiply that number by our number e, so our public exponent, which we chose 65,000 for it, so this multiplied by d, and then its remainder by the phi number that we already have, this should equal to, and I'm going to use JavaScript equal sign, this should equal to 1. We already have our phi, we also have our e, so we just need to figure out what to pick right here. We only have one option, so we don't have multiple answers, we only have one answer. We're going to use our calculator to do it. Doing it by hand could be a little difficult. We need to use the extended Euclidean algorithm to calculate this, which is something that we're not going to talk about. It could be a little too much math. So I'm going to show you how to do it using a calculator, using Python specifically. It's very straightforward. So what we need to do is to find out what number, if we multiply that by 65 and then 537, and then get its remainder by our phi, which is 94 and then 860. So what number should we pick so that the result of this operation is going to be 1? So here I'll say d equals, and let's now go to Python and see how we can do this. Alright, so here I have a Python file, calc.py. If you want, feel free to use this online-python.com IDE here. Both will work just fine. So here I have written a piece of comment, and the way that we're going to calculate our d is using the pal function. Right here I have one example. So what we need to calculate here is called the modular inverse, okay? And all it means is that we need to find that what number, so that when we multiply this by arg1 and then get its remainder by arg3, we get 1. All right, so if we put the second argument here as -1, that's what it means. So our public exponent was 65,000 and then 537, okay? And then here I'm going to put in our fee. If you recall, our fee was 94,000 and then 860. And that's it. Now, if I don't put in a -1 here, so if I here put in a positive number, it's going to, for example, if I put in 2, it's going to take this, raise it to the power of the second argument here, and then get its remainder by this one, all right? And this is called modular exponentiation, okay? So the same function, but depending on what we put here in the second argument, it's going to work very differently. All right, so this is what we need to do right now to calculate our private exponent. So I'm also going to print x here at the end. So let's go ahead and run this. Let me make sure that I put in the numbers correctly. So this one is correct, and my fee number, if I take a look here, well, actually it should be 860, okay? And now let's go ahead and run this. So Python 3calc.py. And now we get this number, 54953. So let's go back to the whiteboard, and I'm going to write it right here. So 54 and then 953. All right, let me make these a little smaller here. All right, so at this point, we have calculated all the numbers that we need, and we're now ready to do the encryption and decryption. I'm going to highlight a few things here. We have, again, our two prime numbers that are very important. We have our modulus, which is the result of those two. Now, I'm not going to highlight this phi one right here because we only use it to calculate our e right here and also to calculate our private exponent. We're not going to save the phi anywhere. We're going to get rid of it once we have these two numbers. But these are our main important numbers in RSA. Two prime numbers, one modulus, and two exponents. One a private exponent and one a public exponent. Here's how we would do the encryption and decryption. It's very straightforward. I'm going to zoom in a little bit here and write in these two formulas. So we're going to take our data. This data could be a plain text or a ciphertext, depending on if we want to encrypt or decrypt. And if we want to use our public key to do this encryption or decryption, we're going to raise it to the power of e. And remember, our e is right here. And then we're going to get its remainder by our n, all right, our modulus, which is right here. And that's it. If we put a plain text right here for our data, we're going to get a ciphertext. If we put a ciphertext here in our data that was encrypted using the private key, we're going to get the plain text. Now, if we want to use the private key to do either encryption or decryption, again, we're going to take our data, raise it to the power of d, and then get its remainder by n. It's very straightforward, and that's the whole thing behind RSA. This is how we now generate our keys and encrypt and decrypt. And as you can see right now, it's very straightforward. So let's go ahead now and see how you right here can use my public key to encrypt your plaintext, send it over here in this clear communication channel, and then I'm going to use my private key to decrypt it. Again, I want you to pay attention to something right here, that I will never ever let my two prime numbers here to leave my private space. I will also never allow my private exponent to leave my private space. The only two things that I'm going to put out there are the modulus and also the public exponent. And that's it. If you ever were to get your hands on my private exponent right here, it means that you have hacked me. All right, so this is something that we should never ever allow to happen. All right, now let's do the decryption. I'm going to first convert this binary number to a decimal number. So I'll put this into my calculator right here, 0111 and then 1110. This is 126 in decimal. So let's now do the actual encryption. So you are going to take 216, raise it to the power of e. So the e is 65 and then 537. And then get its remainder by n. So n is 95 and then 477, which is right here. Now, remember that I have put these two numbers here in public, so you can easily go ahead and retrieve them at any point that you want. So let's go ahead and calculate this. I'm going to move it a little bit here to this location. And let's go back to the Python code to calculate this number. So here I'll put in the plain text, which is 126. And here again, remember, if we put in a positive number, we're going to raise this one to the power of this one. And here I'm going to put in the E number, which is 65537. And then here I'm going to put in the modulus, which is 95,000 and then 477. Let's go ahead and run this. And I get this number, 65,956. Now, this is our ciphertext. So let's go back here to the whiteboard, and I'm going to write that number right here. So we got 65,000 and then 956. So now you have encrypted the data. So all you have to do is to go ahead and send it over through this clear communication channel. So let's create a copy of it. So you're going to send this ciphertext through this TCP channel. Hundreds of people are now going to grab it, but they have no idea what it means. I'm going to grab it right here, and now let me decrypt it. So to decrypt this, all I have to do is again use this formula. So I need to now raise this to the power of my private exponent, which is 54, and then 953, then get its remainder by the modulus, which is 95,000, and then 477. So now let's plug this into our calculator. So here I'm back in Python. Here I'm going to put in the ciphertext, which is 65 and then 956. Here I'll put in my private exponent, which is 54 and then 953. And then here I'll leave the modulus the same because it's the same in both our private and public key. And now let me go ahead and run it. And as you can see, we got our plaintext. So 126. So I'll go back here to the whiteboard and write that down. So let's see if our math checks out. So the plaintext here was 126, and I also ended up here with 126. And we transferred our ciphertext over this channel. And that's it about the mathematics behind RSA. This is how RSA works. It's very straightforward. All we need to do is to have these two prime numbers, calculate our modulus and our phi. We're going to use our phi to calculate our exponents, and then we're going to get rid of it. And to encrypt and decrypt, all that we're going to do is to use one of these formulas, depending on if we want to use our private or public key. Now, you might be wondering, is this really secure? And the answer is yes, 100% if we choose large prime numbers. Right now, our n is very small. So if you want to break RSA, all you have to do is take the modulus, which is public, and you have to figure out what were the two prime numbers that were multiplied together to end up with that final modulus. And that's it. If we can do that, you can really wreak havoc on the internet. So that is not an easy operation to do. In reality, this number is going to be hundreds of digits in length, and trying to find out what were the two prime numbers that were multiplied together to give us that number, that will take us many, many years, okay? Trillions of years, believe it or not. So this is not an easy thing to do. And in fact, RSA has never been broken. And it's quite fascinating. It's some very simple math, as you can see right now. We're just multiplying, raising to the power of something, and calculating remainders, or this modulus. And that's all that we're doing here. And yet, it is so incredibly secure. Now, I want to ask you one quick question, and you should be able to answer it. Here you can see that I was the one who generated both of these keys, and you are the one who was going to send me this plaintext. Now, my question is, what if you that want to send this plaintext also go ahead and generate your RSA keys? So I'm not going to generate anything, but you are going to do it. Do you think we're still going to be able to do this operation? And the answer is that no, we won't be able to do it. So if you go ahead and generate your private and public keys, let's see what's going to happen. If you want to now encrypt your plaintext, using your public key, and then you put it out there, I'll get your encrypted data here, but I cannot decrypt it because I don't have access to your private key. So you can't do this operation by starting the encryption with your public key. Now, what if you encrypt it with your private key? Now, if you encrypt this plaintext with your private key and you put it here in the clear text communication channel, everybody out there has access to your public key. Therefore, they will be able to immediately decrypt the data. All right, so if our problem is that you want to send me some amount of data securely, I have to be the one who's going to generate these keys, okay? All right, so let's go back here to our terminal and take a look at those two keys that we had. So I'm going to go back to this command to take a look at the private key first. If I scroll up, we now know what the modulus is. We also know what the public exponent is and also what is the private exponent. And the two prime numbers that were generated. Now again, these last three are for optimization purposes, so we're not going to talk about it. Maybe in an optional video we're going to dive deep into them, but not right now. Let's also now take a look at the public key right here. Here we have the modulus, which is the exact same thing as this one right here, the result of the two prime numbers added together, and here's our public exponent. And that's it. That's it about RSA and how we can do encryption and decryption. Now let's go ahead and take a look at some real-world examples. Here I'm going to open up my Firefox. I'm going to go to the CRA website, which is the Canada Revenue Agency website. This is a government website. It's very secure. And let's take a look at its certificate and see what is its public key. So here I'm going to click on this log icon, then click on Connection Secure, and here I'll click on More Information. So here I'm going to click on View Certificate. Now we're going to talk about what exactly a certificate is. For now, just think of it as a file that also contains our public key. All right, so the public key that we use to do this key exchange or key transport, that is embedded here in these certificates. And if you want, you can go ahead and download it. So here, let's scroll down a little bit, and here's where the public key info is mentioned. So it says that the algorithm used is RSA. The key size is 2048. In our example, we went with 1024. Here it's using double the size, which means that it's more secure. The exponent is the same thing that we had, 65,000 and then 537. And here's the modulus. All right, you have to click on it to expand it. And this is the large number that is the result of two prime numbers multiplied together. If I can now go ahead and factor out this number, I can break this website. So this is not an easy operation to do. Now, you can do this with many other websites. I went with this because government websites usually use RSA because they're kind of old. And usually nowadays we use elliptic curve, but RSA is perfectly secure right now. The reason that we might want to use elliptic curve is again because of speed and something else that we're going to talk about later on. So you can do the same thing by going into IRS website. And if you click on here and take a look at the actual certificate, so I'll click on this. And then I'm going to scroll down here to find the public key, which should be somewhere right here. There we go. It is using the exact same algorithm with the exact same key size, and this is the modulus used by this website. Now, maybe by the time that you're watching this, if you go to these websites, they might not use RSA. Instead, they might use maybe elliptic curve. So for example, if I go to google.com and take a look at this one's certificate, here, if I scroll down, here for the public key, it is using elliptic curve, all right? And if you take a look here, the key size is way smaller. That's what makes it faster compared to RSA. Now again, there's something else that we need to discuss. That is, how do I now make sure that this public key really belongs to IRS or CRA? Okay, and this is the topic that we're going to talk about in just a bit in one of the future lectures. For that, we have to understand digital signatures. And once we understand digital signatures, we will then understand how exactly this public key right here is used. Now, this is not used to do the actual key transport like we talked about. That's what used to happen in older versions of HTTPS. but nowadays that is deprecated. So a couple of years ago, what used to happen was that you would still get this certificate with this RSA public key, but then you would use it to do an actual key transport like we talked about. So you would generate as a client some amount of bytes, and then you would raise that to the power of the exponent, the public exponent, and get its remainder by the modulus. The result will be the ciphertext. You will then transfer it over in TCP, so in clear text. The server will get it and then raise it to the power of its own private exponent and then get its remainder by the modulus. And just like that, you both have access to the same shared data that you can both now use to generate, for example, an AES key. So this is how it was usually done before. Nowadays, this is used for calculating a digital signature, which is something that we're going to dive deep into later on, but that's still the same idea. So we're still doing encryption and decryption in signatures, but we will also bring a hash into play, all right? So the mathematical logic there is also identical to what we've discussed, okay? But we're going to dive deep into it again later on and not right now. For now, let's try to understand the core concepts of RSA, and then we're going to be in a much better position to tackle the rest of the topics. All right, so let's wrap up and do one final challenge. So now I'm going to give you a few numbers, and I want you to go ahead and calculate the modulus and do some encryption and decryption. But before we do that, make sure to take a screenshot of this. You do not need to memorize how RSA works. For as long as you have this one, you should be good to go. You can also download this from the resource section of this video in case you cannot take a screenshot. And here's just exactly what I talked about. So you first have to generate two prime numbers, calculate the modulus, calculate the phi, which you're then going to use to calculate the two exponents. And then you'll put only the modulus and the public exponents in the public key and keep the rest in the private key. And to encrypt and decrypt, you're going to use one of these two formulas. So you would either raise to the power of E or D, and then get the modulus or the remainder by N. And that's it. All right, so here's the challenge. Imagine you and I are right here, and you want to now send me this amount of data over in clear text. I have already generated two prime numbers for you. So go ahead now, pause the video, and calculate the modulus, which is N, the phi number, and then the private exponent, and then encrypt this data, send it over, decrypt it right here, and whatever you get, the decrypted data should be exactly identical to this plain text right here. So grab a piece of paper and a pencil, give this a shot, and I'll see you in a bit. All right, hopefully you've managed it. I'm not going to do it from scratch. I'm just going to show you the final answers. So all your numbers should exactly match with what I have right here. Okay, you don't have a second option. Your D can only be this, your N can only be this, same with the rest. All right, you have control over the two prime numbers and the E that you want to pick, but once you pick these three, for each of the rest, you only have one solution that you need to find. All right, that's it about the RSA algorithm. Next up, we're going to try to implement this in Node from scratch and make sure that we get the same output as we would get when we use the crypto module to encrypt and decrypt using RSA. So that's it about this video, and I'll see you in the next one. Now that we have a pretty good understanding of the RSA algorithm, in this video we're going to implement RSA from scratch and get the same output that we would get here by using the Node.js crypto module or by using the OpenSSL library. Well, the Node crypto module is just based on OpenSSL, so it shouldn't matter. We should get the same result in both. And what we're trying to achieve is, so let's create one file here in the RSA folder. Let's call it simply rsa.js. And then what we're trying to do is to read three numbers, prime 1 and prime 2. And finally, we need to read the public exponent. And this one is, well, by default, 65537. And these other two, we're going to read them by generating a key pair and then deciphering that with the OpenSSL library. And by just having these three things, we should then be able to calculate the modulus, the private exponent, and also encrypt and decrypt so that we would get the same ciphertext as we would get by doing an encryption right here. So let's do one example. Let me actually comment this section. So we're not going to do this shared secret right now. And let's also generate a new keeper, and this time go with a very small length. So here I'm going to put in 512. We're going to do it this way to keep our numbers small so that we can now copy paste. And later on, we're going to try a larger number, 2048 for example, to see what's going to happen. And then once we have the keys, here we're going to do one encryption. So let's define a plain text. And I'm going to put something here in hex. So let's go ahead and figure something out. So here in my node REPL, I'll say buffer.from and maybe one message. So this is some text. And let's convert this one to hex. And then I'll grab the hex value. And I'm going to go ahead and copy this and paste it here in the plain text. And I'll say plain text hex. I'll explain in a minute why I'm doing this. I'll also add a comment here that this is some text. All right. Now, after having this, let's do an encrypt. So I'll say const cipher text equals crypto dot public encrypt. I'll give it the key and then the plain text. So once we have this, let's also create the plain text buffer. So plain text equals buffer dot from the plain text hex. Okay, now that we have the binary data, I'm feeding it to the public encrypt function, and it's going to encrypt it and give me this ciphertext. And now that we have this, let's go ahead and log it. So console.log ciphertext.toString hex. I'll now go ahead and run this. This is in my server folder and then app.js. Actually, we need to specify not just the key here. I need to specify the public key, all right? Which we should have. Well, where is it? Here. So I should say here, private key. I'll run this one more time, and there we go. So this is the ciphertext that we get, and to make it a little easier to distinguish, I'll say the ciphertext is this. Every time I run it, I'm going to get a different result right now for two reasons. One is that, well, we're generating a new keeper. So let's first not do this. I'm going to now comment this section and then uncomment this part. And I'm also going to move the part where we're reading the key. So we have it here. Actually, let me clean up a little bit here. So I'll move this one up in this location. And then read the public key like we did here. So I'll say const public key is equal to crypto.create public key. The key is the private key PEM, and the format is a PEM file. Actually, here it should be public key PEM because we are creating a public key. I shouldn't have put the private key here because we're doing a public encrypt. So this one should be public key. So now it should work fine and we get the ciphertext, but now we're reading our key instead of generating it every single time. Now I'm going to run this a few more times, and you can see that every time that I run it, I get a different ciphertext. Now the reason that we're doing this, well, the math is solid. It's just like what we've discussed before. But what's happening right now is that the Node Crypto module, or OpenSSL, is by default using some random data before encrypting it. So just like in AES that we were using an IV vector, and we had to use an IV vector to introduce some random data into our encryption. Otherwise, the same piece of data will always end up having the same ciphertext, which we know is a big problem. So RSA is doing the same thing here, but it's doing it behind the scenes, and we don't need to worry about it. Okay, so it will itself generate some random data and then somehow append that to our plaintext. Now, we're not really going to talk about how this padding thing works. That's really as far as I'm going to talk about it. Just know that we have some random data and we add it into the plaintext. It's nothing too complex. It's quite straightforward. And if you scroll down here, where we are doing our public encrypt, we have an option to specify this padding. So I'm actually going to change this back to this option where we specifically specify the key. And then as another parameter here, we can specify the padding. We can specify what padding mechanism it should use, or if it should use any. We can also specify that no padding should be used. Now, I'm going to go with the no padding option right now because, well, we're not going to implement this padding mechanism here in our code. It could be a little too much, and well, it's not really anything too important. So I'm going to specify number 3 here, meaning no padding. Now, if I run this, it is going to give me an error that our data is too small. Because if we don't use any padding, our data size should be something that would work nicely with our modulus length. All right. So right now we have how much data? We have 34 characters. So 34 times 4. We have 136 bits of data. So let's change this to be exactly this much. So what I'm going to do is to generate, let's see how many bytes 512 bits is. So 512 divided by 8. This is 64 bytes of data. So we need to have 64 bytes of data here. And we can just keep adding on zeros here until this is 64. But it could be a little tedious to do it. And if we want to change our plaintext, then we need to calculate again how many zeros to add in right here. So I'm going to use the buffer module to handle this one. So let's say const plaintext, and this one is buffer.alloc 64. So now we have exactly 64 bytes of data here, and all that we need to do now, it's all zero filled. We need to write this plaintext hex at the ends of the buffer, so that we would end up with a format like this, but something that's exactly 64 bytes or 512 bits, so that we can do this operation without using any paddings. Now this should be fairly easy to do. All we have to do is say plaintext.write, and then specify our plaintext hex. We need to specify an offset, which we're going to calculate in a bit. And here are the formats that I'm going to say hex. All right, so this thing that we're going to write to our buffer is in hexadecimal format. Now for our offset, we need to just add in 64 right here, and then minus the size of this hexadecimal value. So let's use the buffer module again to get the size of that. So I'll say buffer.byte length, and I'll give it the plaintext hex and say that the format is in hex. And that's it. Let me just log the plaintext here in hexadecimal, just so that we see what we're dealing with. Now, before I run this, let me also fix my public key right here. So we wrote it to this path before, but now we're reading it from the RSA folder here. So let me add in, let's go to the server and then server-public. I'm going to delete this one. So now we only have these two keys in the server folder. Now if I run this, so here we can see the plaintext. All that we did was that we took our data and added in some zeros before it. So now it's going to work well with RSA with no padding. And this is our ciphertext. And if I run this multiple times, I always get the same ciphertext because now we're not adding any random data whatsoever into our plaintext before we encrypt it. All right, so with this setup in place, let's now go ahead and implement RSA from scratch right here so that we would get the same ciphertext as we would get here by encrypting it with the same keys. We're not going to read the keys here from this file. We're going to actually give them to OpenSSL to decipher, and then we're going to read the prime numbers. So I'll run it one more time to keep this as reference, and then I'll use the OpenSSL command to decipher our private key. So I'll specify my input file. We need to go into server and then server-private and then -text -no out. And there we go. So you can see that the numbers are quite small right now. So let's copy prime1 and prime2. Here I'm going to create a new tab. I'll paste that here, and let me remove all the colons. So I'll search for all of them and then replace with nothing, and then put them in a single line like this. And now I'm going to copy this one. I'll paste it here, and then I'll copy this one and then paste it right here. Now, please download the starter.zip file from the resource section of this video, because I'm going to give you two functions. I'm not going to explain how they work, but we're going to use them to do the modular exponentiation and also modular inverse. So I'm going to paste a piece of code here. And, well, you don't need to understand this. This really has nothing to do with JavaScript or Node.js. If you have difficulties understanding this code, we're just implementing some theoretical math, okay? So the syntax is fairly straightforward. We're doing quite a bit of bitwise operations, but the actual thing that we're doing in terms of Node or JavaScript is something simple. All that I want you to know is that this works like the pow function in Python, all right? So we give it a base and an exponent and our modular, and here, if our exponent is larger than 0, so if it's positive, it's going to give us this output, all right? So it's going to calculate this power and then get its remainder by arg3. The reason that we can't just simply do this, so read arg1 and arg2, and then say arg1 to the power of arg2, and then its remainder by arg3. So you might be thinking, why don't we just do this? Well, we could, but this is way slower compared to this one. Here we're using a technique in math called square and multiply, which I'm not going to talk about, maybe in an optional video after I have published this remaining part of the section. But for now, all that I want you to know is that this will give us the result of this one. But it's just miles faster than trying to do this power first, and then after we calculate the whole thing, get its modulus by this. All right, this is very slow. You can try it if you want, and it would only work with small prime numbers. Right now, we're dealing with real-world prime numbers, and trying to calculate them in a naive way is not going to work. We have very large prime numbers, and we need an efficient way to deal with them. So that's as far as I want to talk about this. If you know how to use the pow function in Python, well, this is the same thing. So let's just collapse this one, and we're not going to ever talk about what we have inside of it. We also have this GCD function that's going to calculate the greatest common divisor, and that's it. I'm not, again, going to talk about it any more than this. I wish we would get these two right out of the box here in Node, like we do in Python. Well, that's not the case, so we have to do it this way. Of course, you can install some NPM packages to get access to these functions, but I just want to keep it simple and not clutter our workspace. So please just download the starter.zip file and copy-paste these two functions. Now, if you want to use an NPM package, here we go. There's this thing called JSBN, short for big number. And with this, you can do all those operations that I just mentioned. So here, if you scroll down, here, for example, we can do mod pow. And then here we can do modular inverse, which is the same thing as using the pow function with a negative value as its second argument. And here's also the GCD function, all right? So if you want, feel free to download this one. It doesn't have any dependencies, but I'm going to just keep it simple and go with these two functions. But please remember that you don't need to understand what we have inside of them. If you don't want to even do this, you can use Python, pow, and also GCD. So these two functions to do those operations, okay? And then copy-paste the result from here over to your Node code. Anyways, so now that we have these two, let's write two more functions that we're going to use to deal with big numbers. I'll call this one hex to big int, because we have to convert our numbers into this big int type. Before dealing with them, it's going to accept a hex value and then return a big int type. In JavaScript, if you just want to do it this way, so we say const a equals a number, you only have a limit, and if you go above that limit, you're not going to get accurate results. But here with this big int, you can go as high as you want. It's, well, a little slower compared to this one, but this is what we have to do if you want to deal with very large numbers. Our numbers are going to be hundreds of digits in length. So we can't save them in a regular JavaScript number format. We have to go with big int. So here in big int, if we give it a hex, it's going to give us this big int type. And also remember, if you don't know it already, in big int, all our numbers end with an n. All right, so this means a big int type. Now our hex needs to start with 0x, but to make it simpler for us, I'm just going to say if hex dot starts with and put in 0x. That's great, just put the hex in the argument. If that is not the case, just add it manually. So we're going to say 0x plus our hex. And here I'll say if no leading 0x is specified, add 1 before converting. Okay, simple enough. And then here, let's have one function to print our big integers. Okay, because we want to print them in hexadecimal, and here it's going to, maybe let's accept a label and then the big number. All right. And here, all that we need to do is to say console.log. I will first put in the label, and then 0x to indicate that we're going to get something in hexadecimal, and then bn.toString 16. So we're going to display the number in base 16, meaning in hexadecimal. All right, with these few functions in place, we can now go ahead and do this operation. What we need to do first is to calculate our private exponent, and for that, we need to first calculate our phi. So here I'll say calculate private exponent, which is also called d. And if you want to do it as a challenge, go for it. You should be able to do it. So calculate modulus and the private exponent, and then encrypt and decrypt. And once you encrypt using the public key, you should get the same output that you saw in your terminal when you encrypt it using server app.js. Right, so your ciphertext should be exactly identical to this. Of course, make sure that you also go with the same plaintext. So let me also do that before you start doing it as a challenge. So here down in the bottom, I'll say const plaintext equals hex to big int. And then I'm going to go ahead and copy paste this value from app.js. We don't need these leading zeros, so let me remove them. And then I'll copy this and then paste it here. So now that you have the plaintext, you should be able to use the POW function to encrypt it. Okay. Right, so pause the video now, give it a shot, and I'll catch you back in a second. All right, hopefully you've managed it, and now I'm going to show you my solution. So let's first calculate phi. As you know, this is prime 1 minus 1, and because we're dealing with big ints, we need to say 1n, and I'll put it in parentheses. I will then multiply this one by prime 2 minus 1. And then with this in place, we can now calculate our private exponent, which is equal to this one. So POW of the public exponent, and then -1, meaning that we want to calculate the modular inverse. And we should say -1n, and then the phi number that we had right here. Now we can calculate the modulus. So const modulus equals prime 1 multiplied by prime 2. Pretty straightforward. And then with these in place, we are now ready to encrypt and decrypt. Let's log whatever we have. So I'll use this function above, print big int. First, let's do prime 1 and prime 1, and then prime 2, and then the fee. We don't really actually need to log the fee, so I'm not going to do it, but instead let's do private exponent and private exponent. Then let's log the modulus, and then the public exponent. Before we do the encryption, let's make sure that we get the same exponent and modulus as we got here in our terminal. So I'm going to create a new tab, and here I'm going to run the RSA file because I want to keep the other logs here in place to do this check. Well, actually, it seems like that I forgot to convert these two into big ints, so let's do that pretty quick. All we have to do is give it to that big int function. So we have hex to big int. Have we used it? Well, only for the plain text, so let's do it pretty quick here. Hex to big int. And then I'll do it again here, hex to big int. And one last time here for this public exponent. Now we can just add in one n here, but to keep it consistent with the ones above, let's do it with the other format. So hex to big int. And I'll add this as a comment so that we know what this number is. And the hexadecimal value of this one, if you go back to the first tab, you should be able to see it. So the public exponent hex value is this. So I'm going to copy it and paste it right here. Okay, so now let me run it one more time. Maybe we have one more error. All right, awesome. So here's what we have now for the private exponent. And if I take a look here, this is the private exponent that was calculated with OpenSSL. It starts with 67 and then ends with FD. In our example, it starts with 67 and ends with FD. All right, so the private exponents match the modulus B2 and then 41 at the end. So let's check right here, B2 and then 41. Amazing. So now that we have all the values in place correctly, we can now do the encryption. So I'm going to scroll down here, and here we're going to now encrypt. As you know, all that we have to do is raise this one to the power of our public exponent, and then get its remainder by this modulus number right here. For that, we can use the pow function. So we'll say const ciphertext equals the pow function, the plaintext, and then the public exponent, and then finally the modulus. Now let's go ahead and log the ciphertext in hex. So I'll say print big int, the label ciphertext, then equals the ciphertext. And just to make sure that the math is correct, let's also decrypt. So here I'll say const decrypted result equals to, again, all we have to do is to take our ciphertext, raise it to the power of the private exponent, and then get its remainder by the modulus. Let's also log this one. Now let's go ahead and run this. So here's the ciphertext. It's 1B and then ends with 56. And here, if we take a look at our ciphertext, you can see that they are exactly identical. So we've managed now to implement RSA from scratch and get the same output that we would get here with the Node crypto module. And you can see that it's fairly straightforward. All that we're doing is to just raise some numbers to the power of something and then get some remainders, and that's pretty much it. Now take your time with this example, try a few more prime numbers, and see that everything should match. Now, I also want you to try it with 1, 0, and -1 plaintexts and see what ciphertext you'd get. As you might have guessed it, your ciphertext is going to be, well, the same thing as the plaintext. Because if you take 1, you raise it to the power of anything, it's still going to be 1, and 1 modulus anything is still 1. Alright. So that's a good example to show you why you should never ever use RSA without padding in production. In general, if you take your plaintext and then you raise it to the power of public exponent, and you end up with a number that is smaller than n, so smaller than the modulus, the result of the remainder, well, is going to be the actual plaintext raised to the power of the public exponent. So doing that modulus has no effect whatsoever in that case. But if you use padding, RSA itself will take care of them behind the scenes, so we'll make sure to add in some amount of data so that the size of the thing, before giving it to a function to encrypt or decrypt, it's going to make sure that it's padded properly so that the size of that thing is going to be identical to the size of the modulus length. Now, one last point, your data always needs to be smaller than the n number, regardless of whether or not you're using padding, okay? So if you go with RSA and you give it some amount of data that's larger than this modulus, it's going to give you an error that your data is too large for this key size. So it's not like AES that you can just encrypt terabytes of data. We can't really do that here with RSA. Now I'm going to try it one more time, but this time with a fairly large key. Now in the real world, you should never ever use this 512. This is a very small key size and it's easily breakable. A good size to go with is 2048. This is fairly large and it's unbreakable as of now. Again, by that, you should know what I mean. I mean, on a supercomputer, if we try to find the answer to this, it's going to take us many, many years. So I'm going to go with this, and then let me comment this section so that we're going to get the new keys. I'll go back to the first tab. I'll run the app.js of the server. And actually, well, again, we need to fix our data to match with this size. So 2048. Let's divide this one by 8. And the answer is 256. So we need to allocate 256 bytes of data. Again, this is in bits. And this is in bytes. And then all that we have to do is to also say 256 right here. And that's it. So it should now work. Let's go ahead and run it. There we go. So now we obviously have way more leading zeros, but that shouldn't be a problem. And here's our ciphertext. It's way bigger now because our numbers are way bigger. And now I'm going to feed that key to OpenSSL again to grab the values. Now, if you take a look now, of course, they're going to be quite large. So let's now go ahead and do what we did before. So I'm going to copy paste prime 1 and prime 2 and clean them up. So here I'll create a new tab. I'll paste them both here. Do some replacing. I'll replace all the columns with nothing. I'll click on this button and then click on replace all. Let's also remove the tabs. And then some manual cleanup. Well, as you've noticed, our numbers are fairly large right now. So let's copy this one, paste it here for prime 1. I'll go ahead and copy the second one, paste it for prime 2. All right, now let's go ahead and do the same operation. So in the second tab, I'm going to run the RSA file again. All right, so let's see what we've got. If you take a look here, this is the ciphertext that we manually calculated. And here's what we've got with the crypto module, and they do match. If we also take a look at the private exponents, all right, here we have, it starts with 0D, ends with A1. And here, our private exponent is, do they match or not? Well, yeah, so D1, and then A1 at the end, D1 here, and then A1 at the end right here. All right, so it also works with large keys, but there's something that I want to mention because I've seen it happen a few times. You might be getting a different private exponent here with the crypto module if you go with a very large modulus length. And the reason is usually because OpenSSL doesn't want the private exponent to get too large, so it's going to do something else to make it a little smaller. So if in your case, you are not seeing that the results match, all you have to do is that your fee number here, after you calculate this one, divide it by the greatest common divisor, so I'll say GCD of these two numbers that you have right here. So this prime 1 as your first argument, and then this prime 2 minus 1 as your second one. All right. Now this is also valid, and this one is actually not called fee anymore. This is now the lambda. It's usually called that. And this is also valid mathematically. With this, everything else is going to be identical. The only difference is that the private exponent is now calculated like this, which is now slightly smaller in size. Alright, so that's just something that I wanted to mention in case you see some discrepancy, and that's usually the case. So divide it by this GCD and you should get the same output as OpenSSL. Now, one last point here, we're using this 3 for the padding, which looks a little weird. It's better to go with the crypto constants, so we have some things here. Let me go to my node REPL, and that includes crypto. And here we have a property called crypto.constants. We have a few of them, and they're just numbers, as you can see right now. For the RSA ones, we used this one, RSA no padding, right, which is number 3. So let me do that here. So crypto.rsa underscore, and then no padding. So here, let's just run it one last time, and this time around, let me read the files instead of generating them. And, well, actually, this one should also be crypto.constants.rsa no padding. So let's run it another time, and there we go. So if you want, you can give it a few more shots and see if all your results are consistent, which they should be. And that's it about implementing RSA from scratch here in Node. So with this in place, you should now feel really comfortable dealing with RSA. You should know exactly what happens in encrypting and in decrypting. In signatures, it's pretty much the same thing, but now we're also going to use a hash. And that topic is coming up next. So that's it about this video, and I will see you in the next one. In this lecture, we're going to discuss digital signatures. This is an important concept in certificates that we're going to discuss later on. And when we talk about signatures, we're mainly talking about either signing or verifying. So signing means to calculate a signature and putting it on a piece of message. And verifying means that another person is going to take your signature along with the message and verify that it was you that put the signature on it, and also that the message was not tampered with. The idea of this is quite similar to signatures in the physical world. So if you sign a contract or something, what you're doing is that you are acknowledging that piece of document. So if you somehow breach it in the future, there could be legal actions taken against you. Now, this is pretty much the same thing here, but it's way more secure, it's mathematically verifiable, and also it's very hard to forge, and some other things that we're going to see. So once you put your digital signature on something, other parties can verify it. So here in our code editor, let's create one folder. Let's call it digital-signatures. And here we're going to have an app.js. And let's say that we have some amount of data. Let's say that this data is that I owe maybe $2,730 to Dylan, with ID maybe this, and payment is due on maybe July 25th, right? So it's about 10 days from now that I'm recording this video. All right, so our goal is that I want to sign this data. So maybe this is some sort of a simple contract in our company or in our organization, and I want to acknowledge that I owe this amount of money to this person, Dylan, which we know exactly who this person is because we know the ID, and you can imagine that we're going to have a database and all that stuff. And also we know the payment due date. All right, so if it's maybe July 30th and I still haven't paid Dylan or the organization can take some legal action against me because I have acknowledged this message right here. All right, I have put my signature on it so that now other people can verify it. So the idea of signing is that I'm going to use my private key to sign this message and then put the message along with my signature out there on the internet, all right, or in any public space that is within our organization, all right? Now, if a third party wants to verify it, they're going to take the signature and also the message and use my public key to verify that I have actually really signed this message. Now, this is used in many different places. If you have maybe gone a place and your landlord sends you a document to electronically sign, what you're doing there is exactly this idea. You're putting your digital signature on it so that now the other entities can verify it. So if you breach that contract, a court or a judge or a lawyer can say that, hey, look, you have signed this message and now you are in breach of it, so that they can now take legal action against you. Now, let's go ahead and see this in Node pretty quick, and then we'll talk about exactly what's happening when you are signing or verifying something. All right, so let's go ahead and include the crypto module here at the top. So const crypto. And then what I'm going to do is to create a private and a public key. All right, just like that we did before. So we're going to have our private key and then the public key. So crypto.generate key pair, and I'll use the sync function. We're going to use RSA to do this verification and signing, and then also I'll specify the modulus length to be equal to maybe 2048. Let me also rename this one to data to sign, and let's also create a buffer out of this one. So buffer.from. And then here's how we would do this sign. So if we want to sign some amount of message, we have a function available to us called createSign. Here we need to specify the algorithm that we're going to use to sign it, and this is the hash algorithm, all right? So I'll say SHA-256, all right, a very common and secure one. And then we're going to have a sign object, which I'll save into this variable. And then we're going to give it the data that we want to sign. So I'll say sign.update, give it that data to sign, and then I'll call the end function to say that I'm now done with feeding it data to sign. All right. Now, once we have our data to sign, we need to create our signature. So const signature. And all that we need to do now is call the sign function on top of this sign object and then give it our private key, because now we're using the private key to sign the message. All right, so I'll add a bit of comment here. Here I'll say me signing a message, all right, because I want to acknowledge this one. You can also imagine that Dylan or our organization is also going to sign it to say that all parties of the contract have agreed to this bit of data right here, okay? And then if somebody wants to verify this, verify that I, for example, have signed this message, here's what they would do. So here I'll say maybe a third party verifying my signature. Now again, I know we don't exactly understand what's going on here. We're going to go into the slides and talk about exactly what is happening here in this create sign. For now, let's just try to see one example. So here, a third party wanting to verify my signature would again take this data. So I'm going to copy paste it, but say data to verify, okay? So I'll just leave it as it was before. I'm not going to change anything about it. And then it's pretty much the same thing as we did here. So we need to create a verify object. So crypto.createVerify. Here we need to again give it the hash algorithm. We used SHA-256, so we need to use the exact same one again. If we use something else, it's not going to work. And then once I have this verify, I'm going to give it the data to verify. So I'll say verify.update. This time around, I'm going to give it data to verify. and then I'll call verify.end. Now again, I know the syntax is a little different. We have this fancy create verify and create sign, but at the end of the day, all that happens is that we're using RSA encryption and decryption along with a hash, all right? And that's it. We can do this from scratch with RSA if we want. In fact, we're going to do it later on. We also need to take care of the paddings, but that's essentially all that's happening here. In the creating our signature, all that I'm doing here is that I'm running this SHA-256 to compute a hash for this message, and then I am encrypting this hash using my private key, and that's it. So the signature, all that this is my encrypted, so I'll say that this is the encrypted digest. All right, and this was encrypted using the private key. So that's all that a signature is. So now you can imagine what's going to happen if we want to verify it. All that we need to do is run the same hash function on top of this data, and then also get this signature and decrypt it using the public key. And if we see that the two results match, it means that the signature is valid. So let's go ahead and do that here. So I have given it the data to verify. And then at this point, we just need to call another function that's called verify and give it the public key to use to do the decryption of the signature, and then also the actual signature that we're going to decrypt. All right, so this is going to be a Boolean value. So I'll say const is valid, and then I'm going to log that value. So console.log is valid. All right. Let's rename this one to is signature valid. Okay. All right, so let's now go ahead and run this. So here I'm going to navigate to the digital signature folder, and then I'll run app.js. Oops, I have a bit of a typo here. I'm calling it sing. It should be sign. And also right here. All right, there we go. So that's all that we're going to see, a simple true or false message. Okay, and that's it. All that we want to know is whether or not the signature is valid. So say that Dylan, let's imagine a case, is going to modify this data, all right? It's going to go to court and say that, hey, look, judge, Joseph doesn't owe me $2,000. He owes me $4,000, all right? So we're going to have this dispute, and the judge wants to verify who is, well, true right here. So if I now go ahead and then run this again, so the judge is going to do this verification again, compute a hash, and then take a look at my signature. This time around, we're going to see false, meaning that the signature is not valid. Okay? Well, actually, the signature itself is valid, but the data that we want to verify is not valid. All right? So the judge can now deduce that, hey, Dylan, you're doing something funny here. All right? There's something wrong with this, and we need to figure it out. So even if a single bit in this message changes, well, we have already talked about the power of the avalanche effect in SHA-256. So you'll know that the hash output is going to be totally different, meaning that we know that our data was modified, all right? Now also, of course, if you use another hash function right here, maybe SHA-512, this is also going to not give us the correct output, okay? So we need to use the exact same algorithm that was used, the same hash algorithm that was used to compute the signature, and also the exact public key that corresponds to this person, all right? So that's it about the idea of signatures here in cryptography. Quite common, they're used in many different places. Now let's now go to our slides and try to visualize exactly what happened right here with this create sign and create verify. All right, so let's have a scenario right here. Let's say that this is you. You've got your private key here in your private space, and also your public key, which is, well, in public. Everybody has access to it. And there's also a message. This could be maybe a contract or a simple message or anything else that you want to sign, so that now other people can verify that you have agreed to this piece of data right here. You're vouching for it. You're saying that, look, I have signed this contract or whatever it is, and I'm going to abide by it as much as I can. So here's how we would now do the signing process. So now I'm talking about specifically signing in this section of the slide. So you're going to take this message, and then you're going to use a hash function. So maybe SHA-256 or SHA-512, but whatever you use, it has to be a secure hash function, all right? So you're going to use this one to calculate a digest. So here you know that the output of this one is just going to be a hash value that's exactly 256 bits in size, all right? So now we have this digest, and then you're going to take the digest. You'll use your private key to encrypt this amount of data, all right? So once you do the process of encryption, you're going to come up with the encrypted digest. And this is actually called your signature. So again, a signature is just your encrypted digest, encrypted using your private key, all right? This would not work if you do this using your public key, and you should be able to see in a bit why. All right, so what you're going to do now is that you will append this signature of yours to this message, all right? So your encrypted digest or your signature. Now, if you just put out your signature without any message whatsoever, this is, well, very useless. Nobody can do anything about it. A signature has to be binded to some amount of data, right? That's the whole point of having signatures. We are computing a hash of some message. So again, a signature on its own without any message is just some gibberish with no meaning. All right, so that's it about signing something here. Now let's talk about verifying it. Let's say that this third person right here, or a company, or whoever this is, wants to verify that you have acknowledged this message. And only this message. So if somebody tampers with this one, we would know 100%. Because we know the security of hash functions, we know how difficult it is to come up with the identical hash output, but with a different message. We know that this has never been done before in SHA-256. So if the message gets tampered with, we would know right away. All right, so here's how we would do this process. This person, to verify the signature, is going to take your message along with your signature and then divide these two. We're going to have the signature here. So let me rename this one to make it a little smaller. And then the actual message. So now they're going to do this process, but now instead of encrypting something, they're going to decrypt it. Okay. So for hashing, it's going to be identical. So the person is going to use the exact same hash function. You can imagine that this SHA-256 is written somewhere here in the message, in the metadata, for example. So they're going to take the algorithm and then compute a hash for it. All right, so I'm going to call this one now computed hash. All right, or computed digest. All right, so this is step 2 of verifying the signature. Taking the message with signature, step 1. Step 2, running this hash algorithm on top of the actual message without the signature. And then step 3 is doing the decryption here for the signature. So the person is going to take your public key and then do the decryption. So they're going to now decrypt this. And the result of this is going to be exactly your digest, because this was your plain text. And now once they do this in reverse, they're going to end up with this digest. Now the final step to verify the signature is to see whether or not these two here match. So if this digest that was calculated after decrypting matches with the digest that was calculated after running this hash function by itself, if these two are exactly identical, it means that the signature was valid. Okay. Again, we right now have one assumption, and that is that we know that this public key really belongs to this entity right here. This would be handled by a third party. For example, if you're using Adobe Sign to sign a document electronically, that Adobe application is going to vouch for these, right? So it's going to say that, hey, this person with this email address has generated this private and public key and signed this document. So now Adobe Sign is going to say that this public key really belongs to this identity right here. So now other people can go on ahead, ask Adobe about the public key of you, and then verify the signature. So this part right here, you can imagine, is going to be in public. This person here does not have control over this area, all right? So this person cannot go on ahead in the future and say, you know what, this public key right here does not belong to me. I have a new public key now. Nope, that's not going to happen, because this was generated by this person with a particular identity. Maybe their identity is only their email address or their domain name, but we know that at that point of time, they used this public key, well actually the private key that corresponds to this one, to sign the message. And we also have access to this one, and the person cannot go on ahead and, well, modify this. We know that once you put something on the internet, it's always going to be there, right? So this is how we would now do this verification process. Now, in the world of HTTPS, this third party here that is going to vouch for different public keys is going to be something called a certificate authority, right? So that third party is going to say that this domain name and this public key are really associated with each other. And if someone else tries to say that, hey, I am actually this identity, but this is now my new public key, we would know it right away. We'll see that later on in the section, but that's it about the idea of digital signatures. We have seen one example right here, but again, we can do this totally from scratch. We can use the RSA public, private, encrypt, and decrypt functions, and also use the crypto.createHash function to do this exact same process. In fact, we're going to do that later on in the section to verify a signature of an HTTPS certificate, just so that you see that, well, there's nothing really complicated going on behind the scenes, right? It's just RSA with hashing. All right, that's it about this video, and I'll see you in the next one. In this lecture, we're going to talk about certificates. A very common format here is an X509 certificate, and this is what you get first when you are establishing an HTTPS connection with someone. As you already know, when we want to set up an encrypted connection with another server, for example, and we're doing it in clear text, what we need to do first is to, well, exchange some public keys. For example, we can grab the public key of the server and then encrypt something and send that over to the server so that now we both have the same AES key. But the problem is, how are we going to get that public key? If we just get a straight public key coming from the server, how do we make sure that it's actually coming from the server and not a man in the middle who is pretending to be the server? All they have to do is to put in the source IP address of that server, and just like that, we have no way to verify if that public key is really coming from the actual server. So with certificates, we can solve this problem. An X09 certificate is just a file, and the public key is embedded in that file. So we're going to get this certificate, and then we'll extract the public key from the certificate, all right? Let's first take a look at some of the key important parts of an X509 certificate. So again, it's just a file, just a PEM file that contains different sections. We're going to focus on some of the important ones. One is the issuer. This is the entity that has issued this certificate, as the name suggests. So this could be the actual server itself in some special cases, which we'll see later on, or it could be issued from something called a certificate authority. We'll talk more about that later on. So we have this one, and we also have the subject. Well, subject is the identity of the server. So here we're going to have the common name of the server, the domain names, some common domain names, for example, and stuff like that, all right? So the identity of the server is here. The main idea of a certificate is to bind a public key to an identity, and we have that identity here in the subject. Then obviously we have the public key, so this is inside of the certificate that we can extract, and also very importantly, we have a signature on the certificate. All right, so this is a digital signature. This is exactly what we've discussed in the previous lecture. But this was done by the issuer and not the subject itself, all right? So if you're trying to communicate with Google.com, the signature that you're going to get on the certificate was not signed by Google.com itself, but rather by the issuer. And the reason that we do this is that we have some certain third parties, so some issuers that we have already said that we trust. So if they put their signature on a certificate, it means that we are now guaranteed that that certificate really belongs to that server, meaning that that public key really belongs to the subject, so that now we can go ahead and set up our shared secret and do encryption. All right, let's go ahead and take a look at one certificate as an example. We can do it here in Firefox, or we can do it in Google Chrome. Let's do it here. And maybe let's try Amazon. All right, so I'll search for Amazon. I'll go to amazon.ca, and let's take a look at its certificate and see what we have. So I'm going to click on this little thing here, and then click on connection is secure, and then I'll click on certificate is valid. All right, here I'll go into details, and then I'll click on export. Let's download the certificate of this website. Let's simplify the name a bit, so I'll say just Amazon-cert. I'll use this cert quite a bit here in this video and section. All I mean is just a certificate, okay? And the format, I'm going to choose this one, which is going to be, well, a .pem file. I'll save it. Now it's in my downloads folder, and I'll move it here in my crypto folder. Let's create one folder called certificates. And then I'll move that file from my downloads. This was called amazon-cert.pem, and I'll move it here over in this current directory. So now we have the PEM file. We have mentioned that the PEM files are very common in cryptography. They are used not only for saving private and public keys, but also for X509 certificates. If we go here and take a look at what we have, it looks quite similar to the private and public keys that we saw, but instead it says begin certificate and end certificate. And also, we're seeing some gibberish here, but again, we can decipher this using OpenSSL. There's some meaningful data here, those sections that we mentioned before, like the subject, the public key. So let's go ahead and take a look at this. Now, there's a command in OpenSSL that we can run to decipher a certificate. We have to say OpenSSL X509, and then the input, so I'll say -n, the Amazon cert, and then -text -no out, so we're not going to see the PEM file itself. So let's run this. I'll scroll all the way up. Let me zoom out a bit. Now let's try to take a look at some of those sections that we've mentioned. Here's the certificate. We have a version, so we've got a whole lot of stuff here, but all we again worry about are those core points, okay? So one is the actual issuer. This one was signed by DigiCert, as you can see right here. And if you take a look here in the subject, so the identity of the server, it clearly says it's amazon.ca, okay? We also have something called validity, but again, quite straightforward. If you get a certificate that is outside of this time range, of course, Google Chrome or your browser is going to show you a warning that this certificate is no longer valid. So we've got some stuff like this that is quite straightforward to understand, but we're not going to really focus on it. Now, if we scroll down here, it says subject public key info. So here's where we're getting the public key. Amazon right now uses RSA to do the key transport, and the public key here you can see the modulus and also the exponent. So we can see the complete public key of Amazon here inside of the certificate. Now let's scroll down. We've got some extensions here, but we're not going to really worry about them. So let's scroll down and take a look at one of the most important parts, which is the signature. All right, this is all the way at the end of the certificate, okay? Now you'll also see some other signatures here, but these are not something that we're going to worry about. This last signature, this is the one that's very important, okay? It says that the signature was done using SHA-256 with RSA, okay? This was signed and put here by the issuer, which is DigiCert, okay? And if you want to verify that this certificate is valid, you're going to reach out to DigiCert, grab this one's public key, and then do exactly what we did in the previous lecture. You're going to manually verify the signature itself. So you're going to hash the certificate starting from the beginning up until this point. All right, so you're going to divide this one. So you have the actual content, the message, and then the signature. You'll compute a hash from this message using SHA-256, and then you'll decrypt this signature with RSA and using the public key of this issuer right here. All right, and if you see two hashes that match, it means that the certificate is valid and it's not coming from a man in the middle. Now, you might be asking, so now how do we verify the certificate that we're going to get from the DigiCert itself? Because DigiCert also is going to give us a certificate with the public key inside of it. And this is where we need to put our trust somewhere. And we usually put it in the hands of the company that has manufactured your device. So on your device right now, on the MacBooks, laptops, Android devices, whatever you have, if you can have an HTTPS connection to a server, it means that some of these issuers were installed on your device offline. So this process of verifying the signature is not done online. Once you get the certificate, you're going to reach out to your disk, grab the certificate of this one, and actually not this one itself, but something called a root CA, and then using that, you're going to verify the signature. So this is where the idea of certificate authorities come into play. That with these, we can verify other certificates. And there's a very special type of a certificate authority that we need to understand, and that is called a root certificate authority. In a root certificate authority, the issuer and the subject are identical. So the CA itself has calculated a signature and put it on the certificate. So everywhere you see this, it means that it's a root CA certificate. And if you get an X509 certificate that was signed eventually by a root CA, you're going to trust it. And there's a whole bunch of them installed on any device. We're going to take a look at them in just a bit, and this is how we're going to verify the other certificates. All right, so I'm going to go ahead and show you that list in two places. First here in Firefox, and then we'll take a look at it in Node. Let me pull up the Firefox application. I'll go again to Amazon.ca, and let's take a look at the certificate here. This looks a bit cleaner compared to Google Chrome. So again, here's the issuer name and the subject, and here's the certificate authority that has signed this one, all right? So here you're going to see a list. And this is the DigiCert itself, which is another certificate authority, which itself was signed by a root CA. All right, so if you take a look here, you can see that the subject name and the issuer name are exactly identical, meaning that this is a root CA. All right. Still, this is just another X509 cert. The difference is that you already trust this one. Now here, if we go to the settings, so I'll click here and then click on settings, and then let's go into privacy and security. I'll scroll down a bit. There should be a section that says certificates. There we go. So I'll click on view certificates, and here's the list of all the root CAs that we have trusted here in Firefox. So you can click on each one of them, you can export them and get the PEM file, and you can see that we have about maybe 100 of them, all right? Now, this was shipped with my machine. Well, in this case with Firefox, but there's also a list there on my system that, well, I used initially to download Firefox itself, but this is a very important list, and we're going to see later on why this is so important. Because if an attacker manages to add on something malicious here, they could then fake HTTPS and TLS certificates. All right, so you go into bank.com, you think that you are connected to your actual bank, but you're not, because that certificate was, well, sent to you by that man in the middle. But your browser has no way to verify it because it trusts that root CA added to your list by a malicious user, okay? Now, if you want to take a look here at this list in Node, let's go ahead here and create a file called root-cas.js. And then I'm going to include the TLS module. We haven't talked about this module much, but for now, just know that TLS is, well, basically TCP but encrypted, okay? So you can create a TLS server and then send data back and forth, just like that we did in the networking video using the TCP module. All right, well, actually the net module, but through the TCP protocol. And HTTPS is basically just HTTP with TLS added on top, all right? So HTTPS is nothing special on its own. A lot of concepts that you're going to see in it is pretty much the same thing with other application layer protocols that are encrypted using TLS. So if you take an unencrypted email protocol and you add TLS on top of it, you're going to come up with a secure email protocol. Same with database connections. You can do them through TLS to make sure that it's encrypted. We'll talk more about TLS later on, but for now, just know that if you understand TLS, you will also automatically understand HTTPS, all right? Because you already know HTTP from the HTTP section of this course, so this will be fairly easy to understand. So all this work of verifying a certificate, setting up AES to encrypt your traffic, and do the key exchange and all that kind of good stuff, all of it is managed by TLS itself, all right, and not HTTP, okay? All right, so now that I have this one, we have something available on this object called root certificates. This is an array of PEM files, so I'm going to do a loop, and we'll get each PEM file along with the index. Let's do a bit of a log here, so console.log, I'll say CA, let's inject the index, so I+1, so CA number this, for example, and then let's add a new line along with the PEM file. I'm also going to log in total how many we have, so I'll say console.log. We have, and then the length of that array, so tls.root certificates .length. So we have this many trusted root CAs. And they are maybe as follows, okay? Let's now go ahead and run this. So I'll say node root cas.js. All right, let's scroll all the way up. So these are all the different root CAs that were added to our Node.js application. You have downloaded all of these certificates when you installed Node on your machine. And in total, we have 174 of them. This list is pretty much the same thing as the one that we have in Firefox. Now, if you want to decipher one of them randomly, we can do so. So all we have to do is to grab one. So let's include the FS module and then save one of them to our files. So here I'll say fs.write file sync, and then maybe call it random-cert.pem, and then I'll say tls.root certificates. Let's grab one of them, maybe number 49, and yeah, that's it. So let me run this one more time. And now we should have a file here that is our random-cert.pem. And we can also go ahead and see what we have inside. So OpenSSL x509-n random-cert.pem. And actually, I also should say dash text and then not get the PEM file itself. Let me also fix my typo here. And now, if I scroll up, you can see that this one is called this, and the issuer and the subject are exactly identical, all right? So not just one of the fields, the whole thing should be identical so that we can now deduce that this is a root CA, or also called a self-signed certificate, because this was signed by the subject itself. And we have it installed on our machine offline, all right? So we're not gonna reach out online to grab this one. We'll do it here in our device itself. All right, and if you scroll down, you can see that it's quite straightforward. We have the signature, and that's pretty much it, and also the actual public key. So if we want to verify a certificate, we're going to now use this one to do the operation. All right, so let's do a bit of a recap here. Let's again imagine that this is you, and you're trying to establish a secure connection with Google.com. All right. So at first, our connection is unencrypted, all right? So our TCP connection, we don't have any encryption whatsoever. So once you send a request to google.com, maybe you want to do a Google search, before anything happens, Google is going to send you its certificate, all right? So it says, there you go, this is my certificate, and it was signed by, for example, root CA number 3, okay? Let's, as a convention, say that when we see this little icon here, so this little documents icon, this is just an X509 certificate. So when you get your device, you have a list of these root CAs installed on it by your manufacturer. Okay, so if they mess up, you will be very badly compromised. And it has actually happened before. It rarely happens, but it could be the case, all right? If this section of your device gets compromised, that is going to be a massive deal, all right? You could be very badly hurt because of it. Because now any attacker can fake any SSL certificate, so any TLS or HTTPS certificate, send you the new one, and you think you're connected to a secure website, but you actually aren't, okay? All right, so going back to this example, Google is going to send you the cert. You know that there's the public key here, but you're not going to use it to start to, well, establish a key just yet, because you are not sure at this point that this certificate was really sent by Google.com and not by a man in the middle. So what you're going to do is that you'll take a look at the CA that has signed this one, in this case, root CA3. You already have that certificate installed on your machine, so you'll pick it up, you'll grab the public key, and you'll verify the signature of this Google certificate. And if you get a true message, that means everything is valid and you're going to proceed with the key establishment, and then the whole traffic is going to be encrypted with AES. Now, you're not going to actually do this verification manually yourself. This is done by your browser. For example, Google Chrome is going to do it behind the scenes. You're not even going to notice it. But if that true message doesn't come, so if in the process of verification, Google Chrome gets a false thing, meaning that the signature is not valid, it is not going to proceed, and it will show you a warning that there is something wrong with this certificate, okay? Now, let's go back here in Firefox. And here we were taking a look at the Amazon.ca cert. And you can also see that we've got multiple ones here at the top. Only this one is a root CA, okay? So this one in the middle is still a certificate authority, but this is not a root CA, all right? So the root CAs themselves, because we only have a few of them, about 100, they are not going to manually verify every single website out there. Instead, what they're going to do is to vouch for some other CAs and say that, okay, if they vouch for another certificate, it means that I also trust them. And this thing that you see here is called a certificate chain, okay? So we have a chain of authority, and you can imagine that the longer the chain is, the longer it's going to take a client to establish an encrypted connection with that server, because now they have to grab the certificate of each one of them and manually verify the signature of that one. So at first, you'll grab the certificate of this one, verify the signature of Amazon.ca, and then you'll grab the certificate of this root one. This one is offline, so you don't need to send any request for it, and then manually verify the signature of this certificate authority right here. And if you get a true for all of them, it means that the certificate of Amazon.ca is valid. Now, you might be asking, what do these certificate authorities really do? Well, we're going to become one ourselves in the next lecture, so you'll see it's something very straightforward to do. And here, I have a very common one of them opened up. It's called Let's Encrypt. If you have tried to set up HTTPS for your website, you've probably dealt with Let's Encrypt or something similar like this. So this is a CA, or a certificate authority, and all it does is that you're going to give it your certificate. And remember, a certificate is just your identity and your public key, okay? And your identity is, well, your domain name in the world of HTTPS. So you're going to talk to Let's Encrypt, and you'll show them that you really own your domain name. So Let's Encrypt is going to ask you to add a new record to your domain DNS, and once you add the record there, they'll take a look at it and verify that, well, all right, so you've added it, it means that you must own the domain name, and then they will sign your certificate for you, okay? So when you go to a website and you see HTTPS, it's really nothing too crazy. All it means is that now your traffic is encrypted from your device to the server. It's not going to verify the business of that website, right? If you want to get a certificate signed by one of these, you don't need to verify your phone number or prove that your business is legit or is an actual business. It could even be something illegal, and you can still get an HTTPS for it. Many websites that are not exactly illegal, they still have HTTPS set up on them. Some websites might not be secure at all. There might be tons of links that if you click on, you'll get hacked, but there's still going to be HTTPS there, all right? So all of that HTTPS means, when you see that in your browser, it means that your connection from your device to that first server there is encrypted. So HTTPS there means that this thing is now encrypted, and that's it. Right? It's not going to vouch for the authenticity of the actual business, that they're not going to try to do something bad to you. It's not concerned about any of it. It's just going to verify the actual domain name. Now, some certificate authorities would go a little further than that and ask for, verifying the actual business. So that could happen too. But again, at the end of the day, all it comes down to is the domain name verification. Okay. So here you can see HTTPS. And well, your traffic will be encrypted until this server, but the server itself might be having another database, and its connection to the database is maybe unencrypted. So now the ISP here, or people connected to that network, can see the whole thing that's going to get exchanged from here. So if you're sending some sensitive information, it could easily get stolen here in this area, and you have no idea that this might be happening, okay? So HTTPS is no magic. It's not full bulletproof, but it is still something that having it is much better than not having it. If you don't have it, this whole thing is going to be unencrypted, so people connected to your Wi-Fi here, to your network, can also see easily what you're doing with that server. All right, so that's it about a quick introduction to certificates and to certificate authorities and also to root CAs, right? Now we know that the standard format is again this X509, and we can also manually verify a signature of a particular certificate. And we're going to do just that in the next video. So that's it about this one, and I'll see you in the next one. Now we're going to manually verify an X509 certificate to see if the signature is correct. This is going to help us understand this process of digital signatures better, and also understand better what really happens when you are setting up HTTPS on your backend architecture. So here in the certificate folder, let's create one file. We have something called an X509 object in the crypto module. So I'll create one file, call it X509, and let's play around with this a bit. First, need the standard crypto and also the FS module. So let me grab them right here. And then we have our Amazon cert here. So let's go ahead and read it. Here I'll say const Amazon cert. So the Amazon certificate. And this is fs.read file sync. And then let's put in this path right here. So amazon-cert.pem. Now that we have the actual binary content in place, we can go ahead and give it to a function here on the crypto module called X509 certificate. And this one here accepts this Amazon cert. So here I'm going to call it maybe Amazon cert file, and then pass it to the function, so Amazon cert file, and save this one to a variable called Amazon cert. Okay. Now let's go ahead and log this to see what we're dealing with. So Amazon cert right over here. Before I run this, this is actually a class constructor, so we need to also put in the new here. So we're now creating this certificate and then logging it here. So if I now run this, so node X509, here you can see some of the common fields that we talked about. So we have the subject alternative names. So the certificate is valid for all these different domain names and not just simply www.amazon.ca. Sometimes servers have different domain names on top of them, so this makes sense. And then here's the issuer. We've got the valid dates, and that's pretty much it here at this point. Notice that, well, we don't have the signature, which I wish we had it here in this object, and in that case, we could have easily manually verified it, but it's not a problem. We can do the parsing ourselves, so it's not going to be that big of a deal. But yeah, so with this in place, let's just do one check. You know, for example, that if a certificate subject is equal to its issuer, what this means is that the certificate is self-signed. And you already know that only root CAs are self-signed. They don't need to be signed by anybody else because we already trust them. And we already trust them because the company that has manufactured our device has decided to say that this is a good CA, all right? So they have gone ahead and put it on our device. So if this is not the case, if the subject and issuer, if these two are different, all it means is, well, the certificate is not self-signed. And if I now run this, as you might have guessed, here we're going to get this, that the certificate is not self-signed because it was signed by this issuer. If we go ahead and give it a root CA, in fact, let's just go ahead and do it pretty quick. So I'll go back to the Firefox. Here we've got the global root G2. Now let me download the certificate for this one, and I'll put it here in my certificates folder. So let me move it. Actually, the name of this right now is quite confusing, I think. I think it was called Amazon Simple HSD domain name, but let me change it to, I'll change it to root-ca, okay? Or specifically, it's called DigiCert root CA. But because we only want to have one root CA here, let's simply call it rootca.pem. Right, so I'm going to actually move this from my downloads over here to my current working directory. So now we have the root CA over here, and if I put that here, so I'll say root-ca.pem, and I'll leave everything else just like before. Obviously, our variable name, it doesn't make sense, but let me just run it just to show you that we're going to get the same result, but now this time, this is, well, self-signed. So node X509, and here you can see that it says certificate is self-signed, and the issuer and the subject are identical, meaning that now we have a root CA. Now again, we have access to this, even if we don't have access to the internet. This is installed on our machine again offline. All right, so now that we know this X509 object, and also we have another thing available on this. Let me actually change this back to the Amazon-cert.pem. We also have something else called the public key. So let's log this one. So Amazon-cert.public key. And here we have a public key object. And using this one, for example, if we grab the one from the CA, we can then manually verify the certificate that was signed by this key. All right, so this is what we're going to do now. We're going to do one manual verification. So let's create a folder here in our certificates, and I'll call it manual-verification. Here, let's have an app.js. And then let's also copy the Amazon cert here in the manual verification. And well, if we want to verify this manually, what do you think we need in terms of the certificate? Well, we don't need the root CA here because this was not used directly to sign the Amazon cert. We need to have the certificate of this certificate's issuer, all right, which is the DigiCert one. So if I go back to Firefox, the certificate that we need is this one. This one in the chain was used to calculate the signature of this Amazon cert, and only this one. And again, the signature of this one was calculated directly only by this. So directly, the root CA was not involved in calculating the signature of Amazon.ca, okay? All right, so let's go ahead and download this one as well. So I'll download it, and then we need to move it again. So I'll navigate over to manual verification, and then move this one from my downloads, which is again called just the domain name, and I'm going to call it Amazon-ca.pem. All right. Now, it would be more accurate to call it DigiCert Global CA-G2, but, well, you know what? I'm going to call it Amazon CA.pem, okay? Now, this is not a CA specific to Amazon. This CA right here has signed millions of websites, and Amazon.ca, well, happens to be one of them, okay? But by this, I mean it was the specific CA that signed the Amazon cert. All right, so now with this setup, we can go ahead and manually verify this. So what we need, let's copy the whole thing that we have here in X509 into app.js of manual verification. And let me just make it a little smaller. And also grab the Amazon CA file. We need to have one more X509 object from this CA, and then use it to verify the signature that we have right here. So fs.read_file_sync. And here we need to grab the Amazon-ca.pem. Then we need to create this X509 object. So I'll call it Amazon CA equals new crypto.x509 certificate, and then the Amazon CA file. Now, let's also delete this portion. What we need to have now is the Amazon signature. A signature that was put by the DigiCert CA. Now again, it would have been quite nice if we could just say Amazon cert.signature. And I'm sure there are many NPM packages that would allow you to do it. But right out of the box here, using the crypto module, we can't do it. But it's not much of a problem. We can either, again, manually parse it or just copy-paste it. So let me go ahead and actually do the copy-paste. So I'll say open SSL here, then X509-N, then give it the Amazon cert, and then dash text, no output. So here's the signature. It's all the way at the end. This is what we need to have here in that variable. So let me copy it. And then, well, let me actually create a new file because we need to clean up a bit. And I'll delete all the colons. So I'll replace all of them with nothing. I'll click on here, replace all. And then let me also remove all the tabs and put them nicely in one single line. So I'm going to quickly do this. And then I'll copy this and paste it here in Amazon signature. So let's create a buffer from it. So buffer.from. I'll paste it here in one nice long line and then say that this is a hex. All right, great. Now we have our signature. Let me close this one. And let me also add a bit of a comment here. I'll say Amazon signature calculated by the CA is this. Now, if we want to manually verify this, we're going to need to have the public key of the Amazon CA. For this, we're in luck. Crypto module gives us an easy ability to grab this one. So let me do that. So const public key equals Amazon CA.public key. And now this is a key object which we can use to go on ahead and, well, do crypto.public encrypt or public decrypt. Now I'm going to leave it up to you to do this as a challenge first. But before we do that, let's also talk about what is the actual message that we need to calculate the hash from. Because if you recall again, in the process of the certificate signatures, the CA would grab the Amazon cert, calculate a hash off of it, and then encrypt that hash using its private key. Okay? So if you want to now verify this, we need to recompute the hash again, and then also decrypt the signature. And if both results match, it means that the signature is valid. But how do we compute the hash? We know that we can use the crypto.createHash function to do it, but what should be the actual message? If you just give it the whole Amazon cert, which is here, it's not going to work because the hash was not computed off of the whole thing. It was only computed from a portion of it because, well, obviously the signature was not there in the first place, okay? So we need to grab the actual data without the signature so that we can now compute the hash. Now, fortunately, there's a command that we can run here using OpenSSL that will give us from what byte to what byte was the actual message of the certificate that was used to compute the hash. So we can use this ASN1 parse thing and then give it the Amazon cert file. And that's it. Now here we're going to see a whole lot of things. But the only thing that we're going to focus on here is the second line. By convention, the second line here tells us exactly what was the message that was used to compute the hash. So the 4 here, this is the offset, this is the header length, and then here's the length of the message. So we need to do some slicing on the certificate, grab starting from this byte, and go forward by this much, okay, including the header. All right, so let's go ahead and do it. Here, let me do one log, it's console.log, and I want to log the Amazon cert.raw. What we get here is the raw contents of the certificate in a buffer. So let's go ahead and run this. Here we can take a look at the buffer. So you should know how to do the slicing now. And that's just, Amazon cert.raw.slice. But before we do that, let's have some variables here. The offset, which is the first one. So the offset is 4. Then we're going to have the header length, which in this case is also 4. I'll put it here. And then we have the actual content length, which is 1454. And now we can do our slice. So I'll say const Amazon cert message. Remember, as a convention, we call the input of a hash function message. So that's why I'm calling it message here. And then I'll say Amazon cert.raw.slice. Actually, let me use the sub array to do the slicing because it's not deprecated. And then here we need to give it the offset. And then here we need the end index, which is offset plus the header length plus the content length. Okay. So now we have the public key of the CA. We have the actual certificate message that we now need to compute a hash for. And with these in place, we should now be able to do the manual verification. And I want to leave it up to you to do this as a challenge first. So manual verification here. And also just one quick point before you do it. After you decrypt this one, so the signature, you're going to get something that also has the paddings inside of it. So only take a look at the last 32 bytes and compare that one with the hash that you're going to compute. Okay, so that part should match. Now, if you don't want to worry about any number, just again, only check the last few bytes, and if they match, it means that, well, you have probably done it right. Okay, so pause the video right now, see if you can get that true thing at the end by manually decrypting and calculating a hash. All right, hopefully you got it right. And now I want to show you how I'm going to do it. So let's first calculate our hash. We already know how to do it, so crypto.createHash. And here we're going to use, well, the function that we need to use, if we go back here, let me grab the certificate again, is this one, SHA-256 with RSA encryption. So we can either just use this actual name or also say SHA-256, okay, because we're now using create hash. So both would work fine, but I'm going to put this one here. That SHA with RSA encryption is more for the crypto.verify function to handle the paddings by itself. And we'll take a look at that in a bit. But here I have the create hash, and then I'll feed it the Amazon cert message, and then call the digest function to grab the hex output. And then I'll log this one, so console.log computed hash is, well, hash. Let me remove this log right here. And then run it again. So here we get this hash. And now the result of our decryption on top of the signature should be exactly identical to this. So let's go ahead and do that now. Let me add some dividers here. And then here, some more dividers. So calculating the hash of the certificate. And then here, we're going to have decrypting the signature. I'll say const plaintext. Again, we also know how to do it using the crypto.public decrypt function. Here I'll give it the key. We know what the key is already, which is Amazon CA.public key. Which I think, do we have it here? Yeah, we have it here, but we don't need to. We can just say Amazon CA.public key like this. And then the Amazon signature. So here we have the ciphertext, and then we're going to have, well, the plaintext. So let's also log this one. So console.log decrypted signature, and then the plaintext. Let's also grab the hex value. Now, if I go ahead and run it, now the values are quite different because, again, the paddings are also included here in the decrypted signature. But if you take a look at the last few bytes, you're going to see that they match. Okay. Now we can easily do one slice or subarray here. So let me do that. So .subarray. And then we need to grab the last 32 bytes. So it should now work. There we go. So now we get two outputs that are now identical, and this means that the signature on the certificate is valid and was 100% calculated by the DigiCert CA. All right, so there you go. This is what happens in the manual verification. Now we can also do this automatically using the crypto.verify function. So let me do that. I'll copy the divider right here and say automatic verification, and then const is valid. Remember, we're just going to get a true or false message using the crypto.verify function. Here we need to specify the hash algorithm, so SHA-256. Now here we also need to specify the algorithm that was used, because this is now what would be used to also do the decryption of the signature. So I'll say SHA-256 with RSA encryption. And then we need to give it the Amazon cert message, the Amazon CA public key, and also the actual ciphertext, which is, well, the signature. And then let's also log whether or not this is true. So I'll say valid signature, and then the is valid variable. Let's run this, and here we can see that we get this true message. So quite straightforward here. Again, we need to put in this RSA encryption because we need to use RSA to decrypt this signature. The verify function is also going to do this public decrypt, so that's why we need to put in with RSA encryption and not simply this. Now this also might work, but the reason is that it will now automatically figure out that this public key here is for RSA, okay? But if it's not able to figure that out, you might get an error, okay? RSA isn't the only public key cryptography algorithm that we have to do verifications and signing, so it is a good idea to explicitly specify what is the encryption algorithm behind the scenes. So again, all that's happening here in the crypto.verify is what we have right here in the manual verification. And this is what happens before you establish a connection with a server. So going back to our Firefox, you're going to do that verification once first before you connect to Amazon.ca. You're going to do that verification first for this Amazon.ca cert using this one's public key, all right? And then you're going to do it again. You're going to now use the root CA's public key, which you have offline. Use this one to verify the signature of this CA. And if you get 2 true messages, it means that this certificate that you just got is a valid certificate. So again, we have a chain of CAs. Usually we have about 3 or 4 of them, and it's quite rare to only have 2 because again, the root CAs don't really handle different websites because we want to keep them as offline as possible, and they only vouch for different CAs. And some CAs, well, they're going to go ahead and sign millions of certificates for different websites. Now, technically, we can have like maybe 10 different CAs right here, but that's very rare, and if that's the case, it means that there's something wrong. The developers of that website need to take care of it. 3 is a very common format. Right now, if you want, you can use, for example, Let's Encrypt to get a certificate for your website, and you're going to end up with only 3 of them, okay? Now, also one final point that I want to mention. Remember that we said the public exponent in RSA is this one, 65537. Now, if I go ahead and put this in my calculator, now this is a very good number. Let me put it here. And if you take a look at the binary content, it's 1, and then many zeros, and then a 1 at the end. Now, if you think about it, we're doing way more verifications than we're doing signing. For each website, well, there's only need to be 1 signing by the CA, only at the beginning, and maybe every few years or every few months, there's going to be another signing. But these signings are done using the private key, so the private exponent there is very large. It's way larger than what we have here for the public exponent. So signing using that gigantic number is, well, quite slow. But verifying, which is something that for each website, it usually happens millions and millions of times per day maybe, for some popular ones, you can imagine that this is a very good choice for the public exponent. If we have a small one for the public exponents, the process of the verifications are going to be way faster. So we're now saving a ton of energy, a ton of money and time from the world by going with a small public exponent. That's why we have it as a convention. So yeah, you can go with some crazy public exponents too, and it's valid in the RSA algorithm. But now every single person that wants to connect to your website, well, they need to do some verifications, and they have to use this gigantic number. So they have to take the plain text, raise it to the power of this one, and then get its modulus by that prime 1 multiplied by prime 2 number. So by going with something simple, you can imagine that we're saving a lot from the world. Now, not only that, but also this number is, well, quite special. Not only it's a small one, but again, taking a look at the binary content, we have all zeros right here. So we use a method called square and multiply to calculate data raised to the power of that public or private exponent and then get its remainder by the modulus, okay? Now, the square and multiply method works faster if we have tons of zeros like this in the middle, all right? So this public exponent, to do now one verification or encryption or decryption using this one, this is faster compared to a number like this, all right? So this public exponent is just a very great choice that we have. Not only it has all these zeros here, but it's also quite small. And we're not really sacrificing security for this because our private exponent is large enough, all right? Our private exponents and the prime numbers, they're quite large. All right, so that was just one other point that I wanted to mention about the exponent right here, because it's a very common one, and there is a reason why we're sticking with this. It's not just a random number. It is just small enough to give us enough security, and also small enough to give us a huge performance boost. All right, so that's it about the certificates, the digital signatures, and also the CAs and root CAs. You should now have a much better understanding about the HTTPS certificates. They are just X509 certificates, as you know, and these are not limited to HTTPS. We use them all over the place. For example, if you want to have an encrypted traffic to your database, well, you're using TLS. So you also need to have an X509 certificate there. Right, so they're used in many different places. TLS is not limited to just HTTPS, and we'll talk about that later on in the section. All right, so that's it about this one, and let's move on. Hey, welcome back. In this video, we're going to set up HTTPS from scratch. So we're going to become a CA ourselves and then use that CA to issue a certificate for a website. And we can use any domain name that we want. You don't need to buy any domain name to do it. You don't really need to even be connected to the internet for this video. So let's go ahead and get started. Please first download the starter.zip file from the resource section of this video. I have added a folder called HTTPS here inside, and then we have an app.js and this OpenSSL-san.config. All right, I'm going to talk about them in just a bit. But here in the app.js, we only have a very straightforward HTTP server. All right, you should know what's really happening here. I've also added this website name that's Facebook, but right now it's not really doing much. It's a useless log, but we're going to get it fixed in just a bit. So let me go ahead now and run this. And also pay attention that 443 port is the default one for HTTPS. All right. And if you want to run your Node apps on this port, here I'm going to navigate to the HTTPS folder, and then we're going to have to run it as sudo because, well, the port is on 443. So sudo node and app.js. Same if you are on Windows using WSL and also on Linux. Now, if you get an error that says it cannot find node if you are using sudo, just change it to this. So it only means that it can't find the path. So if you do something like this, it should work. So wrap this in a $sign and 2 parentheses and just say which node. All right. All this means is to grab the output of which node, which is just a path, and then replace it here, and that's pretty much it. All right, so let's confirm that we're getting something. Now, don't try to go to facebook.com just yet. If I do that, I'll just get the regular facebook.com. All right, I get this https www.facebook.com. All right, so instead of doing this, go into the IP address, so 127.0.0.1, and then port 443. And here you should see this "Hey there" message. Simple enough. So if you see this, it means that the server is running fine. But well, we don't have any domain name. We don't have any HTTPS here. And by the end of this video, you're going to get a beautiful HTTPS facebook.com domain right here for this website. Okay. All right. So let's see how we can approach this. Here, if you scroll down, I've added in some commands that we're going to run. You're welcome to copy paste them if you want, but I'm going to type them out from scratch here. And basically what we need to do is to first become a CA. So we're going to become a root CA ourselves and then tell our browser or our system to trust it. And then using this CA, we're going to issue and sign a certificate for facebook.com. Then we're going to use the HTTPS module instead of the HTTP and give it the certificates here in an options thing. All right. And just like that, we can then go into https://facebook.com and get our own application. Now, before we do so, let's modify our DNS so that facebook.com would point to our server. All right. A man in the middle might just modify the packets before they get sent and received. But here we don't want to worry about it, so we're going to simply modify our DNS, which is fairly straightforward to do on all machines. So I want to first show you how to do it here on Mac. It's also a similar process on Linux. So all you have to do is to open up this file. So I'll say sudo, I'll use vim to do it, but you can also use the code command to do it, or any other text editor that you want. So say sudo vim etc and then /hosts. All right, if you're on Windows, just bear with me for a sec, please. I'll show you how to do it on Windows too. And here, just add a new entry. So I'm going to add the local host IP address, which is 127.0.0 and then .1, and then www.facebook.com. Let's add one more for just facebook.com. So the loopback address, which is the local host, and then facebook.com. This is how we would modify any DNS out there. It's just, again, kind of like a table lookup. So we just need to add in these entries. Now I'm going to save and close. If I go now back to facebook.com. I might need to restart. No, I don't need to. So here you can see that it says that the site cannot provide a secure connection. We are now not connecting to the actual Facebook's servers. We are connecting to our own application. Okay, but we're now using the HTTP module. We're trying to connect through it with HTTPS, and well, we're going to get this error. Now, also, I want to show you how to modify your DNS on a Windows pretty quick as well. Here, search for the Notepad application and make sure that you run it as administrator. Then here, go to File and then click on Open, and then go to this path. Now here, in the resource section that you download, there should also be a file called maybe instructions or something. I'll make sure to add it and follow the instructions there. All right, so just copy that here. And I want to show you how to do it pretty quick, but again, very quickly. Here, change this to all files and then select the hosts file. And then that's pretty much it. I've already added it here, but you can just copy this and put it here. And then save and close, and just like that, you have modified your DNS here on Windows. All right, so now we're going to use OpenSSL to run a few commands. We're going to first become a CA, and then, well, let's first do that. So I'll head over to my terminal, and I'll use the OpenSSL command, and then gen RSA. We need to generate an RSA key pair. But first, let's only generate the private key, all right? So I'll say -out. And for the name, well, let's have a convention because this could get a little confusing. So for our website that we want to set up, our domain name is either facebook.com or www.facebook.com, all right? So let's have this established. Now, I rarely use facebook.com on my machine, so that's why I'm going with this domain. You can go with anything else that you'd like, all right? Just make sure whatever website you pick, you're not frequently using it on that machine because you're not going to be able to access the actual website while you're doing this. So if you want, go with maybe google.com or microsoft.com or test.com, whatever you want. It doesn't matter, honestly. But in this video, I'm going to use facebook.com. Now, for our root certificate authority, because, well, we're going to become a CA ourselves, for the organization name, I'm going to use UNCC Inc. UNCC, the name of the course, and Inc. or INC, meaning that it's a company. It's a made-up thing, but you get the point. We just want to have a simple name that we would easily recognize. And for the common name of the certificate, I'm going to use UNCC Root CA, okay? So the company is going to be the whole thing. We might be a certificate authority company, but we do much more than maybe just signing certificates. And this UNCC Root CA is, well, the common name. Now, if you go to Firefox, now let's try to maybe take a look at one of these certificates. So I'll go back to the settings, privacy and security, and then scroll down here, click on View Certificates. And let me click on maybe this one. The name that appears at the top, this is the common name. So our common name is going to be UNCC Root CA. And then the organization, this is going to be UNCC and then INC. All right, so hopefully this is clear enough. If you want, you can take a look at a couple more here. For example, a DigiCert, which is quite common. Organization is DigiCert. And then the common name is this. Now, we don't need to have a domain name for the certificate authority. And the subject, as you can see right here, this one does not have any domain name whatsoever. But also we could, like DigiCert here, it has a domain name. But again, we don't have to. But for the certificate of the actual website, we for sure need to have a domain name. All right, so let's go back to here, our terminal. Our name is going to be UNCC. Right now, we're generating only the private key. So I'll say uncc-private.pem, and I'll say 2048 for the modulus length. Here we have this key, and if we take a look at it, it's just, well, a private key. So it's nothing but an RSA private key. That's all that we have done so far. One more convention throughout the video. Everywhere you see -private.pem, it means that it's an RSA private key. All right. All right, now that we have the private key, we're ready to go ahead and generate our certificate for the CA. For that, I'll say OpenSSL request and then -x509. Here, I'll say -new -key, and for the key, we have to specify the private key, so uncc and then -private.pem, and I'll now specify my output file, which now will say uncc-cert.pem. -cert, again, remember, just stands for certificate, meaning an X509 certificate. Now I'll say -days, this is the validity of the certificate, and I'm going to say that it will be valid for 1 year from now, okay? And then for the hash function, let's use SHA-256. All right, once you run this, it's going to ask you a couple of questions. For the country name, I'll put in Canada. You can put in your own country, doesn't really matter. For the province, Ontario, and city, I'll put in Toronto. Now, for the organization name, this is, again, that first thing that we talked about. This is going to be UNCC, so let me put it here, so UNCC and then C. Now, for the organizational unit name, here, for example, we can put in a domain name if we want, but I'll leave it blank. Let's keep it simple. Now, here, the common name, this is the thing that appears here on the tab, all right? So this is going to be the actual name of the certificate. And as we have mentioned, we're going to use UNCC root CA all in capital. Now, I also suggest that you stick with the same name because we're going to then put this certificate to our trusted root CAs. And if there's this name, it would be easy for you to later on find it and delete it if you want. So you just have to search for this name UNCC, and everywhere you see it, you're going to delete it, okay? All right, so I'll put in UNCC and then root CA for the common name. We don't need an email address, and then I'll hit enter. And now, here, we also have our certificate. OpenSSL X509-N, and then uncc-cert.pem, and then I'll say -text and no output. And here, if you take a look, it's just a common certificate. And our issuer and our subject are identical, meaning that this is self-signed. This is a root CA, okay? We're using SHA-256, we're using RSA encryption, and everything else is, again, quite straightforward, okay? We also have our signature at the end, which we have calculated ourselves. All right, great. So now at this point, we have a CA just like that, all right? We can now go ahead and issue certificates for other people, for other organizations, domain names, whatever we have. So now we're going to move on to the Facebook.com website. I'll use the OpenSSL Gen RSA, so generate an RSA key. And this is now for the Facebook.com. So let's call it Facebook-private again, meaning that this is first the private key, .pem, again, 248, or also other key sizes would work just fine. But let's go with this. Now we have our Facebook private key here. This is the private key that Facebook now, well, for our own application, this is the private key that our application, this app.js, is then going to use to establish a shared key with a client before doing the actual thing. So before sending, hey there, Node.js, or more specifically the TLS module, this HTTPS is built on top of the TLS module, which we'll talk about later on in the section. So the TLS module, or HTTPS here, is going to first use this private key to, well, share a secret with the client. And then once we both have the shared secret, maybe an AES key or a SHA-20 key, Node is going to encrypt this hey there and then send the encrypted data over to the client. And then the client is going to decrypt and display hey there right there on the page. All right, now that we have our private key for Facebook, you might think that we would now go ahead and generate our certificate, but there's one other step that we need to go through before we tell our CA to generate the certificate. And that is that we need to generate a certificate signing request. Let's first take a look at this. So I'll say OpenSSL, then request, -new, and then -key. So now we need to give it our private key, and then -out. This is now going to be the certificate signing request. So let's call it Facebook dash certificate signing request, so csr.pem, and then dash config. So now here we need to put in the OpenSSL configuration file that I have given you here. If you take a look at it, it looks quite similar to a part of a certificate, and this -san stands for subject alternative name. All right, so this one. We're doing this because we may have different domain names that we want to use this certificate for. For example, back in Firefox, here in Google, if I just do one quick Google search, and if you now take a look at the certificate that we have for google.com, here in these subject alternative names, you can see a whole bunch of things. So Google uses the same certificate right here for all these different domain names, right? If you scroll down, you can see that they have a whole lot of them. For example, Android and YouTube.com. So they use the same certificate for both their Google searches and also for YouTube, which is a valid thing that you can do too, okay? So they are all tied to this organization, which is Google Trust Services. And well, again, they all use the same public key right here. All right, so that's why we need to have this config. Right now, I have only put in two things. So star.facebook.com, so that we can now go maybe into api.facebook.com, or more specifically here, just www.facebook.com, and also the root domain. So without the www, it will also work fine. So that's all that this file really is, okay? So let's specify that here in the config. So I'll say openssl-san.conf. Now I'll run it. And now if you take a look, we have something called the certificate requests. Now in the real world, if you want to set up HTTPS on your server, what you're going to do is to create one of these requests using this command. So you're going to get a file like this, begin certificate request. You'll then send this over to Let's Encrypt, and then they're going to sign it for you. So if you take a look here at the contents of that file, so let me do that pretty quick. So I'll say OpenSSL rec-in, and then I'll give it the Facebook-csr.pem, and then the same thing, no output, and then dash text. Here, if you take a look, it's just like a certificate, but it says now certificate request. So we still have the subject here. We have our public key embedded inside of this file. And also at the end, we have one signature, but this was signed by ourselves. Okay, so by Facebook in this case, for example. This was not signed by any CA whatsoever. And then the CA is going to just use this signature to verify that this really came from you. And then they'll use the data over here to generate that certificate for you and then sign it, okay? So the last step that we need to do for the commands is to, well, sign this certificate request with the CA. All right, let's do it. It will be a little bit of a long command, but shouldn't be that bad. You can also, of course, copy paste it. So OpenSSL and then x509-request. Let's give it the Facebook certificate signing request first, and then I'll specify our CA, so uncc, and then dash cert.pem. All right, so this is now our CA, which we're going to use to sign it. And if you know, for the signing, we're going to need to have our private key. So the CA private key here is uncc-private.pem. I'll then add another option here. I'll say CA and then create serial, and then dash out. I'll now specify the output of this command. Let's call it Facebook, and then dash certificate.pem, like we always do. And then now we need to specify the days, so for how many days this certificate will be valid for. And I'll put in 1 year here. And then SHA-256 for the hashing. Now we also need to specify our OpenSSL-san file. So I'll say dash extension file, and then OpenSSL-san.conf. And the extensions, I'll say ext. So what this means is to look in this file, which we have right here, and then look here in the ext section, so request extensions, to grab the alternative names, and that's it. All right, that's all that this little piece right here is. So maybe we can also simplify this, but I didn't try to experiment much with this. All right, so now let's run this. And I think I've got a typo here in CA key. Yeah, the K here should be lowercase. So let me quickly fix this. All right, so here I'll change this to key with lowercase k. Now I also have one last typo here at the end. It should be dash extensions. So I'm missing one S. And now if I run it, it will tell me that certificate request self-signature OK. All right. So now we should have the certificate for Facebook. So let's take a look at this. So open SSL X509 -in Facebook -cert.pem and then dash text and this. And now the signature is different from the one that we saw on the certificate requests. This is now an actual X509 certificate that was issued by UNCC root CA, as you can see here in the issuer. The subject is facebook.com, and the public key, now this one belongs to this subject right here. And here in the date, it's valid for exactly 1 year. That's what we specified, and here the signature was calculated by the UNCC root CA, okay? Now we are ready to put in these certificates on top of our application to use them to do encryption. So here we're using HTTPS, but we also need to specify some options. So const options, and the options, we need to first, of course, have the private key, the certificate. So let's specify them all here. I'll use the fs.read file sync here. That's actually what you should do in production. You should read it synchronously, because this is what you should do before you establish any connections. So here I'll specify the path, which we called it. Actually, we have the website name right here, so let's inject that variable, website name, and then dash private.pem. Then we're going to have our certificate. I'll inject this name again. Now this one is dash cert.pem. And this should be pretty much it here for the options. Now let's encrypt right here. The core of what they do is this command that we ran. So they're going to get certificate signing requests and then sign it like this. That's pretty much it. Now, of course, they're also going to verify that you own the domain, for example, facebook.com. They're going to ask you to put a record in your domain name DNS. So in reality, you cannot go with facebook.com because you don't own the domain. But yeah, this is at the heart of what certificate authorities do. All right, so now back right here. Let's go ahead and run this. So I'll exit out and then run sudo app.js. I'll put in my password. And it says server running here. Now we have an HTTPS in this case. So let me fix this. All right, let's now go right here and see what's going to happen. So I'll go back here. Now it's not going to work, but let's do a refresh. Now we see a different message this time. It says that the connection is not private. Right? So it seems like that things work fine. It knows now what this is. It is trying to connect. But it says that our certificate is not valid. Well, there's no proceed option here in this case, but let's fix this pretty quick. Actually, let's go now to Firefox and try to do it here. So if I now go to facebook.com, we see the same issue here. And if we click on View Certificate, we're going to see facebook.com. So this is the common name. And also the issuer, which is UNCC root CA. So it seems like so far it's all valid, but the problem is that our system, or Firefox in this case, does not trust this UNCC root CA. The Firefox company, or my MacBook company, Apple, they did not put this certificate in the trusted CA list. So now we are not able to do it, but it's a very easy fix. Let's go back to the settings here in Firefox, go to privacy and security, and then here I'll scroll down, click on View Certificates again, and let's import our own certificate. So here I am in UNCC-code and then crypto. I'll go into HTTPS, and then we need to select uncc-cert.pem, not the private key, and hopefully it makes a lot of sense to you why you should not upload the private key here. So I'll select my certificate, I'll click on open, and then click on trust this to identify websites and also email users, and then I'll click on OK, and then one more OK right here. Let's now go back here and do a refresh, and now we can see the hey there, and our domain name is now https://www.facebook.com. Pretty cool. So that's really all that it takes to set up HTTPS, quite straightforward. And you know that in production, well, you're not going to become a CA yourself, but rather you're going to submit your certificate request to another CA. But here in your node code, it should look similar to this, all right? Now we can also not handle it here in Node, and instead do it maybe in Nginx. That's valid too. You don't need to encrypt your traffic like this inside of your own machine, but you've got multiple options. If you've got a proxy running directly on top of your server, that will work too. But if your proxy is outside of your server, you want to also encrypt from your server up to that proxy. All right, so the whole thing should be encrypted, not just the connection that's from a client to the closest HTTP proxy, which could be problematic because the rest of the connection from the proxy, maybe up to your server, that is not encrypted. Okay, so you also want to do this on your servers, and either with Node or with Nginx or anything else that you're using on those servers. Now, feel free to also try it with different domain names. You can go with google.com, google.org, whatever you want, it doesn't matter. You just need to select this, hit Command D or Control D a couple of times, and then go with whatever name you want. For example, Google, all right? But also make sure that you modify the OpenSSL-SAN file. So this one should also be google.com, but I use google.com quite a lot, so I'm not going to do that. Now, if you want to do this for another website, you do not need to run the first two commands, of course, because the CA is the same. You just only need to run the last three commands that we ran. You do not need to, again, add this back to your trusted root CAs. It's already there, but of course, modify your DNS and, well, also take care of the OpenSSL.conf file, and that's pretty much it. Now, if you want to remove the CA here in Firefox, all you have to do is to go back here in the settings, view certificates. Well, UNCC, because it starts with U, it should be all the way at the end, so you don't need to check a whole lot of them. There you go. So it's UNCC root CA, and then right here, select it and click on delete or distrust, and that's it. Now, before I end this video, I'm going to talk a little bit about some system-specific things. So right now, if you try to go to facebook.com on Google Chrome, it's not going to work because, well, we modified it on Firefox. Firefox uses its own trusted CA list, but here, Google Chrome does not. This uses your system's trusted CAs, okay? Same with if you want to now do a curl. So let me do this. So a curl HTTPS and then facebook.com. It's going to give you an error that the certificate is not valid. Now I want to talk about how to fix this so that your whole system now trusts this instead of just Firefox. And I'll show you how to do it on Mac, Linux, and also Windows. So if you don't care about this, please feel free to skip the rest of the video. All right, so on Mac, all you have to do is to open up an application called Keychain. So search for Keychain, and then Keychain Access. Right here, go to the system, and here in the certificates, drag and drop the UNCC cert. All right, so drag it here. You have to put in your password quite a few times for it. So let me do that. And then at first it says that this is not trusted. So double click, then expand this trust option. And then here, change it to always trust. Then close, put in your password another time, update settings, and now it's trusted. So now if I go back to my terminal and run curl, we're going to get hey there, and it's not going to complain about the certificate not being valid. Now, same back here in Google Chrome, we can now also do this, and we see https facebook.com. And we get that connection is secure. Now, I'm going to show you how to do it on Windows. I have the server running. If I go into facebook.com, it's not trusted. Now, if you want to trust it, create a new Windows PowerShell, but run it as administrator. Now here, navigate over to your folder, and all you have to do to tell your system to trust this uncc-cert.pem is that you need to run this command. So run cert util-add store, and then root, because we're adding a root CA, and then specify the uncc-cert.pem. If you run it, it says that command completed successfully. And now we can go into Google Chrome, do a refresh, and you get this one. I'll also add in this instruction file how to delete this after you've added it. And then on Linux, it's also quite straightforward. All you have to do is to just move it to one folder. But before you do that, you need to change the extension, I think, to a .cert file. So I'll just copy it to a new file called uncc-cert.cert, right, without the E. This is also pretty common, and sometimes you see that the X509 certificates have the .crt extension and not the PEM. They're still encoded using PEM, but, well, the extension is just this. It doesn't really matter much. And then copy this one, so uncc-cert.crt into a folder called user/local, and then share, and then ca-certificates. Now, right now, if I do a curl, now here in this Linux machine, I'm using google.com, and if I do a curl on it, so curl https and then google.com, it's going to tell me that the certificate is not valid. But after I move it, actually, we need to do it as sudo, so let me redo this. Put in the password, and now we got to run one final command, so sudo update-ca-certificates. If you run it, it's going to tell you, well, it says 0 added. I've actually done this process once before recording this video, so maybe that's why it says 0 added for me, but for you, it should say 1 added, all right? And then once you run this, you should get the hey there. So now you can access google.com or whatever other domain name you went with everywhere on your system without getting any warnings whatsoever. All right, so that's it about this video. Hopefully you had some fun, and now you should have a much better idea about how to set up HTTPS and what really happens when you are doing that. Now, next up, we're going to talk a bit about the TLS module, because we've mentioned that HTTPS is built on top of that, and it's pretty similar to this one, so you have to specify the options in TLS as well, and that's coming up next. So that's it about this video, and I'll see you in the next one. In this video, we're going to talk about the Transport Layer Security Protocol, or TLS. This is one of the most common encrypted protocols on the internet, and this is at the heart of HTTPS. In fact, HTTPS is just TLS with HTTP itself. So going back to our networking layer, we've got these layers. We've got HTTP all the way at the top. This is the application layer protocol. Then we've got TCP. Here's where we have the port numbers, and then the IP layer, here's where we have the IP addresses. So this is one common architecture. There's no encryption here whatsoever. The whole thing here is unencrypted. Your ISP and anybody else connected to the network can see exactly what's happening on each one of these layers. Now with TLS, so let's have another thing here. Now let's see how we can now use TLS to encrypt a portion of this thing. Now, TLS sits between the transport layer and the application layer. So if you take it and put it right here, it will now encrypt everything on top of it. All right, so now we're going to have HTTPS. So that's how TLS works. And it works with any other protocol that you might have. If it is not encrypted, you just stick this TLS in, and now it's going to encapsulate the whole traffic on top. For example, in HTTP, before you send some data out from your machine, TLS is going to encrypt it, send the ciphertext, and then the other endpoint is going to grab the ciphertext, and TLS will then decrypt it automatically before showing it to the user. Okay? So it's quite versatile. You can use it in many different places, and it works really nicely with different protocols. Now, I want you to pay attention to one thing, that HTTPS is really this. So HTTPS is not another application layer protocol that's different from HTTP, okay? We still have the exact same protocol as before, well, the HTTP protocol, but now we also have this TLS underneath it. So HTTP itself does not handle certificates. It doesn't do anything with the AES encryption or any public cryptography mechanisms. It has nothing to do with those. All right, HTTPS just means this architecture right here. Now, TLS itself is also not limited to just HTTP. So HTTPS is again only one of them. For database connections, we also have TLS here. And I've seen many developers who make this mistake that they are trying to connect to their production database, and they do it through an unencrypted connection. So they would just put in the database stuff and use an application like maybe DataGrip or pgadmin or something like that. And the whole thing there is unencrypted, which is a massive problem. And if you do one select all from a table, all of that stuff is now able to be seen by anybody else who's connected to that internet. So that's not something that you want to do. Almost all database applications out there, like Postgres, MongoDB, or MySQL, they all offer a way to connect to them through TLS. All right, so you're going to have to set up a certificate on all this stuff, but it is something that you should 100% do. All right, then we have WebSocket over TLS, which is WSS. TLS is also used in some VPNs. Then we have FTP over TLS, which is FTPS. Another common mistake made by some people, they just use FTP to access all their files, and they're not doing any form of encryption, which means that, again, all the files can be accessed by many different people. Whoever can capture the traffic can now see what that person is doing. Then we have SMTPS, SMTP, another application layer protocol on top of TLS. And also in microservices, we have TLS. It's used there quite a bit. So if you've got different servers, maybe a server that handles comments or another one that handles posts, if these two want to talk together, the traffic has to be encrypted if they are not on the same private network. So in that case, of course, you gotta go ahead and encrypt the whole thing. And many protocols that are used for communication between microservices also have support for TLS. In fact, if they don't, you should not use them. And they do have this support, and you should use it. So again, you have to set up these certificates and make sure that everything is encrypted. All right, so you can see that TLS is used in many different places, and HTTPS is only a small part of it. Now, having said that, it also doesn't mean that whenever we're using encryption on the internet, we are using TLS. We have also other encrypted protocols on the internet that do not use TLS. One common example is SSH. SSH is an encrypted protocol directly on top of TCP. It's used for secure shells, so that's what you use when you want to connect to your servers. And also it is used for file transfers. If you have used something like SCP or SFTP to transfer some files between machines, that's where it's also used. So SSH has nothing to do with TLS, although they work in a similar way. We still have symmetric encryption in SSH, obviously, because we are encrypting everything. So we have AES and SHA-2 there as well. We also have public key cryptography to do a key exchange. So we have these things there as well, but keep in mind that SSH is not based on TLS. Another protocol that is also encrypted and has nothing to do with TLS is IPsec. But IPsec is more commonly used in VPNs. So we're not going to talk about SSH and also IPsec, but just keep in mind that we also have other encrypted protocols apart from TLS. Now, let's go ahead and see the TLS module in action here in Node. So let's create one folder and call it TLS. Then here, let's have a server, and let's also have a client, and each one of them, we're going to have an app.js. And let's set up a server and then send some information back and forth with the client. Now, it's very straightforward. It's just like the net module. You just say .write and .on, and that's pretty much it. And the whole thing is going to be encrypted. So TLS handles all of the certificates, verifying the certificates, setting up a symmetric key, a shared secret. All of this is automatically done for us by the TLS itself. We can, of course, specify some options, for example, use AES or ChaCha20 or what key sizes to use, but we don't need to manually handle the regular stuff like sending some shared secret over, and then using that to run a KDF function on top of it to derive an AES key. All of it is again done by the TLS module itself. So let's go ahead and include this. And then let's have our server object. We have a function called createServer. This one accepts some options, or I'm going to just put it like this. And here's where we need to specify our certificate and also our private key. So let me first grab the FS module. And then we want to have a key option. So fs.readFileSync. Here we're going to put in our private key. We'll talk about it in just a sec. And then we also need to have our cert, right? So our certificate that contains our public key as well. So here, read file sync. Now for the actual files, we can use the same things that we had here in HTTPS, all right? We don't need to use OpenSSL anymore. We have created these. Remember, these are X509 certificates. And these certificates are not specific to HTTPS, all right? They are specific to TLS. In fact, that's where the X509 certificates are mainly used. They are mainly for TLS. So we can just copy paste these here, and everything should work just like before as we had right here, okay? So let's go ahead and do it. I'm going to copy the Facebook cert, paste it here in the TLS folder. Let's also, again, imagine that whatever we have inside of the folders are the private space of that entity, okay? So I'm going to also copy-paste the Facebook private, but paste it only here in the server folder because we don't want the client to be able to access it. So here's the Facebook private key. I'll copy this one and then paste it here in the server folder. All right, great. So now let's put in these two. I'm going to run them from the TLS folder. So going back to my terminal, navigate right here. This is how I'm going to run them. So I'll say node server and then app.js. So this is my current working directory. So I need to specify the paths relative to the TLS folder. So here for the private key, we need to go to server and then /facebook-private.pem. Here, this is in our root. So we need to say facebook-cert.pem. All right, so now we have our server object, and we've got a few events that we can access here. One of them is connection, and here, this is like the connection in net module. So at this point, nothing is encrypted. We can go ahead and do a log. So I want to make something clear here. We have first this event, and we also have an event called secure connection. And here's where we're going to have our socket, which we can use to write and read data from. This is a duplex stream. And at this point, the whole thing is encrypted. So here, when we get the connection, this is just a regular TCP connection. All right, so let me make it clear. So I'll add in one log that TCP handshake successfully completed and traffic is not encrypted yet. All right, now here, once we get this event, it means that now we have something called our TLS handshake done. So I'll say TLS handshake successfully completed and secure connection established. So we have two handshakes here. One is for TCP and one is for TLS. Here at this point, we have the standard stuff like .on data. And then here we receive some amount of data. We can go ahead and log it maybe. We can also write something to the socket. So socket.write, maybe I'll say hello from Facebook. And here we can send buffers, so we can send files or whatever else that we have. Now, let me also go ahead and fire up the server. So let's define our port. We'll go with port 8000 and then server.listen on port. For the IP address, I'll put in the localhost address, which is 127.0.0.1. And then here, I'll say console.log Facebook server running on port. We're calling it Facebook server, which sounds a little funny, but hopefully you get the point of why we have this. And let's also log maybe server.address. All right, let's talk a little more about this secure connection event here. So let's see what happens here in the TLS handshake. So I'm going to go back here to the slides. So we have a client, we have a server, and at first what happens after the TCP connection is established is that the client is going to send a request to the server. So in a TCP packet, the client is going to say that, look, server, I support these ciphers and these TLS versions. All right, so for example, I support AES, I support ChaCha20, I support the GCM mode. So all of that stuff is going to happen right here. In one packet, it's sent over to the server. Now, the server is going to look over them. It's going to choose something, for example, a cipher that it also supports, and then send back a response to the client. So in the response, the server is going to send its own certificate, so the X509 certificate, and the chosen stuff, like what cipher or what key size to go with, and also the TLS version. After the client grabs the certificate, well, it's going to do the usual stuff. It's going to grab the CA as well, and then use the public key of the CA to verify the signature, okay? And also go through the certificate chain to reach, finally, one root CA. And then once it verifies that the certificate is valid, it is going to send a finish message back to the server, and the server is also going to send one last finish message back to the client. And at this point, now we have our connection established. So now at this point, both entities have access to the same shared secret, so to the same AES key, and they can now use that key to encrypt the whole thing, all right? So at this point, once we get this event, it means that that handshake was completed, and we both now have access to the same key. This right here, though, is just the TCP handshake. In fact, in production, so let me add a comment here, you don't even need to have this thing right here. So in production, we don't really need to do anything with this event when using TLS. When using the net module and you want stuff to be unencrypted, well, then you get this connection event there. The server type right here, so here we are creating a TLS server, and the type of this server is TLS.server. Now this extends the server from the net module. That's why we also have this one right here. And it looks very similar to, well, whatever stuff we had in the net module. Now I'm adding this type right here if you want to go ahead and take a look in the node documentation so that you know what the type of this server right here is and what sort of events and functions we have available on it. Now let's go on ahead and try to run it and see what's going to happen. So here I'll hit enter, and it says, well, Facebook server running on port 8000. Again, the port right here is just a TCP port. We do not need to use any special port. Port 443 is not anything specific to TLS. That port is just something that we commonly use for HTTPS, but we don't have to stick with that. Now, we can go on ahead and start to work on the client file. So I'll open up the client and let's try to first include the TLS module. And then we can say const client equals TLS.connect. Now here we can specify some options. So let's put them here in this options. So const options. We're going to have our host. Our host is www.facebook.com or whatever else domain name you went with. Also make sure that your DNS is set up correctly. The port here, port 8000. And let's leave it at this right now. And then here at this point, we have the client object. So here I'll say connecting to the server, and type of this client is TLS.TLS socket. All right. Again, we can just write and read from this. This is a duplex stream, so we can pipe and do all that stuff that we have mentioned in the streams section. So let's first do a log. I'll say connected to server, and then I'll add one more log here to log the certificate that we've got. So I'll say Facebook's certificate, and then we have something available on this client socket called get peer certificate. This is going to give us the certificate that was given to us by the peer connection, which in this case is the server, okay? And also at this point, because we have everything established, we can also log the cipher that was negotiated. So I'll say console.log cipher suite and TLS version negotiated, and then I'll log client dot, we have this function called get cipher. And this is exactly what I have put right here. Now let's also send some amount of data to the server. So I'll say client dot write, and let's just say hello from a user. Now also we have an event available here on the client to read the data coming from the server. In fact, let's add it right here maybe. So I'll say client dot on data. Again, these are just standard streams stuff. So if you are not familiar with how they work, please refer to the stream section and also the event emitter and, well, also the networking module. So here I'll just say, let's log the received data first. So console.log received from server, and we can just say data.toString, and that should be pretty much it. We can also go on ahead and maybe end the connection at this point, but we don't have to. If we want to keep it open and keep sending data back and forth, we can just omit this line and then continue on doing something. We can just keep building on it. So you can have the exact same things that we built in the networking module. So the file uploader application or the chat application, you can do them here with the TLS module. And what you're doing is, well, you're now kind of putting this TLS in between these two protocols that we had. All right, so you just need to copy paste all of that stuff, but wrap it around this TLS. Because this TLS socket, this extends the net module, all right? So we have access to all the same things that we had before. Let's add one more event here. So client.onEnd. Here at this point, we have the connection fully closed, disconnected from server. And here I'll add a comment, receiving data from the server. And let's now go on ahead and try to run this and see what's going to happen. I'll go back here to the server. We can also add a couple more things here. For example, here when we get the data, we are not logging it, so let's do that. So console.log received from client, and then data.toString. We can also add the end event, so socket.onEnd. And here I'll say client disconnected. We can also add in one error handler. Let me add it pretty quick. So server.on, this one is called TLS client, and then error. All of these are from the Node documentation. I'm not memorizing any of them. So here we get an error and then the socket again. So I'll just do a log TLS error and then the error that we've got. All right, so let's run it and see what's going to happen. There's one issue with it, and I want you to think about what this issue is. We are trying to establish a secure connection from here over to the server. All right, something's going to happen that we've seen before. So let's go ahead and restart the server. I'll create a new tab, and now I'm going to run the client file. So node client and then app.js. All right, so the error that we get is that it's unable to verify the certificate that it got. All right, so this is just like once you sign and you set up HTTPS, you go to the browser and you see an error that it's unable to verify the signature. Okay, but once you tell your browser or your system to trust that certificate, then everything is going to be just fine. So note here, like Firefox, is not using the system trusted CAs by default. It is using its own trusted CA list, just like again in Firefox. So we now need to tell Node to trust this uncc-cert.pem, all right? Because Node right now does not trust this root CA. So let me copy this and paste it here in the TLS. And here's how we would do it in Node. So in the TLS module, this would also be the same thing in the HTTPS module. So here in the options of the client, we have an option called CA. And in an array, we can specify whatever CAs that we want. All right, so these are the root CAs. Now, whatever you specify here is going to replace the whole thing. So you can grab the whole thing and then concatenate with it if you want. So if you want to connect to the outside internet quite often, that's what you should usually do. But here we just want to connect to our own server, so it's okay to replace everything with just the one that we trust. And for that, all we have to do is read it. So fs.readFileSync, and then I'll put in the uncc-cert.pem. And now with this in place, Node is going to trust this connection. More specifically, it's now going to be able to verify the signature because it knows what cert to use and also it trusts it. So let's go ahead and run this one more time. Actually, we need to also include the fs module here. So const fs equals require the fs. Data is not defined. Maybe I'm doing something wrong here. Oops, I forgot to add it here. There we go. All right, hopefully we're not going to get another error. Okay, cool. So now it says connected to the server, and if you take a look here, well, we've got a couple of errors from before. So let me restart and then do it again. Now in the server, we get that the TCP handshake was done, and then the TLS handshake was done, and it received hello from a user, and then the client disconnected. So back right here, if we scroll all the way up, here it says this is our Facebook certificate. This is, well, what we saw before. So we have the alt names as these. We have the subject as this. We also have the public key info. And then if we scroll down, here it says Cypher Suite and TLS version negotiated. So this is the exact same thing that we saw here in Firefox. So here if we go to any website and then we click on more information, this thing here that we see, this is our Cypher Suite, okay? So we know now what TLS version we're using and also the encryption method used. So here, this is the same exact thing. So we're using AES with a 256-bit key, we're using the GCM mode, and for the hashing, we're using SHA-384. And also for the versions, we're using TLS version 1.3. Now we have two common versions of TLS. One is version 1.2 and version 1.3. We have a couple more here, 1.1 for example, but everything else is now fully deprecated. We also have SSL that was before TLS, and you'll hear this quite a lot. This is also fully deprecated. TLS has replaced SSL, and we no longer really use it. unless it's a very, very old machine. But right now, we only have 2 versions to worry about, and 1.3, you should stick with this as much as you can, but 1.2 is also good. It's not considered unsecure, it's just slower. You have access to more options, to more ciphers here with 1.2, but a lot of them are deprecated. So with 1.3, you have less options, but more secure ones, okay? Now, also, one very important point that I want to mention here is that 1.3 does not support RSA for key transport. So no support for this, all right? Now, we're going to talk about why this is the case in the next video when we're talking about Diffie-Hellman and elliptic curves. There you'll know why this is not the case, but it's not that RSA is no longer secure. With RSA, we have a private and a public key for the server, right? And the server uses its private key to decrypt the messages that it's getting from the client. So the client is going to encrypt a secret with the server's public key, and then the server is going to decrypt it using its own private key. Now, one problem with this is that if an attacker gets their hands on the private key of the server, they can now go on ahead and decrypt all the past communications, provided, of course, that the attacker has all these ciphertext over time. And if they have done that, they can now go on ahead and decrypt everything that they have gathered, which is quite a bit of a problem. But with Diffie-Hellman, what we're doing is that we're going to generate a new key for each session, okay? So now, even if the server gets hacked, only those particular sessions at that time could be decrypted and not everything before, all right? So that's one reason that we no longer use RSA for the key transport in 1.3, but it's still supported in 1.2. Now, another good advantage of 1.3 is that the handshake process is about 2 times faster compared to 1.2. All right, I'm not going to really get into why, but we're saving 1 round trip. So it's faster, but the rest is not necessarily faster. So the actual encryption of the traffic is going to have the same performance regardless of the TLS version. But in the initial handshake process, 1.3 is quite faster compared to 1.2. So again, 3 points about this. No RSA support here. It's faster in the handshake process. And also, it no longer supports many of the legacy and deprecated ciphers. So that's why sticking with 1.3 is always a good idea. And if you get a client that does not support this, you can easily fall back on 1.2. All right, so that's it also about the TLS versions, and you should also now fully understand what's happening here in this section. I want to mention one last point here about TLS, and that is mutual TLS. Right now, only the server has a certificate, and the client does not have a certificate. Well, which is what is usually the case when we are browsing the internet. We do not have a certificate as clients, and we only verify the ones from the servers that we are trying to connect to. But sometimes being able to verify the client is a good idea. For example, if you are using microservices and you have 2 servers that are connected over the internet, you want to have a good way to make sure that if your posts server, for example, is talking to, I don't know, maybe the comments server, and these 2 are maybe on 2 separate regions. So the post server wants to authenticate the comments, and the comments server also wants to authenticate the posts, right? So in this case, it also makes sense for the client, whoever is going to be in this case, to also have a certificate and give that certificate to the server for verification. We are not doing that here at this point, and if we do that, it is called mutual TLS or MTLS. Now, we're not really going to do it. It's straightforward. If you want to do it, just generate one new certificate and a private key for the client and specify them here in the cert and key options. Also, whatever CA you use to sign them, make sure you specify that CA here in the server. So here you have to say CA is this. And just like that, you've got now a mutual TLS connection. So now both entities are going to verify the other one before establishing the connection. This could reduce down the risk of man in the middle and just make the whole thing more secure. So I'll copy paste a comment here. And here I have said what to do if you want to set it up. So uncomment this to do mutual TLS. And also make sure that the client has a valid certificate. So you need to specify the CA here. You can also specify it here as one thing or in one array if you want to maybe concatenate. And this is whatever CA was used to issue the client's certificate. Then here we have something called request cert. And if you set it to true, the server is also going to request a certificate from the client. And then there's one more reject unauthorized. And if you set this one to true, well, as the name suggests, it's going to reject people who don't have valid certificates. Or you can set it to false. In that case, regular clients can also connect without needing to give you a certificate. So you can also handle both. With one of them, you're going to give them maybe some special access because they have a certificate and you know who they are. And with the rest, I don't know, maybe you're going to do something else. So this is what you have to do here in the server section. And here in the client, I'm just going to say maybe, let me clean up a bit. I'll say maybe provide a cert and a key here as well if you want to do mutual TLS. Okay, and that would be pretty much it. Now also let me add a comment here that this means to only trust this root CA. So now we are replacing the whole thing. And here I'll just add a bit of more comments that we can also change this to MTLS for increased security, to reduce the risk of man in the middle attacks, and also unauthorized access. All right. So I'll leave it up to you to do if you want, but hopefully you understand what mutual TLS also is. All right, so let me do just one final recap. That at first we connect through TCP, and then we establish our TLS handshake. And once we get to this event, where is it? Let me go back here to the server. So once we get to the secure connection, whatever stuff we put here, so whatever we send back to the client will be encrypted, all right? Encrypted using AES in our case. We can also specify to use SHA-SHA-20. Now let me do one more run here, but this time around, I'll open up Wireshark and listen on my loopback interface. So I'll double click here, I'll send this, and then I'm going to stop capturing. All right, so we've got some stuff here that we don't need to worry about. But here, if you take a look, wherever we have this 8000 port number, these are for our application. So we first have the client hello. This is that first request that's sent over to the server from the client that, hey, I support these ciphers and these TLS versions. And then we get the server hello. This is where we get the change cipher spec, for example, meaning that the server now has chosen a specific cipher and a specific TLS version and all that stuff. All right, and then we send the actual data over, but we're not able to see it here. We're just seeing some gibberish. We're only seeing the ciphertext. We can sure see the IP address and also the port numbers, but that's pretty much it. We're not able to see anything else. So that hello from a user or hello from Facebook is fully encrypted. So this is the stuff that, well, the government, for example, or the ISP network, or anybody else, okay, they can take a look at all your packets, but they cannot understand what's happening deep inside of them, right? Because it's encrypted. And all this stuff really doesn't have anything to do with our program. So only this much is related to us, okay? Now also, it doesn't mean that if you're using your company's laptop and you're using TLS or HTTPS, for example, that your manager does not have any ability whatsoever to see what you're doing. In a lot of cases, especially if you're using a company device, they have probably installed maybe something on your machine, maybe a surveillance thing or something to monitor what you're doing. So if that's the case, it doesn't matter if you're using any encryption at all. Still, your manager is able to see whatever is going on. But that's usually maybe what you want in a workplace. But still, even in that case, you should use TLS. but just remember that your manager might be able to see it if they have access to your device, but still not the outside world. For example, still the ISP or other people connected to the network who are not authorized to have access to your computer still cannot see what's going on. So again, for as long as you keep your keys secure, you should be good to go. If they do get compromised, then it doesn't really matter how secure the encryption is. Alright, so that's it about TLS, one of the most common protocols here that you can use now, and whenever you can, you should use it. Please do not use unencrypted connections to production servers or databases. It's a massive problem, and using TLS, as you can see, is very straightforward. You don't need to handle anything. You just need to set up the certificates, and everything else is going to be encrypted for you behind the scenes. You can also now go to the Node.js documentation and take a look at the TLS module and be able to understand some of the things here, right? We haven't talked about all of them, but I'm sure if you want, you can dive deeper into them. We've only talked about the main important concepts. For example, one thing that you can do is to reuse a session, because establishing a TLS handshake over and over again might be a little more time consuming. So you can easily do a session reestablishment, and here are some of the events that you got to take care of. If you want to do that, you get this new session, you save it to an array or an object, and then whenever you get this resume session, you're going to pull it back from here and just resume the session, so you don't need to now negotiate everything from scratch again. Here at the beginning, it says that TLS, a set of protocols that rely on public key infrastructure, or PKI. It's a common term that you hear a lot in cryptography. We haven't directly talked about it, but this is just a system that handles the CAs, the certificates, the signatures, and the whole thing that we've talked about so far. So it's an infrastructure that is going to help us to handle all of the public keys and certificates and whatnot, all right? So you should know what this is if you look it up. The definition should make a lot of sense to you. We've talked about most of the things that a PKI system does, but not all of them. For example, we didn't talk about what's going to happen if a certificate then gets invalidated. So if the private key of a server gets stolen, the PKI has a system to revoke that certificate. But we haven't specifically talked about it, but this, well, just refers to this whole system of public keys. Then it talks about the OpenSSL commands here that we've also seen. Here it talks about perfect forward secrecy. We'll talk about this next in the section when we're going to talk about Diffie-Hellman. But this is essentially the idea that if the private key of the server gets stolen, the attacker should not be able to decrypt all the traffic gathered, all right? If they could do that, it means that we don't have perfect forward secrecy. We'll talk about it again later on in the section. All right, so I'll leave it at this, and that's it about the TLS module. So I'll see you in the next video. In this video, we're going to talk about the key exchange protocol, and also at the end of the video, we're going to talk about some digital signature algorithms that are based on something called an elliptic curve. So far in this section, we haven't really talked about the key exchange protocol, and the main algorithm that's used for this process is Diffie-Hellman. All right, let's first talk about why would we need this. Recall that in the key transport, for example, using RSA, one entity, for example, the client trying to communicate with the server, would generate some amount of random data and then use the server's public key to encrypt the data and come up with a ciphertext. They will then transfer it over to the server. So here's where we have the key transport, and the server using the private key is going to decrypt it and end up with the same exact data. They would both now use the same KDF function to end up with the same AES key for the main traffic encryption. So this is the key transport protocol that we've been talking about so far in the section. Another one, which is way more common and standard right now, is the key exchange. Here, both entities have a private and a public key. Okay, so here I've got the client with its own private key and its own public key, and same here with the server. In key exchanges, we do not do any sort of encryption whatsoever. So we don't have any plain text or any ciphertext. Rather, what we do is that at the beginning of the connection in clear text, we're going to exchange our public keys like this. So now the client has the server public key, and also the server has the client public key. What's going to happen now is that each entity is going to use its own private key along with the other entity's public key to generate some amount of shared secret data. So the client right here is going to use the server public key along again with its own private key to end up with this shared secret, which is a few bytes in size, and the server is going to do the same thing. So using its own private key and the client's public key is going to now generate some amount of shared secret that's exactly identical to the shared secret that the client came up with. Again, we can do these because these keys are mathematically linked together. They are just numbers. So the private keys are just numbers. This private key is a gigantic number that was chosen randomly. And then the client's public key is, well, we take one number, we raise it to the power of the private key, and then we get its modulus, its remainder, by a gigantic prime number, all right? And the result is going to be the client's public key. Same with the server, all right? So the math behind it is very straightforward, but we're not going to get deep into it, all right? All I want you to know is that once we do this operation, we're going to both end up with the same shared secret that we can now both use the same KDF function on top to end up with the same AES or SHA-SHA-20 key, all right? Now, if you want to come up with the same shared secret and you only have the public keys, you're not going to be able to do it. You need to also have the private key of one entity to be able to do this process, okay? So this is how the key exchange protocol and, well, Diffie-Hellman works, okay? All right, let's see this in action in code. So we're going to now take a look at one Diffie-Hellman example. Please download the starter.zip file from the resource section of this video. And then here I've added a folder called Key Exchange. In this video, we're not going to do much coding. Instead, we're going to take a look at a few pieces of code, run them, and try to understand them. In the real world, you rarely need to do Diffie-Hellman from scratch. It's usually done for you behind the scenes. There are some cases where you might want to do it. For example, if you're trying to develop a protocol like TLS from scratch, or if you are trying to do some end-to-end encryption like WhatsApp and iMessage. In these cases, you will need to directly deal with Diffie-Hellman, but as a software engineer, again, you rarely need to do this, but it's important still to understand what they do. All right, let's take a look here. It's very easy. The math behind Diffie-Hellman is actually easier than RSA. So if you understood RSA fully, I can guarantee you that understanding Diffie-Hellman would be like no problem. But in this section, we're not going to talk about the math of Diffie-Hellman. All that I want you to know is that while we've got some amount of shared stuff, like a very gigantic prime number, and something called a generator, which is usually just number 2, so we've got these in our public space. And then each entity, for example, the server, is going to generate its own public and private key. So we have to call create Diffie-Hellman with this prime and generator, which are just 2 numbers. And then we're going to get a public and a private key, right? We have these two because it's an asymmetric algorithm. But again, remember that we're not doing any encryption here whatsoever. All right, so here I'm doing a bit of logging the public key and private key of the server. The clients would now do the same thing. So here the create Diffie-Hellman function is called with the same prime and generator. And also here we have the client public key and also the client private key. Now here we don't need to do anything with the private key. I'm just saving it here so that we can now take a look at the content and see what this is. All right, now if I scroll down, here's where we have the key exchange process. Now we're emulating it, but you can imagine that now at this point, the client would send its own public key over TCP to the server, and the server is going to do the same thing. So what's going to happen is here, the server will now call the compute secret with the client public key. So what this compute secret does is the exact same thing that we saw in the slides. It will now use this public key along with the server's private key to generate some amount of shared secret data, all right? And then I'm logging that. And also the client does the exact same thing. calls compute secret with the server's public key, all right? And that's pretty much it. It's very straightforward. It's actually easier than RSA. All that we're doing is exchange the public keys, and that's it. So let's go ahead and run this. I'll navigate over to the key exchange and node dh.js. So dh stands for Diffie-Hellman, which is again this one. So Diffie-Hellman is the main algorithm for the key exchange in cryptography. Okay, all right, if I run this, now it's going to take a little bit amount of time. We're going to talk about what we could do to fix it, but the reason that it's taking so long to run is because we're generating this prime from scratch. It's a very large prime number, and generating large prime numbers is not computationally easy, right? We have to go through many numbers, check whether or not each one is a prime, and also we're dealing with gigantic numbers, okay? Now, I'm going to wait a little bit here. I'll actually fast forward. All right, it's done. I don't know how long it took on your machine, but on mine, it took about a minute. All right, so let's take a look here, and then we're going to talk about this speed. And you might be wondering, all right, do we do this for every single TLS connection? Well, we do generate the keys, but what we're not going to do in TLS is to generate the prime and generator from scratch again, all right? So we already have them, and we're just going to use them, all right? They are out in public. We don't need to generate a new one for each key exchange, so everybody can use the same prime and generator right here, okay? So let's take a look here at the server. This is the prime number. It's absolutely gigantic, and this is in hex, so if you turn it into decimal, it's going to be even larger than this. And then if you scroll down, here's the server public key, and then the server private key. They are just numbers, okay? And then also the client, same with its own private key. And then here's where the key exchange happened, and now we have the same secret. So if you take a look at the server and client secrets, they do match, all right? Again, we're doing it here in the same file, but you can imagine that the client code is its own application, the server code is its own application, and here the client public key, for example, for the server is going to be read from maybe the net module or the HTTP module or something like that, okay? All right, now let's talk about that long amount of time that it took. In the real world, we're not going to do this for every single key exchange. If you open up this file, Diffie-Hellman-TLS, this is a better emulation for what happens in the TLS protocol for each connection establishment. Here, you don't need to do this first part at all to specify the key size, for example, and then get the prime. All you have to do is only specify a group name, mod P15, for example. The key size for this is 3072 bits. Same with here, we also have the same key size. So all you have to do is specify the group here, and the prime and generator are already chosen for us. And I have also put them here in a comment what these two are. So the prime is this. It's quite gigantic. Also the generator, which is only number 2. So now this is going to run way faster than before. And I'm also logging the prime number and the generator, but we don't have to. And then here, it's even simpler than what we had before. So I'm not logging the private keys anymore. So here I'm grabbing the server public key by calling server.generateKeys after calling this create Diffie-Hellman group. And then same with the client. And I'm also logging, well, actually, I think I meant to do it with the clients over here, just to show you that the primes and generators also do match. All right, let's leave it at this. And then here we have the public key of the client, and here we also have the compute secret. So everything is just like before, but instead we have this group. We've got a couple different groups, for example, mod P16 or mod P15. Each one has its own large prime number, and also the key sizes for each one is different. So if you increase this number, your key size will also increase, therefore your security will increase. Okay, let me now run this. So node Diffie-Hellman-TLS, this would now run way faster, and this is what happens in each TLS connection, okay? So here's the prime number, which also matches with the client's prime number, And then just like before, I'm logging the public key over here. This is our generator, and all the numbers here are in hex. And if I scroll down here, if you take a look at the computed secret, they do match, right? So all we have to do at this point is run a KDF function on top of both using maybe SHA-512 or SHA-256 hash algorithm, and we would both now end up with the same AES key. All right, that's it about Diffie-Hellman really, and quite straightforward. Again, I've added a whole lot of comments and logs here, but if you remove all of them, you're going to see that it's only a few lines of code, okay? Now, Diffie-Hellman itself is actually by itself rarely used again in production, and the reason is that our key sizes are quite large. So what we're going to do is to combine Diffie-Hellman with something called an elliptic curve. So an elliptic curve is just a mathematical thing. So we're going to swap out a portion of the math here in Diffie-Hellman with this new mathematical thing called elliptic curve, okay? And as a result, we're going to have the same amount of security, but our key sizes will be vastly smaller. So now in our key exchange protocol, we need to transfer less, which is quite a great save of resources. Now still, it's Diffie-Hellman. Everything works just like before, so we exchange the public keys, and we use the public key of the other endpoint and our own private key to generate the secret. So that's also what's happening in elliptic curve Diffie-Hellman. Let's take a look at one example. Here, if you open up this ECDH, so ECDH stands for elliptic curve, so EC stands for elliptic curve, and DH stands for Diffie-Hellman. And when we combine both, well, we're going to call it elliptic curve Diffie-Hellman. So here we've got different curves that we were going to specify. Let's see one example, and then I'm going to talk more about what these curves are. So here we're going to call create elliptic curve Diffie-Hellman. We'll specify a curve. The key size is already in the curve itself, so we don't need to specify that. And then here we get the public key, we get the server private key, and we do the same thing here with the client. And just like before, all we have to do is call compute secret with the other endpoint's public key, and that's it. Then I'm logging them both right here. Here, we're actually getting the same amount of security as this Diffie-Hellman, but our key size is way smaller. Here we have 3072 bits. And here in the elliptic curve Diffie-Hellman, we only have 256 bits. So elliptic curve Diffie-Hellman is way more performant than raw Diffie-Hellman on its own. Okay, let's run this. So node elliptic curve ecdh.js, and you can see that it ran in just no time, and our keys are also way smaller than what we saw before, okay? And the computed secrets are also identical. I want to just show you one thing. Here I've added again tons of comments and logs, but here I have one more example. So let me remove everything that I've got and paste this one. This is how it would look like with no logs and comments, all right? Just a little bit of amount right here, okay? So all you have to do again is to call this create, then generate the keys. You don't even need to do anything with the private key. I was only saving it to log it to show it to you, but you only need to deal with the public key like this. Then you're going to call the compute secret, and also you can imagine that at this point, we're going to share our public keys in clear text, and then I'm logging whether or not they're equal. So let me run it one more time. Oops, I actually removed the includes line, so let me add it back in. And now we're going to get this true message, okay? So that's it. That's really all that happens here in elliptic curve Diffie-Hellman. Again, the same logic here, but just a bit of the Diffie-Hellman math is swapped out with this new mathematical thing. Let me back up here. We don't need to take a look at this. Now, I just want to talk about one quick point before we talk about the curves. You might be wondering, why do we have to worry about this whole idea of key exchange? Why not just use RSA to do the key transport and just call it a day? Well, first of all, this is way more performant than, well, doing it with RSA, way faster. And because of this performance that we have now, we can achieve something called perfect forward secrecy. Now, what this means is that if you're talking to an entity and your connection is encrypted, you need to have a peace of mind that you have forward secrecy. Meaning, if in the future, maybe a couple of months from now or a couple of years from now, the server or your other endpoint gets compromised and their private key gets stolen, your traffic would not get decrypted, all right? So using RSA, what could happen? If we go back right here, an attacker can be somewhere right here in the middle, hoarding all these ciphertexts that are getting exchanged, and then maybe in a little bit amount of time, in a couple months or years, the attacker will hack the server, grab the private key, and what they could do is that they can now decrypt all that ciphertext that they have gathered, which is a big problem. This is why RSA is no longer supported in TLS version 1.3 for the key transport. And even in TLS version 1.2, it was discouraged to use RSA for the key transport, and instead many used Diffie-Hellman to do the key exchange, all right? Usually Diffie-Hellman with elliptic curve to increase the performance quite a bit. So now, here in the key exchange, because it's way more efficient, what we're going to do is to generate a new pair of keys for both entities for each TLS connection, all right? And then after we're done with our connection, we're going to get rid of the keys completely, all right? So the keys will be totally destroyed. So even if an attacker gathers the ciphertext and they manage to hack the server, they're not going to be able to decrypt that ciphertext, all right? Because the keys that were used to generate the AES key are now totally gone. In fact, here, let me go to the Node.js documentation, and in the TLS module, if I scroll a little bit down to find the ciphers that are supported, here, for example, it says DHE. So this E here stands for ephemeral. Let me see if I can find that here. So it's mentioned in a couple of different places. So an ephemeral key exchange. What this ephemeral means, here it's talking about it in the perfect forward secrecy section. This means, well, short-lived, okay? We add this E at the end, so Diffie-Hellman ephemeral, or elliptic curve Diffie-Hellman ephemeral. This means that after we are done with the key exchange, we're going to totally get rid of the keys, all right? So that's the ephemeral version of the elliptic curve. Everything would be exactly identical as you can see right here, but you can imagine that here at this point, you're going to delete the keys and that's it, all right? So it's not like another algorithm. This DHE is not another algorithm. It's just the idea that you have to get rid of the keys after each key agreement, okay? So that's one of the main reasons why it's way better to use Diffie-Hellman or elliptic curve Diffie-Hellman to do this key exchange as opposed to using RSA to do it. All right, let's now talk a bit about the curves that we have, all right? Why is it even called a curve? Now I'm going to open up my Mac Grapher application, and I want to show you a few graphs here. So the elliptic curves, let me hide most of them. The elliptic curves, as the name suggests, are just curves, all right? They have a mathematical formula, which for this one, I have written it down here. So it's y squared equals x cubed minus x plus 1. All right, so we have a mathematical equation for each one of the curves that we have. We have actually a whole lot of them. So here, if I go into the node REPL and then grab the crypto, there's a function called crypto.getCurves. And you can see that we've got a whole lot of them. You can specify each one that you'd like here in the ECDH, all right? And each one of them has its own mathematical curve, okay? Now, a whole lot of them here are deprecated and also obsolete. You only need to worry about a couple of them. So the way that this elliptic curve thing works is that, remember that in the RSA, we had a final large number, so our modulus, and we knew that this is the result of two prime numbers that were multiplied together. But if we try to find those two prime numbers, it would take us trillions of years. So here in elliptic curve, we have a concept similar to that. So what we're doing here is that we have a starting point on this curve, and we're going to get a tangent line over this. If I pick this point and draw one line tangent to it, it is going to intersect with the curve in this other location, all right, right here. one characteristic of all these elliptic curves is that they are all symmetrical here with respect to the x-axis. All right, so if I divide it in half, we're going to end up with two exact lines right here. So here we have our point of intersection, and if you mirror that point again with respect to this x-axis, you're going to end up in this other point on the curve. All right, so you're going to continue on doing this. You have a point, you do this, and then keep doing it. Essentially, all that we're doing is that we're multiplying this point by a scalar, right? By just another number. And we're going to do this process of multiplying and moving this point around on the curve many, many, many times, all right? And then we're going to end up with a final point, maybe a point right here. So we had our starting point right here, and we did that process maybe a couple of trillion times, and we ended up with this point, okay? The coordinates of these 2 points will be in our public key. But the amount of times that we did this multiplication will be then in our private key. So if you have 2 points on a curve and you try to figure out how we ended up here, so how many times we had to multiply this starting point by a number to end up right here, you have no idea to figure that out. It's like factoring out the modulus that we had in RSA. It was very difficult. Same thing here. It would take us trillions of years. Here, I have added another file, elliptic curve Diffie-Hellman coordinates. Here I have one quick function, parse public key. It's going to get the public key, and well, the first byte is just something that means the key format is uncompressed. But then the next 32 bytes are the x-coordinate, and then the next 32 bytes are the y-coordinate. So I'm running the exact same thing here. So I'm generating these keys for both the server and the client. This starting point is also something static for each curve. So I'm also putting it right here. And then here I'm logging the public keys in this format, so the x and y coordinates of them. All right, so let me run this pretty quick here. Node ecdh-coordinates.js. So here, if you take a look, our starting point coordinate is this, and then here's our public key, which is just this coordinate on the curve, but you can see that they are very, very large, okay? And our private key is also how many times we had to multiply this starting point to end up in this final position, right? So this is our final point, and our thing called a generator is called our starting point. Now this is also in public, so in the specification of each curve, you can take a look and see what is the starting point. And for this curve, this particular curve, the starting point is always this, okay? And we have, well, a couple more curves. I'm going to show you a couple of them. This curve, for example, this is a very common one. Y squared equals x cubed plus 7. This is what Bitcoin uses, and we'll talk about that later on a bit. Same idea there. So starting point somewhere, multiplying and all that stuff. And here I'm going to show you just a couple of these curves just so that you get an idea of how they might look like. And actually, let's talk about the common forms of them. We have 3 main forms of elliptic curves. One form is called Weierstrass, and the equation looks like this. Y squared equals x cubed plus ax plus b, and the a and b are constants. This is the most common one, and also it's a NIST standard. And some of the common ones are these. This ECDSA is elliptic curve digital signature. We'll talk about it later on. And also this main one, and also prime 256 v1. Another common format is the Montgomery form. The equation looks like this, and here we only need the x-coordinate to do the key exchange, and 2 of the common ones are these 2. Now, we haven't talked about this one yet, and you're not able to actually just use it like putting it here. So if you try to put that x number here, it's not going to work because it's a new modern curve. The API for it is different. So for that, here I've added another file just so that you see it. This is also still an elliptic curve, but it's a specific implementation of it, and it's one of the most modern key exchange algorithms that we have right now, okay? Here, if you take a look, all you have to do is to now call generate key pair sync, and now you call Diffie-Hellman, but you specify the private and public key of these 2. and everything else is just like before, okay? So here, what this would return is the secret. Still, we're doing it based on the public and the private keys. All right, so that's as far as I want to talk about it. But again, this is a different form, and this is called, again, the Montgomery form. And the equation looks like this. And just to show you one example here in the Grapher application, this, for example, is a Montgomery form, and the rest that I've got right here, these are the Weierstrass forms, okay? The equations, again, look like this. All right, so one last point that I want to mention here before we move on to the digital signatures. So we mentioned that we're doing this key exchange thing, but you might be wondering, so how does it now play out in our TLS handshake? Here's what we had before in the key exchange, and I mentioned that at this point, after the connection is established, we both now have the same AES key, all right? But I didn't talk about how this key exchange happens, okay? So what will happen is that here in the client hello message, in the first packet that the client sends to the server, here we also have our client's Diffie-Hellman public key. By Diffie-Hellman, I mean the main algorithm. It's usually Diffie-Hellman elliptic curve, but you get the point. So we're going to send the public key over to the server, and the server is also going to send its own Diffie-Hellman public key back in this server hello message. Now here we're going to verify the certificate. Now, if you remember, one of the most important part of a certificate is, well, the public key part of the certificate. Now, that public key part can be used for two different cases, depending on what protocol we're using. So if we're using the key transport in TLS version 1.2, for example, which keep in mind is not recommended, in that case, the public key is used to do the actual key transport, okay? But if we are using the key exchange protocol, which is way more common now and the standard, in that case, the public key of the certificate is used for calculating a signature, all right? And sometimes the RSA algorithm is used for that. So in that case, RSA is used here to verify that the key that we're getting here really came from the server and not from a man in the middle. We do not have our Diffie-Hellman public key in our certificate. There's nothing in the certificate that even mentions that we're using Diffie-Hellman. That's negotiated by TLS itself. But what we're going to do here is that the server is going to compute one signature over all the data that was transferred, okay? So the server will grab the client Diffie-Hellman key with its own public key and then, well, do a crypto.sign, for example, all right? So it would now calculate a signature over everything that was transferred, and then transfer the signature over to the client. The client will now use the server's public key, because if you remember, these signatures are done using the private key. So now the client would use the server's public key to verify the signature, okay? And if the signature matches, it means that, well, the Diffie-Hellman public key really came from the server, right? A man in the middle cannot compute a valid signature with that data because, well, the person does not have the private key of the server. Now, please pause the video if you need a minute to digest what's going on here. This idea of signature could maybe take a little while for you to totally get comfortable with. Again, remember that all that we're doing in a signature is to calculate a hash and then encrypt the hash, and that's it, okay? So if you take a look at some of the common ciphers that we've got here in the TLS, so let me try to find this section again, all of them have a hash function as well, all right? So this is the hash algorithm that's used to calculate the signature and anywhere else that we need to use a hash function for. For example, running a KDF function on top of the shared secret. There also we need to specify a hash algorithm, and this is also what's used. So the hashes, they're not used in only one place. They're used for everywhere in the handshake process where we need to do some hashing. So that's also why you see elliptic curve Diffie-Hellman used with RSA, right? So the RSA here is what's used to do the process of making sure that the elliptic curve Diffie-Hellman is really coming from the server, okay? All right, so that's pretty much it about the key exchange protocol. Now, at this point, you should be able to totally understand what's going on in a cipher, okay? This video is getting pretty long, so I'm going to cut it right now, and in the next video, we're going to continue on with our discussion more specifically about elliptic curves in digital signatures. Alright, now let's talk about elliptic curve digital signatures. We know that RSA is one of the most common ones, but we also have a couple other digital signature algorithms that we're going to now discuss. The main reason why we have these other algorithms is because RSA, as you know, is a little slow in calculating a signature, alright? So when we're doing this sign, we're using our gigantic private exponent. So that takes a bit of time to complete. But, well, on the other side, the verification is incredibly fast because we're using that small e number. Now, this is not a problem in the CA signatures because CA needs to compute a signature for each certificate only once. And for that one signature, there could potentially be millions of verifications, okay? But in the TLS example, if you pay attention right here, for each TLS handshake, the server needs to compute a signature, okay? So this could add up to something quite big. If the server gets maybe thousands of concurrent connections and it needs to compute a signature thousands of times, maybe per minute or per second, that could be quite a whole lot with RSA. All right, still possible, but using elliptic curve signatures, the process of calculating a signature is now way faster, all right? Not only that, but also the final signature is way smaller in size compared to an RSA signature, which is quite large. So now we're doing less transfer over the network, and also if we want to save these signatures, we now need to use less disk space to save all of our signatures. All right, let's take a look at one example. It's very straightforward. In fact, I'm going to copy this rsa.js in the digital signatures folder and paste it again. We're going to change it to an elliptic curve one. So one of the most common elliptic curve algorithms is called elliptic curve DSA. DSA is an algorithm of its own, and it stands for Digital Signature Algorithm. DSA on its own is very rarely used, but DSA with elliptic curve is a way more common choice. Okay, so let's change it. Here in the generate keys, instead of RSA, we have to say EC, stands for elliptic curve, and then here, instead of having to specify a modulus length, we need to specify our curve. All right, so it's called name curve and then curve. So one more time, we have access to some of these curves by running console.log crypto.getCurves. We have access to a couple more that are actually more modern, and I'm going to talk about them in a bit. One of them is, as we saw here in the key exchange, is this X25519. You will not see this here in the get curves, but it's actually more modern. And TLS version 1.3 is now mainly using this one to do the key exchanges, okay? Now here we don't need the key size. Instead, let me specify the curve. Let's go with SECP. And then 256K1. Now this is the one that's used by Bitcoin. Another very common choice is if you change the K into R, still the key size is 256 bits. And this is what is usually used by TLS. I mean, it's the second choice after this X255. And these curves also are the same here in digital signatures and also the same in the key exchanges, all right? But there's actually something very interesting about this curve and some of the other curves of this family, and that's the potential of a backdoor existence. All right, that's the whole reason why Bitcoin went with this and not with the other one, and there could potentially be a backdoor. A lot of people have been talking about it, and I'm not going to talk about the math of why there could be a backdoor, but just to very overly simplify this, let's say that we have a very gigantic number out there. And if you want to come up with that number yourself, if you want to calculate it, it would take you trillions of years. But the people who know it, well, then they know it, right? The people who picked that number, they have access to it. And that's kind of the same idea here, why we have a backdoor. It's related to the concept of randomness. We have a number and we don't really know if it's truly random or not. And if we want to figure it out on our own, it could take us a very long time. But the people, well, the NIST organization who came up with that number, we don't know if they know that number and they could now, well, decrypt the whole thing, all right? Because if there's a backdoor inside of it, TLS has been using it for so long, those people could now potentially decrypt a good portion of the internet. Now, we do not know for sure if a backdoor exists in it, but there are some speculations. But that's on its own is enough suspicion to move away from it, okay? So that's why Bitcoin went with this. And well, with this one, there's no indication that there could be a backdoor, okay? Now, I'll link a video at the end of the section if you want to learn more about this backdoor, but that's as far as I want to talk about it. All right, so let's calculate one signature here using this curve. So everything else here is, well, just the same. We need to call create sign. And then here, I'm going to change this log to EC. Actually, I've already added this log. So let me run the RSA version once. So I'll navigate to the signatures and then node RSA. All right, so we get that our signature size is 3000 bits. And now let's do the same here with the elliptic curve. So I'll change this to ECDSA curve. Signature size is, well, the same thing, all right? And I'll leave everything else like before. So let's now run this one. So node ECDSA. And, well, we're getting a whole lot of things here, all the curves. But at the end, you can see that now our signature size is only 500 bits, which is way smaller than 3000. If you have billions of signatures, it could really add up. Now, fun fact again about Bitcoin. Now, keep bringing up Bitcoin. Please note that I'm not an advocate of Bitcoin or any other cryptocurrency. I just keep bringing it up because I consider it as a phenomenal piece of cryptographic engineering, and that's it, all right? So Bitcoin, as I mentioned, has decided to go with this instead of going with RSA, all right? And right now, the whole Bitcoin blockchain is about 0.5 terabyte, right? So about 500 gigabytes. And there are about 1 billion, so we have about 1 billion transactions in Bitcoin history, as of now that I'm recording, okay? Now, each transaction also has about 2 signatures. It could have 2 up to sometimes 10 signatures. On average, it's about 2.2, but let's say 2 signatures per transaction. So we have in total about 2 billion signatures. All right, this ECDSA signature, that each one is about 500 bits or about 70 bytes. Now, each person that wants to become a full node, which right now we have about 20,000 of them, if I'm not mistaken, needs to download the whole blockchain, so all the 500 gigabytes. And a good portion of this is for the signatures. So we have about 200 gigabytes of this allocated just for signatures. Now, if Bitcoin had decided to go with RSA instead of this, you can do a bit of math on your own that how much bigger this would have been. If it was using RSA, we needed to have about more than 0.5 terabyte, so just about 700 gigabytes for these signatures alone, all right? So the total size would exceed terabytes, and that's if Bitcoin had gone with RSA. And if you also do a bit more estimation on your own, like the cost of electricity, the transaction costs, it would have costed the world a couple more millions. So some simple changes like these, we're not only going with this elliptic curve because, well, it's a little faster. Sure, that's great. But if you add it up, if you are a popular website, like maybe Facebook or Google, making changes like these could add up to something quite big, all right? Having to save only 500 bits instead of having to save 3,000 could be quite substantial. So we're getting actually the same amount of security here with 500 bits as we would get here with RSA 3072, all right? So the security is pretty much the same thing, but here this is faster in calculating a signature, and also we have a much smaller signature size. That's why we need to care about these elliptic curve signatures, okay? But still, ECDSA verification process is slower than RSA. RSA is more efficient in verifying the signatures because of the great E number that we have, which is very small, and we have all those zeros in between in binary, which makes it very, very efficient in verifying signatures. Now, there's one other curve that I want to talk about, and let me maybe duplicate this again. So I'll copy it and paste it. I'll change this name to EDDSA. ED here stands for Edwards. Still, it's a digital signature algorithm, but slightly different. This one is considered to be one of the most modern ones, and it's based on the same curve as this, but now it's, well, for a signature. And this is what most cryptocurrencies are moving towards to. So let me change it here to use the other one. What we need to do here in generate key per sync, we need to specify ED, which is Edwards, and then the same number that we had, 25519. We do not need to specify anything else here. The key size is already chosen for us, and we don't have control over it. So let me remove this and remove this one. Now for signing, we don't have control over this hash algorithm. It is already chosen for us, again, in this algorithm. So we need to put in null. And because of that, we can't use create sign. Rather, we have to straight up use crypto.sign. And then here in the second argument, we need to put in our data to sign, and then the private key that we have generated. So I'll remove this, and here we'll get our signature. So I'll remove this one. We can keep one log here, but let me copy this one, put it right here. So I'll say this signature size is this. And then to verify, it's also more straightforward. So we have to say crypto.verify, pretty much the same thing as before. So here it's going to be null, and then data to verify, and then the public key this time, and also the signature. I'll remove this. This would now be a true or false. So I'll change this to is signature valid. And then we can log it here at the end, and that's pretty much it. So let me run this. Node ed DSA. The signature size is pretty much the same as before, but this is now more efficient. So this is more modern, and that's why I'm mentioning it here. Okay. Now again, this is not mentioned here in the curves because it has its own API, and you can also see that we're using it in a little different way. And I know that these curves are getting a little confusing because we have so much of them. We have this new API here, and then tons of curves here in this section. So let me try to maybe make it a little simpler for you. So all these curves that you see here, most of them are obsolete and completely deprecated. So I'd say that the only two ones here that you need to worry about are the SECP family here and also the Prime family. Okay, some of them are also, well, we have a bit of suspicion that there could be a backdoor in them. So also keep that in mind. And some key sizes here are also too small that we should not be using them. But in general, these are the two families that we have to use. The rest, they're rarely used in the real world, and most of them, again, are deprecated. And also back here in the slides, for all these elliptic curves, we have three common forms. This first one, which the equation looks like this, then the Montgomery form, which the equation looks like this. This is where we have this x25519 and x448. This is also something else that you can use. So here, you can change this one to x448, but this is rarely used. x25519 is way more common than this, but still this would work fine. So let me create a new tab just to run it once. So node, and then what did we call it? x2, but we're using the other one, but you get the point. So still works the same way, but yeah, this is way more common. So these are in the Montgomery form of the elliptic curves, and the equation again looks like this. We have another form, it's called the Edwards form, and the equation is like this. The D here is a constant, and these are used in the digital signature algorithms like ED25519, and same with ED448, but again, ED448 is way less commonly used than this, all right? And if you're curious to take a look at an Edwards form curve, let me pull up my grapher again. This is how usually a curve that's Weierstrass or Montgomery looks, but the Edwards form is quite different. So this is a curve in the Edwards form. Again, the equation is like this. X squared plus y squared equals 1 plus a constant times x squared times y squared. But still, the idea is the same. We have a starting point, we move it around, and then we're going to end up with a final point. All right, so three forms that you got to worry about. Pretty much all these forms that you see here in the get curves, they are the Weierstrass forms, okay? And this x thing here with this or 448, this is the Montgomery form, and here in the EDDSA, this is the Edwards form, okay? All right, so that's it about elliptic curve signatures, and now going back to our TLS ciphers right here, the whole thing should now make total sense to you. All right, so here's, for example, where the ECDSA is used with elliptic curve Diffie-Hellman to do this process. Now, these ones are for TLS version 1.2, and the first 3 ones are TLS version 1.3. And you can see that the key exchange protocol is not mentioned here. That's because TLS version 1.3 mainly uses elliptic curve Diffie-Hellman, all right, with this algorithm right here, right, X25519. So it's not even mentioned here because RSA is now completely deprecated for use in the key transport. But, well, whenever you see TLS 1.3, it's almost a guarantee that it's using elliptic curve Diffie-Hellman. But here in the 1.2 ones, you can also see, well, the actual protocol for key exchange and also the digital signature one. So ECDSA, and let me go back to Firefox. Here in google.com, let's try to take a look at the certificate one more time. So here you can see that the public key info is elliptic curve, meaning that this is ECDSA, all right? And the public value here is very small, way smaller than if it were to be an RSA one. So now everyone who wants to connect to Google needs to use this to verify a signature that Google will send to them, all right? So Google, for each connection, has to use this to calculate a signature over everything transferred so far for that connection, and the client would then use this one to verify the signature, right? And what they're going to do is exactly like what we see here, right? So Google is going to sign. Data to sign would be, you can imagine, the keys exchanged and some other stuff like the cipher chosen, the TLS version, and stuff like that. And then here, where the third party is verifying the signature, this is what the client would do to verify the signature that Google just gave them. All right, so now that's it about the elliptic curve signatures. So now we should have a much better idea about the Diffie-Hellman and elliptic curve stuff, all right? Again, Diffie-Hellman is only used for key exchange. All of these that you see here are based on Diffie-Hellman, even this one, okay? And these signature ones, they are based on, well, just elliptic curve. Elliptic curve itself is just a mathematical thing. It does not do the actual key exchange or the actual calculating the signature. We'll talk a bit about what the elliptic curves are, that they are just the curves. We have a starting point and a final point. It's very hard to figure out how many times that starting point was multiplied to end up with that final point, okay? All right, that's it about this video, and I'll see you in the next one. In this video, we're going to talk about the security of RSA, elliptic curve cryptography, and also Diffie-Hellman. We're going to see what it takes to break them. Now, we do not have a mathematical attack against any of them to consider any of them to be broken, and the only real threat that we have to asymmetric cryptography as of now is quantum computing. So we're going to talk about that for a bit in this video. Now, let's take a look at a table, and here we can see how secure each of the algorithms that we've discussed are. Now, this is a table that I grabbed from a NIST specification, which I will link to the resource section of this video. Title of this is a recommendation for key management. And if you go into page 67, here in this table, it mentions what is the security strength of each of the algorithms, all right? For example, the AES-128 has a 128-bit security, all right? Meaning that if we want to break this one, it's going to take about 2 to the power of 128 operations to do so. Now, we talked about how long this will take to complete on current supercomputers, which we know is trillions of years. Now, for the asymmetric algorithms, we can't just easily compute that, but we have an estimation, all right? I'm not going to talk about how this estimation was calculated, but for example, here it mentions that if you want to go with RSA and get the same security as a 128-bit security, you're going to have to go with a key size that's 3072, all right? So your modulus length should be 3072 bits in size if you want to get the same security as AES-128, all right? So now breaking both of these would roughly take the same amount of time to complete on current computers, alright? So that's what this table means, but I simplified it a bit and put it here. So we have AES, we have RSA, and Diffie-Hellman. You can see that we're going to get the same security level here in RSA and Diffie-Hellman using the same key size, alright? So if you want to have a 112-bit security in RSA and Diffie-Hellman, you're going to have to go with a 2048-bit key size, alright? But here, if you pay attention, the elliptic curve ones have a significantly lower key size to give us the same security level, alright? So if you want to get the same security as AES 128, which is a 128-bit security, with RSA you're going to have to go with 3072, which is quite large. But with elliptic curve, for example, going with elliptic curve Diffie-Hellman, your key size only has to be 256 bits, alright? Same with your signature sizes, so here with ECDSA and these Edwards curves, you're going to have a much smaller signature size compared to RSA, okay? And still you have the same amount of security level, okay? So in the real world, if you want to go with RSA, please make sure that you go at least with 248. If you go with anything smaller than this, that is considered broken, okay? Because on current computers, we can break, for example, RSA 512 in almost no time. So you should stay away from smaller key sizes. Now, please do not memorize this, and always before you're about to choose a key size, look online on reputable sources to see what is the right key size that you should go with at that point of time. RSA 248 is secure right now that I'm recording this video, but maybe in a couple of years it won't be, right? So it's something that you always have to check at that point of time. But right now here, I just want to give you some rough ideas about what to go with right now in 2025. So again, I just want to mention it one more time. Everything that we have here, these are all key sizes of these algorithms. And also here, this is the corresponding security level that we're going to get for each of the key sizes, okay? So if you pay attention here, X448 and ED448, we know that ED448 is a digital signature one and X448 is for key exchange. We mentioned before that these are not used much in production, all right? But if you take a look here, we're going to get a much higher security compared to, for example, X25519, okay? But the thing is that it doesn't really matter. The performance trade-off is not really worth it. Because the higher security level that you have, the slower your application, alright? So X448 is very secure, but it is slower compared to X25519. And we know that on current supercomputers, it's going to take us trillions of years to break 128 security level, alright? We know that we cannot do this. So going with this is good enough, alright? And we don't need to go higher than this. Now, having said that, you're going to see that AES 256 is used quite a bit, even though we know that AES 128 is secure enough. Now, the reason that this is the case is that AES 256 is quantum resistant. It is not quantum proof, but it is quantum resistant, meaning that with AES 256, once we get powerful enough quantum computers, maybe in a decade or two, the security level is going to drop from 256 to somewhere around here, right? 100 bits something. It is still incredibly secure, and we cannot break AES 256 even if we have very powerful quantum computers, all right? That is not, however, the case here with asymmetric ones. All of these will be broken in essentially no time with quantum computers, all right? So none of them is either quantum resistant or quantum proof. All these security levels here for the asymmetric ones with quantum computers will be essentially dropped down to a 0-bit level. So it doesn't matter if you go with something crazy like RSA 15,000. Even this one will be broken in a couple of days or even hours with quantum computers, all right? So none of the asymmetric algorithms that we have discussed in this section are quantum resistant, all right? Quantum computers pose a real threat to all of them, and we know mathematically that the threat is very real, and it's not just an assumption that they will be broken. we know that mathematically they will all be broken. All right. And I want to mention that the thing that's going to break asymmetric cryptography as we know it is the Shor's algorithm. It's a quantum computing algorithm, and we're not going to talk about how it works, but what it's going to do. So if we go back to all the algorithms that we have, so elliptic curves, Diffie-Hellman, and RSA, all the asymmetric ones, they either get their security based on the integer factorization problem or based on the discrete logarithm problem, okay? Now, we know what this integer factorization problem is. It's very straightforward. I have defined them here in the cheat sheet. So if you scroll here to the asymmetric cryptography, here I have the integer factorization problem, which is the idea that if we have very large prime numbers and we multiply them together to end up with that modulus, and then we put it out there and don't let anybody know about our prime numbers, on current computers, it is impossible to break that, all right? So it is impossible to factor out that very large number. We have never been able to do that before. And the RSA algorithm is based on the problem, all right? So once we solve this problem, RSA will be essentially broken. We do not know as of now how to factor out a very, very large number, okay? But with the Shor's algorithm and quantum computing, that problem will be solved in a very short period of time, which is very fascinating. Now, also, with Diffie-Hellman and elliptic curve, these are based on a problem called discrete logarithm, okay? Now, this is also quite straightforward. All it means is that if we have a very large number that is this, so you take number g, for example, you raise it to the power of x, and then you get its remainder, or so-called modulus, by another large number, all right? So this is one number, and we know g and p, these are in our public keys, but we do not know x. X is only in our private key. So we know that on current computers, it is impossible and will take trillions of years to figure out what x is given g and p, all right? But again, on quantum computers with the Shor's algorithm, this will be broken in no time. And that means that Diffie-Hellman and also elliptic curve cryptography will be broken in essentially pretty much instant time, all right? In a very short period of time, a couple hours or days. So that's a real problem that we have, and as of now, TLS does not support any quantum-proof asymmetric algorithm. I'm sure that'll change in a couple of years. That's also why I did not cover post-quantum cryptography here in this section, because I believe that we are a very, very long way from quantum computers. To break these ones, we need to have a quantum computer that has at least 1 million qubits, and the best that we have done so far is a quantum computer with only 100 qubits. So we still have a very long way to go, and by the time that they become a reality and we get close, I'll make sure to update this section to also talk about post-quantum cryptography. Now, I'm sure that quantum computers are not a threat to your applications, because by the time that they become a reality, far before that time, you're going to move to these other secure ones. So all you have to do is swap out, for example, RSA with a newer one that's quantum proof. And there's a lot of research done in that field, and they look very promising. So I'm sure in just a little bit amount of time, we're going to have all these algorithms, and probably TLS and Node.js itself will also support them right out of the box. So if you're at this point in the course, I have no doubt that you'll be able to easily transition over to the secure ones. But still, quantum computers do pose a real threat to the internet as a whole. Again, the MD5 example. After it was broken, it took many applications, many years to migrate over to the secure hash algorithms, okay? So we're going to see the same thing happening with quantum computers. It's not going to be a shift overnight. It's going to take many years for all the applications and websites to migrate over to the quantum-resistant ones, okay? But I'm sure that'll be no problem to you. All right, that's it about the security of these asymmetric algorithms that we've discussed in the second part of the section. We know that they are all secure, and the only threat is quantum computing, which we are a very long way away from. And also we have a concern about some of the curves that we've discussed, that they may have a backdoor. Again, it's not proven, but there could be. And if there is something in there, the NSA organization is the one that knows about it. So some of the curves, not all of them, you can easily Google to see which ones are suspected of having this backdoor and which ones are secure. And there's no suspicion around them that there is a backdoor, okay? All right, that's it about this video, and I'll see you in the next one. Congratulations on completing this section. This was one of the most demanding sections of the course. For me as well, I had to put a far greater effort into making this module, and I'm glad that I did. I do believe that we have a problem in the software engineering community, and that is a lack of understanding of security and cryptography. This can result in making catastrophic mistakes in development and more. Not to mention the crazy amounts of conspiracy theories that we have around cryptography, which arise due to a lack of understanding of the field and the algorithms. And I strongly believe that this could be dangerous to society. If people start to subscribe to this idea that the algorithms are already broken and we have backdoors in them and governments and powerful organizations can already spy on us with ease, people might then think, why bother using cryptography or supporting independent cryptographic research or help protect this field in general? And if these false beliefs get stronger, this could result in public support for cryptography fading away, and this waning support would make it far easier for powerful organizations like governments to launch attacks on cryptography and slowly take it away from us without people even noticing. So you have now taken a valuable step forward. Remember though that security is a process that you've got to keep building on. There are people who dedicate years of their lives to this, and we have people who do their entire PhDs in cryptography and only focus on a single algorithm. So you can get as intense as you want in this field, and do not expect to be a security expert right now if this section was your first introduction to security and cryptography. But again, you have now taken a great leap forward in your security journey. You are now far better positioned to not only design more secure systems and communicate better with the cybersecurity experts on your team, but also to better protect yourself digitally. I do believe that the topics that we've covered here are the bare minimum that software engineers need to understand. You now can make more informed choices about what algorithms to go with and why, and avoid some of the common pitfalls like using weak ciphers or not doing proper key handling. But still remember that you've got to keep yourself updated and continue the learning process. Now I'm going to leave you with some resources here in this video. And again, remember that this was a very intense section. We had a lot of topics to cover, so do not feel bad if you have to do it again. In fact, I encourage you to do this section maybe another time or 2 more times. And also, there is a playlist on YouTube that I have put together. You can find it from the resource section of this video. These are mainly from Computerphile by Dr. Mike Pound. And if you want to dive deeper into something, or if you want another recap or another review of the topics, some of these videos here can help you. You do not need to go over all of them, but say, for example, you want to go over the GCM mode again in AES. You can either refer back to a lecture of this section, or maybe watch this one. We have covered most of the concepts here in this playlist, but for example, here's one video on Diffie-Hellman about the mathematics, so if you want to dive into that, here's a video for you. And there are a couple other things here as well. So again, this could both be a recap and also in case you want to dive deeper into a topic that we only briefly mentioned. Now, another resource is the Seed Labs. So search for Seed Labs. I'll also give you a link. And here, these are some hands-on great labs on computer security and cryptography. And if you go into this section, Seed Labs, and then Seed Labs 2.0, here you can see some different sections. For example, if we go to cryptography, we have something here on RSA, something else on the public key infrastructure. So we can check some of them out. And then once you come here, make sure to click on this PDF, or if it says English or Spanish, click on one of those, all right? And then once you do this, it is going to redirect you to the actual lab. So you can go over them. Don't expect to do them in a couple of minutes. They usually would take hours or even a whole day, and we've got about a couple dozen of them here on this website. I had to do a whole bunch of them when I was taking some computer security courses, and I found them quite helpful. So I would also encourage you to maybe try some of them out. You would usually go on ahead and do some sort of an attack. And also, I'm sure there are some YouTube videos and other resources that you can see people going over some of these labs. Now, if you also want to take things further, I recommend that you take an ethical hacking course. You can find many. I'm not going to give you any specific courses in this lecture, but if you look up ethical hacking courses online, I'm sure you'll find many different resources. If you know how to break the system, then you'd be better positioned to also know how to protect against those attacks. So that's another recommendation that I have if you want to dive deeper into this security field. And one last recommendation is, of course, to check out some textbooks and different books on security and also on cryptography. I wouldn't say that you need to get crazier than this about cryptography unless you want to become a cryptanalyst or a cryptographer, or you want to become a cybersecurity expert. So if these apply to you, then sure, you have to go ahead and dive deeper into cryptography. But as a software engineer, I wouldn't say that you need to get so much crazier than this, okay? Of course, do reviews, keep updated, but that should be pretty much it, okay? But of course, about security in general, because cryptography isn't the only field of security, it's a very important one, but there are other things that you can do as well. And for these other things, I would recommend that you continue on with your journey of learning. I'll try to link maybe some books at the end of the course in a bonus lecture, because that's what Udemy allows. Most of these books are not free, so I'm not able to just link them, but as a bonus, I might be able to link a few at the end of the course. So I'll see if I can put a section at the end, like conclusion or something, and then add a bonus lecture with some supplementary resources, some books, maybe some other courses that you can check out if you want. Now, if you want to go and read some of these textbooks, you should be well positioned to understand them very well, but I want to just mention one point, that throughout this section, I deliberately stayed away from mathematical notations because I thought they could throw you off a little bit, and I did not do that. But if you pick up any book, for example, here I took this picture from this book, and this might look a little too overwhelming, but this is exactly what we've discussed, that how we're going to use public key cryptography to exchange a shared secret that we can then use as our AES key. All right, so here it uses this notation. You would also see this Alice and Bob example quite a bit in different textbooks, but it's the same thing as using a UNI example or a client and server example. So here this Bob, this would be maybe the server, and then the server has a public and a private key, and the client here generates some random data, and then using the public key of the server, or Bob in this example, is going to encrypt that data, all right? So this Y here is going to be the ciphertext, then the ciphertext is transferred over, and this notation here means decrypt using the private key, all right? And then here AES using this key, it means encrypt, and here this -1 means to inverse, all right? So decrypt. So you'd usually see notations like these in textbooks, which could be kind of confusing, but not really if you understand the logic. We did not simplify the actual logic, but I tried to use JavaScript and human language instead of using mathematical language, all right? For example, here's another case. Looks kind of crazy, but all it means is this, that we are encrypting our plaintext. Well, here, this I here means a block of our plaintext, but you get the point. And then we are decrypting again, all right? So it means that the result of encrypting a plaintext and then decrypting it would give us back the plaintext, okay? But mathematically, it looks crazy, but once you try to simplify it, you're going to see that it's something very straightforward. Here's another example in RSA. This looks kind of weird if you're not a mathematician, but for regular people, you can just look at this and understand how this really works, all right? So all it means is we take E and D, our public and private exponents, we multiply them and get the remainder by phi, and we say that this result should be 1, okay? Mathematically, we would write it down like this, but logically, in human language, we would write it like this, all right? Or mostly in JavaScript language, I mean. So this is something that I did throughout the section. So the point that I'm trying to make is that if you pick up a textbook and you see all these mathematical notations, do not feel frightened. You can sit down. If you work yourself through the notations, they should eventually make sense, all right? Of course, if it's more directly talking about the math, like the deeper concepts in AES, that how the math works, the S boxes, for example. So for those, you have to work yourself through them if you want. Again, I wouldn't say that it's 100% necessary to do them, but if you're interested and if you want to work more in this field, I would encourage you to check that out. But when doing regular software engineering work, and while you also have cybersecurity experts on your team, which you usually should have, in these cases, you don't need to get this much crazy about the algorithms, but still you need to understand the basics. All right, so that's it about this section and cryptography, and thank you very much, and I'll see you in the next one.